So we're going to do a new topic today. We're going to talk about evolution. We're going to talk about the connection between evolution and game theory. All right. Now there's going to be an extra I think I already emailed you about this. There's going to be an extra reading on this for the people who want it. There's a reading packet that's available to anybody who wants it. I emailed you all the websites where you can order that reading packet and figure out where to pick it up. It's not compulsory. You don't have to look at that reading packet. It's just it might help. In addition, as with last Wednesday, since some of the material here is new, I have written a handout that goes with this lecture, and that handout will appear magically this afternoon on the website. All right, so if things today are fast, don't worry, there's a handout that goes with it. All right, so why look at evolution in the context of game theory? There are really two reasons. The first reason is because of the influence of game theory on biology. All right, it turns out that in the last few decades, there's been an enormous amount of work done in biology, in particular looking at animal behavior, and using game theory to analyze that animal behavior. And just to give you a loose idea about how this works, the idea is to relate strategies with genes, or at least the phenotype of those genes, and to relate payoffs to genetic fitness. All right, so the idea is that strategies are related to genes, and the payoffs in the games are related to genetic fitness. And the big idea, of course, is that strategies grow if they do well. All right, so strategies that do well in these games grow, strategies that do less well die out. All right, so we're going to be visiting that today. One thing to bear in mind from the start is there's an important difference between game theory as analyzed in animal behavior and biology and game theory that we've been doing so far in the class, and that is that we're going to think of these behaviors, these strategies played by animals, not as chosen by reasoning individuals, but rather as being hardwired. So if strategies grow, it isn't that some lion or ant has chosen that strategy. It's simply that the ant or lion who has that gene that corresponds to that strategy grows and has many children. All right, so it's important this is a new idea for us, that these strategies are hardwired. All right, so that's interesting in and of itself, but there's also an important influence the other way. So a second reason for studying this stuff is that there's been an enormous influence from biology, or from evolutionary biology in particular, back on the social sciences. All right. This influence the other way uses evolution largely as a metaphor. And you'll find this if you're a political scientist, if you're a historian, if you're an anthropologist, if you're a sociologist. And let me give you an example from economics, since it's perhaps closer to home. So here's an example. You might imagine some firms in the marketplace. And you could think of these firms not necessarily reasoning out what is the most profitable strategy for them, or what is the most cost-reducing strategy for them. However, so they might just have rules of thumbs to select their strategies. However, in a competitive marketplace, survival of the fittest firms will lead to us ending up with a bunch of firms who have low costs and high profits. All right, that makes sense? So here, competition in the marketplace substitutes for competition in the jungle, as it were. All right, and the analog of a gene dying out is a firm going bankrupt. All right, so this is the kind of ideas we're going to explore. These are the kind of ideas that are going to be in the background for today and Monday. Now, before I go on, I want to put in a couple of kind of important riders. So there are two things that I am not. Right? The first thing I am not is I'm not a biologist. I'm sure there are people in this room who are biologists who know a lot more about the genetic side of this than I do. All right? So I'm not going to attempt to teach you biology here. I'm going to focus on the game theory part. Right? The second thing I'm not is I'm not an American citizen. And I worry slightly when we talk about evolution, because I realize it's very controversial here, and some of you might be from places like, say, Kansas. And if you are from some place like Kansas, then please don't write to your senator about this. All right? Or if they see the movie, just tell them it was some other English guy giving the lecture. All right. So what we're going to actually do is we're going to look at a highly simplified model of evolution, at least for today. All right? We might get onto a more complicated model on Monday, but today it's going to be very highly stylized. So this is going to be our extremely simplified model. And this simplified model is going to do tremendous violence to the biology, but it's really just to fix some ideas, okay? So we're going to focus on what we're going to call within species competition. So the lions are competing against the lions, and the ants are competing against the ants. And the way we're going to think about this is we're going to look at symmetric two-player games. So we look at very simple games. They're only going to involve two players, and they're going to be symmetric games, which means both players have the same strategies, both players have the same payoffs. All right? The way we're going to think of this is we're going to imagine that there's a large population out there, each of whom is playing a particular strategy. And we're going to assume that what happens is we randomly pick two people from that population and pair them up. So everyone in this large population will be randomly paired with someone else. They'll play the strategy that they are hardwired to play, and then we'll see what happens. All right, so the idea here is there's a large population of if you like, animals that are hardwired to play particular strategies, and we're going to have random matching. And the idea here is, when we do lots of these random matching, we're going to keep track of the average payoffs. All right, so what we're going to focus on are the average payoffs of particular strategies when randomly matched in these games. All right? All right? And again, the underlying idea is that relatively successful strategies will grow, and relatively unsuccessful ones will decline. I'm not going to write that. That's obviously the other part of that. So relatively successful strategies are growing, and relatively unsuccessful strategies are declining. All right, now to keep things simple, I'm not going to do any dynamics here. That would take us beyond the math that a lot of you can do in the class. So we're not going to worry about dynamics here, but this is the underlying dynamic. The idea is that if a strategy is successful, that strategy will grow in the population. If a strategy is unsuccessful, it will decline. So this isn't horrible violence to biology yet. It's the next bit that's the horrible violence. All right? So to keep things simple today, we're going to assume that there is no gene redistribution. All right? We're going to assume that there's no gene redistribution. So in principle, what we're looking at is asexual reproduction, which is clearly not a good model, but it will do for today. All right, so you want to think about a practical example of asexual reproduction? Think about root vegetables, or judging from our experiments with the dating game, we better hope that's true for economic majors as well. All right, maybe the fact I'm focusing on asexual reproduction will get me off with the guys in Kansas. Maybe I won't lose my green card after all. All right, so that's going to be our basic story. And the basic idea we're going to use is this. It's an idea due to a guy called Maynard Smith in the 70s, although obviously the big idea goes back earlier. So this is the big idea. Suppose that we imagine that there's a particular game, and there's a large population. So think of yourselves as the large population. And suppose that the entire population were all playing the same strategy, call it S. So they're all hardwired to play the same strategy S. And suppose now that there's a mutation, right? So some small group start playing some other strategy, let's call it S prime. Right? What we want to ask is, will that small mutation group the S prime strategy, will it thrive or will it die out? If it's true that for all possible mutations, all possible little groups of mutation of people who are playing S prime, they'll die out, then we'll say that the original strategy, the strategy S, is evolutionarily stable. Right? And we're going to write that up more formally later on, but that's just the basic idea. So let's try it again. There's a strategy out there that everyone's playing, call it S. We're going to look at a mutation, that's S prime, so a small group of people are going to start playing S prime. They're going to go on being randomly matched. Everyone's going to be randomly matched. And we're going to ask if the S prime group does well, in which case they'll grow, or does badly, in which case they'll shrink and eventually die out. If they die out, we'll say that S was evolutionarily stable. That's true for all possible mutations. All right? And just notice when we're randomly matching them, one thing to note is, since there's only a small mutation to start with, most of the time when they're randomly matched, they're going to match against somebody who's still playing S. Occasionally they're going to meet one of the other mutants, but most of the time we're going to have to worry about how the mutants do against the incumbent population. All right, so that was too abstract to really get one's head around, so let's try and do an example. All right, so let's remove our motivation and get down to actually doing some work. All right, so we're going to start with a very simple example that you'll all recognize. Here's a game. It's a 2x2 game, and the payoffs are as follows: 2-2, 0-3, 3-0, and 1-1. All right, we'll call these strategies cooperate or defect. C for cooperate, D for defect. C for cooperate, D for defect. All right, and you'll all recognize immediately that this game is what? This game is what? This is Prisoner's Dilemma, right? So we're going to start by imagining these animals playing Prisoner's Dilemma. And to put it into context, imagine that these are a group of lions, all right? Again, leave aside the fact it's asexual reproduction for a second. Imagine these are a group of lions, and cooperating means cooperating on the hunt. It means using a lot of energy going after, as you cooperate in a group while hunting. And defecting here would mean not working hard on the hunt, letting the other lions catch the antelope, whatever, and they're just sharing in the spoils. So free riding, basically. All right? Or another example, think about ants with an ant nest, and imagine this ant nest has been attacked by, I don't know what, some other creature. You could imagine that cooperating is joining in defending the nest at the risk of being hurt, and defecting is running away. All right? All right? And we all know in this game roughly how to analyze it. I'm not going to go over that now. I want to ask a different question today. I want to ask, in this model of asexual reproduction, is cooperation evolutionarily stable? Is cooperation evolutionarily stable? All right. Okay. So to try and illustrate that, let's just think about this game being played for real out there. So what we're going to do is, we're going to start off by imagining that you are all, I don't know, ants, lions, what do you want to be? Ants, I think. All right? All right, so you're, from up here look like ants, right? You're all ants, and all of you have been hardwired to play the strategy C. All right? You've been hardwired to play the strategy C. All right, so life's going on fine, and let's do some random matching here. So suppose, that's going to get me eventually, suppose that we randomly match this ant, all right, so stand up a second, all right, so this ant gets randomly matched with this ant, all right, so they now play this Prisoner's Dilemma against one another, all right, but both of them have been hardwired to cooperate. Right, both have been hardwired to cooperate, so they both cooperate. Is that right? Right. So this ant, whose name is Lenore. Lenore the ant cooperates, and Wu the ant cooperates. So since they both cooperate, we can look at what their payoff is. Their payoff is cooperate against cooperate, so they get 2. So that's pretty good. So they're doing pretty well in terms of genetic fitness. And suddenly there are 2 ants, right? So this ant produces another ant. well, it's one without a computer. Okay, so this ant produces another ant. All right, and this ant produces another ant. Sorry. Okay, all right. All right, so they're doing fine, right? And the whole population is matching against other cooperative ants, and more ants are being produced, and everything's fine and dandy. All right, everything looks good. All right, sit down a second. All right, now imagine that there's a mutation, a small mutation, and this small mutation involves a group of rather nasty, uncooperative ants. All right, so the scary mutation. So here's our scary mutation. All right, let's use the TAs, right? So the TAs are my scary mutation. So all of the TAs here are the scary mutation. There's another one over there. All right, so there's a bunch. So everyone else is still playing cooperate. There's this vast number of cooperative ants, but now there's this small number of ants with this mutation that says don't cooperate, play D. All right, so let's see what happens with random matching. So a lot of these cooperative ants are still matching with each other and doing fine, but that's not the point. What we're worried about is what's going to happen to the mutants. All right, so let's pick our representative nasty mutant. So that's going to be Rahul. All right, so Rahul is our scary mutant. All right, and let's go back and randomly match him against one of our incumbent ants, our nice cooperative ants. Let's pick this one. All right, so it just happens he's randomly matched with this cooperative ant, and this cooperative ant, whose name is Nick, is hardwired, since he's a regular ant, he's hardwired to play cooperate. So he's going to play cooperate. Say cooperate. All right, I should put the mic, but never mind. And meanwhile, do we have a mic handy? Thank you. All right, so he says cooperate, but unfortunately, he's been matched against the nasty, uncooperative ant. It's not that he's nasty, he's just been hardwired to say
not cooperate.
Not cooperate, to say defect. All right, so what's going to happen now? All right, so unfortunately for Nick, he, the cooperative ant, was matched against a not very nice ant. He was playing C, and Rahul was playing D, so Nick's payoff is 0. So we went from 1 Nick to being no Nick, right? He got wiped out. All right, and Rahul, meanwhile, he got a payoff of what? What was Rahul's payoff? Rahul's payoff 3. So suddenly there's not just Rahul, but there's the mutation is growing. All right, and now we go on matching each period. Some of you are going to be matched against other cooperative ants, and you're going to be doing fine. But every now and then, and actually increasingly often, you're going to be matched against one of our mutants, and those mutants are going to grow. Those mutants are going to go on growing. Now, it's true that every now and then a mutant's going to meet another mutant. Is that right? Right? But we don't have to worry about that. What we have to worry about is, are they going to die out early on? It's going to be very rare for them to meet another mutant, at least early on. All right? So the strategy cooperate is evolutionarily stable if this small mutation, there's our small mutation, disappears and doesn't turn into a bigger mutation. All right? And of course, in this case, as we just saw, the mutation didn't die out, it actually grew. All right? So be formal about this and be careful. For the strategy to cooperate to be evolutionarily stable, it needs to be the case that the mutation actually dies out on average. And here, far from dying out, it grew. We now have lots of these nasty TAs. All right, people understand? All right, so thanks. All right, so let's just try and do that a little bit more formally on the board. All right, that was the basic idea, or the basic graphics of the idea. But let's look at it a little bit more formally. So we basically have cooperative ants and a few mutant defector ants out there, so mutant not cooperative ants. And what we want to keep track of are their average payoffs in random matches. All right? So the incumbent ants, the cooperative ants, they're playing, we're interested in their payoff, and they're playing a population that's mixed. Almost everybody in the population is cooperative. So let's say 1 minus epsilon of the people they're playing against, where epsilon is a small number, very small number, are also cooperative. But every now and then, like our poor friend Nick, every now and then they're going to come across a nasty mutant. They're going to come across Rahul. All right? So what's their payoff going to be on average, their average payoff? Okay, so 1 minus epsilon of the time. We can actually think of this mix here, so it's 1 minus epsilon and epsilon. 1 minus epsilon of the time, they're going to meet another cooperative ant and get a payoff of 2. All right? But epsilon of the time, they're going to meet Rahul and get a payoff of 0. Is that correct? So that's their average payoff. Now how about the mutants' payoffs? So the mutants, there aren't many of them around, but they are also playing against the same mixed population. 1 minus epsilon of the time, they're going to be matched against a cooperative ant, and epsilon of the time, the two mutants, the two TAs, are going to play off against each other. All right? Let's have a look at what their payoff is. So their payoff is 1 minus epsilon. They get a payoff of 3. That's what we saw when Rahul met Nick. And the other epsilon of the time, Rahul meets Jake or somebody and has to make do with a payoff of 1. All right? But if we keep track of this, what do we have? This equals 2 1 minus epsilon, and this equals 3 1 minus epsilon plus epsilon. Is that right? All right, and clearly, I hope this is clear, the payoff to the mutant is bigger. Everyone happy with that? The payoff to the mutant is bigger? Which means the mutation is not going to die out. In fact, it's going to grow. Mutation is not going to die out. So we can conclude that C is not evolutionarily stable. I'm going to start using ES for evolutionarily stable. All right? All right, so in this particular game, evolution is not evolutionarily stable. So we might ask, what is evolutionarily stable in this game? Well, it's not going to be hard to figure it out, but since there's only one choice, I claim that D is going to be evolutionarily stable. But let's just prove it. So is it going to be the case that these mutants will eventually take over the whole population and everyone will end up looking like a TA and being uncooperative? All right, so they're busily asexually reproducing all the time, they get bigger and bigger, and is it in fact the case that once they've conquered everything, that they're evolutionarily stable? So is defect evolutionarily stable in this game? All right, to figure that out, we have to do exactly the reverse experiment. So the experiment now is, imagine everyone in the population, all of you guys, all of the students in the room, are nasty, non-cooperative, defecting ants. All right? All right? And you're going along, and most of the time you're meeting each other all the time for now, and you're getting a payoff of 1. And now there's a mutation, but this time the mutation isn't the scary non-cooperative mutation that we saw before with Rahul. It's going to be Murtu over there, all right? And Murtu is a nice mutation who cooperates. All right, so Murtu is our nice cooperative mutation. All right, let me just get the camera to pan on poor little Murtu. All right, so there's poor little Murtu, who's the only little cooperative mutation in the room. Wave. All right, there we go. Okay. All right. All right. And what's going to happen to our cooperative mutation? All right. So most of the time, you non-cooperative people are matching up against each other. We can figure out what your payoff is. So the uncooperative incumbents, they're playing a population that is 1 minus epsilon non-cooperative, and epsilon of the time, they meet Murtu. All right? So what's their average payoff? So let's be careful. Let's switch things around up here, just to make sure we can see what happens. So switching things around on our chart up here, we're now looking at the case where there's 1 minus epsilon non-cooperators and epsilon cooperators. All right, so these you guys, you non-cooperative ants, are most of the time meeting each other, and when you meet each other, you're getting a payoff of 1. So 1 minus epsilon of the time, you're getting a payoff of 1, but epsilon of the time, you're doing great, because you're meeting Murtu, and unfortunately you're beating up on Murtu. All right, and how's she doing? Well, she's a cooperator, and 1 minus epsilon of the time, she's meeting you guys, and epsilon of the time, she meets another nice cooperative ant like Jake. All right? So her payoff is 1 minus epsilon of the time, she gets nothing, and epsilon of the time, she does pretty well and gets 2. But it's only epsilon of the time. Is that right? So far, so good. So what's going to happen to this mutation? Well, the incumbent population, their average payoff comes down to being 1 minus epsilon plus 3 epsilon. And Murtaugh's payoff, the mutant, ends up being 2 epsilon. All right? So unfortunately, these nasty ants are thriving, and Murtaugh gets wiped out, so you can sit down again. All right? So what have we shown here? We've shown that defect, not cooperate, is evolutionarily stable in this game. Right? Any mutation, there's only one possible mutation, any mutation gets wiped out. All right? Think about these two different models here. The first, not different models, but different metaphors. So we started out with this population of relatively nice people, and we had a nasty mutation. So think of the movie Alien. Actually, don't, it's a horrible movie, but, but all right. All right? And if you remember that horrible movie, Alien or Species is not. Think of the movie Species, an even worse movie. Right? Think of the movie Species. That was Rahul, and he grew, albeit asexually, very rapidly. That's a pretty scary movie, right? Right? Conversely, when we had this population of nasty people, and we tried to have a nice little invasion of a nice mutant, so think of the movie E.T., unfortunately, E.T. got squished. All right? All right? So that's the two extremes. All right. So what is the lesson that we can actually draw from this? All right. So there's a lesson here. And the lesson, I guess there's going to be two lessons here, but let's start with one. The first lesson here is that, well, let's just put it on the board first of all. Nature, the outcome of evolution, nature, can suck. All right? So again, we could use a more formal term, but this is an important lesson. There's a tendency for some people to think that if something arises as a consequence of evolution, if something is natural, if something is in nature, it must therefore be good in some moral or other way, efficient or something. All right? And what we're seeing here is in this game, the consequence of nature is a horrible consequence. All right? For those people who doubt that nature can be pretty unpleasant, have a look at yesterday's science page of the New York Times and read the piece about how baboons basically kill baby baboons. The biggest cause of death among baby baboons is infanticide. Right? This is evolutionarily stable, it turns out, and they explain why in the Times. It isn't pleasant. All right? So nature can suck. Nature can be pretty inefficient. Okay? Now, this raises a question in this particular game, because look at the examples we started with. We started with lions who were thinking about, or not thinking about, they weren't thinking about, they were hardwired to go after antelope and either cooperate or not. And we thought about ants who were hardwired to defend the nest or not. And we all know from watching endless nature shows as children on TV that actually lions do cooperate when they go after antelope, and actually ants do defend the nest when it's invaded by a spider or something. Is that right? Looking for some nodding, is that right? Yeah, okay, good. So what happened? What's wrong with our model here? We've argued here that in this model, nature's going to produce this non-cooperative behavior. We know there are examples of cooperation in nature. What's going on? What are we missing? Yeah, can I get a mic in it's here. Let me do it. I'll do it. Yeah, so what's going on?
Different communities might compete against each other, so one community that doesn't have any of these mutations and stays cooperative might succeed, so communities in general don't have as many mutations. Okay, so that's an interesting idea. So part of this is because we're focusing on within species competition rather than the cross-species competition. That turns out to be a complicated idea, and large literature on it, and it's actually a little difficult. I was looking for, but it's good. It's a good suggestion. I was looking for something simpler, actually. Let me come back here. So yeah.
Do these species have ways to detect cheaters and punish them?
Okay, that might be a possibility, and that certainly there is some evidence of that, but not much. Again, we're looking at pretty high primates by the time you get to that. Something simpler, something you should all have on your mind all the time if you're normal teenagers.
The payoffs could change as the proportion of cheaters increases, so you're not going to get the payoff of 3 if everyone's cheating.
All right, but it's true that you're going to get a different expected payoff, but that isn't the payoff they get. I'm thinking of something really simple that, let me repeat, I'm guessing is on all of your minds as teenagers. Let's see if that hint's going to get the right answer. Yeah.
Ants are not asexual.
Right, right. The assumption that's really driving this here is the assumption of asexual reproduction. Right? Sexual reproduction with gene exchange is going to make a difference. Why? I don't want to delve too much into the biology here, but the main why is what matters is survival of the gene, not survival of the individual ant or individual lion. So if you have sexual reproduction, you get gene redistribution among children and cousins to a less extent. All right? So provided the other ants in the nest are closely enough genetically related to you, and provided the lions are close enough related to you, then it may turn out to be that you will cooperate, and that in fact does change the payoffs of the game. It doesn't change the payoffs for the individual lion or ant, it changes the payoffs for the gene. All right? Now if we have time, we'll come back and look at that on Monday, and even if we don't have time, in the reading I've left for you in the reading packet, it goes into that in some detail. All right? It's a much more complicated model, but that's where we're going to get, for the most part, that's where we're going to get cooperation from, rather than from the other points that you made. All right? So sex can make a difference here. But we're going to stick with asexual reproduction because it's easier to analyze, and stick with it for the minute. And what we've learned, the second lesson we've learned here, I'm going to generalize from this lesson. We learned that a strategy that was strictly dominated was not evolutionarily stable. Right? Well, all right, so I've only shown an example here, but we'll extend from the example. All right? So if a strategy is strictly dominated, and of course cooperate is strictly dominated here, then it is not evolutionarily stable, at least in this simple game of just asexual reproduction. And even though I haven't proved this here, the idea is exactly the idea of this example. So let's just try and talk it through. Suppose a strategy was strictly dominated. How do we know, how can we see that it will not be evolutionarily stable? Somebody? Where are my pre-med majors? I mean, not pre-med majors, but my pre-med people. They're all hiding now. I know you're out there because I've seen your forms, but never mind. Okay, so why is this dominated strategy not evolutionarily stable? I want to try this out. Yes? Yeah.
The strategy that dominates will be a successful mutation.
Good, good. So the strategy that dominates, the strategy that does the domination of this strictly dominated strategy would be a successful mutation. If it enters, it does well, not just against this strategy, but against any mix involving itself and this strategy. All right, so the strictly dominator strategy will invade. All right, so we can't have strictly dominated strategies surviving in evolution. All right. Let's do another example, and we'll see if we can learn some more. So this is going to be a slightly more complicated example. Let's have a 3x3 game. So here's our 3x3 game, and we'll just label the strategies A, B, C, and A, B, C. And once again, we're going to focus on symmetric games, so this game will be symmetric. 2, 2, 0, 0, 0, 0, 0, 0. Lots of zeros in this. 0, 0, 0, 0. 1, 1, 0, 0, 1, 1, 0, 0. All right, so this is a symmetric game. Okay, and if we look at this game a little bit, I don't want to look at all of it. I want to ask the question, is strategy C evolutionarily stable? Is strategy C evolutionarily stable? Let's go back to our experiment. What does it involve? Imagine everyone in the room is hardwired to play C. Could that population be invaded by a mutation? So what do we think? What do we think? Is C evolutionarily stable? Who thinks it is stable? Who thinks it's not stable? Right, so most of you think it's not stable, so you must have some idea why. Why do we think it's not stable? Let me just try and cold call a little bit. Anybody? Let me sample somebody. If it's not stable, it must be it's going to get invaded. So who's going to invade it? Can we try this gentleman? Have a guess who's going to invade it?
Strategy B.
Strategy B. Okay, that's correct. Okay, so your name is?
Greg.
So Greg is saying strategy B might invade here. Let's have a look. Let's see what happens. All right? So Suppose there's an invasion of B. So again, the TAs are playing B, everyone else is playing C. And let's see how these incumbent genes do. So C is playing against 1 minus epsilon of the population who are playing C and epsilon who are playing B. And its average payoff, well, 1 minus epsilon of the time, it'll be matched against essentially itself and get a payoff of 0. All right? But epsilon of the time, it will be matched against a B and get a payoff of 1. All right, everyone agree with that? All right, so 1 minus epsilon of the time it meets itself and gets nothing. Epsilon of the time it gets lucky, and it meets a TA and gets a payoff of 1. How about those B invaders, the TAs in the class? So 1 minus epsilon of the time, they're going to meet C's, and epsilon of the time, they're going to meet B's. And 1 minus epsilon of the time, therefore, the B is meeting a C and getting a payoff of 1. Right? So 1 minus epsilon of the time, the TA is meeting one of you. And epsilon of the time, the TA is meeting another TA, playing B against B, and getting 0. All right, so this works out as epsilon, and this works out as 1 minus epsilon. All right? But notice that if epsilon is small, if there are just a small number of these mutations, 1 minus epsilon is bigger than epsilon. Is that right? And that means that this mutation will not die out. Right? It'll probably go on, and we can actually say a bit more, it'll probably go on growing until it's roughly half the population. All right? But in particular, it won't die out. Since it won't die out, since the mutation doesn't die out, we can conclude that C is not evolutionarily stable. All right, everyone okay with that? Everyone okay with that idea? Now this example is a little bit more complicated than the previous example, because it turns out that the invading mutant population, the population B, is itself not evolutionarily stable. Right, everyone see that? Right, C wasn't evolutionarily stable because it got invaded by B. Who's going to invade B? Who's going to invade B? C is going to invade B. Turns out everything's exactly symmetric here. So even though we're arguing that C is not evolutionarily stable because it's invaded by B, it doesn't have to be the case that the successful mutant is itself evolutionarily stable. Right? So in this particular example, the invader, namely B, is itself not evolutionarily stable. Nevertheless, it doesn't die out when it invades a population of C. All right? But there's a second observation I want to draw off this one. I'll give us some better chalk here. I'm not finding it. All right. There's a second observation I want to draw off here. What do we observe? What else is true about this, about both C and B? So what's true about everyone playing C or everyone playing B? What else? Just going back to what we've learned in the course so far, what do we think about everyone playing C? So if everyone's playing C, we'd be looking at an object like this, C comma C, right? And we might ask the question, is C comma C what? Is it a Nash equilibrium? Right, so is CC a Nash equilibrium? Here we asked, was it evolutionarily stable? We found it wasn't. Now let's ask a different question. And forget evolution for a second. Is CC a Nash equilibrium? Well, that's a question you all should be able to answer for the midterm. So somebody tell me the answer. It's not a Nash equilibrium. How do we know it's not a Nash equilibrium? What do we have to do to show it's not a Nash equilibrium? We have to show that there's a profitable deviation, right? Right? So shout it out, what's the profitable deviation here? The profitable deviation is B, right? It's not, no, because B is a strictly profitable deviation. Right? B is a strictly profitable deviation. Notice that the thing that was a strictly profitable deviation was the same thing that would have invaded the population of C's in the context of our ant's nest, in the context of this classroom being an ant's nest and looking at evolution. Is that right? Right? So what have we just learned here? Well, this idea turns out to be general. The idea is, if a strategy S, right, perhaps I should make this a lesson. If a strategy S is not Nash, so in other words, SS is not a Nash equilibrium, it's not a Nash equilibrium, then S is not evolutionarily stable. All right. If S is not Nash, then S is not evolutionarily stable. All right? A little bit of logic, we can flip that around, and we'll say what that actually tells us is, it's equivalent to saying, if S is evolutionarily stable, then SS is a Nash equilibrium. That's the equivalent way of saying that. All right, so what's the idea here? Let's look at the first line rather than the second line. It's pretty easy to understand. The idea here is if a strategy is not Nash, what that means is there's some other strategy that would be a strictly profitable deviation. And that's enough to tell us that S cannot be evolutionarily stable. Why? Because take that same strategy, that was a strictly profitable deviation, B in this case, and that strategy can be thought of as the mutation that's going to invade the strategy we started from. Right, everyone see that? Say it once more. Suppose a strategy S is not a Nash equilibrium. Right, that means there's some other strategy, S prime, say, that is a strictly profitable deviation. Now think of that strictly profitable deviation, S prime, as a mutant invasion. So now Rahul is hardwired to play S prime. Right? Since it was strictly profitable, it's going to be it was strictly profitable as a deviation, it's going to be successful as an invader. All right? So again, I haven't formally proved it, but that's exactly how the proof would run. All right? So let's pause for a second and just see where we are. All right? What we've managed to show is there's a connection here between dominance and evolutionarily stable. We've said if a strategy is not dominated, it cannot be evolutionarily stable. And we've also begun to show a connection between Nash equilibrium and evolutionary stability. So two of the ideas we've developed over the last 6 weeks are re-emerging in this completely other context of animal behavior. The idea of dominance and the idea of Nash. And so far, how far have we got? We've said that if something's going to be evolutionarily stable, it better be the case that it's also Nash. All right? And that raises, I think, a natural question, which is the opposite true? It would be really pretty great if it were true the other way around. If I could show that if a strategy was Nash, then it would necessarily also be evolutionarily stable. And that would be pretty cool, right? So this idea we've spent a lot of time developing in the class turns out to be the key idea. Unfortunately, life isn't quite so neat. Let's see why. All right, so what I'm going to do is I'm going to show you an example, and what this example is going to illustrate is that we can find Nash strategies that are not evolutionarily stable. And the example is embarrassingly simple. Here's a game. It's a two-player, two-strategy game. And the payoffs are 1-1, 0-0, 0-0, 0-0. All right, this is kind of an embarrassingly simple game. All right, what are the Nash equilibria in this game? Well, let's go through slowly. All right, if player row is playing A, then column's best response is to pick A. And if row is playing B, then column's best response is either to play A or B. Right? If column is playing A, then row's best response is to choose A. If column is playing B, then Rho's best response is either A or B. All right, so this is kind of exercise that is almost second nature for you guys now. All right, so we can conclude by looking where these best responses coincide that the Nash equilibria here are AA and BB. Okay? Everyone happy with that? Should be looking like this is, yeah, this is easy, right? All right. So, all right. But let's look at this second Nash equilibrium, the BB Nash equilibrium, the one that's down here. Right? Is B evolutionarily stable? Is B evolutionarily stable? Well, again, let's think about it. Let's just think through the exercise. Suppose the entire class were playing B. All right? Wake up the guy in the middle and tell him he's playing B too. Him, yeah, okay? All right? The whole class is playing B, all right? And suppose there's an invasion. What could the invasion be? The invasion better be an invasion of A's. All right? What's going to be the expected payoff, or the average payoff, of the incumbents, of all of you in the class who are playing B? Well, without doing it too laboriously, 1 minus epsilon at a time you're going to meet another student, in which case your payoff, in which case you'll be playing B against B and your payoff will be 0. And epsilon at the time you're going to meet a TA, and these TAs are playing A, but again you'll get 0. So your average payoff will be what? 0. All right? Payoff will be 0. All right? So if you're incumbent and you against this mix, your payoff will be 0. And if you're an invader, so how's Rahul doing this time? Rahul's playing A. 1 minus epsilon of the time, this A is playing against a B. Right? So 1 minus epsilon of the time is playing against a B. Right? So 1 minus epsilon of the time, Rahul meets a student and gets a payoff of 0. But epsilon of the time, Rahul hits it lucky. And Rahul meets another TA. Rahul meets Jake. And when he meets Jake, his payoff is 1. Is that correct? Is that correct? So his total average payoff is epsilon, which is bigger than 0. All right? So indeed, it turns out that Rahul's gene is going to grow, the B's are going to shrink. BB was Nash, but it's not evolutionarily stable. It can be invaded. All right? Everyone see that? Everyone see how that invasion worked? So the key to that invasion was, when Rahul met another incumbent student, he did no better than the students did against students. But on those rare occasions, when Rahul met another TA, he made hay. Or not hay, it's asexual reproduction. He got a payoff of 1. All right? And those rare occasions were enough to make Rahul grow and thrive, whereas the B's, relatively speaking, shrink. All right, everyone happy with that? Yeah? Okay, so what we have here is an example of something that is Nash, but is not evolutionarily stable. Can anyone say, what's special about this example? How did I rig this example? There's something really kind of knife edge and rigged about this example. What's rigged about this example? Anybody? Don't want a cold call on this. No takers? Everyone's kind of in that pre-midterm scared mode. Yeah? Yeah, this guy's rescuing. This guy is saving the class today. Someone else has to get in. Okay. What's your name again?
Stephen.
So Stephen is saving the rest of you, but go ahead, Stephen.
B is only a weak best response to anything.
Good. So what's true about this example is that although B is a best response against B, it only is so weakly. Is that right? It's only so weakly. Right? If, in fact, we got rid of Nash equilibria that relied only on weak best responses, then we wouldn't be able to produce this example. Right? So in particular, if we looked at Nash equilibria where the Nash strategies was strictly a best response, it was strictly better than playing any other pure strategy, those cases would be evolutionarily stable. Right? Anyone remember what we call Nash equilibria where the Nash strategy is a strict best response? We call them strict Nash. All right? So what is in fact true is that if S is a strict Nash equilibrium, by which I mean S is a strict best response to S, then S is a Nash equilibrium. Sorry, and S is evolutionarily stable. All right. Excuse me. Okay, so we've been only semi-formal so far. I haven't really put up a formal definition. And what I've been groping towards slowly is a connection between an idea growing out of biology, namely evolutionary stability, and an idea growing out of economics and mathematics, namely Nash equilibrium. And what I want to do now is I want to show you formally how are these connected. I'm not going to prove this part of the class because a proof is a bit lengthy, but I will include a proof on the handout that's going to be available this afternoon. I'm just going to argue it for now. There we go, there's some chalk. All right? So what I want to do first is I want to write down a formal definition of evolutionary stability. And it's a definition that comes out of biology, and it's a little bit of a, you're going to see, it's a little bit of a mouthful, this definition. All right? So for those people who are kind of a little bit sleepy, you need to wake up a little bit, because this is going to be a little bit of a difficult definition. All right? But this is the definition that came out of biology. This is a formal definition. It comes out of biology, and in particular, it's due to a guy called Maynard Smith, who wrote this in 1972. So obviously the earlier idea is due to Darwin, but this formal idea is due to Maynard Smith. All right, so here's our formal definition. So in a symmetric two-player game, so everything we've been looking at so far, the pure strategy S, let's call it S hat, to give it a name, S hat, is evolutionarily stable, and again I'll just use ES for that, but let me be a little bit nerdy here. I'm going to say in pure strategies. It's evolutionarily stable in pure strategies. I'm putting this in because we're going to come back on Monday and consider mixed strategies. Right? So it's evolutionarily stable in pure strategies if, and just leave a little bit of a space here, because I'm going to need a little bit of space between these next two lines. Leave a little space here. All right, so here's our big mouthful. What we need is 1 minus epsilon of the payoff of playing S hat against S hat plus epsilon of the payoff of playing S hat against S prime has to be strictly bigger than 1 minus epsilon of the payoff of playing S prime against S hat plus epsilon of the payoff of playing S prime against itself. All right? This has to be true for all possible deviations S prime. But we also, this is why I need the extra line, and for all mutation sizes epsilon less than some epsilon bar. All right, now, this is where I need to go back and just be a bit more careful. So I'm going to write in this extra line, there exists an epsilon bar. All right, that's why I left that extra line there. So this looks like very nerdy things. Let's talk our way through it. All right, what's it saying? It's saying that S hat is evolutionarily stable if, against all possible mutations, so all possible versions of Rahul, S prime, all right, the payoff of S hat against the subsequently mixed population is bigger than the payoff of S prime against the subsequently mixed population. Let's see why that's so. So this on the left is the payoff of S hat against a population in which 1 minus epsilon of the population, like it, is playing S hat, and epsilon of the population is like Rahul. Right? Because 1 minus epsilon of the time it meets something like itself, and epsilon of the time it meets a TA. All right? Conversely, on the right-hand side, we have the payoff to the mutation. The payoff to the mutation is 1 minus epsilon of the time the TA meets a student and gets the payoff of S prime against S hat. Epsilon of the time the TA meets itself and gets a payoff of S prime against S prime. And we have this inequality we had before. It says the mutation, the invader, has to do worse, so it dies out. All right? So the nasty bit of this definition, the part that's a little bit, if it takes a while to get your head around, is this qualifier about the size of mutations. And all it's saying, I mean, ignore the math of it, all it's saying is this better be true for all small mutations. All right? You could think of that saying this has to be true for all small mutations. So this definition from biology is it exactly mimics the argument we went through several times now, both using the class and using the board and figuring out average payoffs. All right? This is an ugly definition. Everyone agree this is kind of ugly? All right? So now what I'm going to do is I'm going to give you an entirely different definition. It's also going to be ugly, but a little bit less ugly. All right, so think of that as definition 1, and it came from biology. It came from this paper in 1972. I think it was in Nature by Maynard Smith and co-authors. And think of this other definition that's coming out of economics. So definition 2. A strategy, S hat, oh, I should have the same qualifier, in a symmetric two-player game. Okay, same thing to start off with. A strategy S hat is ES in pure strategies, so same as we had before, if, all right, if two things. Thing number 1, let's call it A, if if S hat is a Nash equilibrium, is a symmetric, obviously, is a symmetric Nash equilibrium of the game. We're not done yet. Let me just write down what it means to be a symmetric Nash equilibrium of the game. What does that mean? That means, i.e., the payoff of S hat against S hat must be at least as big as the payoff of S prime against S hat for all S prime. Right? That's a standard thing, which is many, many times it says S hat is a best response against S hat. All right? Not quite done yet. And B, what else do we need? We need, if this weak inequality I wrote above is actually an equality, if the payoff of S hat against itself is actually equal to the payoff of S prime against S hat, then the payoff of S hat against S prime must be bigger than the payoff of S prime against itself. Right? So this is still a bit of a mouthful, but I claim it's going to end up being a little simpler to think about. Right? So it says again, it says S hat is evolutionarily stable if it's a Nash equilibrium. Right? That's basically this. And if it's only a weak Nash equilibrium, if it's only a weak Nash equilibrium, if there's a tie, then it better beat up on the mutant. Right? It better beat up on the mutant when it meets the mutant. All right? So I'm going to try and give you an intuition as to why this is true in a minute. But first, I want to tell you why you should care about this. So without getting too religious, I want to tell you why I think this is an exciting result. Why am I dragging you through more algebra than usual? So I think there are two reasons why this is an important result. The first is, it's going to turn out that when we analyze games, it's very easy to check definition 2. Right? It's going to turn out it's very easy to check definition 2. It's really rather a pain to check definition 1. Why? Because you've got to keep track of these epsilons and so on. But the fact that definition 2 is equivalent to definition... Did I say that? That's the point. The fact that definition 1 and 2 are equivalent, so 1 is equivalent to 2, the fact that these definitions are equivalent means we only have to check the second definition. And that's easy. So when biologists are setting up experiments involving wasps or ants or lions or chimpanzees, provided they can check this in the game, they're done. And that turns out to be easy. And we'll see that on Monday. All right, that's the sort of instrumental reason. All right, now I want to give you the religious reason why you should care about this. All right, so let me just try and... I often find that this appeals to like a third of the students, and the other 2/3 of the students think I'm completely bonkers at this point. Okay, so that's fine. You can think I'm bonkers, I'm fine. I want to guess, for the third of you who are nerdy like me, I want you to sort of see the appeal of this. Here we have 2 ideas. One idea arises out of biology. I say it arose from Maynard Smith, but it really comes from Darwin. So it's a 19th century idea in biology. It's probably the most important idea in biology in the 19th century. It may be the most important idea in biology for 200 years. Is that a fair judgment? Right? The notion of evolutionary stability. Right? The other idea comes out of economics. It's looking at Nash equilibria and strict Nash equilibria and so on. Right? Up there we've got biology. Down here we have economics. This is an idea that emerged in economics in the 20th century, in the 1950s. Right? So roughly 80 years after Darwin. Right? This is a big idea in economics. This is a big idea in biology. So what appeals to me, because I'm kind of a nerdy kind of guy, is I think it's kind of wonderful that those 2 ideas are almost the same. Right? I think it's kind of it's a beautiful thing that those 2 ideas are kind of the same thing. And now you are looking at me and thinking I'm bonkers, okay? So let me push it harder. All right, so think about the great intellectual coincidences of earlier periods. Think about the 17th century. In the 17th century, people figured out that the mechanical laws that governed the rotation of the planets were at least approximately the same as those that governed a clock. Right? The basic laws of Newtonian physics were the same. And they thought this was a wonderful thing. Right? They had these completely different areas of intellectual pursuit, and they turned out to be the same. The scientific revolution said they were the same. Right? And for those people who chose to continue believing in God at that point, they thought of God now as being what? As being a heavenly clockmaker. Right? It was a wonderful moment. So here, in our own time, or perhaps just before it, we see a similar thing, right? Here we see, one of the most important ideas in science coinciding with one of the most important ideas in economics, right? And where does this lead us? Well, now I guess, the bad news is this may make a lot of people doubt the existence of God. I guess that's going to get me in trouble. I didn't say that, but at least if you did go on believing in God, you're going to have to believe God's an economist. That's a pretty good thing. All right, all right. So that's my little religious piece on this. All right, now I want to spend the last 10 minutes, having told you this wonderful thing, trying to convince you that it's true. And again, there's a proof on the handout that you can read on the web. I just want to give you an idea of why it's true. Okay, so here we go. I need some space. Well, okay. All right, so what I want to convince you of is that this definition, this kind of game theory definition, this econ definition, implies the one above. The one above we've kind of already argued several times today corresponds to the notion of evolutionary stability. We talked about it several times. We wrote down these kind of equations several times. So I want to convince you that this one implies that one. All right? Okay. So what do I have to convince you? So let's imagine, let's fix... Okay. There's no way of getting you to see that one without... No, never mind. That was a bad idea. Never mind. Okay. Let's bring it back in. The embarrassment of playing with heavy boards here. All right, let's try and shoot this one up. If you ever think of asking your dean about some new technology for Yale, we might think about having some slightly lighter blackboards, just for the evolutionary stability of the average weakling economist. All right. All right, so what we're going to do is, let's fix a strategy S, hat, and suppose S hat is in fact Nash. All right, so that's what I want to convince you of, is that S hat is going to be evolutionarily stable. So I claim there's two possibilities. There are two cases. Right? The two cases are, either it's the case that S hat against S hat does strictly better than S hat against S prime for all S prime. Right? So let's be careful. Since we know it's Nash, we already know that the payoff of S hat against itself is at least weakly better than any possible deviation. That's what it means to be Nash. Right? So everyone agree with that? We know that S hat is the best response to S hat, so it must be weakly better than any possible deviation. All right, so let's take the first case where actually it's strictly better. And let's go back to our classroom example and suppose that let's go back to the first definition by going back to our metaphor of the class. So you guys are all ants, all right? And suppose that every student in the class is playing S hat. Right? You're all playing S hat. And suppose it's the case that, in fact, the payoff of S hat against S hat is bigger than the payoff of S hat against S prime. And suppose that a mutation arises. Sorry, Rahul, here we go again. Suppose a mutation arises. Here's Rahul, our mutation. Right? And he's going to be randomly matched against one of you guys. Right? So let's compare Rahul's payoff against this gentleman's payoff. Stand up a second. Your name is? Pat. All right. So Pat is our typical S hat incumbent ant. Doesn't look like an ant, but never mind. You know, stretch your imagination a bit. And most of the time, what's happening? Most of the time is Pat is being matched against one of the rest of you. And when he's matched against one of the rest of you, he's getting the payoff of S hat against S hat, which is US hat, S hat. All right, that's what he's getting most of the time. Right? And every now and then, he's meeting a mutant. Okay, fine. Okay, fine. So every now and then he's getting a slightly different payoff. But most of the time, he's getting a payoff which is US hat, S hat. All right? What about Rahul? So Rahul, okay, every now and then, he's going to be lucky and meet another TA, but most of the time, almost all the time, he's being matched against one of you. For example, he's matched against Pat. Right? And when he's matched against Pat, his payoff is US hat, S prime, which is lower. Right? So Pat's payoff almost all the time is US hat, S hat. And Rahul's payoff almost all the time is US hat, S prime. But our assumption is US hat, S prime is lower, so Rahul's going to die out. Okay? Okay, so in this case, Rahul dies out because most of the time he's playing an incumbent and just doing horribly. Okay, sorry, Rahul. Okay, okay. Is everyone convinced by that? So in this case, the mutant dies out. So the mutant dies out because she or he meets S hat often. Right? The mutant meets the incumbent often and just does horribly against the incumbent. That's the first way. That's the first case. That's case one. And case two is, it could be the case that in fact Rahul does pretty well against the incumbents. Rahul does pretty well against the incumbents, but unfortunately for Rahul, could be the case. But in that case, according to definition B, Rahul doesn't do so well against other TAs. All right, so this is case two. Case one was Rahul just gets beaten up whenever he meets one of you. Sorry, Rahul, getting beaten up a lot here, but Rahul gets beaten up when he meets one of you. And here's the case where Rahul is doing fine against you, but he does horribly against incumbents. So that's the harder case. Let's talk through that case. So back up again. So Rahul, sorry again, you're up again. All right, so once again, you guys are all playing S hat. There's a mutation of Rahul's playing S prime. All right, and let's get Pat up again. All right, so when Pat meets one of you guys, so let's pick out one of you guys. So let me pick up, your name is? Christine. So when Pat meets Christine, which is most of the time, he does okay. And when Rahul meets Christine, which happens most of the time, he does exactly the same. So if you just compared them in their random matches against Christine or the rest of you, they're the same. All right? But every now and then, thanks Christine, every now and then, instead of every epsilon at a time, rarely, Rahul is going to meet Jake. Oh no, Jake's writing. He's going to meet Kai. All right? All right, so no seconds. All right? And on those occasions, let's see what happens. So when Pat meets Kai, he does pretty well. And he gets some big bonanza. He gets a much bigger payoff than when Rahul meets Kai. They just do horribly against each other. Right? And the fact that they do horribly against each other causes them to die out. All right? All right, so let's talk this through. There were two ways in which Rahul could die out. One is he dies out because he does horribly against you. And the second way he can die out is if he does equally well against you as you do against yourself, but he does horribly when he meets the other TAs. Right? In either case, you guys are evolutionarily stable and Rahul's in trouble. All right? Was that convincing enough an argument? There's a formal proof. Thanks, guys. There's a formal proof in the handout, but this will be enough to get us started. All right? So in this case, the mutant does okay against against S hat, but gets clobbered, or does badly, let's say, against S prime. Right? Right? So mutants that are going to die out are those that do badly against incumbents or do badly against themselves. In either case, S hat will be evolutionarily stable. All right? Now, next time, I want to take this further in two directions. I want to see what happens about evolutionary stability in more complicated games, for example, in cooperation games. And we're going to see that evolution doesn't do great in cooperation games. Right? And we're also, if we have time, going to look at sexual reproduction, which is probably what you guys are all interested in anyway. All right, I'll see you all on Monday. All right, so this was the definition we saw at the end last time. I tried to write it a bit larger. It just repeats the second of those definitions. This is the definition that connects the notion of evolutionary stability, for now in pure strategies, with Nash equilibrium. And basically it says this: to check whether a strategy is evolutionarily stable in pure strategies, first check whether S hat is a symmetric Nash equilibrium, and if it is, if it's a strict Nash equilibrium, we're done. And if it's not strict, that means there's at least some other strategy that would tie with S hat against S hat. Then compare how S hat does against this mutation with how the mutation does against itself. And if S hat does better than the mutation does against itself, then we're okay. Right? And one virtue of this definition is it's very easy to check. All right, so let's try an example to see that. And also to get us just back into gear and reminding ourselves what we're doing a bit. All right, so in this example, it's a sort of trivial game, but still, the game looks like this. All right, and we're asked the question, what is evolutionarily stable in this game? So no prizes for finding the symmetric Nash equilibrium in this game. Shout it out. What's the symmetric Nash equilibrium in this game? AA. Okay, so AA is a symmetric Nash equilibrium. That's easy to check. So really the only candidate for an evolutionarily stable strategy here is A. All right? So the second thing you would check is AA a strict Nash equilibrium? So what does strict Nash equilibrium mean? It means that if you deviate, you do strictly worse. All right, so is AA strict Nash? Well, is it strict Nash or not? It's not, right? So if you deviate to B, you notice very quickly that UAA is equal to UBA. Is that right? It's just a tie. Right? Both of these get 1. So it's not a strict Nash equilibrium. So we have to check our third rule. What's our third rule? So we need to check how does A do against the possible deviation, which is here, which is B here, how does that compare with B against itself? All right, so UAB, the payoff to A against B is 1, and the payoff to B against itself is 0. 1 is indeed bigger than 0, so we're okay, and A is in fact evolutionarily stable. All right, so just a very, very simple example to illustrate how quick it is to check this idea. All right, I want to spend all of today going over more interesting examples, so having the payoff for having invested in this last time. All right, and to start off with, let's get rid of this rather trivial example. I want to think about evolution as it's often applied in the social sciences. All right, so one thing you might talk about in the social sciences is the evolution of a social convention. All right, sometimes you'll read a lot in sociology or political science about the evolution of institutions or social conventions and things like this, maybe also in anthropology. And I want to see a trivial example of this just to see how this might work and see if we can learn anything. And the trivial example I'm going to think about is driving on the left or the right, on the left or right side of the road. All right, so this is a very simple social convention. I think we all can agree this is a social convention. And let's have a look at the payoffs in this little game. So you could imagine people drive on the left or drive on the right. Okay, and if you drive on the left and the other people are driving on the right, you don't do great, and nor do they. And if you drive on the right and they're driving on the left, you don't do great, and nor do they. All right, and if you both drive on the right, you do fine. But if you drive on the left, you do a little better because you look a little bit more sophisticated. All right? Okay, so this is our little game. And we can see this could be an evolutionary game, right? So you could imagine this emerging, you could imagine a government coming in and imposing a law saying everyone has to drive on the left or everyone has to drive on the right. But you could also imagine at the beginning of roads in different societies in different parts of the world, people just started doing something and then they settled down to one convention or another. And you can see how evolutionary stability is going to play a role here. Well, perhaps we should just work it through and see what happens. All right. So, what are the potential evolutionarily stable things here? What are the potentially evolutionarily stable things? Let's get some mics up. What's liable to be evolutionarily stable in this setting? Anyone? Yeah, there's I'm in here. Where's my other mic on that side? Yeah, there it is.
Left, and right are both candidates.
Good. So our obvious candidates here are left, and right. These are the two candidates. All right, or more formally, left is a candidate and right is a candidate. But you're right to say that left, and right are both Nash equilibria in this game. Is that right? And what's more, not only are they Nash equilibria, but what kind of Nash equilibria are they? They're strict Nash equilibria. In fact, they're strict. Both are strict. So indeed, left is evolutionarily stable, and right is evolutionarily stable. All right, let's just talk through the intuition for that and make it kind of clear. So suppose you're in a society in which everybody drives on the left. So this is England. And suppose a mutation occurs, and the mutation you could think of as an American tourist. All right, an American tourist is dropped into English society, hasn't read the guidebook carefully, starts driving on the right, and what happens to the tourists? They die out pretty rapidly, right? Right? And conversely, if you drop an unobservant Brit into America and they drive on the right, they're going to get squashed pretty quickly, right? So it's kind of clear why everyone driving on the left or why everyone driving on the right is each of these are perfectly good evolutionarily stable social conventions. All right, but despite that simplicity, there's kind of a useful lesson here. So the first lesson here is you can have multiple evolutionarily stable settings. You could have multiple social conventions that are evolutionarily stable. We shouldn't be surprised, particularly, if we think there's some evolutionary type force, some sort of random dynamic going on that's generating social conventions that are then stable. We should not be surprised to see different social conventions in different parts of the world. And in fact, we do. We do see parts of the world, like England and Japan and Australia, where they drive on the left, and we see parts of the world, like France and America, where they drive on the right. All right, so we can have multiple evolutionary stable conventions. All right. And there's another lesson here, which is you could imagine a society settling down to a social convention down here. You could imagine ending up at a social convention of right-right. And what do we know about the social convention of everyone driving on the right? We know it's worse. We know it's worse than the social convention of everyone driving on the left. All right? At least in my version. All right? So what do we regard it? What we see here, we can see that they're not necessarily efficient. These need not be equally good. All right? So it's hard to resist saying that American society's driving habits, if we think about the alternatives to evolution, are a good example of unintelligent design. All right? All right? All right? So when you're talking about this in a more a less formal way in your anthropology or political science or sociology classes, you want to have in the back of your mind what we mean by evolutionary stability, and that it doesn't necessarily mean that we're going to arrive at efficiency. Right? And in some sense, this is exactly analogous to what we discussed when we looked at games like this with rational players playing, if you think about coordination games. These are essentially coordination games. All right, that was a fairly straightforward example. To leave it up there, let me... Well, there's another board here somewhere. Here we go. Let's look at yet another example, slightly more interesting. All right. So today I'm going to spend most of today just looking at examples and talking about them. All right, so here's another example of a game we might imagine. And once again, it's a 2x2 game, nice and simple game. All right, and here the payoffs are as follows. So down the diagonal, we have 0, 0, 0, 0, and off the diagonal, we have 2, 1, and 1, 2. All right? So what is this game, essentially? It's very, very similar to a game we've seen already in class. Anybody? This is essentially Battle of the Sexes. Right? I've taken the Battle of the Sexes game, the dating game, I've just twiddled it around to make it symmetric. All right, so this is a symmetric version of Battle of the Sexes. Or our dating game. All right? And you could think of this game also in the context of driving around. All right? So you could imagine that one version of this game, you sometimes hear this game referred to as chicken. All right? What's the game chicken when cars are involved? Anybody? What's the game chicken when cars are involved? Now, it's probably a good thing if people don't know this. No one knows this? Okay. Somebody knows it. Can I get the mic way back there? Yeah. Shout out. Right. So you could imagine, here we are on a road that perhaps isn't big enough to have driving on the left and driving on the right. These two cars face each other. They drive towards each other, both of them going in the middle of the road. Right? And the loser is the person who swerves first. So you could think of A as being the aggressive strategy of not swerving, and B as being the less aggressive, the more benevolent strategy, if you like, of swerving. So the best thing for you is for you to be aggressive and the other person to swerve, and then at least they remain alive. All right? And conversely, if you're benevolent and they swerve, you remain alive but they win. And unfortunately now, if you're both aggressive, you get nothing. And the way we've written this game, if you're both benevolent, you get nothing. Right? You could imagine making some more negatives here. All right. So this is a game that seems kind of important in nature, not just in teenage male behavior, but in animal behavior, since we're starting to talk about aggression and non-aggression. All right? Okay, so what's evolutionarily stable in this game? Well, remember, our starting point is what? Our starting point is to look for symmetric Nash equilibria. Okay, so are there any symmetric Nash equilibria in this game? And if so, what are they? Anybody? Well, there are some Nash equilibria in pure strategies. There are some Nash equilibria in this game. For example, AB is a Nash equilibrium, and BA is a Nash equilibrium. But unfortunately, they're not symmetric. Right? They're not symmetric. And so far, we're focusing on games that are symmetric. Right? This is random matching. There's no asymmetry in the roles of the row and column player. Although in the in the reading packet I made for you, they do also look at some asymmetric versions of games. But for now, we're just looking at symmetry. So neither AB nor BA will serve our purpose because they're not symmetric Nash equilibria. In fact, there is no symmetric. There's no symmetric pure strategy Nash equilibrium in this game. All right. So it can't be that if this was a species, if this was an animal that came in that had two possible strategies, aggression or passivity. All right. It can't be the case in this particular game that you end up with 100% aggression out there, 100% aggressive genes out there, or 100% unaggressive genes out there. In either case, if you had 100% aggressive genes out there, then it would be doing very, very badly, and you get an invasion of passive genes. And if you had 100% passive genes out there, you get an invasion of aggressive genes. Right? You can't have a pure ESS, a pure evolutionary stable gene mix out there. All right. So what does that suggest? It suggests we should start looking at mixed strategies. All right. There is a mixed strategy. Yeah, there is a mixed. Let's have the word symmetric first. There is a symmetric mixed strategy Nash equilibrium in the game. All right? And we could go through and work it out. We all know now, probably you've been laboring through the homework assignments, so you all know how to find a mixed strategy Nash equilibrium in this game. You have to set the mix to make the other player indifferent between her two strategies. But this is a game we've seen already. It's essentially Battle of the Sexes. All right, so we probably remember from a week ago what that equilibrium mix is. Can anyone remember what the equilibrium mix is in Battle of the Sexes? It's 2/3, 1/3. Turns out that 2/3, 1/3, 2/3, 1/3 is a Nash equilibrium here. So if you go back to your notes a week ago, you'll find something very much like that was a Nash equilibrium in the original version of Battle of the Sexes. A week ago, it would have been 2/3, 1/3, 1/3, 2/3 because things weren't symmetric. Now I've made things symmetric. It's just 2/3, 1/3 for both players. You can check it at home. All right? So what's this telling us? It's telling us that there's at least an equilibrium in this game in which 2/3 of the genes are aggressive and 1/3 of the genes are unaggressive. All right? But does that mean anything? What could that mean? In terms of biology, what could that mean? Well, so far, we've been looking at evolutionary stable pure strategies. All right? And evolutionary stable pure strategies correspond to evolutionary stable situations in nature, which are what are called monomorphic. All right? Monomorphic. And monomorphic means one shape or you only get one type out there. But you can also have situations in nature where there are actually stable mixed types. All right? And they're called polymorphic. Polymorphic. probably not hyphenated, it's probably just one word. So you can have a monomorphic population. That's what we've focused on so far, but you could also have a mixed population. All right? Now, for this to be a mixed population, we better change the definition accordingly. All right? We'll come back and talk about what it means in a second a bit more, but first we better make sure we have an okay definition for it. So what I'm going to do is, I'm going to drag this definition down and do something you're not meant to do it usually in teaching. I'm going to use the eraser to correct my definition. All right, so here I have my pure strategy definition, and let me just change it into a definition that will allow for these polymorphic populations. So I'm going to change this into a p hat. I'm going to change this pure into mixed, and everywhere you see an s hat, I'm going to put a p hat, and to here too. And everywhere you see an S prime, I'm going to put a P prime. And the reason I'm doing this way is I want to emphasize that there's nothing new here. I'm just writing down the same definition as we had before, except I'm now allowing for the idea of populations being mixed. And I'm also, just note in passing, I'm also allowing for the possibility that a mutation might be mixed. Mutation might be mixed. Did I catch them all? All right, so I've just gone through the definition you have, and I've switched everything from pure to mixed. Let's lift it up there again. Okay. So in our example, does the mix 2/3, 1/3, satisfy the definition above? Let's go through carefully. All right? So 2/3, 1/3 is a Nash equilibrium. So we've satisfied part A. It's a symmetric Nash equilibrium. So we're okay there. Is this equilibrium a strict equilibrium? Is this mixed population, 2/3 aggressive and 1/3 unaggressive, or this mixed strategy, is it a strict equilibrium? Well, how do deviations do against it? Anybody?
Equally well.
Yeah, go ahead.
Equally well.
Equally well, thank you. So, right, so it can't be a strict Nash equilibrium, because if we deviated to A, we'd do as well as we were doing in the mix. Or if we deviated to B, we'd do as well as we're doing in the mix. And what I'm saying is, an A mutation does exactly as well against this mix as the mix does against itself, and a B mutation does exactly as well. In fact, that's how we constructed the equilibrium in the first place, right? We chose a P that made you indifferent between A and B. All right? So in a mixed Nash equilibrium, it can't be strict. Cannot be strict since it is mixed. In a mixed equilibrium, in a mixed Nash equilibrium, a genuinely mixed Nash equilibrium, by definition, you're indifferent between the strategies in the mix. All right? So to show that this is in fact evolutionarily stable, we'd have to show rule B. So we need to check, give ourselves some room here. We need to check how the payoff of this strategy, let's call it P hat, how P hat does against all possible deviations, and compare that with how those deviations do against themselves. We have to make this comparison. How does this mix do against all other possible mixes versus how those mixes do against themselves? And we'd have to do this, unfortunately, we'd have to check this for all possible, and now we have to be careful, all possible mixed mutations P prime. All right, so that would take us a while. All right, it's actually possible to do. If you do some enough math, it isn't so hard to do. So rather than prove that to you, let me give you a heuristic argument why this is the case. All right, I'm trying to convince you, without actually proving it, that this is indeed the case. All right, so here we are with this population. Exactly 2/3 of the population is aggressive, and 1/3 of the population is passive. All right, and suppose there is a mutation, P prime, that is more aggressive than P hat. It's a relatively aggressive mutation. For example, this mutation may be 100% aggressive, or at least it may be very, very highly aggressive. It may be 90% aggressive or something. All right? Now, I want to argue that that aggressive mutation is going to die out. And I'm going to argue it by thinking about this rule. So I want to argue that the reason this very aggressive mutation dies out is because the aggressive mutation does very badly against itself. Is that right? If you have a very aggressive mutant, the very aggressive mutants do very, very badly against themselves. They get 0. All right? And that's going to cause them to die out. All right? What about the other extreme? What about a deviation that's very passive? So a very nice mutation of very passive types. For example, it could be 100% B, or 99% B, or 98% B. All right? How will that do? All right? Well, it turns out in this game, again, it doesn't do very well against itself. Right? And in addition, the original mix, the mix P hat, that is more aggressive than this very passive mutation, does very well against the mutation. All right? So the mix that's in there, the mix in the population already, is relatively aggressive compared to this very passive mutation, and so that the incumbents, the relatively aggressive incumbents, are doing very, very well on average against the mutation, and hence, once again, this equality holds. All right? So just heuristically, without proving it, more aggressive mutations are going to lose out here because they do very badly against themselves, and more passive mutations are going to do badly because they make life easy for P hat, which is more aggressive than them. All right? Right? So it wasn't a proof, it's a heuristic argument, and it turns out indeed to be the case. All right? So in this particular game, a game you could imagine in nature, all right, a game involving aggression and passivity within this species, it turns out that in this example, the only equilibrium is a mixed equilibrium with 2/3 aggressive and 1/3 unaggressive. Now this raises the question, what does it mean? What does it mean to have a mix in nature? All right? So it could mean two different things. It could mean that the gene itself is randomizing. It could mean that the strategy played by the particular ant, squirrel, lion, or spider is actually to randomize. Right? That's possible. But there's another thing it could mean that's probably a little bit more important. What's the other thing it could mean? It could mean that in the stable mix, the evolutionarily stable population for this particular spider, say, it could be that there are actually two types surviving stably in these proportions. If you go back to what we said about mixed strategies a week ago, we said one of the possible interpretations of mixed strategies is not that people are necessarily randomizing, but that you see a mix of different strategies in society. Right? And again, in nature, one of the impossible interpretations here, the polymorphic population interpretation, is that rather than just have all of this species look and act alike, it could be there's a stable mix of behaviors and or appearances in this species. All right? So let me try and convince you that that's not an uninteresting idea. All right? So again, with apologies, I'm not a biologist. I spent a bit of time on the web this weekend trying to come up with good examples for you. And the example I really wanted to come up with, I couldn't find on the web, which makes me think maybe it's apocryphal. But I'll tell you the story anyway. All right? It's not entirely apocryphal. It may just be that my version of it's apocryphal. All right? So this particular example I have in mind is to do with elephant seals. All right? And I think even if it isn't true of elephant seals, it's definitely true of certain types of fish. So the elephant seals make a better story. All right? So, okay, so imagine that these elephant seals, it turns out that there are two possible mating strategies for male elephant seals. By the way, do you all know what elephant seals are? Yeah, they're these big, people looking blankly at me. You have some rough image in your mind of an elephant seal? You've all seen enough nature shows, right? Yeah? Yes? No? Yes? Okay. So there are two male mating strategies for the male elephant seal. One successful male mating strategy is to be the head, the dominant, or a dominant male elephant seal, and have, as it were, harem of many female elephant seals with which the male mates with. All right? For the males in the room, don't get too happy. These are elephant seals, right? They're not you guys, right? All right. So one possible successful strategy is to be a successful bull elephant seal and have many, essentially wives, right? So to be polygamous, all right? And presumably to do that well, a thing that would go well with that strategy is to be huge, right? So you could imagine the successful male elephant seal being an enormous animal, looks like a sort of a linebacker in football, right? And basically fights off all other big elephant seals that show up, all right? But it turns out, I think I'm right in saying, if I did my research correctly, this is true among northern elephant seals, but not true among southern elephant seals. We're talking about the Arctic, not the Antarctic, but someone's going to correct me. Once it's on the web, I'm going to get floods of emails saying I've got this wrong. Never mind. Okay, so it turns out that this is not quite evolutionarily stable. All right? Why is this not evolutionarily stable? What's the alternative male strategy that can successfully invade the large bull harem keeper elephant seal? Any guesses? Anyone looking for a successful career as an elephant seal? As a male elephant seal? No? Say again? Good. So good. Thank you. Did people catch that? So a good alternative strategy is to be a male elephant seal who looks remarkably like a female elephant seal. All right. So instead of looking like a linebacker, they look like a wide receiver. All right. I'm probably offending somebody in the football team, right? But you get the idea, right? And what do? They sneak in among these large numbers of male elephant seals, and they just mate with a few of them. All right? So they look like a female elephant seal. They can hide among the female elephant seals in the harem, and they mate with a few of them. And provided this is successful enough, it'll be evolutionarily stable for the female elephant seal to want to mate with that too. All right? Right? Now, I forget if actually this is exactly right, but it's certainly, I did enough research over the weekend to know it's right, at least in some species. And the nicest part of this story is that at least some biologists have a nice technical name for this strategy that was well described by our friend at the back. And the name for this strategy is SLF. And since we're on film, I'm going to tell you what the S and the L are, but you'll have to guess the rest. So this is sneaky. This is little, and you can guess what that is. All right? So this turns out to be actually quite a common occurrence. It's been observed in a number of different species, perhaps not with the full added color I just gave to it. All right? Okay. So having convinced you that polymorphic populations can be interesting, let's go back to a more subtle case of aggression and non-aggression, because that seems to be one of the most important things we can think of in animal behavior. Okay? So let's go back and look at a harder example of this, of where we started. All right? So as these examples get harder, they also get more interesting. So that's why I want to get a little bit harder. So the chicken game, the battle of the sexes game, is not a particularly interesting version of aggression and non-aggression. Let's look at a more general version of aggression versus non-aggression. And let's look at a game that's been studied a lot by biologists and a little bit by economists called hawk-dove. All right? And again, just to stress, we're talking about we're only talking about within species competition here. So I don't mean hawks versus doves. I mean thinking of hawk as being an aggressive strategy and dove as being a dovish, a passive strategy. All right? So here's the game, and now we're going to look at more general payoffs than we did before. All right? So this is the hawk strategy. This is the dove strategy. Hawk and dove, and the payoffs are as follows: V plus C, start again. V minus c over 2 and v minus c over 2. And here we get v over 2 and v over 2. And here we get v and 0, and here we get 0 and v. All right, so this is a generalization, a more interesting version of the game we saw already. Let's just talk about it a little bit. So the idea here is there's some potential battle that can occur among these two animals, and the prize in the battle, the prize is v. All right, so v is the victor's spoils, and we're going to assume that v is positive. Right? And unfortunately, if the animals fight, so if the hawk meets another hawk and they fight one another, then there are costs of fighting. So the costs of fighting are c, and again, we'll assume that they're positive. Right? So this is the cost of fighting. All right? And this more general format is going to allow us to do two things. We're going to look and ask what is going to be evolutionarily stable, all right, including mixtures now, and we're also going to be able to ask what will happen to the evolutionarily stable mix as we change the prize or as we change the cost of fighting. All right? Seems a more interesting, a richer game. Okay, so let's start off by asking, could we have an evolutionary stable population of doves? All right? So is D an evolutionary stable strategy? I'll start using the term ESS now. So ESS means an evolutionary stable strategy. Is D an ESS? All right, so in this game, could it be the case that we end up with a population of doves? Seems a nice thing to imagine, all right, but is it going to occur in this game in nature? What do people think? How do we go about checking that? How do we go about checking that? What's the first step? First step is to ask, is dove a Nash equilibrium? Right? If it's evolutionary stable, in particular, dove would have to be a Nash equilibrium. That's going to make it pretty easy to check. So is dove a Nash equilibrium in this game? It's not, right? But why not? Because if you had a mutation, I'm tempted to say deviation, but I won't think of it as a mutation. If I had a mutation of hawks, all right, the hawk mutation against the doves is getting V, whereas dove against dove is only getting V over 2. All right? So it's not Nash. All right, so we can't have an evolutionary stable population of doves, and the reason is there will be a hawk mutation, an aggressive type will get in there and grow, much like we had last week when we dropped Rahul into the classroom in Prisoner's Dilemma, and he grew. All right, or his type grew. Okay, so second question is hawk an evolutionary stable strategy? Is hawk an evolutionary stable strategy? So how do we check this? Well, we have to look at once again and ask the question. This is first question to ask is HH a Nash equilibrium? All right. So is it a Nash equilibrium? Well, I claim it depends. I claim it's a Nash equilibrium provided V minus C over 2 is at least as large as 0. Is that right? Is that right? It's a Nash equilibrium. It's a symmetric Nash equilibrium provided hawk against hawk does better, or does at least as well as dove against hawk. So the answer is yes if V minus C over 2 is at least as big as 0. All right? So now we have to think fairly carefully, because there's two cases. So case 1 is the easy case, which is when V is strictly bigger than C. If V is strictly bigger than C, then V minus C over 2 is strictly positive. Is that right? In which case, what kind of a Nash equilibrium is this? It's strict, right? So if V is bigger than C, then hawk-hawk is a strict Nash equilibrium. It's a strict Nash equilibrium. All right? The second case is if V is equal to C. If V is equal to C, then V minus C over 2 is actually equal to 0, which is the same as saying that the payoff of hawk against hawk is equal to the payoff of dove against hawk. Is that correct? All right. So in that case, what do we have to check? Oh, I've deleted it now. You have to come from your notes. What do I have to check in the case in which there's a tie like that? What do I have to check? I have to check. In this case, I need to check how hawk does against dove, because dove will be the mutation. I need to compare that with the payoff of dove against dove. All right. Okay. So how does hawk do against dove? What's the payoff of hawk against dove? Anybody? Payoff of hawk against dove. This shouldn't be that hard. It's on the board. Hawk against dove. Shout it out. V. Thank you. So this is V. And how about the payoff of dove against dove? V over 2. So which is bigger, V or V over 2? V is bigger because it's positive, right? So okay. So this is bigger. So we're okay. So what have we shown? We've shown. Let's just draw it over here. We've shown that if V is at least as big as C, then H is an evolutionary stable strategy. All right. So in this game, in this setting in nature, if the size of the prize to winning the fight is bigger than the costs that would occur if there is a fight, then it can occur that all the animals in this species are going to fight in an evolutionary stable setting. Let me say it again. If it turns out in this setting in nature that the prize to winning the fight is bigger, or at least as big as, the cost of fighting, then it will turn out that it will be evolutionarily stable for all the animals to fight. The only surviving genes will be the aggressive genes. All right? And what does that mean? So what typically do we think of as the payoff to fights and the cost of fighting? So let's put this in a biological context. The fight could be about what? It could be, let's go back to where we started from, it could be males fighting for the right to mate with females. That's going to be pretty important for genetic fitness. It could be females fighting over the right to mate with males. It could also be fighting over, for example, food or shelter. Right? So if the prize is large and the cost of fighting is small, you're going to see fights in nature. All right? But we're not done yet. Why are we not done? Because we've only considered the case when V is bigger than C. So we also need to consider the case when C is bigger than V. This is the case where the cost of fighting are high relative to the prize in the particular setting we're looking at. So again, let's go back to the example. Suppose the cost of fighting could be that the animal could lose a leg or even its life, and the prize is just today's meal. Right? Perhaps there are other meals out there. Then we'd expect something different to occur. However, we've already concluded that even in this setting, it cannot be the case only to have doves in the population. Right? We've shown that even in the case where the cost of fighting are high relative to the prizes, it cannot be evolutionarily stable only to have dove genes around, passive genes around. So in this case, it must be the case that if anything is evolutionarily stable, it's going to be what? It's going to be a mix. It's going to be a mix. So in this case, right, we know that H is not ESS, And we know that D is not ESS. So what about a mix? What about some mix p hat? All right? And we could actually put the p hat in here. We can imagine looking for a mix p hat 1 minus p hat that will be stable. Now, how do we go about finding a possible mixed population that has some chance, has some hope of being evolutionarily stable? So here we are, we're biologists, we're about to do an experiment, we're about to either experiment, we're about to go out and do some field work out there, and we want to set things up, and we're asking the question, what's the mix we expect to see? What's the first exercise we should do here? What if it has any hope to be evolutionarily stable, what does it have to be? It has to be a symmetric Nash equilibrium. So the first step is, step 1, find a symmetric mixed Nash equilibrium in which people will be playing p hat 1 minus p hat. It's symmetric, so both sides will be playing this. Okay, so this is good review for the exam on Wednesday. How do I go about finding a mixed equilibrium here? Shouldn't be too many blank faces. This is likely to come up on the exam on Wednesday. Let's get some cold calling going on here. How do I find a mixed strategy? Just find anybody. How do we find it? Yeah. How do I find a mixed strategy equilibrium?
Just use the other player's payoff.
I use the other player's payoffs, and what do I do with the other person's payoffs?
You set them equal?
Set them equal, okay? Okay, so here it's a symmetric game. It's really, there's only one population out there. So what I need the payoff of hawk against p hat, or p hat 1 minus p. I need this to be equal to the payoff of dove against this p. All right? So the payoff of hawk is going to be what? Just reading up from up there. Let's use our pointer. So hawk p hat of the time will meet another hawk and get this payoff. Right? So they'll get, so p of the time, they'll get a payoff of v minus c over 2. And 1 minus p hat of the time, they'll meet a dove and get a payoff of v. And dove, against this same mix, p hat 1 minus p hat of the time, they'll meet a hawk and get nothing. And 1 minus p hat of the time, they'll meet another dove and get v over 2. Okay, everyone happy with the way I did that? That should be pretty familiar territory to everybody by now. Is that right? Okay, so I'm going to set these two things equal to each other, since they must be equal if this is in fact a mixed strategy equilibrium. All right, and then I'm going to play around with the algebra, but so as to save time, I did it at home. So trust me on this. Trust me. All right, this is implication with the word trust on top of it, right? Right? Trust me that I got the algebra right, or check me at home. This is going to turn out to imply that p hat equals v on c. Right? P hat equals v on c. All right? So it turns out that there is, in fact, a mixed Nash equilibrium. There's a mixed Nash equilibrium, which is of the following form: v on c and 1 minus v on c, played by both players. Okay? V on c, 1 minus v on c, played by both players. All right? Is this a strict Nash equilibrium? I found the Nash equilibrium. Is it strict? Everyone should be shouting it out. Is it strict? It can't be strict because it's mixed, right? By definition, it can't be strict because we know that deviating to h, or for that matter deviating to d, yields the same payoff. So it can't be a strict Nash equilibrium, so we need to check something. So we need to check. So it's not strict, not strict. So we need to check. We need to check whether u of p hat against p prime is bigger than u of p prime against itself. And we need to check this for all possible mutations p prime. And again, that would take a little bit of time to do in class, so just trust me on it. And once again, let me give you the heuristic argument I gave to you before. It's essentially the same argument. All right? So the heuristic argument I gave to you before was, imagine a p prime, a mutation that is more aggressive than our candidate equilibrium. Right? If it's more aggressive, then it's going to do very, very badly against itself. Right? Because C is bigger than V in this case, it's actually going to get negative payoffs against itself. Right? Since it gets negative payoffs against itself, it turns out that will cause it to die out. Conversely, imagine a mutation that's relatively soft, that's relatively dovish. This mutation is very good for the incumbents because the incumbents essentially beat up on it or score very highly on it. Right? So once again, the more dovish mutation will die out. All right? So again, that isn't a proof, but trust the argument. And just, we need to show this, but it does in fact turn out to be the case. All right. So what have we shown here? I didn't prove the last bit, but what we've argued is that in the case in which the costs of fighting in nature are bigger than the prizes of winning the fight, it is not the case that we end up with 100% doves. Right? So we don't end up with no fights, for example. No fights is not what we would expect to observe in nature. And we don't end up with 100% fights. 100% fights is not what we'd expect to see in nature. What we end up with is a mixture of hawks and doves such that V over C is the proportion of hawks. Right? So the fights that occur are essentially V over C squared. All right? We can actually observe those fights in nature. Okay, what lessons can we draw from this? Sort of biology lessons. All right, so we used a lot of what we learned in the last day or so to figure out what the ESS was there. We kind of did the nerdy part. Now let's try and draw some lessons from this. All right. So the first thing we know is I've hidden what we cared about here. So we know that if V is smaller than C, then the evolutionary stable mixed population has V on C hawks. All right. So let's just see how much of this makes sense. So as V goes up, as the prizes go up, if you took the same species and put them into a setting in which the prizes tended to be larger, all right, what would we expect to see? Do we expect to see the proportion of hawks go up or down? Up, right? As V goes up, we see more hawks. All right, what else do we see? Not so surprisingly, as C goes up, if we look at settings where the cost of fighting is higher, right, settings where the cost of fighting is higher, we tend to see more doves. All right? All right? And this is in S, so more hawks in the evolutionary stable mix, and more doves in the evolutionary stable mix. Now, it's possible, of course, that the species in question can recognize these two different situations and be coded differently, to behave differently in these two different situations, but that's beyond the class for now. All right? Perhaps a more interesting observation is about the payoffs. Let's look at the actual genetic fitness of this species overall. So in this mix, what is the payoff? Well, how are we going to figure out what is the payoff? So the payoff in this mix, we can actually construct by looking at the payoff to dove. It doesn't really matter whether you look at the payoff to dove or the payoff to hawk. So let's look at the payoff to dove. All right, so the payoff was what? It was, if you were dove, then 1 minus v on c of the time you met another dove, and in that instance you got a payoff of v on 2. And it must be the payoff to being a dove is the same since they're mixing. All right, so this is the payoff. All right. So what's happening to this payoff as we increase the cost of fighting? All right. What happens as C rises? So just to note out what happens as C goes up. So you might think, naively, you might think that if you're in a setting, be it a social evolutionary setting or a biology, a nature evolutionary setting, you might think that as the cost of fighting goes up for you guys in society or for the ants, antelopes or lions we're talking about, you might think that the payoffs in society go down. Right? Cost of fighting go up, more limbs get lost and so on. Sounds like that's going to be bad for the overall genetic fitness of the species. But in fact, we don't find that. What happens as C goes up? The payoff goes up, right? As C goes up, the payoff goes up. If we take C bigger, all right, this begets smaller, which means this is bigger. All right, everyone see that? Everyone see that? So just look at that term, 1 minus v over c times v over 2. It's actually increasing. It's increasing in C. So how does that work? As the cost of fighting go up, it's true that if you do fight, you're more likely to lose a finger or a limb or a claw or a thank you, whatever those things are called. Right? Or a foot, whatever it is you're likely to lose. But the number of fights that actually occur in this evolutionarily stable mix goes down, and it goes down sufficiently much to compensate you for that. Right? Kind of a remarkable thing. Right? So these animals that actually are going to lose a lot through fighting are actually going to do rather well overall because of that mix effect. Because that, if you like, it's one of those strategic effects again. All right? Now, of course, that raises a question, which is what would happen if a particular part of this species evolved that had lower cost of fighting, right? That could regrow a leg. Right? Sounds like that would do pretty well, and that would be bad news for the species as a whole. All right. Third thing we can observe here is what's sometimes called identification. Identification. So what does identification mean here? It means that by observing the data in nature, by going out and filming these animals behaving for hours and hours, or changing their setting in a lab and seeing how they interact, or changing their setting in the field and seeing how they interact, we can actually observe something, namely the proportion of fights. Perhaps we can do better now and actually look at the genetics directly, since science has evolved, all right? And we can actually back out the V and the C. Right? By looking at the proportion of hawk genes out there, or hawkish behavior out there, we can actually identify what must be the ratio of V to C. We can tell what the ratio V over C is from looking at data. Right? We started off with a little matrix. I just written in V's and C's. I didn't put any numbers in there. We can't tell what V is. We can't tell what C is. But we can tell what the ratio is by looking at real-world data. So if you spend enough hours in front of the TV watching nature shows, you could back this out. Not literally. Right? You need to actually do some serious work. All right? So this is a useful input of theory into empirical science. You want theory to be able to set up the science so you can back out the unknowns in the theory. And that's called identification, not just in biology, but in economics as well. All right. Now, there's one other thing you'd like theory to be, other than identifiable. You'd like theory to be testable. Right? You'd like theory to make predictions that were kind of outside of the sample you started with. Right? Is what I'm saying familiar to everybody in the room? This is a very familiar idea, I'm hoping, to everybody. slightly philosophy, but very familiar idea. If you have a new theory, it's one thing for that theory to explain the existing facts, right? But you'd like it to predict new facts. Why? Because it might be a little bit too easy to reverse engineer a model or theory to fit existing facts. But if it has to deal with new facts, that's kind of exciting, right? That's a real test. That make sense? So you might ask about this theory. You might say, well, it's just a whole bunch of just so stories. I don't know what I mean by a just so story. It's a just so stories was children's stories written by Kipling. And people sometimes accuse a lot of evolutionary theory as being just so stories because you know what the fact is already, and you reverse the game, you come up with a story afterwards. And I say that doesn't sound like good science. So you'd like this theory that matches game theory with evolution, to predict something that we had not seen before, and then we can go out and look for it and see if it's there. And that's exactly what we now have. So our last example is a slightly more complicated game again. And the slightly more complicated game has 3 strategies. And the strategies are called, well, I'll tell you what the strategies are called in a second, actually. I'll give you the payoffs, first of all. So once again, this is a game about different forms of aggression, and we'll look at we'll look at other interpretations in a second. And once again, V is going to be the prize for winning, 0 is going to be the prize for losing, and 1 is if it's a tie. I'm just short-sighted enough so I can't read my own writing, so I hope I got this right. There we go. All right. So this is the game, and we're going to assume that the prize V is somewhere between 1 and 2. All right. So V you can think of as winning, 0 is losing, and 1 is if it's a tie. Does anyone recognize what this game essentially is? It's essentially rock, paper, scissors. Now, it turns out that when biologists play rock, paper, scissors, they give it a different name. They call it scratch, bite, and trample. Scratch, bite, and trample is essentially the tactics of the Australian football team. All right, so scratch, bite, and trample are the 3 strategies. And it's a little bit like rock, papers, and scissors. How we change it? First, we added 1 to all the payoffs to make sure there's no negatives in there. And second, we added a little bit more than 1 to winning. Right? If we add 1 to everything, sorry, a little bit less than 1 to winning. Right? So if we added 1 to everything, then V would have been 2, but we've kept V somewhere between 1 and 2. All right? So this is certainly a game you could imagine in nature. There's 3 possible strategies for this species, and the payoff matrix happens to look like this. All right, so where's my prediction going to come from? Well, since this is rock, paper, scissors, we know that there's really only one hope for an evolutionary stable strategy. Right? Since it's essentially rock, paper, scissors, if there is an evolutionary stable strategy or an evolutionary stable mix, what must it be? 1/3, 1/3, 1/3. Right? So the only hope for an ESS is 1/3, 1/3, 1/3. All right, let's put that in here. So 1/3, 1/3, 1/3. And you can check at home that that indeed is a mixed strategy equilibrium. All right? And the question is this evolutionarily stable? Is this evolutionarily stable? All right? So we know it's a Nash equilibrium, that I've given you, and we know it's not a strict Nash equilibrium. Everyone okay with that? It can't be a strict Nash equilibrium because it's mixed. All right? So if this is an ESS, it must be the case we'd have to check that, let's call this P hat again, like we've been doing. Right? We have to check that the payoff from P hat against any other P prime would have to be bigger than the payoff from P prime against itself. Right? We need that to be the case. All right, so let P prime be scratch. Let P prime be scratch. All right? So let's compare these things. So U of P hat against scratch is what? Well, you're playing against scratch. You are a third scratch, a third bite, a third trample. So a third of the time you get 1, a third of the time you get nothing, and a third of the time you get V. Is that right? So your payoff is 1 plus V over 3. All right? How do we do if we're scratch against scratch? The payoff of scratch against scratch is what? No prizes for this. What's the payoff of scratch against scratch? 1. Which is bigger, 1 plus V on 3 or 1? Well, look, V is less than 2, right? V is less than 2, so 1 plus V on 3 is less than 1, so 1 is bigger. So in this game, the only hope for an evolutionarily stable mix was a third, a third, a third, and it isn't stable. So here's an example. In this example, there is no evolutionarily stable strategy. There's no evolutionarily stable mix. And then the obvious question is, what does that mean in nature? Can we find a setting that looks like rock, paper, scissors in nature in which nothing is evolutionarily stable? If nothing is evolutionarily stable, what's going to happen? We're going to see kind of cycling around. You're going to see a lot of the scratch strategy followed by a lot of the trample strategy, followed by a lot of the bite strategy, and so on. All right? So it turns out that's exactly what you see when you look at these. The example I've left you on the web, there's an article in Nature in the mid-90s that looks at a certain type of lizards. And these lizards come in 3 colors. I forget what the colors are. No, I wrote it down. One is orange, one is yellow, and one is blue. And these lizards have 3 strategies. One, the orange lizard is like our big elephant bull. It likes to keep a harem of many, or a large territory with many female lizards in it to mate with. But that can be invaded by our SLF strategy, which turns out to be the yellow lizard. The yellow lizard can invade and just mate with a few of these female lizards. All right? But when there are too many of these sneaky yellow lizards, then it turns out that they can be invaded by a blue lizard, and the blue lizard has much smaller territories. It's almost monogamous. All right? So what happens in nature is you get a cycle: orange invaded by yellow, invaded by blue, harem keeper invaded by sneaky, invaded by monogamous, invaded by harem keeper again. And indeed, the population does cycle around exactly as predicted by the model. So here's an example of evolutionary theory via game theory making a prediction that we can actually go off and test and find. This, for biologists, was like finding a black hole. It's a really cool thing. All right, we'll leave evolution here. Midterm on Wednesday. We'll come back to do something totally different next week. See you on Wednesday. Okay, so I want to set up a new topic today. And to get us started, I thought we'd play a game. So the game is going to be called Cash in a Hat. And we'll see what this game is like in a minute. So the idea is this. There's going to be 2 players. I'm going to pick on 2 of you. I hope I can find people who've brought some money to class. All right, so player 1 will have a choice. Player 1 can put nothing, $1, or $3 into a hat. The hat will then be given to player 2. And player 2 can look at what's in the hat, and either she can match what's in the hat, i.e. add the same amount in, so 1 if it's 1 or 3 if it's 3, or she can simply take the cash. All right, the payoffs of this game will be as follows. Player 1, if they put nothing in, they're not going to get anything. If they put 1 in and it's matched, then they double their money, so they get 2 back. If they put 3 in and it's matched, then they double their money, so they get 6 back. They'll net 3. However, if they put 1 in and player 2 takes it, they've just lost their $1. And if they put $3 in and player 2 takes it, they've lost $3. Right, everyone understand that? Pretty simple. From player 2's point of view, if player 2 matches, then they get their investment back plus $1.50 if they matched 1, so they get $2.50 back in all. And they get their investment back plus $2 if they match 3, so that's if they get 5 back in all. And of course, if they simply take the money out of the hat and put it in their pocket, then that's what they get in the game. Right, so once again, if player 2 matches with $1, there's $1 in the hat and she matches, then she gets back $2.50 for a profit of $1.50. If there's $3 and she matches 3, she gets back 5 for a profit of 2. And if she simply takes the money out of the hat and puts it in her pocket, then she gets however much money was in the hat. All right, so I here will be the provider of the hat. We'll use the same hat we used before. And if necessary, I'll provide sheets of paper we can write IOUs on, but I'm hoping we can play for real cash. Later on, it could be nice to get a chair here, but for now, let me just go down here. And I'm going to grab this mic. Who here wants to be player 1? Who brought some money to class today? I'm quite willing to pick on somebody. All right, good, good, good. So player 1 is, what's your name again?
Justin.
Justin. So hold on to that hat for a second, all right? And who wants to be player 2? All right, so this gentleman here, whose name is?
Nate.
Nate. All right, so we have Justin and Nate. All right, so Justin, you have to decide how much money you're going to put in the hat. Did you bring some money too, Nate? Better make sure you have, otherwise borrow some from your neighbors.
All right, I'm going to put in $1.
All right. All right, so the money's been put in the hat and delivered to Nate.
So I'm going to put in the $1 too, so that I get...
All right, so if we empty out the hat, here's our beautiful pink hat. I should really have the hat passed across the room rather than have me do it, but we have $2 in the hat, so I'm going to pay each, I'm going to pay, what am I going to pay? I'm going to pay player 1 $2. I'm going to give back their original $1 and give them 2 in a second. And I'm going to pay player 2 $1.50. You just hold the hat. We'll do that for
$2.50, right?
$2.50. Yes. Well, you got your money back. Trying to cheat you here.
Is that it?
All right. So player, I'll get you the rest in a second. Hang on a second, right? For now, and so double the money. All right. All right. All right. So there's one reason to take this class is if you play well, you get money. All right. Now let's just try again. All right. So we had one round of this. Let's have another round. Who wants to play player 1 now? All right. So Katie is player 1. All right. Katie, you bring some money?
Yeah, sure.
All right, and who wants to be player 2? Someone further away. Let's have Stephen, isn't it? Is that right? So Stephen's going to be player 2. Do you bring some cash?
I think so.
All right, all right. Otherwise, borrow it from your neighbours. I can have IOUs here. So here's the hat.
I've only got coins.
Oh, you got coins? All right, all right.
Put it in a bucket.
Okay, great. So pass the hat down. We'll see if it makes it there. Test the honesty of the class here. It's working its way down. I'm going to have to, there we go, here we go, all the way down to Stephen.
Okay.
Check how much is in there.
There's $1 in here.
There's $1 in there, so you can decide whether to match or not.
Okay, I'll match it.
All right, so Stephen's going to match as well. All right, once again, we have this time, rather annoyingly, $1 and some coins in here, which I will empty on the stage to prove it to everybody. All right, and I will, all right, there are coins in here. All right, so I'll match this in a second and give it back to you guys. All right, so everyone understand the game? All right, everyone understand how this game works? So we're going to spend a while discussing this, and we'd go on playing, except I'd eventually lose so much money I'm going to run out of lunch money. The TAs would object. All right, so what I want to do is I want to analyze this game. I want to think about what this game's about, what's really going on here. All right, so first, this is just a little game involving putting some money in a hat. But I want to suggest to you that this is a toy version of a much more important game. This is a toy version of a game involving a lender and a borrower. So you could think of our player 1s here. That was Katie on the second round and is it Justin on the first round? Yeah. Justin on the first round. As imagine them working in an investment bank or perhaps in a venture capitalist firm. Right? And what they're doing is they're giving a loan to somebody, some budding entrepreneur, who's come up with a new project. So Stephen in round 2, and who was my budding entrepreneur in round 1? What was your name? Nate in round 1, have come up with some budding project. They've left Yale, perhaps after their junior year. They've left early because they've got some great idea for something which is going to make them millions, so either it's a new mousetrap or a new version of Facebook or something, and they go to the, oh, that's half, isn't it? So something better than a new version of Facebook, right? And they go to this venture capitalist firm, maybe it's some firm in New York, or maybe it's the Yale Investment Trust, whatever, and they explain this great idea to them, and they ask for some money to invest in this firm to buy machinery and to pay early wages and so on. Right? And the lender, the guy who works at the venture capitalist firm, has to decide how much money to invest in this project. Right? After this money has been invested in the project, the person who borrowed it faces choices. They could go forward with their project, work hard, spend the money on the things they're supposed to spend, or they could just disappear to Mexico. All right? All right? Go back to Yale, for that matter. All right? And there's actually something in between they could do, which is less dramatic than disappearing to Mexico. They could just not work particularly hard, shirk, perhaps join in someone else's project, and just let the money run down without the lender really knowing about it. All right? So this is a very real problem that some of you, some of the budding entrepreneurs in the room, are going to face when you leave Yale, and more of you who are going to end up working for investment banks, perhaps unfortunately, are going to face as well. All right? Okay, so we're going to spend the whole of today analyzing this, but before we even start, let's notice that there's something different about this game, other than its sheer triviality. There's something different about this game than games we've played all the way up to the midterm so far. What's different about this game? What's different? Yeah, can I get a mic in here? Sorry. Yes, what's different?
The moves aren't simultaneous.
The moves are not simultaneous. This is a sequential move game. Put the rules up here and bring this down. So for the first time, we're looking at a sequential move game. And we're going to spend most of the rest of the term looking at sequential move games, or at least looking at games that involve sequential elements. Now, what makes this a sequential move game? Let's be careful about this. What makes it a sequential move game is not simply that player 1 moved first and player 2 moved second, although that's true. What really made this a sequential move game is that player 2 knew what player 1 had done before he got to make his move. It isn't the timing per se that matters. It's going to turn out it's the fact that player 2 could observe player 1's choice before having to make his or her choice that matters. And notice, just while we're on the subject, more than that, player 1 knew this was going to be the case. All right, so let's get that down. So in this game, player 2 knows player 1's choice before she chooses. She being player 2. Let's say before 2 chooses. All right? And second, player 1 knows that this will be the case. And the way we dramatized this just now is player 1 put the money in the hat was transported across the classroom with people very honestly not stealing the money to player 2. Player 2 could look in the hat, could see how much money was in there before Stephen or Nate had to make their choice. Is that right? All right. So how do we go about analyzing games that have this sequential structure? So it turns out that a useful way to analyze them, and a way I want to get us used to today already, is to draw a tree. So in the first half of the class we drew a lot of matrices. Now we're going to draw trees. And for those people who haven't seen trees before, it's not a big deal. It's an object that looks like a tree. That's why it's called a tree. All right, so let's have a look. So in this particular game, here is player 1 making her choice. And in fact, she has 3 possible choices. She can put nothing, 1, or 3 into the hat. All right. Player 2 then chooses, although really player 2 only has choices to make if there's some money in the hat. And player 2 has 2 choices in this particular game in either case. Either player 2 is going to add $1 or $3 into the hat, or they're going to disappear off to Mexico, taking our investors' lunch money with them. All right? And let's put down the payoffs, and let's put down as payoffs the net gains they make. All right? So if nothing goes in, no one makes any money, so 0, 0 will be the payoff. If 1 is matched by 1, then the investor, the lender, doubles her money, so she makes a net profit of 1. If the money is taken out by player 2, then she loses 1. Right down here, if 2 matches her investment of 3, she doubles her money again, so she makes a net profit of 3. And if the money is taken out, she loses 3. Everyone all right with that? Let's do player 2's payoffs. In the case in which he matches 1, he makes a net profit of 150. In the case in which he just steals the 1, he makes a net profit of 1. And down here, in the case where he matches 3, he makes a net profit of 2. He gets 5 back that he'd invested 3 to start with. And here, if he just takes the money out, he makes a profit of 3. All right? So this game is just illustrated on the board. And for some of you, this is the first time you've seen a tree, but I'm going to claim it isn't such a complicated object. And we could spend a lot of time analyzing this in terms of connected graphs and so on, but it isn't really worth it. It's just a tree. All right? OK, so let's just make sure we understand that the payoffs here represent player 1's payoff and player 2's payoff, respectively. All right. So how do we analyze what to do in these games? It's a good idea always to write up the tree, like it's a good idea to write up the matrix. But how to analyze what we should do? Well, before we do that, let me just grab the mic and find out from our players what they should do. All right? All right, so where was my first investor? All right. So, Justin, why did you put $1 in there?
Well, if I put $1 in, he has an incentive to put $1 in too. If I put in $3, he's just going to take the money and run.
All right, OK, so what's Justin doing? Justin is looking forward, if you like. He's putting himself in player 2's shoes. This was, who was our receiver? Nate's shoes, and anticipating what Nate's going to do. And as Justin said, if he puts in 3, Nate's going to have an incentive to take the money and run. In fact, what would Nate have done? If 3 had been in the hat, what would you have done?
I like Justin, but I would have taken the money.
All right. Even though you know Justin, you'd have taken the money and disappeared somewhere. We don't quite know, right? Is the same true for the other pair? So Katie, you also put 1 in. Is that your explanation as well?
Same reasoning.
Same reasoning. OK, so everyone figured out what was going on. And once again, we think probably, let's try, Stephen, if there'd been $3 in the hat, what would you have done?
I would have taken it.
We've taken it. All right. So we're basically getting what's predicted here out of the game. All right, and let's just see that more formally, that idea. So the idea here is that the players who move early on in the game should do something we've always talked about before. They should put themselves in the shoes of the other players. But here, that takes the form of anticipation. Right? They're anticipating what players down the tree are going to do. Right? So the key idea here is anticipation. All right? What they're going to do is they're going to look forward down the tree, imagine themselves in the shoes of the later players, look at the incentives facing those later players, imagine that they do the best they can, those later players do the best they can, and then walk backwards through the tree. So the key idea here is to look forward to the end of the tree and work back. Look forward and work back. All right, and that's exactly the process that Katie and Justin describe themselves as doing. All right. All right. Now in this tree, let's have a go at this. So let's imagine ourselves in Stephen or Nate's shoes, having found, as they did in fact, having found $1 in the hat. They then are making a choice between adding $1, which nets them $1.50, or taking the $1, which nets them 1. 150 is bigger than 1, so we think they're going to go this way. All right, everyone happy with that? Conversely, if they found themselves with $3 in the hat, then if they add $3, they match, they're going to get $2. They're going to net $2. And if they take the money out, they're going to get away with $3. All right, 3 seems bigger than 2, so we think they're going to go this way. Right? Again, we're assuming that these are their real payoffs. Okay, so from player 1's point of view, since player 1 knows that player 2 will observe the choice before making her own choice, and since player 1 can put him or herself in player 2's shoes and anticipate this choice, player 1 is essentially choosing between what? If she puts in 0, she gets 0. If she puts in 1, she knows 2 will match, and she'll double her money and get 1. And if she puts in 3, then she knows player 2 will take the money and run, in which case our lender will have lost $3. So she's choosing between 0, 1, and -3, and she's going to choose 1. Right? Which is exactly what happened in the game. Right? Everyone happy with how we did that? Right? So this idea of starting at the last player, the player who moves last, solving out what they're going to do, and then working our way back through the tree has a name. The name for this is backward induction. And I apologize for the business school students in the room who've had this hammered into them too many times already, so I apologize for them in advance. All right, backward induction. Now it turns out there's precisely one controversial thing about backward induction, which is whether you should say backward induction or backwards induction. So I'm going to leave the S off and call it backward induction, but it's up to you which you think the correct English is. All right? Okay. So since we've got this game here, let's talk about it a bit, this idea of the lender and the borrower. It's not an unimportant situation. We've simplified it down to a very simple choice here, but it's a very basic choice out there in the real world. All right? And it's an important choice. After all, what keeps the economy running is the ability of lenders to lend money to businesses that then invest them profitably and are able to make returns. So this underlies a whole bunch of stuff going on in the economy. All right? So let's talk about this. And the first thing I want to talk about is I want to point out that there's a problem here. There's a bad thing here, much like there was a bad thing in the very first class of the semester. In the very first class of the semester, the bad thing was a prisoner's dilemma. All right, but here it's a little different, and let's focus on it a while. So the bad thing is we ended up here. Not a disaster. All right, the lender doubled her money. The borrower was able to go ahead with the project on a small scale and make some money. The bad thing, however, is that we would have liked to end up here. All right? Had we been able to have a large project funded with $3 and had the borrower repaid those dollars, so matched in effort or whatever it happens to be, then we'd ended up at an outcome that is better not just for the lender, it's obviously better for the lender, but it's also better for the borrower. Everyone see that? Right? So the outcome we'd like to have reached gets the lender 3, whereas she's only getting 1 where we ended up, and it gets the borrower 2, where he's only getting 150 where we actually ended up. All right? Why is it that we were unable, so both of our pairs, both Justin and Nate, and Katie and Stephen, why were we unable to get to here? Why were we unable to get to here? Any takers? What got us? What prevents us from getting to this good outcome? Let's go back to Katie a second and see if we can. Yeah, you go ahead. Oh, I'll come. It's all right. All right. So Katie was saying why she invested 1. I picked on Justin before. So here's this good outcome. It's better for you. It's better for Stephen, who's your borrower. Why aren't we getting to this 3-2 outcome?
Because if I play 3, him matching my money is dominated.
All right.
Strictly dominated.
All right. So the problem here is Katie would like to invest 3 if she knew that in fact Stephen was going to match, but she knows Stephen's not going to match. Right? Stephen, in fact, is going to run off with the cash. All right? It's going to end up being spent at Starbucks or something. All right? And from Stephen's point of view, he would actually like to be able to borrow the $3. He would like to be able to end up at this 3-2 outcome as well. The problem is he knows, and he knows that Katie knows, and Katie knows that he knows, that in fact he's going to run off with the cash. Is that right? Is that right? All right, so we're in a bit of a problem here. We'd like to get this good outcome, but incentives are preventing us from getting there. What do we call this kind of situation? What do we call this kind of problem? Anybody? No takers? All right, this is called moral hazard. This is called moral hazard. How many of you have heard the term moral hazard before? All right, a number of people have heard it. So here we are, moral hazard. Here is the problem that the agent, in this case the borrower, has incentives, will have incentives to do things that are not in the interests of the principal. All right? If we're not careful, for example, by giving too big a loan, the incentives of the borrower will be such that they will actually not be aligned with the incentives of the lender, and that will prove to be bad for the lender. But notice, the existence of this moral hazard problem isn't only bad for the lender, it ends up being bad for the borrower as well. All right, let me give you another example. In insurance, there's a classic, probably the classic moral hazard problem. If an insurance company insures me against having my car stolen, there's a moral hazard problem in that I might, if the car is fully insured, I might now have the incentive not to bother to lock my car or to leave it anywhere on the street in New Haven. All right? All right? Because I'm not bearing the cost anymore. All right? So we need to be able to, the insurance company needs to worry about that in writing an insurance contract for me. And in practice, what the insurance company does is it forces me to take a deductible. It doesn't allow me full insurance. It makes sure that some of the cost of having a car stolen is going to fall on me. That's bad for me, by the way, because it means I can't get full insurance. All right? And notice that what happened here is rather similar. In this case, both the lender and the borrower would rather have a big project, a big loan, and have the agent pay back that loan. They'd prefer this 3-2 outcome. But they can't get there, and therefore, rather than having a full-scale project, Katie or Justin only offered the borrowers a small-scale project. All right? So the idea here, in this example, was, what happened was we kept the size of the project, or the size of the loan. You could think of this as the project if they're borrowing something. Small to reduce the temptation to cheat. Okay, to reduce that temptation not to repay the loan. All right. So these problems are all over all over society, but they're particularly prevalent in situations involving lenders and borrowers. All right? So a good question is, how might we solve this problem? A lot of you are about to go out and try and borrow money to set up your projects, to run your new version of Facebook, whatever, and a lot more of you, as we said before, are going to end up loaning money, perhaps someone else's money, probably, at least for a while, and we want to know how you might solve this moral hazard problem. We've seen one way to solve it. One way is simply to keep the size of the project small. What else could we do? Let me come down and try and have a bit of a discussion. What else could we do? So Stephen, what else could we do? You were the borrower. What else do you do?
Like impose laws.
We can impose laws, okay. So we can impose laws, much like we talked about in Prisoner's Dilemma. We could regulate this market. There's going to be a little bit of a problem we're going to run into in regulating the law, in using the law here. What's the problem we're going to run into here? Well, I mean, we do have laws that regulate borrowers and lenders. What's the law that regulates borrowers and lenders? So bankruptcy law, right? So we have law that regulates to some extent what lenders and borrowers can do. One of the things we do in that law is we limit the degree to which we're allowed to punish the borrowers. Right? So bankruptcy law pretty much says we're going to put some limit on how much Katie can inflict pain on Stephen for running off with the lunch money. Right? Stephen can simply say, I can't repay, I'm bankrupt, and he's more or less allowed to have a fresh start. So the law would be good here, but there's limits to what we can do. Right? We could go back to the Dickensian world of throwing Stephen in jail for not repaying the loan, but it's tough. There are downsides to that, it turns out. All right. So what else could we do? Yeah, I'm going to have to dive in there a little bit. So shout into the mic.
The venture capitalist can impose restrictions on what the person can do with the money.
All right. So you could try and say there's only certain things you can do with the money. And for example, to make that credible, what you might have to do is to say, show me what you're going to do with the money. Show me the receipts. Right? Another thing you could say is, I will only give you the money if you show me exactly how you're going to spend this. Right? That's a good solution. Notice that you could regard that as changing the order of play. Right? It's a little bit like saying, let's have the borrower have to move first. Let's have the borrower have to commit what their actions are going to be, how they're going to spend the money, before, and show the contracts before the lender lends them the money. Right? And that's a good solution. But again, there are limitations to this solution. What are the limitations to that solution in the real world? Let's go back to all of you who are thinking about making millions with your new Facebook. What are the limitations to having some contract with the bank, with Chase, saying exactly how you're going to, not only saying exactly how you're going to spend the money, but actually detailing it already with contracts ahead of time? What are the problems with that? Someone else? Someone's thinking of going into business here? Let me pick on somebody a second. So what's your name, sir?
Kelly.
Kelly. So imagine you have some project, you're going to borrow some money from Chase or Mr. Swenson to set up this fund. Why might you worry about having everything written out and contractually ahead of time?
I mean, then it restricts your freedom on what your ideas are, I guess.
Right, so one problem is the sheer lack of flexibility, all right? If in fact the entrepreneur is not going to be flexible in how they actually run the project, there's not much point of being an entrepreneur in the first place. Right? There's a limit, to how much control you want to give to the lender. The lender doesn't really want to run the project for you. Right? There's also simply a problem of timing. It's simply not going to be possible to specify all the expenditures of a project up front. You're going to need some money to do some things ahead of time. All right? All right? So it's a good idea. Changing the order of play is a good idea, but there's going to be limitations to this. What else could you do as the lender? What else could you do? Thinking of loaning some money in here. Loaning some money to one of your classmates for some project. Let's try again.
Something like loan money over time in stages and observe progress.
Good. So one possibility is to break the loan up and give it, let it come in small installments. If you do well on the first installment, I'll give you a bigger installment next time. All right? And notice that that's a little bit like something we talked about the very first week. It's a little bit like taking this one-shot game and turning it into a repeated game. Right? It's turning a one-shot interaction into a repeated interaction. And we'll come back and talk about repeated interactions later on in the course. Again, notice that there might be some limitations to this. I mean, I think it's a good idea, and in general you should be trying to do this, but it could just be that for Nate to set up his new Facebook and for Stephen to set up his new mousetrap factory, they just need a chunk of money at the beginning. There may be some limit to how little money you can give them at the beginning, since they have to hire workers and set up the factory and make some big splash in advertising and so on and so forth. All right, so again, it's a good idea, but there may be limitations here. What else could you do? Let's have a look at the numbers on the board. Right now, the numbers on the board say that if Stephen's mousetrap project, were you the Facebook or if Stephen's mousetrap project goes well, and it ends up being a big project with lots of money available, there are 5 units of money available in profit. Right? 3 plus 2. Right? The way we've designed things so far, our lender, I gave you these payoffs in the game, the lender is going to double her money. She's going to get 6 back to net 3, and Stephen's going to get 2. So the division of that 5 is 3 and 2. But we don't have to divide the money like that. If you're a lender, you may want to think about how you divide up the spoils of a successful project. All right? So how else could you divide up those $5, that 3 plus 2, in a way that might be better for everybody? Nate?
Give the investor $3.01 if they do that other choice, and then take a little bit of a hit, but that way you'll still have something that's pretty optimal to the other choice that we came to before.
All right, I'm guessing people didn't hear that, but that was right, so just say it. That's exactly right. So what you could do here is you could redesign the payoffs of this project in the event that it's successful. All right, what you could do is take these 5 units of profit, and instead of having 3.2, let's write it in a different color, we could give the borrower, the entrepreneur, 3.1, leaving 1.9 to the lender. All right, so we could change the payoffs of this contract to be 1.9, 3.1 in the event of a big project. Why does that help? Because now our borrower, Nate or Stephen, were they to end up with a hat with $3 in it, they now will find it in their interest to match the $3 and get 3.1 rather than 3. All right? All right? So what's this an example of? This idea of changing the contract to give the borrower incentives to repay, incentives not to shirk, incentives not to disappear with the cash, is an example of what's called incentive design. All right? So the idea here is in a lot of businesses, incentives are not given by God, they're designed by the people who write the contract. All right? And if you're either the borrower or the lender, you should be thinking about writing a contract that's going to achieve the end that you want. Now notice in this particular example, exactly as Nate said, the lender is going to take a bit of a hit here. They're not going to get 100% return, but they're ending up doing better than they would have done by giving a small loan. All right? They've ended up getting 1.9 rather than 1. Right? They're getting 1.9 rather than 1. So in this particular example, it won't always be the case, but in this example, they're taking a smaller share of a larger pie. And sometimes a smaller share of a larger pie is bigger than a larger share of a smaller pie. Not always, but sometimes. Right? The reason the pie is larger is we're able now, in an incentive-compatible way, we're able to go ahead and have a large project. So in this example, the smaller share of the larger pie actually ended up being bigger than the larger share of the smaller pie. So a smaller share of a larger pie can be bigger than a large share of a small pie. Not always, of course. All right, this is just an example. All right. Now let's just be a little bit careful here. All right, so in this particular example, even though this 1.9, this return that our lender is able to make by accepting a smaller share of a larger pie, even though it's a bigger absolute return, it's smaller in another sense. In what sense is it smaller? Let's be careful here. So we're tempted to say, look, it's 1.9. 1.9 is bigger than 1. That's got to be a good thing. But since some of you actually are going to go out into investment banks, and you might be posed this question, let me just make sure we don't make a blunder that's going to spoil your interview. So what might you be worried about as an investment banker about this deal, about this contract? Somebody else? Anybody else? I'll come down again. That's all right. What might you be worried about? Who here's be honest, who here has been interviewing with either investment banks or venture capital firms or private equity firms? Raise your hands. Oh, come on, it's doing more than that. All right, all right. There was a hand. Where was the hand at the back? There was a hand way back here. No? Yeah? So what might be wrong with this project from your point of view? Actually, can I get the mic on that side? This gentleman here. What might be wrong with the project from your point of view?
If you could actually just find 3 small projects, then you could still get 100% returns just by dividing it up. Good, good. You're going to make lots of money for Morgan Stanley, whatever it is. Good, good. Your name is Brian, right? So there's a good ad to hire Brian at Morgan Stanley. All right, all right. So what Brian said was, it's true that you're making a bigger absolute return here. This is a bigger absolute return,
But this return up here is a 100% return on your capital. The rate of return on capital is higher making a 100% return on an investment of 1 than making a 1.9 return on an investment of 3. The rate of return is better in the smaller case. So which is the right answer? Should we worry about the rate of return, the 100% rate of return, or should we worry about the absolute return? If you're in the business of investment banking, who thinks you should worry about the absolute return? Who thinks you should worry about the rate of return? Who thinks it depends? What does it depend on? What does it depend on? Yes, keep you from falling off this thing. What does it depend on? Somebody said it depends. What does it depend on? Depends is only a good compromise vote if you know what it depends on. Yeah, the gentleman here.
Since an investment banking firm only has a limited amount of money to invest, you want to see if you can get a higher rate of return investing elsewhere.
All right. So I think you're on the right lines. There's two things to worry about. One is, what is your supply of funds to invest? And the other is, what's the other supply you're worried about as an investment bank or a venture capitalist firm or a private equity investor? What's the other supply coming your way? Yeah, the number of projects coming across your door, if you like, the demand for your cash, the supply of projects. All right? All right, so what we have to worry about here is what is the true opportunity cost of that money. All right? If there are very few projects out there, all right, then you basically just want to go down the list of projects picking off absolute return. However, to go to the other extreme, if there's an infinite supply of projects all coming in, all of which will offer 100% return, then as our banker at the back told us, you should just go for 3 small projects rather than 1 large one. Right? But the question of which is better, it isn't as simple as saying, yes, we should always go for 3 small projects. There may not be 3 small projects out there that offer 100% return. All right, so what's going to matter here is what's the true opportunity cost of the capital, and that's going to depend on what projects are available to you. All right, this was just an example of incentive design. Just one example of incentive design. Let's talk about other examples of incentive design. Incentive design's been a lot in the news lately. Who else tends to have incentive contracts other than borrowers? Who else out there tends to have incentive contracts? It's a big topic in the news these days. So who has incentives written into their contracts? Yeah, way over here. Let me run over at the risk of blurring the camera. All right. So who else has incentives in their contracts?
Managers.
Managers. All right. So CEOs have huge incentive clauses in their contracts. All right. Sometimes in the form of options. All right. Why do they have those incentive clauses in their contract? Well, there's 2 interpretations of this. One interpretation is it's just a bad thing and they're just trying to screw the world. But there's a more moderate view of this. The more moderate view of this is that those incentive clauses in their contracts are attempts to align the interest of the managers with the interest of the shareholders. Just as this contract is attempting to align the interest of the lender and the interest of the borrower. All right? So by managers, I took it to mean CEO, but what other kind of managers recently in the press, very recently, this weekend, have been talking about incentive contracts? Somebody way over there. I'm caught on the wrong side as usual. But, yeah, can I squeeze through? I'll try and squeeze through. Can I squeeze through? Sorry. All right, sorry. Here we go. Where was it? Where was my answer to that question? Here we go.
Managers of baseball teams.
All right, so managers of sports teams also have incentive contracts these days. Right? Incentives to achieve certain levels. All right? Here it's not quite clear to me exactly what's going on. Right? We call those incentive contracts, but you might want to worry a little bit. I mean, do we really think that the manager has an incentive to lose otherwise? Right? So part of what's going on with incentive contracts isn't actually incentive contracts. Part of it is about sharing the risk. Right? And particularly in the kind of contracts that have been written about over the weekend with Joe Torre's contract for the Yankees, which he turned down, is partly perhaps to give him incentives to try and win, but perhaps is more to do with sharing the risk among the general manager and the manager of the team if they don't make it to the playoffs. But all right, they're still incentive contracts. Now we see incentive contracts elsewhere, and we've seen them since the Middle Ages. Right? So in the Middle Ages, incentive contracts took a particular form, and the form was called, well, 2 things: peace rights put it up here. Piece rates and in agriculture it took the form of sharecropping. What are piece rates? Somebody, what are piece rates? What are piece rates? Anyone know anyone who's on piece rates? What is sharecropping? Somebody must be from a farming state. Yeah, there's somebody out here. The guy in orange out here, yeah.
Sharecropping is where the landowner takes a portion of the farmer's crop at the end of the farming season.
All right, so sharecropping is a contract whereby part of the output of the farm goes to the landowner and part is kept by the farmer. All right, going back to the Middle Ages, part of the output would stay with the peasants and part of it would go to the lord of the manor. Right? Piece rates are a similar idea. Rather than paying wages to workers, just bundles of cash, the amount at which they're paid depends on output. So piece rates would say if you produce 17 yards of cloth, then you'll get paid the revenue that's derived from 3 of them, say. All right? Both of these forms of contracting are there partly to create incentives. They create incentives because they create the incentive for the farmer to increase yields, and they create incentives for the part of the worker to increase output. All right? So piece rates are a big part of the story. All right. Incentive design is a pretty big topic, and we don't really have time to go into it much in this course, but it's worth mentioning that, in fact, the Nobel Prize that was won last week by those 3 economists we talked about was partly about incentive design. All right, so it's regarded as an important enough topic for the design of incentives across society as a whole to have been worthy of winning the Nobel Prize. And my guess is there's another Nobel Prize that's going to come out in this same area in the next 5 or 10 years. All right? Just to make it clear, you can have problems. You can write incentives badly. It's a classic story that you've all heard of, I'm sure, that often in the provision of public goods, let's say bridges or highways or tunnels, the incentives for the construction companies tend to be rather badly written. They're meant to have incentive clauses, but they never seem to quite get them right. It's easy to get these incentives wrong. And just to prove this doesn't just happen to management, let me just tell a story against myself. So a year and a bit ago, I was picking fruit with my then 3-year-old daughter, and I wanted to make sure that we got some fruit home to eat for dinner, and she didn't just eat all the fruit as we picked it. These were raspberries. So I decided to have a rule that sounds efficient. I said, well, any item of fruit that gets picked that's in good condition, we'll take it home for dinner, but if it's squashed, then we'll eat it then and there while we're picking the fruit. All right, so my 3-year-old proceeded to go along the bushes of raspberries, picking the raspberry, turning around to me and saying, squashed, and putting it in her mouth. All right? All right, squashed, squashed, squashed. Right? Which shows that a 3-year-old knows more than a professor about moral hazard in some way. All right. All right. So one thing we can do is worry about incentive design in the design of the contract. There's another thing we can do here. What's the other thing we can do here? We're missing out something very basic. What is it that our borrower, Stephen and Nate, can do? Or put it more generally, for all of you, if you go out and start a company and you borrow some money to start your company when you leave Yale, what are you going to have to do? What's the borrower, what's the lender, what's the bank going to insist on? What's they going to insist on? Anybody? They're going to insist on collateral. They're going to insist on collateral. What is collateral? I'm somewhat charmed to see how few of you are going to end up borrowing money, but for those of you who haven't got trust funds, you're going to end up borrowing money. So what is collateral? Yes, what's collateral?
You give someone the whole, you let the bank hold on to something?
Right, you let the bank hold on to something in the event that you default on the loan. All right? You're going to let the bank hold on to something in the event that you default on the loan. Now, for most people here, what are they going to post as collateral? Let's assume that we're back to our original contract here. We can't do this. We're back to our original case. What are most of you going to end up using as collateral if you borrow money? Yeah, everyone's saying a house. I'm guessing that for most of you, I'm not going to look around the room because I don't know how many trust fund babies I've got in the room, but for most of you, it's going to be what? It's going to be your parents' house. All right? All right? So why is it that your parents' house being posted as collateral is going to prevent you from disappearing to Mexico with the loan? Well, let's have a look at how it changes the payoffs. Now, if you take the money and run, you disappear to Mexico, but you end up with $1 minus a house here and $3 minus a house there. Of course, we're relying here on you liking your parents enough not to mind about the fact that we're sleeping in the rain, but as long as that's the case, I think with high probability, you're now going to decide to return the loan, at least if you can. Is that right? Now notice that the way in which this collateral works, there's a subtlety to how this collateral works. You might think that the way in which collateral works is that now the lender feels safer because even if you end up defaulting on the loan, at least they get this house. All right? And that's true. There's some truth in that. But that's really not the key here. Right? Frankly, most bank lenders don't want your parents' house. Right? I mean, your parents might have very nice houses, but this isn't a good housing market right now, and they don't particularly want to see your parents on the street. The way in which this works is not so much that it gives an extra positive return to the lender. The way in which it works is it gives an extra negative return to the borrower. All right, so let's just do this backward induction again with the house in place. All right, so with this house in place, as before, you'll return the loan up here. But now, provided you like your parents enough, you would also return the loan here, because you'd refer $2 to $3 minus your parents' house, in which case you'll get a loan of $3. All right? So the way in which the collateral worked was by hurting you enough, or in this case hurting your parents enough, in the event of default, in such a way as to change your behavior. But notice, it helped you. So here's a subtlety coming in here. By issuing collateral, we actually lowered the payoff of the borrower at certain endpoints of the tree. We lowered the payoff of the borrower at certain endpoints of the tree. But as a consequence, we were able to end up at an outcome that was better for the borrower. Sometimes having lower payoffs can actually make you better off. And the reason it makes you better off is it changes the behavior of other players in the game in such a way as may benefit you. In this example, by inducing the lender to give you a bigger loan. All right, so the way the collateral works is it lowers your payoffs if you do not repay, but it leads to you being better off. And the reason it makes you better off is it changes the choices of others, in a way that helps you. All right, we're going to see lots of examples of that in the next couple of days. All right. Now, collateral is an example. We talked about incentive design. Collateral is also an example of something larger. The larger thing is the idea of commitment. Collateral is a commitment strategy. It's a commitment strategy. It commits you to repaying the loan. All right. I want to give another example of a commitment strategy. Because I think this idea of commitment is an important one, and we have just about time to do it. So I wanted to go completely away from the context of our lender-borrower game a second and look somewhere else entirely. All right, so we get rid of this for now. I want to take us back to 1066. What happened in 1066? What happened in 1066? I know this is America and no one gets an education anymore, but still, what happened in 1066? The Norman conquest took place in 1066, right? So the Norman army invades from Normandy, led by William the Conqueror, and lands on the Sussex beaches at Hastings. All right? And what I want to imagine is a game involving the Norman army, or William the Conqueror in particular, and the Saxon army. All right? So here's the little game. So we're now in the area of medieval military strategy. All right? And here is the game. We'll start with the Saxons here. The Normans have already invaded, so I guess the Normans have already moved. But here's the Saxon army making a decision. They're deciding between fighting and the important medieval military tactic known as running away. And of course the Normans are going to know whether the Saxons are actually going to charge down the beach and attack them, and they are going to have to decide whether to fight or run away. All right? And let's put the payoffs in. Now leave some space below here. Leave some space down here on your notes. All right? Let's put the payoffs in. So I'm going to put the Norman payoffs first and the Saxon payoffs second. Okay? Norman payoffs first, Saxon payoffs second. All right? So the payoffs are going to be like this. If both sides fight, a lot of people end up dead, and we'll call that 0-0. If the Saxons fight and the Normans run away, the Saxons get 2 and the Normans get 1, because at least they're alive. If the Saxons run away and the Normans fight, then the Normans get 2 and the Saxons get 1. It just flips things around. And if both lots run away, then ultimately it's good for the Saxons. All right? So this is the game. All right, let's be careful. I put the Saxon payoff second. Put the Saxon payoff second. If we analyze this game by backward induction, we can see that the Normans are in trouble. Why are the Normans in trouble? Because if they are attacked by the Saxons, then fighting yields 0 and running away yields 1, so they're going to run away. And conversely, if the Saxons run away, then in fact the Normans will stay and fight, because it's easy to stay and fight against people who are running away. Even I can do that. All right? So they're going to go for 2 rather than 1. But now the Saxons face this choice. They know that if they attack the Normans will run away and the Saxons will get 2. But if the Saxons run away, then the Normans will stay and fight, and the Saxons will only get 1. So the Saxons are going to end up fighting. All right? Everyone see how we did the backward induction? So this is not a good situation if you happen to be the Norman commander, if you're the guy who led these troops across the Channel. All right? So what did William the Conqueror do? He burnt his ships, all right? So let's now make this game a little bit more like the real historical situation. Here's a move that William the Conqueror, the king of the Normans, can do. He can either not burn his ships, or he can burn them. If he burns them, then the game is rather different. Once again, the Saxons can decide whether to fight or run away, but now the Normans really don't have any choice. They have to stay and fight, because swimming back to France wearing armor is difficult. All right, so the payoffs become 0-0 and 2-1 as before. All right, so we know now that the Normans are going to stay and fight. That's all that's available to them. I put it that they don't even have the option of running away. If you want, you could put running away yields them minus infinity or whatever it is to get drowned. All right? So now, if the Normans have burnt the boats, the Saxons know that if they fight, the Saxons will get 0. If they run away, they'll get -1. So now they'll run away. And then from William the Conqueror's point of view, what's he choosing between? He knows that if he doesn't burn his boats, the Saxons will fight and his troops will run away. But if he does burn his boats, the Saxons will run away and his troops will fight. So he wants to burn his boats. All right, everyone okay with the example? All right. Now this is probably the classic example of a commitment strategy. Right? William the Conqueror in this example, or Cortez in perhaps the more famous example, burn the boats to get rid of some strategies, to get rid of some choices altogether. And you might think, how can getting rid of choices make me better off? And the reason in a game, particularly in a sequential game, but in the game generally, the reason getting rid of choices can make me better off is it changes the behavior of people on the other side of the game in such a way as benefits me. In this particular example, it makes the other side less likely to fight. All right? So once again, this is a commitment. It's a commitment, and the way it works is, this example of a commitment is actually to have fewer options. To have fewer options, and it changes the behavior of others. If it didn't change the behavior of others, it wouldn't be worth doing. All right. So let's just talk about this a little bit more. There's another famous example of a military commitment strategy that occurs in the movie Dr. Strangelove. How many of you have seen the movie Dr. Strangelove? How many have not seen the movie Dr. Strangelove? All right, good homework exercise for the weekend. Rent the movie Dr. Strangelove. Great, it's a very good movie. All right, Stanley Kubrick, I think. All right, so in Dr. Strangelove, there's a famous commitment strategy. What is the famous commitment strategy in Dr. Strangelove? Somebody? Let's get a mic. Ali, can we get a mic down here? There's one on the way. The guy in white. There you go. There you go. Yep, there you go. Great.
They lose radio contact with the base, which means that they're going to end up dropping the bomb.
All right, that's true. I was thinking more deliberate. What's the more deliberate? The guy in red. What are there? There's somebody in red here. Here we go. Try.
The Soviets construct a doomsday device, so if they're attacked, they automatically launch all of their nuclear weapons.
Good. Good. So the worry that the Soviets have is they think the Americans might attack them, and they worry that the Americans might attack them thinking that they won't retaliate, because they won't really have any incentive to retaliate once their cities are destroyed. So they construct a device they call the doomsday device that will automatically launch nuclear missiles back on the Americans if the Russians are attacked. All right? It's a commitment device to make it credible that they will actually respond were they to be attacked by the crazy Americans. All right? So there's a mistake, however, that the Russians make. What is the mistake that the Russians make? What's the mistake the Russians make? Tell you what, we're here. There's the guy in the Yale sweatshirt here.
They don't tell anyone about the machine.
Right. They don't tell the Americans that they've built the doomsday device. All right? So this is really an important idea hidden in what's really a great movie. Commitment strategies are a good idea. They can make things credible. But the only reason that having fewer strategies is good for you is because it changes the behavior on the other side. In this case, it changes the behavior of the Saxons. It doesn't work if the other side doesn't know about it. Right? It's crucial that the other side knows. So the other players must know. All right? Just to hammer this home, notice that the expression in the English language is burning your boats. It's not going over to your boats and quietly drilling a little hole in them. Right? It's burning your boats. You want the other side to see this big bonfire on the beach and to know that the boats are no longer available. Right? Just as in Dr. Strangelove, it's crucial, and it's a terrible mistake, for the Russians not to tell the Americans that they've built this machine. All right? All right? So knowledge here is crucial, knowledge of the other side. Now I should just complete the history of this. This didn't work in the case of the Battle of Hastings. The Saxons attacked anyway, and it just turned, there was a big bloodbath, and the Normans really only won this battle because somebody got a lucky shot and hit King Harold in the eye. So actually, this is a good story, but didn't they, as a military tactic, not actually a true story. And I'm adding that in because otherwise I'm going to get hundreds of letters from people who watch the video. All right. Now, we've had a bunch of lessons today, but I'm not done. I want to play one more game. Before I do, though, I want to make sure you understand. We're going to play another game, so everybody stay put. I want to make sure that there's a bunch of lessons on the board, and I want you to understand what's important and what's more important. Everything's important, but some things are more important. All right? So the idea of commitment is an important idea, and the idea of incentive design is an important idea, but there's one idea here that is more important than anything else, and that idea is backward induction. All right, put a little sun around it, okay? How important is backward induction? Backward induction is the most important thing I'm going to teach you in the second half of the semester. It's probably the most important thing I'm going to teach you in the whole semester, and it may be the most important thing you're going to learn at Yale. All right? It's the answer to all questions. If I ask you a question, and as happens from time to time, you've been sleeping in class, and you wake up startled because I've now asked you a question, and that camera is on you, right, and you don't know what the question is, then the answer is backward induction. All right? Now, I'm stressing this because 6 weeks from now, whatever it is, in December, there's going to be a final exam, and I guarantee now that there will be a question on the final exam that involves backward induction, and I guarantee that at least one person in the room will forget to solve it by backward induction. All right? So are you going to use backward induction on the final exam? Yes? You're all going to remember it? Okay, okay, good. Now we'll play one more game, just for fun. All right. Oh, before we play one more game, I'll do one other thing. Sorry, one other thing before we play one more game. I apologize. The one other thing I want to do here is I put up a tree here, but I forgot to tell you anything about the tree. This was a tree, and I would be remiss if I didn't tell you a few things about trees. So there's a certain amount of jargon that goes along with trees, and I want you to be able to read the textbook and know what that jargon is. So these spots, these dots in the tree, these things are called nodes. All right, they're called nodes. And in fact, the end points of the tree, where the payoffs are, these are also called nodes, but they're called end nodes. All right? And these branches in the tree, the branches, here they are, the branches are called edges. All right, so a tree consists of nodes, edges, and these missing dots are the end nodes. The end nodes are associated with payoffs. Do we need to write that? That's obvious, right? They're associated with payoffs. And every other node belongs to somebody whose turn it is to make a decision at that node. All right? So these other nodes, the ones that aren't end nodes, are called decision nodes. And it's perfectly possible, for example, in our Norman Conquest game, for somebody to have several nodes. Somebody could move once, and then later on in the game. There may also be nodes that are never reached in a game. One last piece of jargon, a route through a tree from the beginning to an end is called a path. A path. A way of getting through the tree from the beginning to the end. So we'll have a pop quiz on that jargon later, and now let's play the last game I want to play. We've got 10 minutes, right? Okay, everyone understand the jargon? I want to play a game now, all right? So the game we're going to play is a game we're going to call the Hungry Lion game. All right, it's the Hungry Lion game. And what I'm going to do is, I'm going to pick on a row of the class. Actually, I'm going to pick on this row of the class. All right? And this row of the class, everyone can see this row from up there. You can lean over the balcony. This row of the class, we're going to imagine that everybody in this row is a lion. All right? Do they all look like lions? Not much, but never mind. Pretend they're lions, right? Suspension of disbelief. All right? They're all lions, and they're all hungry. Right? Except for one person, who's this guy at the end, whose name is Alex. So Alex is a sheep. Alex has had the misfortune of wandering into this pack of pride of lions, and is liable to get eaten because they're hungry. All right? However, one thing stands between Alex the sheep, and being eaten. The one thing that stands between him and being eaten is that in lion society, the only lion who is allowed to eat the sheep is the head lion, the big lion, whose name is Ryan. Right? Ryan is the head lion here. Right? Only Ryan can eat Alex the sheep. No other lion can eat Alex the sheep. All right? Now there's a catch if Ryan eats Alex, if Ryan the lion eats Alex the sheep. The catch is that if Ryan the lion eats Alex the sheep, then Ryan the lion will fall into a postprandial stupor, fall asleep, at which point the second largest lion, whose name is Chris, can eat Ryan. Now notice, Chris can never eat the sheep. He can only ever eat the lion, the big lion, and only then if the lion has eaten the sheep and falls asleep. This is very strict, right? Lion society is very hierarchical, like England. All right? Right? If, however, Ryan the lion eats Alex the sheep and is then eaten, falls asleep and is then eaten by Chris the lion, then, and only then, he will fall into a stupor, at which point he can be eaten by Isabella, who's the third largest lion, and so on. Ever understand the game? All right, no questions, no talking among yourselves. Write down what you would do if you were our key decision maker, who is Ryan the lion. But before we write it down, can I get Alex to stand up a second? Stand up. All right, camera on him. All right, this is the menu. All right, thank you. All right. Okay, so you have to write down in your notepad whether you, Ryan the lion, in Ryan's shoes or paws or whatever, whether you would eat Alex the sheep. Everyone written something down? All right, now let's ask Ryan the lion what he's going to do. So Ryan, are you going to eat Alex the sheep?
No.
He says no, he's not going to eat. Why not?
Well, because then I'd be...
Shout out.
Then I'd be eaten as well.
Then he'd be eaten. Well, let's see if he would have been eaten. So had he eaten Alex the sheep, then he would have fallen asleep, and then he'd have been in danger of being eaten by Chris. Chris, would you have eaten Ryan?
No.
So he wouldn't have eaten him, in fact. In fact, it looks like Ryan would have got a free lunch, right? There are no free lunches in economics, something's wrong. All right. And why is Chris worried about it? Chris is worried about it because Chris is worried about Isabella eating him. And what am I doing wrong? What's wrong with this analysis? By the way, before I say what's wrong, how many of you in Ryan's shoes would have eaten the sheep? And how many of you would not have eaten the sheep? Okay, what am I doing wrong? I'm in totally the wrong part of the room. I shouldn't be here at all, right? I shouldn't be at all in this part of the classroom. I can't get round. Wait a second. Excuse me. All right, I should be... Which row were my lions? Where's my lion row? Okay, I should be way over here with the baby lion, whose name is... Ege. Yeah. So Ege is a little baby lion, very cute. But Ege, if he gets a chance to eat, is going to eat. Why is he going to eat? Because there's no one to eat him. All right, so if Ege gets the chance to eat the second babyest lion, whose name is... John, then Ege will eat. All right? So if John gets a chance to eat... Ben, is John going to eat Ben? John, are you going to eat Ben? No, John's not going to eat Ben because John knows he'll get eaten by Ege. So Ben, if you get a chance to eat Vidar, are you going to eat Vidar? No. Wait a second. So we just argued that if you eat, then the second largest lion, whose name was John, is not going to eat you. Yes. Okay. So we know the littlest lion's going to eat. So the second littlest lion is not going to eat. So the third littlest lion can eat safely. So the fourth littlest lion should not eat, right? So the fifth littlest lion should eat. We've got eat, not eat, eat, not eat, eat. Eat, not eat, 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 eat. Is that right? So in fact, he should have eaten him. But the more important point is, how should we have analysed this game? What should we have used? Backward induction. How many of you used backward induction? Be honest. How many of you? So what's the point here? The point is this. 5 minutes ago, I said the most important thing you'll ever learn at Yale is backward induction. Then I distracted you with some fairly irrelevant nonsense. And 5 minutes later, nobody used backward induction. So the main lesson from today, the lesson we're going to pick up on Wednesday, is to use something. What are we going to use? All right, we'll see you on Wednesday. All right, so today I want to do something a little bit more mundane than we did on Monday. I want to go back and talk about quantity competition. So in the first half of the course, we talked about price competition, we talked about quantity competition, we talked about competition with differentiated products. I want to go back and revisit essentially the Cournot model. So this was the Cournot model. The two firms are choosing their quantities simultaneously. Firm 1 is choosing Q1, and firm 2 is choosing Q2. And all of this is just review. So this is all stuff that's in your notes already. This is the demand curve. It tells us that prices depend on the total quantity being produced. So this is Q1 plus Q2, and this is prices. Then the demand curve is a straight line of slope B. All right, that's what this tells us. This has slope minus B. All right, and we know that payoffs are just profits, which are price times quantity revenues minus cost times quantity costs. We're assuming constant marginal costs. And we did this model out in full in maybe the third week of class, and we figured out what the best response diagram looked like. And if you remember correctly, this was the best response for firm 1, taking firm 2's output as given, and this is the best response for firm 2, taking firm 1's output as given, and there were a few other details in here. This was the monopoly quantity, this was the competitive quantity, and so on. But this is enough for today. And actually, we'd done a bit more than that. We'd actually worked out in class what the equations were for these best responses. Here they are. And I'm not going to rederive these today, but they're somewhere in your notes. We kind of crunched through some calculus and figured out what firm 1's best response looks like algebraically. Here it is. So this is the equation of this line. And similarly for firm 2, so this is the equation of this line. All right? And finally, we figured out what the Nash equilibrium was, and there was no prizes here. The Nash equilibrium in Cournot was where these best responses crossed, and this is the equation for the Nash equilibrium. Have I made a mistake? Thank you. Thank you. Best response, thank you. Best response for firm 1 is a function of Q2. Exactly. Thanks, Jake. All right? So this is all stuff we did before. I want to go back to this model now to revisit it in the context of thinking about sequential or dynamic games. So what we're going to do is we're going to imagine that rather than having these firms choose their quantities simultaneously, one firm gets to move first and the other firm moves after. Let's be clear, we're going to assume that one firm is moving first and the other firm, we'll assume firm 1 is going to move first, the other firm 2, is going to get to observe what firm 1 has chosen and then get to make her choice. All right, so we're just going to see what difference it makes when we go from this classic simultaneous move game into a sequential move game. All right, and this model is fairly famous, and I'm almost certainly spelling this wrong, but it's due to a guy called Stackelberg. So what we're looking at now is the Stackelberg model. All right, so how do we want to think about this? So a natural question to bear in mind is, assuming we're in this world of quantity competition, is it an advantage to get to move first, to set one's quantity first? Or is it an advantage to be able to wait, see what the other firm has done, and then respond? Right? Is there an advantage in going first, or is there an advantage in knowing a bit more about the other firm and being able to move second? Right? That's going to be the question at the back of our mind for most of today. All right? So how are we going to think of this? How are we going to figure this out? How are we going to figure this out? There shouldn't be a silence in the room. There should be an instant answer. How are we going to figure this out? We're going to use backward induction, right? This is going to be an exercise in backward induction. We won't be able to draw a tree here because the game's too complicated because there's a continuum of actions, but nevertheless, we are going to use backward induction. So what does using backward induction mean here? Using backward induction means starting at the end, and the end is what? The end here is firm 2. Right? Firm 1 is going to move first. Firm 2 is going to observe that choice and then move. So the end of the game is firm 2. So we're going to solve out firm 2's problem first. And we're actually going to do this entire analysis twice. We're first of all going to do this analysis a bit intuitively, looking at pictures, and then I want to go back and crunch it out in the math. All right? I want to get used to seeing that we can actually do it crunchily. All right, so this board is just review, so I'm going to get rid of it, I think. I didn't manage to get rid of it, never mind. We're not going to be using this board, this is just what we did do in the simultaneous move game, so we'll get rid of it. All right, so in the sequential move game, we're going to start by analyzing the move of firm 2. Right? So imagine yourself as the manager of firm 2. You're coming along to make your output decision. Right? The output of firm 1 is already set. All right, so analyze firm 2 first. Firm 2 sees Q1, right, and now must choose Q2. So what is firm 2 going to do? What's firm 2 going to do? So I claim we already know this. We've already solved this problem. When did we solve this problem? Anyone know when we solved this problem? The problem of what firm 2 is going to do? Well, we already solved it about a month ago when we looked at the simultaneous move game. Because what we worked out then was what is firm 2's best response for any particular choice that firm 1 makes. All right, we already solved out that problem. It was kind of it took us a while to solve out, but basically it was to maximize firm 2's payoff, taking as given firm 1. We already know what the equation looks like, and let's just remind ourselves what the picture looked like. Just a repeat of the picture we had before. We said for any particular choice of firm 1, firm 2's best response can be drawn on a best response diagram. And it looks like this. It's exactly the picture we have up there. All right, so this is the best response for firm 2, taking as given the choice of firm 1. All right? And we even know the equation of it. I won't bother to rewrite it there, but we already know the equation. All right? So in some sense, firm 2's problem is a problem we've already seen. We already worked out months ago what firm 2 should do if, taking a firm 1's output as given, and that's exactly the problem firm 2 finds herself in. She wakes up one morning, Q1 has been set already, and now she must choose Q2 to maximize her profits, so she's going to choose her best response. And just to remind you how we read this picture, for any particular choice of Q1, if we go up to the line and look across, this tells us what Q2 will respond. All right, so if Q1 chooses this amount, then Q2 will choose this amount. If Q1 chooses this amount, then Q2 will choose this amount, and so on. All right, so there's no mystery here. We already know what firm 2 is going to do. All right, so by definition, the best response of 2 to Q1 tells us the profit maximizing output of firm 2 taking Q1 as given. All right, so we've done the second step of this already. We already know what firm 2 is going to do. Of course, the additional step here now is that firm 1 knows that firm 2 is going to do this. Firm 1 is going to move first, and firm 1 knows that after she sets her quantity Q1, firm 2 will respond by choosing her corresponding quantity, which is the best response to it. So firm 1 knows that if firm 1 were to choose this quantity, then firm 2 will respond by choosing this quantity. And firm 1 knows that if she chose this smaller quantity, then firm 2 will respond by choosing this larger quantity. Is that right? Is that right? So firm 1 can anticipate how firm 2 is going to respond to each of these choices. All right, so let's just make that clear. So in particular, if firm 1 was to choose Q1 hat, I'm not suggesting it should, but if firm 1 was to choose this Q1 hat, then firm 1 knows that firm 2 will produce this quantity, which is the best response to Q1 hat. And if firm 1 were to choose Q1 double hat, then firm 2 will respond by choosing the best response to Q1 double hat. All right, so this is pretty straightforward so far, but what we're able to see now is the problem facing firm 1, which is the interesting problem. The problem facing firm 1 is, what quantity should firm 1 choose, knowing that this is how firm 2 is going to respond? Right, and before we solve this out mathematically, I just want us to think it through a little bit. So the first way I want to think this through is to make the following observation. From firm 1's point of view, firm 1 knows that any Q1 she chooses leads to a response on this line by firm 2. That's what firm 1 knows. So firm 1 is effectively choosing points on this line. Firm 1 is effectively choosing points on this line. Let me say it again. So what's actually happening is firm 1 is choosing Q1, and firm 2 is responding by choosing a Q2 that puts them on this line. But in effect, that means firm 1 is choosing points on this line. All right? So you could think of firm 1's problem as choose the joint output level on this line that maximizes firm 1's profits. Right? We could think of firm 1's problem as choose the combination of outputs on this line by choosing Q1 and Q2 respond. Choose the combination on this line that maximizes profits for firm 1. Right? So I'm belaboring this a little bit because it's a more general mathematical idea here. How many of you are in Econ 150 right now? Right? So for those of you in Econ 150, should be a very familiar kind of thing. This is a constrained optimization problem. And you've been having constrained optimization problems rammed into you for the last month or so, right? So this is an example of a constrained optimization problem. Right? You have to choose a point, but you can't choose a point freely. You have to choose a point on the line. All right? All right. OK, so let's talk about it a bit more before we do the math. All right, let's actually redraw it again, since I made a mess of this picture. So one thing you might want to ask is, in making this choice for firm 1, should firm 1 choose more or less or the same as it used to choose when the problem was simultaneous? All right, so let's put in again what it used to choose when the problem was simultaneous. I'll put it in just faintly. So here's our old Cournot picture. Looked like this. All right, and this was the quantity that firm 1 chose in the Cournot game. So let me call that Q1C. Right? So certainly one possibility is that firm 1 could choose her Cournot quantity. Right? She can certainly do that, and she knows that if she does that, firm 2 will respond by choosing the best response of firm 2 to firm 1 choosing the Cournot quantity. But we know what that is. What's firm 2's best response to firm 1's Cournot quantity? It's firm 2's Cournot quantity, right? So if firm 2 does that, if firm 1 chooses the Cournot quantity, then firm 2 will also choose the Cournot quantity. So one thing that firm 1 could do is effectively choose the old equilibrium. All right, that's certainly something that's available to firm 1. But firm 1 could also do other things. Firm 1 could produce less than that, or firm 1 could do more than that. All right? So who thinks firm 1 should choose the old equilibrium quantity? Who thinks firm 1 should choose more than that? Who thinks firm 1 should choose less than that? Right, I'm not getting much of a majority. Let's just try it with the camera on you, all right? All right. So once again, how many people think that firm 1 should choose the old equilibrium quantity? Dribbling of hands. And how about less than that? A few hands, and then they went down again. And how about more than that? There's a majority for more. Turns out more is correct. That's good. That's good news. It's good news. Why? Why do we think firm 1 should produce more than it used to produce before? Any takers on this? Well, let's think about it. As firm 1 produces more, or if firm 1 were to produce more, then firm 2, there, my voice is going, then firm 2 would produce what? Less, all right? As firm 1 produces more than her Cournot quantity, firm 2's response is to produce less. All right? Does anyone remember the jargon for this? What do we call games where the more I do of my strategy, the less you do of yours? Strategic substitutes. Good. This is a game of strategic substitutes. It's a game of strategic substitutes. And what that means is that as Q1 goes up, Q2, the best response of firm 2 to Q1, goes down. So what? So what? We can look at that just by looking at the picture. Well, the so what is, now we're in a sequential game. If firm 1 produces more than her Cournot quantity, she induces firm 2 to produce less. That's what we just said. And that's what? That's good for firm 1. Right? My producing more, inducing you to produce less, is good for me. It's going to keep prices higher in the market. Is that right? So let's just think it through again. In the Cournot equilibrium, the choice of firm 1 was the best choice for firm 1, taking the choice of firm 2 as given. And that was the old Cournot quantity. Right? But now we're in this Stackelberg setting, this sequential setting. There's an additional feature. Firm 1 doesn't have to take firm 2's output as given. There's an additional reason for producing, right, at the margin, which is at the margin, if I produce some more units of output, that leads you to produce less, which is good for me. All right? So that suggests that I'm going to produce more than I used to produce under the old assumption. All right? So this suggests that firm 1 should set Q1 bigger than Q1C to induce Q2 to be less than Q2C. All right, so the first thing we've learned, and we'll see this in the math later, is that firm 1 will in fact produce more than they used to under Cournot, and that will result in firm 2 producing less than Cournot. All right? Now we're already got a lot on the board now that we can actually solve out intuitively the problem. Do we think that firm 1's profits by this procedure are the same as they were under Cournot? Are they less than they were under Cournot? Or are they more than they were under Cournot? So let me say again. Firm 1 is going first now. We've argued that firm 1 is going to produce more. Do we think that firm 1's profits at the end of the day are going to be the same as they were under Cournot, higher than they were under Cournot, or lower than they were under Cournot? So let's have a poll again. Let me get the camera on you guys. So who thinks their profits are going to be the same as they were under Cournot? Who thinks the profits are going to have gone up? Who thinks profits have gone down? Now we're in good shape here because indeed the profits have gone up. There's a very simple argument why the profits have to have gone up. How do we know the profits must have gone up? Let me actually, this is simple enough, let me grab a mic on this. How do we know the profits just must have gone up? There was a hand at the back. Was there a hand at the back? Yes, okay, way at the back. How do we know profits must have gone up here? Way at the back. Yeah.
If firm 1 was going to lower their profits, they wouldn't have chosen to produce more.
All right, good, exactly. The fact that firm 1 has changed their output, in particular producing more, tells you they must be able to increase their profits by this maneuver, right? Let's just think that through. One option that was available to firm 1 before was to set output at the Cournot level. If firm 1 had set output at the Cournot level, that would have led firm 2 to set output at the Cournot level, and in that case, profits would have been exactly the same as before. The fact that firm 1 has moved away from that must mean there are higher profits available. So another way, firm 1 could have had exactly what it had before, so it must be doing at least as well as it was doing before, and the fact it's changed means it must be doing better than it was doing before. All right? So indeed, firm 1's profits have gone up. Firm 1's profits have gone up. We don't even need any math to prove that. It just must be the case logically. All right? What must have happened to firm 2's profits? What do you think's happened to firm 2's profits? So that's not so immediately obvious, right? It's obvious, I think, that firm 1's profits have gone up here because firm 1 could have had the same old profits and has chosen something else. But it's not immediately obvious what happened to firm 2's profits. Is that right? And before we get to what's happened to firm 2's profits, let's go through an intermediate step. Let's try and ask what must have happened to total output in the market, right, in this example, this nice simple example. Right? That's not immediately obvious either. Why? We've argued that firm 1's output went up, but firm 2's output went down relative to Cournot. All right? So it's not immediately obvious whether the sum of those two, Q1 plus Q2, went up or down. Right? We'd like to know what happened to Q1 plus Q2, total output in the market. And by the way, one particular reason we might care about this is, of course, consumers would like it to have gone up. Right? Because if total output's gone up, prices have gone down, and that's good for consumers. Right? So if you're the regulator, if you're designing this industry, if you're working for the Justice Department, or if you're working for the European Commission, you're going to want to know the answer when we switch from a simultaneous setting to an asymmetric setting where there's a leader firm and a follower firm. Is that going to be good for consumers or bad for consumers? All right, well, let's have a look. Well, we know that firm 1's output went up, and we know that firm 2's output went down, but can anyone tell me what happened to total output and why? Let's have a poll again. Who thinks total output, who thinks total output went down? Who thinks total output stayed the same? Who thinks total output went up? There's lots of abstentions. Let's try that again, because too many abstentions. Who thinks total output went down? Who thinks total output stayed the same? Who thinks total output went up? That's pretty split. So I think I know actually, that total output went up. And I claim I can see it on the picture. I claim if you stare at that picture, you can actually see that total output must have gone up. Who's good at looking at a picture? Let me get the mic in here. Right, the picture's there. Whoops. Okay. Okay. Let me try this first. So your name is?
Andy.
Andy, go ahead.
Judging by the slope of the line, you know that as it moves, the amount that Q1 changes will be greater than the amount that Q2 goes down.
Good, good. So what Andy said, I probably didn't hear it, everyone. What Andy's saying is, look at the slope of the line along which we slid. Right? When we went from Cournot to the Stackelberg equilibrium, we started here, and we slid in this direction down this line. Right? Q1 went up and Q2 went down. And what Andy's pointing out is we can see from the slope of this line that Q1 goes up more than 1 unit for every unit of reduction of Q2. Let me say it again. For every unit of increase of Q1, there's less than a proportion. Sorry, say again. For every unit of increase of Q1, there's less than a unit of decrease of Q2. Right, now they're saying it is the slope of this line is less than 1. Everyone see that? All right? So we know, by the slope of the line, we know that Q1 had to go up more than Q2 went down, which means total output went up, which means that prices went... What happened to prices as total output went up? That shouldn't be hard for everyone. Everyone's taking 115 here, right? So when total output went up, prices went down. Good. Right? Demand curve sloping down is not as important as backward induction, but it's still quite important. All right, so prices went down. So therefore, we now are ready to say what happened to firm 2's profits. Firm 2 is producing less than before. Firm 2's costs are the same, and prices have gone down. So what's happened to firm 2's profits? They must have gone down as well. So firm 2's profit has gone down, and we know that consumer surplus, this was CS, consumer surplus, has gone up. Right, for those people who remember their 115, prices have gone down, quantities have gone up, so consumer surplus here has gone up. All right, so we've analyzed everything qualitatively I can think of in this game without reference to any math at all. Is that right? We really haven't done any math there. And we talk about slope of a line. I guess that's math. I guess that's math in junior high or something, but we haven't really done any math there, right? Is that fair? Is that fair? Right, and we already have a pretty good intuition for what's going to go on in this market. We think Q1 is going to go up. We think Q2 is going to go down. We think that firm 1's profit are going up. We think firm 2's profits are going down. We think total quantity is going up. All right? Now let's see if we're right. Let's go back and do the math. All right? So I want to spend a bit of time grinding this out. So I don't claim that doing the math is fun, but I want to prove that we can do it, because otherwise everyone's going to either think that this was all kind of just blah, 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 and or people are going to be scared to do the math when it arrives on a homework assignment. All right. So for now, we're going to more or less, for the next few minutes, we're going to forget we're economists, and we're going to turn into nerds. That isn't a huge transition, but we'll do it anyway. All right, I've got the demand curve up there, but let me... All right, so the demand curve is still there. It's P equals A minus B, Q1 plus Q2. and I've got profits written up there, but let's put them somewhere more convenient anyway. So P equals A minus B Q1 plus Q2, and profit is equal to profit for firm I is equal to PQI minus CQI. All right? And what we're told to do in backward induction is what? First of all, solve things out for firm 2, taking firm 1 as given, and then go back and solve for firm 1. So exactly the discussion we've just had informally, we're now going to do we're going to do more formally. All right? So backward induction tells us solve for firm 2 first, taking Q1 as given. And what is that problem? As a sort of boring math problem, it says maximize by choosing Q2 the profits of firm 1. So that's going to be A minus B Q1 minus B Q2, that's the price, times the quantity Q2 minus C Q2. All right. All right, so this bit here is the price. These two terms together are revenues, and this term is costs. All right? Now I could do that. I could grind that bit out, but we already ground that bit out three or 4 weeks ago, right? So I'm not going to grind it out again. We know how to do that. But by the way, let's just remind ourselves what we did. We differentiated with respect to Q2. We set the thing we found, the derivative equal to 0. That was our first order condition. And then we solved for Q2. Is that right? Is that right? So when we did that, we went through the first order condition, and then we solved it. We know what we actually got, right? So what we actually got was that Q2 star, if you like, or Q2, let's just call it, is equal to A minus C over 2B minus Q1 over 2. And in fact, I've already given it to you up there. It's up on that top board. It's the best response for firm 2. So again, I could do this again, but since we did it a few weeks ago, I don't want to redo it. All right. All right, now the more interesting part. Not thrilling, but a little bit more interesting. All right, now let's solve for firm 1. All right, so what is firm 1 doing? Firm 1 is also trying to maximize profit. Firm 1 is choosing Q1. And firm 1, at least initially, looks like the same problem. It's A minus B Q1 minus B Q2 times Q1 minus C Q1. All right, this is the same line we had before. But now, whereas firm 2 was taking Q1 as given, firm 1 knows that Q2 is given by this formula here. All right, so what we're going to do is we're going to plug this Q2 into there. All right, again, for those of you in 115, this isn't the only way to do it. Sorry, 150, this isn't the only way we could do it. We could also set up a Lagrangian equation. But for those people who don't know what that is, don't worry, we're going to plug in today. All right, so we're going to plug this in, and when we plug it in, we get a right old mess, but let's do it anyway. So we're going to get max Q1 A minus B Q1 minus B, big bracket, A minus C over 2B minus Q1 over 2. Why don't I put this C inside the bracket as well while I'm here? Okay, so minus C, close bracket, Q1. All right, so just while I'm at it, why don't I put the C inside the bracket? Everyone okay with that? I'm doing algebra on the board, which is not fun, but it's useful to do occasionally. All right? So eventually, what are we going to do? Eventually, we're going to differentiate this thing, set it equal to 0, look at our first order condition, and so on. just as we normally would. So eventually, we're going to use basically 112 level calculus to solve this thing. All right, everyone remember how to solve a maximization problem? Yeah? But before we do that, let's tidy up the algebra a bit. All right, so this thing is, let's just tidy it up. So this is equal to max respect to Q1. And notice I've got an A minus C here, an A minus C here. And once I take this B inside the bracket, I've got a minus A minus C over 2 here. All right, so I've got an A minus C minus an A minus C over 2. So that's going to give me an A minus C over 2. And I'm really going to pray that the TAs are watching me carefully and going to catch my errors here. OK, so I think I'm OK so far, but please catch me. All right, what else have I got? I've got a minus BQ1 here. And from in this bracket, I've got a minus minus, that's a plus BQ1 over 2. Right, so I have a minus BQ1 plus a BQ1 over 2, so that's a minus BQ1 over 2. So far, so good. And that whole thing is multiplied by Q1. OK, so far? Let's multiply out the bracket, because otherwise I'll make a mistake. So this is the same as saying A minus C over 2 times Q1 minus B Q1 squared over 2. So far, so good? All right, now we're at the level where even my very rusty memory of calculus will get us through. OK, so let's try and do it. So what we're going to do is we're going to differentiate this thing with respect to Q1. All right, let's differentiate with respect to Q1. OK, so differentiating with respect to Q1, let's do it up here. Differentiate with respect to Q1, we get A minus C over 2 from this term. All right, and from the minus BQ squared over 2, we're going to get, the 2's are going to cancel rather pleasantly, so we're going to get BQ1 from that term. All right, everyone with me so far? All right, I'm going through this in sort of slow steps. I agree it's not exciting, but I want to make sure I don't make a mistake. All right, so to turn this into a first order condition, what must be true about this derivative? At the maximum, what must be true about this derivative? Set equal to 0, good. Set equal to 0. All right, and we should just check the second order condition. All right, how do I check the second order condition? I differentiate again and check it's negative, but if I differentiate again, I'm just going to get minus b. So minus b is certainly negative, all right? So second order condition's OK. So let's solve it out. Solving this for Q1, I get Q1 is equal to A minus C over 2b. All right, some people are leaving in sheer boredom. It has to be done occasionally. Right? Q1 is A minus C over 2b. All right? And we're not done yet. Now we want to go back and solve that algebraically for Q2. I know what Q1 is now. Q1 is A minus C over 2b. How do I find Q2? Somebody? Shout it out. How do I find Q2? Yeah, I've got to plug it in, right? I'm going to go back and plug this Q1 back into this expression here. So if I plug it back in, I'll get Q2 is equal to A minus C over 2b minus a half of A minus C over 2b for a total of A minus C over 4b. Is that right? That's what I have in my notes. This looks good. All right. So I'm now done. I've now found the equilibrium. I found that in this leader-followership game, this Stackelberg version of quantity competition, Q1 is given by A minus C over 2b, and Q2 is given by A minus C over 4b. Let's see how it matches up with the intuition we developed before without using any boring math. All right? So first of all, we're comparing Q1 and Q2 with what they used to produce, and what they used to produce is on the top board. What they used to produce, I can use this to guide the camera as well, what they used to produce is A minus C over 3B. Is that right? So our claim was that we think the new Q1 is bigger than the old Cournot quantity. So now firm 1 is producing A minus C over 2B. Previously it was producing A minus C over 3B, so that is indeed bigger. That's good news, right? So this is indeed bigger than Q Cournot. And our claim was that firm 2 will produce less than the old Cournot quantity. So firm 2 used to produce A minus C over 3B, and now it's producing A minus C over 4B, and that is indeed less than the old Cournot quantity. All right, so far so good. What about total output? How do I solve for total output? Add the two outputs together. That's not too hard. All right, so Q1 plus Q2 is equal to A minus C over 2B plus A minus C over 4B, which is in fact 3AC over 4B. Is that right? So it's going to be 3A minus C over 4B. So I just actually, for the first time today, I skipped a step, but is that okay? A half plus a quarter is 3/4. Okay, right. So total output is 3AC over 4B. What was total output before? Well, it used to be the Cournot total output. Let's put it here somewhere. This is bigger than 2A minus C over 3B, which is equal to the Cournot quantity Q1C plus Q2C. All right, so everything we predicted, just by looking at the picture and thinking about the economics, works out in the math. That's a good thing. We should feel a little bit relieved. I'm feeling a little bit relieved. All right? All right, everything we thought out intuitively, just using the economics, the logic of the situation, when we grind out the algebra, we get the right answers. We get confirming answers. All right? Everyone okay? So that isn't a particularly fun exercise per se, but I want to do it just to show that you can use backward induction to solve out problems exactly. Right? Backward induction, a little bit of what you learned in high school and or freshman calculus, can get you the answer. All right? All right, so now I want to leave aside the math and go back to the economics again. All right, so we started off with the question, who would you rather be, firm 1 or firm 2? And we know the answer now. Who would you rather be, firm 1 or firm 2? Firm 1, right? Because firm 1's profits went up and firm 2's profits went down. Let's just talk about this a little bit, about what's going on here. So firm 1, previously firm 1 and 2 were just setting quantities simultaneously. Right? We know now there's an advantage in going first. So suppose we change the game from the simultaneous move game to a game in which firm 1 and firm 2 can make announcements. All right? They can announce how much they're going to produce. So firm 1 comes in one day and says, I'm going to produce this much. And firm 2 comes in and can see firm 1's announcement. Right? So I've changed it into a sequential game. Firm 1 has announced how much it's going to produce. Firm 2 is going to go afterwards. Is that really a sequential game? Is that going to make a difference? Why is that? I claim that's not really enough. Let me say it again. We start from the simultaneous move game. If we just change it by simply allowing firm 1 to announce what they're going to produce, not actually produce it, but just announce what they're going to produce, you might think that's a sequential move game. And you might think that firm 1 now has an advantage. But I'm claiming that's not enough, really, to give firm 1 an advantage. Why? Why is that not enough? Let's try and get some ideas here. We come around to this side. So, yes, Patrick, why is that not enough?
There's no credible commitment that you're going to produce at that level.
Good, good. So imagine these two firms are, let's say they're newspaper-producing firms, and one is owned by NBC's parent company, and one is owned by Rupert Murdoch, right? And they're moving into this new market, and the market is a town that but both of them are going to issue newspapers in this market that currently doesn't have any newspapers. And Murdoch simply says, I'm going to produce lots of newspapers. Right? There's no reason for NBC to believe that. Right? So moving first here, it isn't enough simply to say you're going to move first. It isn't enough even to make a decision that's reversible. Right? Even if Q1 moves, but that decision could be undone, that isn't enough. What we need, and Patrick gave us the key word, what we need is commitment, a word that came up last week. All right? So for moving first to help you here, there really has to be commitment. Let's just get some of this down. There really needs to be commitment for this to work. So going back to the example of Murdoch and his competitor, Murdoch actually has to build the plant. There actually has to be a factory that he's built in, and that factory can't just be sold for scrap. Right? So what creates the commitment in the case when you've built the plant is what? Because having built it, it's a sunk cost. It's there. Right? So sunk costs can help here. Sunk costs can help. It can help making you committed. Once that money's gone, you can't get it back, so you're really committed to that scale. Does everyone know what I mean by sunk costs, by the way? Yep. Okay. So here's a case where a strategic move, entering first and sinking some investment, can help you in the marketplace. All right. Let's also look at this another way. Let's again go back to the simultaneous move game that we had before, where Murdoch and his competitor, the NBC parent corporation, are in fact going to move simultaneously. So both of them are in the business of discussing how big a newspaper plant to put in this new town, which hasn't got a newspaper yet, right? Somewhere in Alabama or something. I don't know. All right. And suppose that there are two boardrooms, both of which are avidly just trying to discuss how big a newspaper plant to build. All right. So suppose that one of the boardrooms are these four people on this row. This is the NBC parent company boardroom, and they're trying to decide how big a plant to build. All right. And over on the other side of the room is our Murdoch group, which is in fact let's take the row parallel. So these guys over there are our Murdoch, our News International group. All right. And it's a simultaneous move-back game, so basically we're in Corno. Right? Now suppose that Murdoch, just to pick a name out of the hat, it might not be the most moral gentleman in the world, who knows, and suppose that he in fact has hired one of the people in the NBC boardroom, in fact this guy, what's his name?
Ryan.
He's hired Ryan to be a spy. So Murdoch has a spy in the NBC boardroom. So Murdoch has a little advantage here, information-wise. Why? Because the NBC boardroom doesn't know what's going on in the Murdoch boardroom, but the Murdoch boardroom is going to know what's going on in the NBC boardroom. But to make the problem more interesting, suppose that somebody tells NBC's parent company that in fact there is a spy in their boardroom. Right? So these guys know they have a spy. They don't know who it is. If they knew who it was, they'd beat him up or fire him or something. Or maybe not. All right? But they know that someone's there. All right? Maybe they even suspect it's Ryan. So what should NBC do here? Well, what decision should NBC make? One thing they could do is they don't know it's Ryan, but Ryan has a sort of Murdoch-like face, so they might just fire him because he might be a spy. All right? Or, what should they do here? Any takers? If you're in you're in the NBC boardroom, you know that Murdoch has some spy in the camp. What should you do?
You can come up with a fake plan and see if it goes back to Murdoch.
All right, so your name is?
Chris.
So Chris is suggesting come up with a fake plan to feed it back to Murdoch. So Chris has been reading spy novels, right? So this was a John le Carre novel. That's certainly what you do. You create a whole bunch of fake information to feed back to the Russians, right, through this spy who, in fact, you've discovered. All right? And that isn't a bad idea. That might be a good thing to do. It's pretty hard to do, right? Because ultimately these actual decisions have to be made in the boardroom. Contracts have to be signed and so on. But I think Chris is onto the right idea here. So Chris's idea is create a fake plan to feed back to Murdoch, to give Murdoch some misinformation. But there's another thing you could do. I mean, get someone who hasn't contributed yet. Anyone else? Yeah, here. What's your name?
Osman.
So Osman, what would you do?
These guys get the first move now, effectively, because they can just decide they know.
So say what you just said, but shout out so everyone can hear you.
NBC now gets the first move because they can decide and they know the other people are going to respond to it.
All right, good. So Osman, what Osman is suggesting is maybe you don't feed Murdoch a fake plan, you feed Murdoch the true plan. Right? Effectively, what's going to happen now is if NBC decide to build a large plant, this information will be fed back to Murdoch, and Murdoch is now in the position of being the second mover. Right? When Murdoch moves, he or she knows what NBC is doing, right? And NBC knows that Murdoch is going to choose the best response to that. So it's as if NBC has been put into the position of firm 1, and Murdoch has been put into the position of firm 2. Right? Even with the correct plan. So the correct thing to do here for NBC is not necessarily to mislead Murdoch, but just go ahead and build a big plant. Have that information be fed to Murdoch, and let Murdoch respond to it. So notice, here's a slightly paradoxical thing. You might think that having a spy in the camp of the other team, you might think having a spy would help you. But here, having a spy, or having more information, if you like, having more information can actually end up hurting you. Right, everyone see that? Paradoxically, Murdoch ends up losing by the fact that he was able to predict what NBC were going to do. Now, there's a key to this, of course. It was crucial to the argument. What was crucial to the argument? It was crucial to the argument that NBC knew that Murdoch had a spy. Right? The key here is that the other side, the other players knew you had or were going to have more information. Right? So what's the bigger idea here? There are two bigger ideas. Bigger idea number one is games being simultaneous or sequential is not really about timing per se. It's about information. It's about who knows what and who knows that who's going to know what. Right? In a situation where firm 1, our boardroom over here, knows that Murdoch is going to have this information before Murdoch moves, that's actually a sequential game. Right? The timing is somewhat irrelevant. That's the first observation. And the second observation is already on the board. What we've learnt is sometimes, in strategic settings, sometimes, not always, more information can hurt you. Sometimes more information can hurt. We'll be careful here, because that's not always true, but sometimes it's true. And the reason that's true is, it can lead other players to take actions, in this case to create a large plant, that hurts you. Now, if you put Monday's lecture together with today's lecture, we've seen something, two very similar things arose. On Monday's lecture, having fewer options burning your boats ended up helping you, or having lower payoffs by putting collateral down ended up helping you. And that might seem like a paradox, but it isn't really a paradox, because what happened was, provided the other side knows you have fewer options, they know you've burnt your boats, or they know you'll suffer a future default on the loan, they know you've posted collateral, it will lead them to take behavior that helps you. In the case of the loan, it led to the lender giving you a bigger loan. In the case of the Saxon army, you at least hope it leads to the Saxon army running away. Right? Today, we see that more information can hurt you, and once again, it isn't really a paradox, it's the same kind of argument. The fact that the other side know you're going to have this extra information leads them to take actions that end up hurting you. All right? So in games, unlike in standard single-person decision problems, more information can hurt and more options can hurt. All right, and here's the reason. All right, now one other thing to say about this. The game we just looked at, the Stackelberg game we just looked at, is an example of something pretty famous. It's an example of first mover advantage. It's an example of a game with a first mover advantage. All right? Now, how many in the room have heard the term first mover advantage before? As few as that? No, seriously, the rest of you, how many of you have not heard the term first mover advantage before? One or two. All right. So I'm always a bit wary of first mover advantage as a term. And if you ask the students in the business school how many of them have heard the term, they've all heard it. It's a very popular business school term. It's a very popular term that you see in bad books. So let me just warn you a little bit about this. So if you go to the airport, let's say the Hartford airport, and the flight you want to get on is late, which is usually the case, and hence you end up in the bookstore, and you find yourself on the economics and business shelves, you start looking at strategy books. And typically, the kind of book you find at the airport on business or strategy or economics is a pretty bad book. All right, so it has some embossed cover, and it says, Strategy for Dummies, or My Boring Life by a Famous CEO. Right? And I worry about these books because you end up buying these books, you've got time on your hands, and you read them, and they give you absolutely terrible advice. All right? So not always, but almost always. And the kind of things they'll say is, it's always a good idea to move first, because that way you'll have a first mover advantage. All right? And this sounds right. I'm always worried about things that sound right, because they may sound right may mean they're right, but the problem is if they're wrong, they're tempting. They sort of lure you in. Right? So it's good to move first, because that way you'll have a first mover advantage. Sounds right, but it's nonsense. Right? There are situations of which this is one. There are situations where it's good to move first. In quantity competition, it's good to set your quantity to be committed, and that will lead the other side to producing a smaller quantity, which helps you. So sure, there are situations, there are games in which you want to move first. But there are also games in which you'd rather move second. Let me give you an example. All right, this is an example we've seen in this class before. Rock, paper, scissors. All right, if anybody is going to read one of those books and believe them, so if anyone's going to read, how to discover your inner Bill Gates and base their life on it, and therefore think there's a first mover advantage, I want to play rock, paper, scissors with that person. All right? All right, everyone happy that you'd rather go second in rock, paper, scissors? Do I need to prove that, or is that obvious? Okay, good. All right. Let me just expand on it a bit more into a more real-world setting. There are plenty of settings in the real world where the advantage of moving second isn't because, as in rock, paper, scissors, you just get to crush the other guy. It's simply that you learn from their mistakes. All right? So, for example, in the game of buying new equipment for the office or home, it's great to move second. The other guy goes out and samples some new piece of equipment. I wait to see if it works, and then buy it if it does. All right? Or if I'm setting up a firm in a new expanding market, let's say a new part of the former Soviet Union, I'm quite happy to let some other firms go in there first and then watch what they did and try and learn from their mistakes. If I'm setting a new curriculum for a university, I'm quite happy to let other universities, Duke and Cornell and so on, move first, and then I can go in as Yale, see what they did, and for sure they'll have made mistakes and I'll learn from them. All right? So there's plenty of obvious situations where moving second helps you for the obvious reason that information is often very useful. Right? We argued here, information can hurt you. But there's plenty of other perfectly natural situations where information is to your advantage. All right? So there are games with first mover advantages, but there are also games with second mover advantages. And let me give you one example of a game that neither has a first mover advantage or a second mover advantage, just to convince you that can happen as well. So when you were a child, you probably occasionally had to divide a cake and or candy bar with your sibling. Anyone been in this situation? There was some candy bar or cake, and you had to divide this thing between you and your brother and or sister? Is that right? And there's a typical way in which we divide things among siblings in that setting. There's a game we play to divide it. What's the game we play? Anyone? Yeah, I'll cut and you choose, or vice versa, right? So I'll cut and you choose neither has a first mover advantage or a second mover advantage, assuming you can cut accurately. It neither has a first mover advantage or a second mover advantage, which is precisely why it's a good way to divide the candy bar. All right? Now, to rub this point home, and because we've had a very dry lecture up to now, let's play a game. All right? So everyone can wake up now. Math is over. I want to play a game, and the game I want to play for the rest of today is called NIM. And it's not going to surprise you that one of the things we're going to learn in this game is that sometimes games have a first mover advantage, and sometimes games have a second mover advantage. So I'm giving away the punchline. How many of you have played NIM before? OK, if you played it before, you can't play now, right? So don't shout out. All right, so this is the game. There are two players, and there are two piles of stones. We'll make the piles of stones into just chalk lines on the board. The players are going to move sequentially. In each turn, the player whose turn it is to move picks one of the two piles and removes some of the stones, which will just be lines on the board. So they decide how many of those lines to delete. Each time it's your turn, you get to move again. You can choose the other pile this time. You move sequentially, and the only rule that matters is the person who gets the last stone wins. All right, so for example, here's a case where there's 1, 2, 3, 4, 5, 6, 7 stones on this pile, and 1, 2, 3, 4 stones on this pile. All right, so I'm going to get some volunteers to come on the stage and do this, but I was told I should choose a volunteer. So is Li Xing Chang here? Is Li Xing Chang here? So Li Xing Chang's going to volunteer for this. I'm volunteering Li Xing Chang because it's his birthday. All right, so can you get a round of applause for Li Xing Chang? You come on stage. Who wants to play against Li Xing Chang? Let's see. Maybe, anyone else want to play who hasn't played a game yet? How about the guy with the Yale hat on back there? Yeah, the white Yale hat. I'm staring right at the guy. Yeah, yes. You want to come up? All right. What's your name? Evan. So we've got Evan and Li Xing. Is it Li Xing? Li Xing and Evan, come up on stage. There's a step up here. Come on. All right. All right, so we'll let Li Xing go first, and we'll let Evan go second. Have you played this game before? I didn't hear it. OK, I didn't hear what the game is. We'll explain the rules again for those people who are sleeping, all right? All right, if you're sleeping, then the game is backward induction. But OK, so, all right, so the rules of the game are this. They're going to take turns. In each turn, they're going to pick one of these two piles. This is pile A, and this is pile B. And they're going to tell me how many of these chalk lines to delete. Yeah, that's a good idea. Thank you. They're going to tell me how many of these chalk lines to delete. Thanks. All right, and I'm going to delete those lines. We're going to go on playing until somebody gets the last line. The person who gets the last line wins. Okay, the person who gets the last line wins. You can get the last line 10 at a go. It doesn't have to be there's only one on the board when you get the last line, but the person who gets the last line wins. All right, so you have to pick a pile each go and tell me how many lines to remove. So Li Xing, why don't you go first? You can choose pile A or pile B and tell me how many lines to remove. Any advice from the audience? No advice? You're on your own here.
Can you remove 3 from pile A?
3 from pile A. OK, so 3 from pile A. Evan, your turn. When you stand nearer the board, so we can get you in there, so we can sort of have a...
And you remove 2 from pile A.
2 from pile A, okay, so pile A is the popular pile here. Lichin?
2 from pile B.
2 from pile B. Suspense is building here.
One from pile B.
1 from pile B, all right. Should go fast at this stage, go on.
2 from pile A.
Wait, last stone wins, last stone wins. Last stone wins, I'm a bit careful here. It's his birthday, come on. Last stone wins. Person who gets the last stone wins. Person who,
So 1 from A.
all right, 1 from A. Can't abstain, so...
1 from B.
1 from B. And Lisa is the winner here. All right? All right? All right, very good, very good. Let's get 2 more volunteers, all right? So everyone understand the game now? Thank you very much, gentlemen. All right? 2 more volunteers. Yeah, have you played before? Come on out. I want to get some female volunteers. It can't be a male-only class. There we go, thank you. This may not be as important in economics than doing the Stackelberg model, but it's probably a little bit more fun. All right, and your names are?
John.
Christine.
John and Christine, okay. All right, so let's make it a bit more complicated this time. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And 1, 2, 3, 4, 5, 6, 7. So we'll pick 2 prime numbers, if that's important. Let's see what happens. Why don't we say ladies first, I think we'd probably say. So Christine, your choice.
So that one has...
This one started off at 13, I believe. And this one started off at 7. Assuming I counted correctly. Let me get out of the way.
6 from pile A.
6 from pile. Okay, 1, 2, 3, 4, 5. Is that right? Is that right? 1, 2, 3. Okay.
3 from pile B.
3 from pile B.
3 from pile A.
3 from pile A.
1 from pile B.
1 from pile B, all right.
1 from pile A.
All right, so I think we're on to this, right?
1 from pile B.
1 from pile A.
All right.
1 from pile B.
All right.
1 from pile A.
All right.
1 from pile A.
Ah, okay, we'll switch.
1 from pile B.
All right, so Christine is the winner. Okay, okay. So a round of applause for these 2. All right. So I think everyone's figured out now how to play this game. Is that right? Has everyone figured it out? All right. Let me take one of these mics and go down and make sure that people have figured this out. All right. So what is the rule for how to play this game? What's the rule for how to play this game? People haven't figured it out. We have to play again. So let's try over here. Someone has an answer. How should you play this game? Yeah.
It depends on whether the piles have the same number in them.
All right.
If they have the same number, you want to be second player, and if they have different numbers, you want to be first player.
All right. And what should you do?
You want to...
Let's assume they have different numbers.
If they have different numbers, you want to make them equal.
You want to make them equal. All right. All right. So the trick to playing this game is, thank you, very good. The trick to playing this game is, if the piles are uneven, then you want to make them even. You want to make them equal. Everyone see that? So you start off with the piles being unequal, as we did both times. For example, 3 and 2. Then you want to be player 1. There's a first mover advantage, and the correct tactic is to equalize the piles. All right, what you'll notice now is that player 2 can't do anything. If they take 2 from here, you'll win by taking both of those 2. If they take 1 from here, you'll equalize the piles again. And if they take then 1 from here, you've won. All right? So the way to play this game is to equalize the piles. What does that mean? It means if the initial position has unequal piles, uneven piles, then you would rather be player 1. It has a first mover advantage. But if the initial position has an even number of has even numbers in the piles, then you'd rather be player 2. Is that right? Right? Because if you start off with an even number in each pile, the person moving first is going to make them unequal, and thereafter the next person's in a winning position. So I want to notice 2 things from this game. First, notice in this game that from any initial position, we can very quickly tell who is going to win and who's going to lose, assuming they play well. 3 things to note, actually. Second, we didn't actually use backward induction here, but it's pretty obvious you do want to use backward induction here. You want to figure out what the end game is going to look like. Is that right? It's very easy to see this game if you look at the end game. Right? And the third lesson is what we just said. In this game, sometimes there's a first mover advantage, sometimes there's a second mover advantage. That was the first lesson have I cycled? Right. So sometimes there's a first mover advantage in this game, sometimes there's a second mover advantage in this game. All right? So I'm just illustrating the point we made earlier, that it's not always the case that you want to move first. Sometimes you want to move second. Now today, I set up the piles with unequal piles, so there was a first mover advantage, but that was just to give an advantage to the guy whose birthday it was. All right? I could have set things up with equal lines in each pile and made the other guy go first. So last time we finished up by playing the game of Nim, and you remember, I hope, that the game of Nim was a game where there was 2 piles of stones. We made do with lines on the board, and the winner was the person who picked up the last stone. Remember, you had to pick piles. And I want to use the game of Nim to make a transition here. So what we pointed out about the game of Nim was it illustrated very nicely for us that games can have first mover advantages or they can have second mover advantages. A very small change in the game, essentially a very small change in where we started from, could switch a game from a game with a first mover advantage to a game with a second mover advantage. All right? Now today, I want to just draw a slightly grander lesson out of that game. So not only was it the case that the game sometimes has first mover advantages and sometimes has second mover advantages, but moreover, we could tell when it had a first mover advantage, and we could tell when it had a second mover advantage. Is that right? When we actually looked at the initial setup of those stones, we knew immediately that's a game in which player 1 is going to win, or alternatively, we knew immediately that's a game in which player 2 is going to win. All right? Now, it turns out that that idea is very general and actually has a name attached to it, and that name is Zamillo. So today we'll start off by talking about a theorem due to a guy called Zamillo. And the idea of this theorem is this: we're going to look at games more general than just Nim, and we're going to ask the question, under what circumstances would you know about a game, either that player 1, the person who goes first, can force a win, or that player 2 can force a win, or will allow a third possibility, which is it's going to be a tie. All right? So here's the theorem. Suppose there are 2 players in this game, like the games we looked at last time, and suppose, I won't define this formally now, but suppose the game is a game of perfect information. So what do I mean by perfect information? I'll define this later on in the class, but for now, all I mean is that whenever a player has his turn to move, that player knows exactly what has happened prior in the game. So, for example, all these sequential move games we've been looking at are moves of perfect information. When I get to move, I know exactly what you did yesterday, I know what I did the day before yesterday, and so on. All right, so it's a game of perfect information. and we're going to assume that the game has a finite number of nodes. So two things here. It can't go on forever, this game, and also there's no point at which it branches in an infinite way. All right, so there's a finite number of nodes, and we'll assume that the game has three possible outcomes. And actually, there's a more general version of this theorem, but this will do for now. The three possible outcomes are either a win for player 1, so I'll call it W sub 1, or a loss for player 1, which is obviously a win for player 2, or a tie. All right, so the game, like NIM last time, we only had two outcomes, so here we're going to go up to three outcomes, or three or fewer outcomes, I should say. All right, so these are the conditions, and here's the result. So I said three, it could be three, but it could also be two here. I'm just allowing for three. One is trivial. All right, so under these conditions, the following is true. Either player 1 can force a win. So either it's the case that this game is a game that if player 1 plays as well as they can, they're going to win the game. All right, no matter what player 2 does. Or or 1 can at least force a tie. All right, which means player 1 can play in such a way that they can assure themselves of a tie regardless of what player 2 does. Or it could be a game in which 2 can force a loss on 1. All right, so a win for 1 this is. All right? All right? So this theorem, when you first look at it, it doesn't seem to say very much. When you're staring at this thing, you might think that we already knew that we're looking at games that only have three possible outcomes, win, loss, or tie. All right? So it doesn't seem so surprising if you look at this theorem. It says, well, you're going to end up with a win or a loss or a tie. Right? But that's not quite what the theorem says. Right? The theorem says not only are you going to end up there, we knew that already, but the games divide themselves, games of this form divide themselves into those games in which player 1 has a way of winning regardless of what player 2 does. Right? Or games in which player 1 has a way of forcing a tie regardless of what player 2 does. Or player 2 has a way of winning regardless of what player 1 does. Right? So these games all have a solution. Let's go back to NIM to illustrate the point. All right? So in NIM, actually, there's no tie, so we can forget the middle of these. And in NIM, under certain circumstances, it is the case that player 1 can force a win. Who remembers what the case was for when player 1 can force a win? Anybody? When people who played last time? No? Yes? Ali, there's somebody here? Yeah, shout it out. All right, so if the piles start unequal, then player 1 can actually force a win. So in NIM, if the piles are unequal at the start, then 1 can force a win. It really doesn't matter what 2 does, 2 is toast. All right? Or the alternative case is the piles are equal at the start, and if they're equal at the start, then it's player 1 who's toast. Right? Player 2 is going to be able to force a loss on 1. So 2 can force a loss on 1, i.e. a win for player 2. All right? Does everyone remember that from last time? Yeah? It's just before the weekend, shouldn't be so far long ago. All right? So this theorem applies to all games of this form. So what games are of this form? Let's think of some other examples. So one example is tic-tac-toe. All right, everyone know the rules of tic-tac-toe? In England we call it noughts and crosses, but you guys call it tic-tac-toe, is that right? Right? Everyone know what tic-tac-toe is? Yeah? So in tic-tac-toe, which category is tic-tac-toe? Is it a game in which player 1 can force a win? Or is it a category in which player 1 can only force a tie? Or is it a category in which you'd rather go second and player 2 can force a win for player 2 or a loss for player 1? Which is tic-tac-toe? Let's have a show of hands here. Who thinks tic-tac-toe is a game in which player 1 can force a win? Who thinks tic-tac-toe is a game which player 1 can only force a tie? And who thinks player 2 is going to win? Yeah, most of you are right. It's a game in which if people play correctly, then it'll turn out to be a tie. All right, so tic-tac-toe, TTT, tic-tac-toe, is a game that leads to a tie. All right? Player 1 can still make a mistake, in which case they can lose. Player 2 can make a mistake, in which case they would lose. But there is a way of playing that forces a tie. All right? So these are fairly simple games. Let's talk about more complicated games. So what about the game of checkers? Right, so the game of checkers meets these conditions. It's a two-player game. You always know all the moves prior to your move. It's finite. All right, so there's some rules in checkers that prevent it going on forever. And there are 2 or 3 outcomes. I guess there's a third outcome if you get into a cycle you could tie. All right, so checkers fits all these descriptions. And what this theorem tells us is that checkers has a solution. Right? I'm not sure I know what that solution is, or I think actually somebody did compute it quite recently, even in the last few months. I just forgot to Google it this morning to remind myself. But what this theorem tells us, even before those people had computed it, checkers has a solution. All right? Let's be a bit more ambitious. What about chess? So chess meets this description. Right? Chess is a two-player game. Everybody knows all the moves before them. It's sequential. All right? It has finite number of moves. It's a very large number, but it is finite. All right? And it has 3 possible outcomes: a win, a loss, or a tie. Let's be careful. The reason it's finite is that if you cycle, I forget what it is, 3 times, then the game is declared a draw, declared a tie. All right? So what's this theorem telling us? It's telling us that there is a way to solve chess. It tells us there is a way to solve chess. Chess has a solution. Right? We don't know what that solution is. It could be that solution is that player 1, who's the player with the white pieces, can force a win. It could be that player 1 can only force a tie, and it could even be that player 2 can force a win. Right? We don't know which it is, but there is a solution. All right? There's a catch to this theorem. What's the catch? The catch is it doesn't actually tell us, this theorem is not going to tell us what that solution is. It doesn't tell us how to play. This theorem in and of itself doesn't tell us how to play chess. It just says there is a way to play chess. All right? All right. So we're going to try and prove this. We don't often do proofs in class, but the reason I want to prove this particular one is because I think the proof is instructive as part of a sort of QR at Yale. All right, so here's another example here, and some other examples you could think of chess as being the most dramatic example. All right. All right, so the reason I want to actually spend some time proving this today is because we're going to prove it by induction. We're going to prove it by induction. All right, and I'm going to sketch the proof. I'm not going to go through every possible step, but I want to give people here a feeling for what a proof by induction looks like. And the reason for that is, my guess is, well, let's find out. How many of you have seen a proof by induction before? How many have not? Right? So for those who haven't, I think it's a good thing in life, at one point in your life, to see a proof by induction. And for those who have, my guess is you saw it in some awful math class in high school, and it just went over your, didn't take over your head, but it kind of, the excitement of it doesn't catch on. I'm hoping to make that this is a context where it might appeal. All right. So proof by induction. We're going to prove this by induction on the maximum length of the game. And we'll call that n. We'll call n the maximum length of the game. So what do I mean by this? If I write down a tree, I can always look at all the paths from the beginning of the tree all the way through to the end of the tree. I should do that your way, from the beginning of the tree all the way through to the end of the tree. And I'm going to look at the path in that particular tree that has the largest length. Right, and I'll call that the length of the game, the maximum length of the game. All right? So we're going to do induction on the maximum length of the game. All right? So how do we start a proof by induction? Let's just remind ourselves, those people who've seen them before, we're going to prove that this theorem is true, the claim in the theorem is true for the easy case when the game is only one move long. All right, that's the first step. And then we're going to try and show that if it's true for all games of length less than or equal to n, whatever n is, then it must therefore be true for games of length n plus 1. Right? That's the way you do a proof by induction. Right? So let's just see how that works in practice. All right, so start with the easy step, and we'll do it in some detail, more detail than you really need to in a math class. So if n equals 1, what do these games look like? Well, let's look at some examples here. So I claim it's pretty trivial if n is equal to 1, but let's do it anyway. All right, so the game might look like this. Player 1 is going to move. Here's player 1 moving. The game is only length 1, so player 1 is the only player who ever gets to move. So the game might look like this. And let's put in a fifth branch. Might look like this. All right? And at the end of this game, rather than putting payoffs, let me just put the outcome. So the outcome must either be a win, or a tie, or a loss. So suppose it looks like this. Suppose it's a win, or here we could have a tie, or here we could have a win again, or here we could have a loss, and here we could have a tie. All right? So in this particular game, I claim it's pretty clear this game has a solution. It's pretty clear what one should do. All right? What should one do? One should pick one of her choices that leads to a win. To be careful, I'll put 1 in here just to distinguish who it is who's actually winning and losing. All right? So in this game, I claim that this game has a pretty obvious solution. Either player 1 is going to choose this branch that leads to a win, or this branch that leads to a win, and either way, player 1 is going to win. Right? Is that obvious? It's so obvious it's kind of painful. All right? So I claim this game, we can actually replace this first node with what's going to happen, which is player 1's going to win. Is that right? That was easy. Let's look at a different example. We'll do 3. All right? So here's another possible example, and this again, player 1 is going to move here, and this time the possible outcomes are a tie, or a loss, or a loss. All right, once again, it's a one-player game. This time he has 3 choices, and the 3 choices lead to a tie, or he loses. So I claim, once again, this is simple. What player 1 should do is what? Choose the tie, since there's no way of winning. But in that case, he can actually force it. He can actually choose the tie, in which case he's going to tie. So this game has a solution called choose the tie. And again, we could replace the first node of the game with what's actually going to happen, which is a tie. Everyone happy? And there's one other possibility, I guess. The other possibility is that here player 1 has a lot of choices, maybe 4 choices in this case. Once again, player 1 is going to move, but in each case, unfortunately for player 1, in each case, the outcome is that player 1 loses. Right? So this is a game in which player 1 is going to lose no matter what they do. Once again, it has a solution. The solution is player 1 is toast and is going to lose. All right? So I claim this has really captured all the possibilities of games of length 1. All right? I mean, you could imagine that there could be more branches on them, but basically there are these 3 possibilities. Either it's the case that one of those branches leads to a win, in which case the solution is player 1 wins. Or it's the case that none of the branches have wins in them, but one of them has a tie, in which case player 1 is going to tie. Or it's the case that all the branches have loss in them, in which case player 1 is going to lose. All right, so I claim I'm done for games of length 1. Everyone okay? So that step is deceptively easy, but there it is. All right, now we do the inductive step, the big step. All right, what we're going to do is we're going to assume that the statement of the theorem, which I've now hidden, unfortunately, let me unhide it, if I can. That would be easy. All right. Is it now visible? Good. So now let's assume that the statement of this theorem is true for all games length less than or equal to n. All right. Suppose that's the case. Suppose the claim is true for all games of this type of length less than or equal to some n. All right, what we need to show is, what we're going to try and show is, therefore, it will be true for all games of length n plus 1. What we want to show is, we claim, therefore, it will be true for games of length n plus 1. Right, that's a key step in inductive proofs. All right, so how are we going to do that? Well, let's have a look at a game of length n plus 1. All right, now obviously I can't use thousands here, so let me choose some relatively small numbers, but the idea will go through. So let's have a look at a game. All right, so here's a game in which player 1 moves first, player 2 moves second. Let's suppose if player 2 does this, then 1 only has a little choice here. Up here, then 1 has a more complicated choice. And perhaps 2 could move again. 1, 2, OK. All right, so this is quite a complicated little game up here. And down here, let's make it a little bit less complicated. Here, the game looks like this and then comes to an end. All right, so the tree looks like this. I haven't put the outcomes on it, but the tree looks like this. All right? So how long is this tree, first of all? Well, I claim that the longest path in this tree from the beginning to the end has 4 steps. Let's just check. All right? So 1, 2, 3, 4. That's what I claim is the longest path. Any path going down this way only has 3 moves in it. All right? So this is a game of length 4. All right? All right, this is a game of length 4. So we can apply it to our claim. Let's assume that the theorem holds for all trees length 3 or fewer, so that n plus 1 is 4 for the purpose of our example. All right? All right, so here's in this example, I don't want to put it here, let's put it here. In this example, n equals 3, so that n plus 1 equals 4. All right, everyone happy with this in the example? All right. Now what I want to observe about this is the following. Contained in this n plus 1, or game of length 4, are some smaller games. You could think of them as sub-games. They're games within the game. Is that right? So let's have a look. I claim, in particular, let's draw around them in pink, there's a game here that follows player 1 choosing up, and there's a game here that follows player 1 choosing down. Is that right? All right. And so these are both games. All right. And what do we have here? So this little game in here, the game in the top circle, the game that follows player 1 moving up, that's a game, and it has a length. All right, so this little thing is a game. This is a game, and I'm going to call it a sub-game. Some jargon we'll be getting used to later on in the semester. It's a game within the game, but it's basically just a game. This is a sub-game, and this is a sub-game following 1 choosing up. Let's put up in here. Following up. And I claim that this game has a length. This subgame has a length. So we knew that we started from a game of length 4. We've taken one of the moves, and let's make sure this is actually a game of length 3. Right? So if the game started here, this would be a game of length 3, because you could go 1, 2, 3 moves. Is that right? So this is a game of length 3. Right? So this is a subgame following 1 choosing up, and the subgame, has length 3. All right? And down here, this is also a subgame. It's a game that follows player 1 choosing down. Following 1 choosing down. And this little subgame has length. Now, here we have to be a little bit careful. You might think that since we started from a game of length 4, after the first move, we must be in a move of length 3. But actually, that's not true. And if we look carefully, we'll notice that this game down here, the game starting here, actually isn't of length 3, it's of length 2. Is that right? So even though we started from a game of length 4, by going this way, we put ourselves into a game of length 2. Is that right? Right, so 1, 2, or 1, 2, or whatever. All right? It has length 2. OK. All right. So in this example, n is 3, and n plus 1 is 4. And our assumption, our induction assumption, is what? We've assumed that the claim of the theorem holds for all games less than or equal to n, which in this case means less than or equal to 3. All right? So what does that tell us? That tells us by our assumption, this game, which I've put a pink circle around on the top, this is a game of length 3, this game has a solution. Right? It must have a solution because it's of length 3 or less. All right? So by the induction hypothesis, as it's called, by the induction hypothesis, this is a technical term, but what's the induction hypothesis? It's this thing. By the assumption that we made, this game has a solution. This game has a solution. Right? It's a game of length 3. 3 is less than or equal to n in this case, so this game must have a solution. Now, I don't immediately know by staring at it what it is, but let's suppose it was W. Say it was W. All right? And the game down below, this is also a game, and it's a game of length 2, but 2 is less than 3 as well. 2 is less than or equal to 3, so this game also has a solution. This game also, by the same assumption, has a solution. So its solution is, say, I don't know, maybe it's L. All right? So what does that mean to say that these games have solutions? In this case, we're going to assume W is this one and L is this one. Right, what does it mean? It means that we could, just as we did with the games up there, we could put the solution at the beginning of the game. We know that if we get into this game, we're going to get the solution of this game. And we know if we get into this game, we're going to get the solution of this game. All right? So we can replace this one with its solution, which by assumption was W, and this one by its solution, which by assumption was L. And here I want to be really careful. I need to keep track of which person it is it's a win or a loss for. So this was a win for player 1, hence it was a loss for player 2, and this was a loss for player 1, hence it was a win for player 2. All right? All right, so these games, each of them have some solution. In this case, I've written down the solutions as W or L. All right? So now what can we do? Let me just bring down this board again. I can translate this game into a very simple game. So I'm going to translate it up here. So this game can be translated as follows. Player 1 moves. If he goes up, then he hits a W. And if he goes down, he hits a loss. Right? So in this particular example, player 1 is effectively choosing between going up and finding himself in a game which has a solution, and the solution is he wins it, or going down and finding himself in a game which has a solution, and the solution is he's toast. All right? But that's what? That's a one-move game. That's a one-move game. So we know this is a solution. In particular, he's going to choose up. Right? This one has a solution. All right? This has a solution, it is a game of length 1. So what do we do? All right, somewhat schematically, we took a game of length n plus 1. In this case, that was 4. And we pointed out that once player 1 has made her first move in this game, we are in a game, or in a sub-game if you like, that has length less than 4. It could be 3, it could be 2, whatever. Whatever sub-game we're in, by assumption, that game has a solution. So it's really effectively, player 1 is choosing between going into a game with solution win or going into a game with solution loss. And if there were 15 other sub-games here, each one would have a solution, and each one, player 1 would be able to associate that solution with what he's going to get. What she's going to get. All right? So I claim that if it in fact is true that each of these sub-games of length 3 or less had a solution, then the game of length 4 must have a solution, which is what? It's the solution which is player 1 should pick the best sub-game. All right? Are people convinced by that step? People are looking slightly deer in the headlamps now, so let me just say it again. All right? All right? We started by assuming that all games of length 3 or less, or n or less, have a solution. We pointed out that any game that has length n plus 1 can be thought of as an initial move by player 1 followed by a game of length n or less. N or fewer, I should say. All right? Each of those games of n or fewer steps has a solution, so player 1 is just going to choose the game that has the best solution for her, and we're done. Right? In this particular example, player 1 is going to choose up, and therefore the solution to this parent game is player 1 wins. All right? Now the hard step, I think, in proofs by induction is realizing that you're done. So I claim we're now done. Why are we done? Well, we know, that was pretty easy, that all games of length 1 have a solution. That was pretty trivial. And we've shown that if any game of length n or fewer has a solution, then games of n plus 1 have a solution. So now let's see how we can proceed. We know that games of length 1 have a solution, so let's consider games of length 2. Right? Games of length 2 do games of length 2 have a solution? Well, let's set n equal to 1. We know that if games of length 1 have a solution, then any game of length 2 can be thought of as an initial step followed by a game of length 1. But that has a solution. So therefore games of length 2 have a solution. But now let's think of games of length 3. All right? We've shown that games of length 1 have a solution and games of length 2 have a solution. Right? Any game of length 3 can be thought of as a game in which there's an initial step followed by either a game of length 1 or a game of length 2, each of which have a solution. So once again, a game of length 3 has a solution and so on. All right? So games of induction, they work by building up on the length of the game, and we're ending up knowing that we're done. All right, for those people who've never seen a proof by induction, don't worry, I'm not going to test you on a proof in induction on the exam. I just wanted you to see one once. And let's all take a deep breath and try and digest this a little bit by playing a game. All right, so I'll leave it up there. I'll leave it up there so you can stare at it. I want it down again later. All right, and let's try and actually play a game and see if we can actually throw any light on this. All right, so I'm going to pick out volunteers like I did last time, but first of all, let me tell you what the game is. So once again, I'm going to have rocks in this game, and once again, I'm going to approximate those rocks with marks on the blackboard. All right, so here's an example. And the example is this. The game involves an array of rocks. So here the array has 1, 2, 3, 4, 5 rows and 3 columns. So the rocks are not arranged as they were before in piles, but rather in a sort of pretty array. I actually made it more even, but this is 1, 2, 3, 4, 5 rows and 1, 2, 3 columns, just in this example. Right, but in general, there's an array of rocks, n times m. All right, and we're going to play sequentially with the players, and the way the game is going to work is this. This is meant to be in this row. The way the game's going to work is when it's your turn to move, you have to point to one of these rocks. And whichever rock you point to, I will delete that rock and all the rocks that lie above or to the right of it, all rocks that lie to the northeast of it. So for example, if you pointed to this rock, right, then I will remove this rock and also this one, and this one. Right? And if the next person comes along and chooses this one, then I will remove this one and also that one. Okay, everyone understand? All right, and the game is lost. Let's be clear, this is important. The game is lost by the person who ends up taking the last rock. The loser is the person who ends up removing the last rock. All right? Do I have some volunteers? Can I volunteer people one? How about the guy with the white T-shirt with the yellow on there? All right, okay, can come on up front. All right, and who else can I volunteer? Everyone's looking away from me, desperately looking away from me. Okay, how about the guy with the Yale sweatshirt on, the Yale, the Yale football sweatshirt on, okay? All right, so come on up. Your name is, let me get a mic up here. Thank you. Great, your name is?
Noah.
Noah, and your name is? Say it into the mic. So
Karan.
Karan, okay. So Noah and Karan are our players. All right, everyone understand the rules? You understand the rules? Yeah? All right, so why don't we let Noah go first? So Noah, which rock are you going to remove? Remember, the last rock loses.
That one?
That one. Okay, so Noah chose this one, so I'm going to remove this one and the one above it.
So all the rocks to the north and east are deleted, right?
All the rocks to the north and east of it are deleted. Wait, that means you last rock loses, okay? Last rock. Okay, good. All right. So, all right.
That one?
That one, okay. So now we have an L shape. That one. All right.
That one.
That one. Okay. All right. So we're done. All right. Okay. Everyone understand how that worked? All right. Round of applause for our players, please. All right. Thank you. Let me get 2 more volunteers. Now everyone's seen it. These guys had the hard job. They had to figure it out cold. 2 more volunteers. Oh, I don't have to volunteer. This is Yale. Oh, yeah, there's somebody volunteering. You're volunteering? Great. I have 1 volunteer. You can pick an opponent if you like. There you go. Okay, thank you. Your name, well, let's just wait for the mics to hear. So your name is? Peter. And your name is? Justin. All right. All right, let me put a new array up here.
Thanks, Peter.
All right, so let's put a new array up here. This time let's make it, doesn't have to be odd, so let's make it this time a little bit more complicated. So we'll have 5, let's have 4 rows and 5 columns this time. All right, so this time, okay, so last time I had 5 rows and 3 columns, and this time I have 4 rows and 5 columns. 4 rows and 5 columns. All right, away you go. Move out the way. Why don't you stand a bit nearer the board, make it a little easier for people to see what's going on. There you go. All right, so Peter, you want to go first?
Sure. I'll go there.
That one? Okay, so this one goes, which means which means all of these go as well. All right. Anyone got any advice from the floor? Anyone shout things out? Not too loud, right?
I'll try going here.
In there. Okay, well, we're back to our L shape again. Here.
Ah!
All right, now people can see what's going on. All right, all right.
I'll go here and speed it up.
All right, okay. All right, thank you. All right, so round of applause again. All right, thank you, guys. So here's what I claim about this game. First, and this isn't a formal claim, this is a lot harder than the game we played last time, right? Everyone convinced by that, all right? So here's going to be an exercise. I'll set it as a challenge. I may even put it formally on the problem set this week. But that's what I just say. If I do put this on the problem set this week, I don't expect you all to solve it. All right? If I do put it on the problem set, it's an optional problem. All right? But here's the challenge. The challenge is, I claim, I know from Zermelo's theorem that no matter what n is, and no matter what m is, this game has a solution. Right? So Zermelo's theorem tells us this game has a solution. Now notice, it could have a different solution depending on the n and the m, depending on how many rows and how many columns. Is that right? So depending on n and m, each such game has a solution. Is that right? Is that right? Right. Right. So which could depend on n and on m, on the number of rows and columns. So just as in NIM, it depended on how those piles started out. All right? So what's going to be the homework assignment? Find the solution. Find the solution. Homework. What is the solution? All right? So I claim, let me give you a hint, I claim it is useful to remember that there is a solution. All right? It turns out to be useful to remember that. That wasn't much of a hint, you knew that already, but I just emphasize that. Okay. Okay, so I want to do a bit of a transition now away from these games like chess and like checkers and like this game with the rocks or NIM. And I want to be a little bit formal for a while. All right, so one thing we haven't done for a while, actually really since the midterm, is write down some formal definitions. So I'm going to do that now. I want at least one of these boards back. All right. So as I warned very early in the class, there are some points of the day when we have to stop and do some work, and the next 20 minutes or so is such a point. All right. So, okay, what is this? This is formal stuff. And the first thing I want to do is I want to give you a formal definition of something I've already mentioned today, and that's that idea of perfect information. So what we've been looking at really since the midterm are games of perfect information. So a game of perfect information, is one in which at every node, or at each node in the game, the player whose turn it is to move at that node player whose turn it is to move knows which node she is at. All right, so it's a very simple idea. Like every game we've seen since the midterm has this property. When you're playing this game, you know where you are. You know where you are. So you know which node you're at. You know what your choices are, and what that means implicitly is she must know how she got there. All right, so the whole history of the game is observed by everybody. When I get to move, I know what you did yesterday. I know what I did the day before yesterday. If I'm playing with a third person, I know what they did the day before that. All right, so a very simple idea, but it turns out to be an idea that actually allows us to, very simple idea, to use things like backward induction very simply. All right, now so far, all we've been doing is thinking about such games. Games like perfect competition, or games like quantity competition between firms, or games like the games where we were setting up incentives, or games like NIM, and we've basically been solving these games by backward induction, rather informally. Right, what I want to add in now is the notion of a strategy in these games. Right, so when we had simultaneous move games, strategies were really unproblematic. Right, it was obvious what strategies were, but when we have games which are sequential, that go on over a period of time, and information is emerging over a period of time, we need to be a little careful what we mean by a strategy. All right? So what I want to do is I want to define a pure strategy, at least, as follows. So a pure strategy, for player I in a game of perfect information so in the games we've been talking about, games which we can represent by trees, is what? It's a complete plan of action. In other words, what it does is it specifies which action I should take let's not make it should take, let's say will take at each of I's nodes, each of I's decision nodes. So when you first read this definition, it seems completely uninteresting and unproblematic. A pure strategy for player I just tells you in this game, whenever you might be called upon to move, it tells you how you're going to move. Right? So if you're going to move 3 times in the game, it tells you how you're going to move the first time, it tells you how you're going to move the second time, and it tells you how you're going to move the third time. All right? All right, so far, none of this seems difficult, but actually, it's a bit more difficult than it looks. So let's have a look. What I want to do is I want to look at an example, and this example, I'm hoping, is going to illustrate some subtleties about this definition. So here's an example. In this example, player 1 moves first, and they can choose in or out. Or if you like, let's call it up or down, since that's the way we've drawn it. So they can choose down or up, and I'll use capital letters U and D. Then if player chooses up, then player 2 gets to move, and player 2 can choose left or right. And if player 1 moves up, followed by player 2 choosing left, then player 1 gets to move, in which case player 1 can move up or down. I'll use little letters this time, little u and d. Right? Let's put some payoffs in this game. So the payoffs are 1, 0 here, 0, 2 here, 3, 1 here, and 2, 4 here. All right. So on paper, on the board, when you first look at it, this is a perfectly simple game. It's just like many of the games we've been looking at since the midterm. It has a tree. We could analyze it by backward induction. In a moment, we will analyze it by backward induction. All right? But what I want to do first is I want to say, what are the strategies in this game? All right? So let's start with player 2, since it's easier. Player 2's strategies here are what? Well, pretty simple. Player 2's strategies are, player 2 only has one decision node. Here's player 2's decision node. Right? And the strategy has to tell player 2 what he's going to do at that decision node. So there's only two choices, left or right. So player 2's strategies are either left or right. Okay? Notice, however, already one slight subtlety here. Player 2 may never get to make this choice. All right? So player 2 is choosing left or right, but player 2 may not ever get to make this choice. In particular, if one chose down, it's really irrelevant whether player 2 has chosen left or right. Right? Nevertheless, a strategy has to specify what player 2 would do were he called upon to make that move. All right? Now let's look at player 1's strategies. So what are player 1's strategies in this game? What are player 1's strategies? Any takers? Anyone want to guess? So I claim it's tempting, but it turns out to be wrong, to say that player 1 has 3 strategies here. It's tempting to say either player 1 moves down, in which case we're done, or player 1 moves up, in which case at some later date she may be called upon to choose up or down again. All right, so it's very tempting to think that player 1 has just 3 strategies here. Down, in which case we're done, or up, followed by either up or down, depending on what followed by either up or down if she's reached at that point. Right? But actually, if we follow this definition carefully, we notice that player 1 actually has 4 strategies here. So let me say what they are, and you'll see why it's a little odd. So here's one of the strategies we talked about, up followed by up. And here's another one we talked about, up followed by down. But I claim there are 2 others. Down followed by up, and down followed by down. Right? So what's a little weird about this? What's weird is we know perfectly well that if player 1 chooses down, she's not going to get to make the choice, the second choice, up or down. But nevertheless, the strategy has to tell us what she would do at every node, regardless of whether that node actually is reached by that strategy. Let me say it again. The strategy has to tell you what player 1 would do at that node, regardless of whether that node is actually reached by playing that strategy. Right? It's a little weird, right? There's a bit of redundancy here. It's a bit redundant. All right? Now, why? Well, we'll see why in a second. Let's first of all consider how this game will be played according to backward induction. All right, so how do we play this game according to backward induction? Where do we start? Shouldn't be a trick question, right? Where do we start the game according to backward induction? At the end, okay. So the end here is player 1. And player 1 will choose here to go down. Is that right? Because 3 is bigger than 2. So if we roll back to player 2's move, player 2, if she chooses left, She knows it she'll be followed by player 1 going down, in which case she'll get 1. But if she chooses right, she'll get 2. So player 2 will choose right. All right, so player 1 here, if she chooses up, then player 2 will choose right, and player 1 will get 0. And if she chooses down, she'll get 1. So player 1 will choose down. All right, so backward induction suggests that player 1 will choose down, and followed by player 2. If player 2 did get to move, she'd choose right, followed by player 1. If she did get to move again, choosing down again. All right? Notice that backward induction had to tell us what player 2 would have done had she got to move. And backward induction had to consider what player 2 would think that player 1 would have done were player 1 to get to move again. So to do backward induction, player 1 has to ask herself what player 2 is going to do, and player 2 has to therefore ask herself what player 1 would have done, which means player 1 has to ask herself what player 2 thinks player 1 would have done, which means we actually needed to say what player 1 did over here. Let me say it again. So backward induction here tells us that player 1 chooses down, in which case the game is over. But to do backward induction, to think through backward induction, we really needed to consider not just what player 2 was going to do, were he to get to move, but also what player 2 would think player 1 would do, were player 2 to get to move and were to choose left. Right? So all of these redundant moves were actually part of our backward induction. Right? We need them there so we can think about what people are thinking. All right, so backward induction tells us that the outcome of the game is down. All right, but it tells us in terms of strategies, player 1 chooses down, and were she to get to move again, would choose down again, and player 2 chooses right. All right. Now let's analyze this game a totally different way. We now know what the strategies are in the game. Player 2 has 2 strategies, left and right. And, sorry, player 2 has 2 strategies, left and right. And player 1 has 4 strategies, up, 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 down, up, and down, down. All right? So let's write up the matrix for this game. All right, so here it is. It must be a 4 by 2 matrix. Player 2 is choosing between left and right, and player 1 is choosing between her 4 strategies, up, 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 down, up, and down, down. And we can put all the payoffs in. So up, up, left gets us to here, which is 2, 4. Up, 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 right gets us here, which is 0, 2. Up, down, left gets us here, which is 3, 1. Up, down, right gets us here again, which is 0, 2. And down, up, or down, up gets us going right out of the game immediately, so we're going to go to 1, 0. And in fact, that's also true for down, up, right. And it's also true for down, down, left. And it's also true for down, down, right. Right, so all of these 4 strategies at the bottom started off by player 1 choosing down, in which case the game is over. So once again, in this matrix, you can kind of see the redundancy I was talking about. All right, in this matrix, the 3rd row, the down, up row, looks the same as the down, down row. Everyone's happy with that? All right. So when we've had matrices in the past, how have we solved the game? Well, we've been doing this backward induction stuff for a couple of weeks, but prior to the midterm, if I'd simply given you this on the midterm, what would you have done? You'd looked for Nash equilibrium, right? So let's do that. Let's look for Nash equilibrium. So if player 2 chooses left, then player 1's best response is up, up. And if player 2 chooses right, then player 1's best response is either down, up, or down, down. All right? Conversely, if player 1 chooses up, up, then player 2's best response is left. If player 1 chooses up, down, then player 2's best response is right. If player 1 chooses down, up, then player 2 doesn't care because they're getting 0 anyway. And if player 1 chooses down, down, then again player 2 doesn't care because they're getting 0 anyway. All right? So the Nash equilibria in this game are what? So one of them is here. All right, so that's one Nash equilibrium. So one of them is down, down, followed by right. Okay? And that's a Nash equilibrium we actually found by backward induction. Right? The Nash equilibrium down, down, right corresponds to the one we found by backward induction. All right? But there's another Nash equilibrium in this game. The other Nash equilibrium in this game is this one. All right? That's also a Nash equilibrium. And what does it involve? It involves down, up, and right. Down, up, and right. Sorry, down, up, and right. Down, up, and right. All right? So what happened in that equilibrium? Player 1 went down, which made everything else kind of irrelevant. Player 2 played right, and player 1, in their plan of action, was actually going to choose up. Right, say it again. Player 1, in fact, went down. Player 2, had they got to move, would have chosen right. Right? And player 1, had they got to move at this second time, would have chosen up. So how can that be a Nash equilibrium? It doesn't correspond to backward induction. Right? In particular, player 1 up here is choosing a strategy that seems silly. Right? They're choosing up rather than down, which gets them 2 rather than 3. Right? So how can it possibly be that that's an equilibrium strategy? Right? The reason it can be an equilibrium strategy is it doesn't really matter what player 1 chooses up here from player 1's point of view, because it's never going to be reached anyway. As long as player 2 is going to choose little right here, as long as player 2 is choosing right, it really doesn't matter what player 1 decides to do up there. From player 1's point of view, it doesn't make a difference, it isn't reached anyway. All right? So we're highlighting here a danger. And the danger is this. If you just mechanically find the Nash equilibria in a game, you're going to find people choosing actions that, if they ever were called upon to make them, are silly. Say it again. If you just mechanically find the Nash equilibria in the game, just as we did here, you're going to select some actions, in this case an action by player 1, that, were she called upon to take that action, would be a silly action. And the reason it's surviving our analysis is because, in fact, she isn't called upon to make it. All right. Now, to make that more concrete, let's take this to an economic example, this same idea. All right. So what I want you to imagine is a market. And in this market, there is a monopolist who controls the market, but there's an entrant who is thinking of entering into this market. Right? So right now, this market has a monopoly in it. Right? And the monopolist is an incumbent. Let's call him Inc. And there's an entrant who is trying to decide whether or not to enter the market or whether to stay out. If they stay out, then the entrant gets nothing, and the incumbent continues to get monopoly profits. So think of this as 3 million a year. All right? If the entrant enters, then the incumbent can do one of two things. The incumbent could choose to fight the entrant, by which I mean charge low prices, advertise a lot, try and drive him out of the market. He could behave very competitively, in which case the entrant will actually make losses, and the incumbent will drive her profits down to zero. Right, conversely, the incumbent could choose not to fight. If they don't fight, then they'll simply share the market, and they'll both make, let's say, corno profits or duopoly profits of $1 million each. All right, so in this game, let's just say again, there's a market there, the monopolist is in the market, and the monopolist is making $3 million a year, which seems pretty nice for the monopolist. All right, the entrant is trying to decide whether to invade this market. If she invades this market, if she's fought, she's in trouble, but if the monopolist accommodates her, then they just go to duopoly profits, and the entrant does very well, gets $1 million in profit. All right, let's have a look at this game, analyzed. First of all, this time, let's analyze it by Nash equilibrium. All right, so I claim in this game, this is pretty simple, the entrant has two strategies. Put it straight into the matrix. The entrant has two strategies. They're either to go in or to stay out. And the incumbent has two strategies. They are either to fight the entrant or not to fight. All right? And the payoffs of this game are as follows. Let's put them in. In and fight was -1, 0. In and not fight was 1, 1. And out led to the incumbent maintaining monopoly profits. Let's have a look at the Nash equilibria of this game. All right, so the first thing to do is to look at the best responses for the entrant. So if the incumbent chooses fight, then the entrant's best response is to stay out. If the incumbent chooses not fight, then the entrant's best response is to enter. All right. How about for the incumbent? If the entrant chooses to come in, then the incumbent's best response is not to fight, because 1 is bigger than 0. But if the entrant stays out, it really doesn't matter what the incumbent does. They'll get 3 either way. All right? So the Nash equilibria here are either in followed by not fighting. You end up with a duopoly. Or out followed by fighting. Of course, the fight doesn't take place. Out followed by we would have fought had you entered. All right? So these are the Nash equilibria. Let's analyze this game by backward induction. All right? From the incumbent's point of view, if the incumbent gets to move, then is she going to choose fight or not fight? She's going to choose not fight. So the entrant should do what? Somebody? The entrant should enter, because if she enters, she gets 1. If she stays out, she gets 0. So backward induction just gives us this equilibrium. All right? Now the question is, what do we think is going on at this other equilibrium? Let's talk it through. All right, so here you are, you're about to enter the market. You leave Yale, you set up your business, and your business is challenging some monopolist or quasi-monopolist, like Microsoft, say, and you go out there and you're about to put out your new operating system. And you know that your new operating system will make plenty of money, provided Microsoft doesn't retaliate and drop its prices by half and advertise you out of the market. All right? So what does Bill Gates do? Bill Gates, the head of Microsoft. He says, wait a second, before you graduate from Yale and go and set up this company, let me just tell you, I'm going to fight. If you enter, I'm going to fight. All right? And if you believe him, if you believe that he's going to fight, what should you do? You're not going to bother to enter his market. Right? If you believe that you're going to get fought by Bill Gates, then you believe that if you enter you're going to make losses, so you choose to stay out. And this threat that Bill Gates makes here, it doesn't cost him anything. Provided you go out, he doesn't actually have to fight at all. Right? That's why it is, in fact, an equilibrium to imagine you staying out, believing that you're going to get fought if you enter. And it is the best response for the guy to fight, knowing that you're going to stay out. But this doesn't sound right. Why doesn't this sound right? It doesn't sound right because you really shouldn't believe the guy who says he's going to fight you when you know that if you did enter, fighting would cost the incumbent money. If you did enter, if he fights you, he gets 0. If he doesn't fight, he gets $1 million. All right? So this threat that the guy is going to fight you, this threat is not credible. Right? This is an equilibrium, but it relies on believing an incredible threat. It's true that if you think about entering the market that Microsoft is in, you're very likely to get a little email from Bill Gates, or it won't be an email because that can be taken to court, but some little threatening remark in your ear from Bill Gates. It's true if you entered into the market that the people who build aircraft are in, the head of Boeing might pay you a call one day or send someone round, right? But these threats are not credible threats. Is that right? They're not credible threats because we know that if you did enter, it isn't in their interest to fight. They're making a lot of noise about it, but you know that if you did enter, backward induction tells us they're not going to fight. All right? All right? But now we're in slightly an odd situation. All right? Why are we in an odd situation? Two things. One, we seem to be finding that there are Nash equilibria in games. We found one here and one up here. There are Nash equilibria that are not supported by backward induction. That's the first reason we're a little worried here. And the second reason we're worried is even the economics of this doesn't quite smell right. Right? For example, if you in fact did if you did in fact announce you were going to operate, you're going to build a new operating system and got a threatening call from Bill Gates, there might be a reason why you might actually believe that call. Why might you believe that call? Why might you believe that call? Can we get a mic out? Let me try. I'll do it. So why might you believe a call from Bill Gates saying he's going to beat you up? Not beat you up, but he's going to charge low prices if you produce an operating system.
If you look at the future revenue streams, like for the next 10 years, and he consistently gets $1 million for the next 10 years, he would be better off if he just drove you out of the market for the first year and then get $3 million for the next 9 years.
All right, okay, that wasn't quite what I was thinking of. Okay, it's true if we cheat a bit and make one of the, okay, so what you're saying is I could get 3 forever versus 1 forever. Assume these are both present discounted values of future cash earnings, all right? So we've done the future cash flow analysis of this, right? So this isn't an accounting mistake, all right? Not for accounting reasons. There's some other reason why when Gates threatens you, you might want to believe it. Let me try up here first.
He can afford to make an example of you so no other people will invade.
Right. So one thing that's in Bill Gates' mind is right now he's thinking about competing with you, right? But down the road, there's a lot more of you guys coming, right? There's whatever it is, 280 of you in this room, and there's another 280 in next year's class, and so on. And Bill Gates knows that each of you might come out and threaten his monopoly, his Microsoft monopoly. And he might think that by setting an example to one of you, he might be able to keep the others out. And somewhere, that kind of argument, the argument of making an example of somebody, is missing here. Missing completely. But it's got to be important, right? It's got to be an important idea. All right? So we're going to come back and spend the first half of Wednesday's class picking up that, just precisely that idea. Okay, so this is what we did last time. We looked at a game involving an entrant and an incumbent in a market. And the entrant had to decide whether to enter that market or not. And if they stayed out, the incumbent remained a monopolist, and the monopolist made $3 million in profit. All right? And if the entrant goes in, then the incumbent can decide whether to accommodate the entrant and just settle for duopoly profits, making $1 million each, or the incumbent can fight, in which case the incumbent makes no money at all, and the entrant loses $1 million. And we pointed out a number of things about this game. One was that when we analyzed it in a matrix form, we quickly found that there were two Nash equilibria. Nash equilibria were in and not fight, and out and fight. But we argued that backward induction tells us that the sensible answer is in and not fight. Once the incumbent knows the entrant is in, they're not going to fight, because 1 is bigger than 0, and the entrant, anticipating this, will enter. And we talked a bit more. We said this other equilibrium, this out-fight equilibrium, it is an equilibrium because if the entrant believes the incumbent's going to fight, then the entrant is going to stay out, and it's costless for the incumbent to, quote, fight if in fact the entrant does stay out, because they never get called upon to fight anyway. So the idea of this was that for the incumbent to say they're going to fight is an incredible threat. Or, that's terrible English, it's the way it's always taught in the textbooks, it's usually called a not credible threat. And that not credible threat is, he's not really going to fight if the entrant comes in. He's not really going to fight if the entrant comes in, and therefore the entrant should come in, and in fact, the incumbent will accommodate it. So what we've shown here is if we believe this argument, then the entrant will come in, and the incumbent is going to let him in. All right? And at the end, we started talking about this in a slightly more elaborate setting. So let's just remind you what that more elaborate setting is. The more elaborate setting is, suppose that there is one firm, one monopolist, and that monopolist holds a monopoly in 10 different markets. So we'll have our monopolist be Ali. All right, so here's Ali, here's our monopolist, and he owns pizzeria monopolies in 10 different markets. All right, and each of these 10 different markets are separate. All right, they're different towns. And in each of those 10 markets, he knows he's going to face an entrant. And those entrants are going to come in order. So let's talk about who those entrants are going to be. The entrants are going to be this person, and so on. Let's find out who they are. So your name is? Isabella. And where are you from? Miami. Miami. So Miami is one of the markets, and your name is? Scott. From where? Wisconsin. Wisconsin.
Where?
Madison. We've got 2 towns. Let's give you your towns now.
My name is Lang. I'm from Bridgeport, Connecticut.
Okay, got 3 towns.
I'm from Miami, too.
It's about Yale diversity. Well, we'll pretend you're from somewhere else. Put them in New Orleans or something. All right?
Rich from Boston.
From Boston, all right?
From Orange, Connecticut.
From Orange, Connecticut, just down the road.
From St. Louis, Missouri.
All right, haven't done 10 yet. I'm not quite at 10. 1, 2, 3, 4, 5, 6, 7.
Sulphur, New York.
All right.
Hong Kong.
Hong Kong, that's way away, and
Long Island.
Long Island. I think I've probably got 10 markets here, okay? So Ali owns a pizza shop. He's the monopoly pizza shop owner in each of these 10 markets. And what we're going to see is, we're going to see what happens as sequentially these entrants try to enter. And the way this game is going to work is that they're lined up. We know the order in which the entrants are going to come. They're going to start off. The first person who has to make a decision is it's Isabella, right? It's Isabella, and we're going to see how our monopolist responds. Okay, so let's have a look at this. All right, so Isabella, who's in which market again? Miami. In Miami. Okay, what are you going to do? Enter. Enter. What are you going to do?
I will fight.
Oh dear. So you owe me $1 million. Okay. All right. So one person's down $1 million. Let's see what happens next.
I'm going to stay out.
Okay. So next second, which market was this?
Madison.
Madison stayed out.
I'm going to stay out.
Staying out. Bridgeport stayed out.
Yes, I'll stay out.
Stayed out again.
Stay out.
Out. Which market are we up to now? Somewhere in Orange County, wasn't it? Where are we?
Orange, Connecticut.
Orange, Connecticut, and you're?
Stay out.
Stay out.
I think I'll stay in.
You're going to come in, okay. And which market is this?
St. Louis, Missouri.
St. Louis, Missouri. Oh, you owe me $1 million as well. Okay. A couple of people owe me $1 million. This is a good class. We're going to have plenty of money for lunch. All right.
I'm also going to fight.
You're also going to fight, and which market is that?
Sulphur, New York.
Whereabouts is it?
Sulphur, New York.
Sulphur, New York. Where are we at? 1, 2, 3, 4, 5, 6, 7, 8. Ali?
I'll fight.
You fight? Okay, so you owe me $1 million too. All right, that was 8. 9.
Out.
out, and 10
Stay out.
stays out, okay? Okay, now let's just notice something here. Which was the 10th market? What town were you?
Long Island.
Whereabouts in Long Island?
Huntington.
Huntington. So if Huntington, Long Island, our last market had come in, suppose you said in, what would Ali have said?
I would have not fought.
Would not fought. Aha. Okay, so what happened here? What happened here? Well, we analysed this last time as an individual market. We argued that each entrant should come in, just as our first entrant came in, and our monopolist should not fight. Right? That's what we have up on the board. That's what backward induction suggests. But in fact, Ali fought, a whole bunch of people came in, and a whole bunch of them stayed out. Is that right? A whole bunch of them stayed out. Now why? Why was Ali fighting these guys, and why were they staying out? Let's talk about why. What market were you again?
Madison, Wisconsin.
So why did Madison, Wisconsin stay out?
Well, we talked about last time how he has an incentive to fight now because there's more than just our analysis up there in terms of establishing that he'll fight to keep people out.
All right, so it looks like there might be some reason for fighting to keep you out. So why, let's just talk about a bit more. So let's go to the third guy. Which market are you again?
Bridgeport.
Bridgeport. So why did you stay out?
Because I knew he was going to fight.
You knew he was going to fight. Now how did you know he was going to fight?
Because he has an incentive to establish that, he established that he was going to fight for every single market, and so I was going to lose out.
All right, so we think we know that Ali is, he's this tough Italian pizzeria owner, and we think he's going to try and establish what? A reputation as being a tough pizzeria owner by fighting these guys, perhaps fighting a few guys early on, in order to keep these guys out. And in fact, he had to fight the first person, but he kept out 2, 3, 4, 5, 6, and this person came in, so 7 and 8 came in, but then 9 and 10 he kept out. So he kept a lot of people out of the market by fighting early on. And this argument sounds right? It seems to ring true, right? It's about establishing reputation. But now I want to show you that there's a worry with this argument. The worry is, this is a sequential game. Right? This is a sequential game, and like all sequential games of perfect information we've seen in the class, we should analyze this game how? Now that wasn't loud enough. How? Backward induction. So where's the back? Where's the back of this game? Way back here. All right, way back here. Sorry for the guys in the balcony. Way back here, we have the last market in town, which was the last market. All right, and if we look at this last market, we in fact saw that if the last market came in, Ali in fact gave in. Right? Ali gave in. Now why did Ali give in on the last market? Let's have a look back on the board. All right? So on the board, we can see what that last market looks like. With 10 markets, this is a very complicated game. This would be the first market, and then there's 3 versions of the second market, depending on what Ali did in the first market, and so there's 9 versions of the third. So the tree for this game is horrendous. But nevertheless, once we get to the end of the game, the 10th market, which was what, Bridgeport or something, I've forgotten where it was at now, so it was, wherever it was, once we get to that last market, this tree pretty well describes that last market. Is that correct? Right? There isn't another market afterwards, there's only 10 markets. So in this last market, what do we know Ali is going to do? In this last market, if the entrant enters, Ali is going to not fight, which is exactly what Ali did do. So Ali, is that right? So when in fact we discussed the 10th guy coming in, you chose to...
I would have chosen not to fight.
Would have chosen not to fight. And that's exactly what the model predicts. Right? He has no incentive to establish a reputation for the 11th market, because there isn't an 11th market. He's down at 10. Is that right? So we know that in the last market, the 10th market, Ali actually is not going to fight. Right? And therefore, the person who's the entrant in the 10th market should know that they can safely enter and Ali won't fight them. But now we're in trouble. Why are we in trouble? Well, let's go back to the 9th market, the second to last market. So I've forgotten where it was. Raise your hand, the second to last market. Okay. Second to last market is this guy? No, this guy. You're the 10th market. So this guy who's in the Hong Kong market, all right, he should know he's the second to last market. He knows that no matter what he does, the 10th market's going to enter, and Ali's going to give in to the 10th market. Ali's going to let the 10th entrant in. Is that right? So the 9th market actually knows that nothing Ali is going to do here is to establish a reputation to keep the 10th guy out. So therefore, in fact, he should what? He should come in, right? He should come in, and in fact, if he'd come in, Ali would have had to give in because there's no way that Ali can keep the 10th guy out. We've just argued the 10th guy is coming in by backward induction. So since we know that the 10th guy is coming in anyway, and in fact Ali is going to accede to them, there's no point Ali trying to scare off the 10th guy. So in fact, Ali is going to say no fight to the 9th guy. Right? I was going to say no fight to the 9th guy. But now we go to the 8th guy. We've just argued that the 10th guy is coming in anyway, and Ali's going to give in to him. We've argued the 9th guy is coming in, so Ali's going to give in to this guy as well because he can't put off the 10th guy. And therefore we know that once we get to the 8th guy, once again, he can safely come in because Ali knows by backward induction he can't keep the 9th and the 10th guy out anyway, and so this guy should come in as well. And if we do this argument all the way back, what do we get? What do we get? Yeah,
he lets everybody.
He lets everybody in. Everybody should come in, and he should let everybody in. So we have a problem here. We have a problem. Backward induction says, even with these 10 markets, Ali, in fact, should let everybody in. Everyone should know that, so they should come in. So there's a disconnect here. There's a disconnect between what the theory is telling us. Backward induction is telling us Ali can't keep people out by threatening to fight, by establishing a reputation, and what we actually just saw that what happened, which was Ali did fight and did keep people out, and we know that other monopolists do that as well. All right. So how can we make rigorous this idea of reputation? It's not captured by what we've done so far in the class. So how can we bring back what must be true in some sense, this intuition that by fighting, Ali could keep people out, and that therefore will keep people out. So to make that idea work, I want to introduce a new idea, and the new idea is that with very small probability, let's say 1% chance, Ali is crazy. All right, so stand up a second. All right, so he looks like a normal kind of guy, but there's just 1% chance that he's really bonkers. Right? If he was here today, I'd say there's 1% chance that he's actually Rahul. All right? All right. So now, let's redo the analysis. And what do I mean by bonkers? Bonkers, I mean, with 1%, Ali is the kind of guy who likes a fight. So with 1% chance, he's actually not got these payoffs at all. He's actually got some different payoffs, which are the payoffs to somebody who, okay, he'll lose money, but he so much enjoys a fight, you know, he gets plus 10 here. All right, that's the bonkers guy's payoff. But, you know, only 1% chance he's this bonkers guy. All right, so now what happens? Let's just walk it through. All right, with 1% chance, if there was only one market, not the 10 markets, if there's only one market, and this one market was, I've forgotten your name, was Isabella, who was in which market? I've forgotten. In Miami. Then she doesn't really much care about this 1% chance that Ali is actually Rahul. Right? It doesn't really bother her very much. Why? Because with 99% chance, Ali is going to give way, and that's good enough odds, right? With 99% chance, she was happy to come in. So if there's only one market here, we'd be done. But with 10 markets, things are a little different. Why? Let's see why. So suppose, in fact, that Isabella in Miami thinks that Ali and everybody else thinks Ali is a pretty sane guy with 99% probability he's a sane guy, and Isabella enters, and everyone sees this, and everyone's surprised, rather than doing the same thing, which is letting Isabella in and switching to a duopoly in Miami, with 1% chance. Sorry, what happens, in fact, after Isabella comes in, is that Ali fights, right? Fight, okay? So now, it's too late for Isabella, she's lost her money. But our second market is, what's your name again?
Scott.
Scott, which market were you?
Madison.
So Scott in Madison has observed what happened in Miami, and initially he thought that Ali was Ali. 99% probability Ali was this sane, nice, calm Italian guy, all right? But on the other hand, he just saw this sane, calm Italian guy fight, as he shouldn't have fought, couldn't have backward induction, fought the entrance in Miami. So now, I've got it again, Scott, was it? Scott thinks to himself, I'm not so sure that Ali is the same guy. Maybe I should update my beliefs in the direction of thinking that Ali might actually be the insane guy. So maybe we're up to maybe probability a third that Ali is actually insane. All right, so he thinks, okay, probably a third, that's still not very much. I'll still risk it. He comes in, and Ali fights him again. Right? So, probably a third he's sane, he's going to give in to me. He comes in, Ali fights him again. So now we're in the third market, which was which market?
Bridgeport.
Bridgeport. And Bridgeport's seen this horrible fight going on in Miami and this horrible fight going on in Madison. All right, and now he's getting pretty sure that this nice, calm-looking alley is not nice, calm-looking alley. He's crazy Rahul. All right, right? I mean, there's a lot of evidence he's crazy Rahul. He's fought the last 2 markets and making huge losses. It must be that Ali likes to fight. So what does he do? He says, I'm going to stay out of here. Right? You know, I'm convinced that this guy may be crazy, so I'll stay out. And all the subsequent markets, they think, oh, well, you know, he fought these first 2 markets. That means he must be a crazy guy, or at least there's high probability he's a crazy guy. So they all stay out, which is exactly what happened until we got to here. And even here, when they came in, Ali acted like crazy Rahul. All right? So what made that argument possible was what? What made that argument possible was the small possibility, the 1% possibility that Ali is bonkers. But you know, how well do you know Ali? There's a 1% chance he's bonkers, right? How many of you think you're really sure that he's a sane guy? Right? I mean, he supports Italian football teams. He's got to be pretty crazy, right? 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 So what happened here? The small possibility that Ali is crazy allowed him to build up a reputation that kept all these guys out. But actually the argument is stronger than that. Let's try and push this argument harder. Suppose, in fact, that Ali is not crazy. Suppose that Ali is the sane Ali, the nice, calm Ali we all know and love. All right? But we've just argued that if Ali acts as if he's the crazy guy, then you're going to be convinced that he is the crazy guy. So by acting crazy, he might be able to convince you that he is crazy and therefore keep you out. All right? So we argued before that if there's some chance that Ali is crazy, by acting crazy early on, he's going to deter these late entrants from entering the market because they think they're fighting Rahul and they don't want to fight Rahul. All right? But we said these early guys, they had probability 0.99 that he was sane and 0.6 that he was sane and maybe even 0.5 he was sane here, so they thought of coming in. But now we're arguing that even if Ali is sane, even if he's a sane guy, a rational guy, he should behave as if he's crazy in order to keep these late guys out. And these early players, knowing that even the sane version of Ali is going to fight them, should also stay out. And notice something's happened here. They're not staying out because they think Ali is crazy. They're staying out because they know that even the sane version of Ali is going to fight them in order to seem crazy. Is that right? Right, we'll see that's a strong argument. So now even these early guys are going to stay out of the market. All right? Now we're almost there. What we've argued, let's just make sure we get the 2 pieces of this on the board. We've argued that if there's an epsilon chance, a very small chance, let's call it a 1% chance, that Ali is crazy, then he can deter entry by fighting, i.e. seeming crazy. And we argue that what really makes this argument strong is once we realize that the sane person's going to act crazy, we really know that everyone's going to act crazy and therefore we should stay out. Now that argument can't quite be right. So that's enough of the argument I want you to have for the purpose of the exam, but let me just point out that that argument isn't quite correct. That can't quite be an equilibrium. Now why can't that be an equilibrium? We've just argued that even the sane version of Ali, this is a sort of slightly more subtle argument, so just pay attention a second. We've argued that even the sane version of Ali is going to act like a crazy guy. All right? All right? So everyone if anyone came in, he's going to act crazy anyway, so you're not going to update your belief as to whether he's crazy or sane, because we know that the crazy guy's going to fight because he likes fighting, and the sane guy's going to fight because he wants to seem like a crazy guy. So you're really learning nothing whether you observe him fighting or not. But now let's go back to our 10th market. Way back in our 10th market, our 10th market participant, whose name was Andy, hasn't learned anything about Ali. He hasn't learned anything because whether Ali was sane or crazy, he's going to fight. So observing what his actions early on, if that was really an equilibrium, our 10th guy wouldn't have updated his belief at all, and therefore would still believe with probability 0.99 that Ali was sane, in which case our 10th guy would enter. And once again, that argument would unravel from the back. So what I described before can't quite be an equilibrium. It can't be just as simple as all sane guys are going to act crazy, because then you wouldn't learn the thing. So it turns out that the equilibrium in this model is actually very subtle, and it involves mixed strategies. And mixed strategies are something we did in the first half of the semester, so I don't want to go back to it now. So trust me, you can solve this out with mixed strategies, and the basic idea I gave you is right. The basic idea is sane guys are occasionally going to act like crazy guys in order to establish a reputation, and that reputation helps them down the tree. All right? So this idea that even when there's a chain store, people will enter. Even when Ali has 10 monopolies, people will enter. This is a famous idea. It's called the chain store paradox. It's due to a guy called Selson who actually won the Nobel Prize. All right? This is the chain store paradox. And this idea of establishing reputation is a big idea. The idea is, once again, you might want to behave as if you're someone else in order to deter people's actions, in order to affect people's actions down the tree. All right? Okay. So what have we learned here? Let's just work it out. Thank you. All right. So the first thing we learned was kind of a nerdy point, but let me make it anyway. Introducing just a very, very small probability, just a tiny probability that Ali might be someone else. He might be a Rahul, he might be crazy, he must like fights. That very small probability radically changes the outcome of the game. If we were all 100% sure he was sane, we'd be tied by backward induction, and entry would follow. He wouldn't be able to keep anybody out. Right? But that small probability allows us to get a very different outcome. That's the first point I want to draw out of this. And the second point I want to get out of this is really this idea of reputation. There are lots of settings in society where reputation matters. And one of them is a reputation to fight. How many of you have friends who have somewhat short fuses? You know people who have short fuses, right? Right? And when you're going out on choosing some movie to go to with these guys who have short fuses, or trying to decide who's going to order something at a restaurant, or who's going to get to be which side, and you're playing some game on some video game, right? I claim, is this true, that the people who have slightly short fuses slightly more often get their way. Is that right? Right? If you have a sibling who has a short fuse, they slightly more often get their way. And that's exactly this idea. They're short fuse, the fact they tend to blow up and get angry at you, gives them a little bit of an advantage. And notice that maybe they don't have a short fuse at all. Maybe they're just pretending to have a short fuse because they know they're going to get their way over you softies more often. Right? None of you have short fuses. You're all sane people, right? All right? So this idea should be a familiar idea to you, but it's not just an idea in the sort of trivial world of bargaining. Right? Notice this idea of reputation occurs all over the place. So another place it occurs, somewhat grim place it occurs, is in the subject of hostage negotiations. All right? In the subject of hostage negotiations, when some other country has seized some hostages from the US, or maybe some criminal organization has seized some members of your family or some members of your community and is holding the hostages, there's a well-known idea, which is what? Which is that you should never negotiate with hostage takers. Is that right? Everyone's heard that idea? You should never negotiate with hostage takers. You should never give in just because they have hostages. Right? And why? Why? It's the same idea. Because you want to have a reputation for being somebody who doesn't give in to hostage takers in order to deter future potential hostage takers from taking hostages. Right? This has grim consequences, but sometimes it's worth bearing the cost of having your relatives come back in pieces in order to deter future relatives from being taken. All right? So that's a somewhat macabre version of this. Let me give you one other version. There are whole areas of the economy where reputation is crucial. Where if people played according to their backward induction sane incentives, we'd have a disaster. All right? But having a reputation here isn't necessarily a reputation as a tough guy. It could be a reputation for somebody who's a nice guy. It could be you want to have a reputation for being the sort of person who derives pleasure and utility from, quote, doing the right thing, from acting honestly. Right? So think about certain professions where the reputation of the person in the profession is crucial. Doctors, for example. Right? It's crucial for a doctor that he or she has the reputation of someone who tells the truth, otherwise you'd stop going to that doctor. Right? Accountants, accounting firms rely on having a reputation for being honest and not cheating the books. When they stop having that reputation for being honest, think of Arthur Andersen after the events in Enron, they pretty quickly ceased to be in business. Right? I gave that example a couple of years ago. It was very embarrassing because it turned out Arthur Andersen was in the class. Literally, Arthur Andersen III was in the class. These things happen at Yale. All right? But nevertheless, all right? Right? Arthur Andersen relied on his reputation, the firm relied on its reputation as an honest firm. And it was worth behaving honestly to maintain that reputation for future business. All right? So that's, I mean, reputation is a huge topic, and my guess is that the next time there's a Nobel Prize in game theory, it'll be for this idea. All right? So that's my prediction there. Now, having said that, I want to spend the whole of the rest of today playing one game and analyzing one game. All right? So we're going to play this game, and for this game, I need a couple of volunteers. So I'm going to pull out some volunteers. Well, anyone want to volunteer? I need 2 volunteers for this game. How about my guy from the football? Was that a raised hand? It wasn't a raised hand. How about my guy from the football team? Is it football team? Baseball team. Well, that may be unfair in this particular game. This particular game, that may be unfair. Maybe I'll take someone who isn't in the baseball team. Okay, anyone who's in the football team? These guys in the football. Okay, great. Okay, so you 2 guys, right? I need you at the front. And your names are?
Chevy.
Patrick.
Chevy and Patrick. So Chevy and Patrick are going to be our volunteers. Now the idea of this game is, you guys provided the volunteers. Wait down here a second. You guys provided the volunteers. This game involves 2 volunteers who you just provided, and 2 wet sponges. I will provide the wet sponges. So I have here a couple of sponges, and in a minute I'm going to wet them. And I'll tell you what the rules are in a second. Okay, so I'm going to give one of these sponges each to Chevy and Patrick. All right, I'm then going to position Chevy and Patrick at either end of this central aisle, of this aisle here. All right, and the game is going to be as follows. It's important that everyone listens to the rules here, because I'm going to pick 2 more volunteers in a moment. All right, so the game they're going to play is as follows. Each of them has 1 sponge. It's crucial they only have 1 sponge. And they're going to take turns. And when it's your turn, as long as you still have your sponge in your hand, you face a choice. You can either throw your sponge at your opponent, all right? And if you hit your opponent, you win the game. Or you have to take a step forward. All right? So either you throw the sponge, or you take a step forward. All right? Now there's a crucial rule here. Each player only has 1 sponge, and once they've thrown that sponge, they do not get the sponge back. Everyone understand that? Once you've thrown the sponge, you do not get the sponge back. So once again, if you throw your sponge at your opponent and you hit your opponent, then you've won the game. But if you throw your sponge at your opponent and you miss, the game continues. All right? Right? So let's make sure we understand that. If you throw your sponge and miss, the game continues. You still have to step forward. So what's your opponent going to do at that point? What's your opponent going to do? Let's make sure that our football players understand this. All right? All right? So, no, that wasn't meant that way. They could have been soccer players. Come on. So, all right?
I didn't appreciate that very much.
Sorry, I'm sorry. I didn't mean it that way. So, if your opponent, whose name is Patrick, throws and misses, what are you going to do?
I will walk forward until I slam the sponge.
There you see. Okay, great. You walk forward until you politely put it on his head. Okay, everyone understand that if in fact you throw and miss, you've lost the game because the other guy can wait until he's standing right on top of you and just place the sponge gently on his head. All right. All right. Now, for fairness' sake, it's important that these sponges are equally weighted. And I'm going to weight them. I'm going to put water in them now. And since this is nothing but the best for Yale students, I'm going to provide Yale University spring water. Who knew that Yale University had a spring? It's kind of a flavor. If it makes you feel better, you can think of this as American beer. All right. Sorry. All right. So let's. And I'm not going to make these too heavy, partly because it makes it too easy, and partly because I don't want to get sued. All right, so I'm going to squeeze these out somewhere, away from the wires. All right. And we're going to get our judge here to weigh them. I need a mic here. So let me get a mic. So, okay, so I want you to hold those sponges in your hand and tell me if they're equally weighted.
Yeah, pretty equal.
Pretty equal, okay, they're pretty equal, everyone agrees? All right, so how this is going to work, I'm going to give the blue sponge to Chevy, was it? And the green sponge to Patrick. And Chevy's going to stand here, and Patrick's going to stand as far back as I can get him on camera, which I'm going to be told how far back I can go. Don't go too far. Okay, come back, Patrick. Too ambitious. Too ambitious. Come back. Keep up. Keep coming. Stop. No, keep going. Yeah. Okay, we're going to start here. Start quite close, actually. All right. Everyone understand how we're going to play this, all right? So Chevy is player 1, Patrick is player 2. Chevy has to decide whether to throw or to step. Oh, step. Okay, let's just hold the game a second. All right, now it's Patrick's turn. Does anyone have any advice for Patrick at this point? Who thinks? Okay, wait. If you think throw, raise your hand. If you think step, raise your hand. There's a lot more steps than throw. I thought the Yale football team was good this year. Okay. All right. Step, your choice, step or throw. All right. Oh, I should announce 2 other rules. It's kind of important. I should have said this. First, a step has to be a proper step, like a yard long. And second, I think this will work in America, gentlemen never duck. All right? No dodging the sponge, okay? All right. Chevy, your turn. Let me put the mic on you, right?
I don't really trust my arm. I'm going to step.
All right, so you're stepping again. Let me go to Patrick, all right? I feel like I'm in the line of fire here. Patrick, what are you going to do?
I'm going to throw.
Patrick's going to throw. I'm really going to get out of the way then. All right? We'll see this in slow motion. Oh! Continue. All right. So you have to take a step forward. So Chevy's going to take a step forward, I assume. And Patrick's going to take a step forward. And Chevy's going to take a step forward. And Patrick's going to take a step forward. And all right. All right. Good. So a round of applause for our players. Thank you. What happened to my... There we are. So I think we have time to do this once more, and then we're going to analyze it. So I want to get 2 women involved. This is too sexist otherwise. So can we have 2 women in the class, please? 2 volunteers, come on. You can volunteer on the... there's a volunteer. Thank you. Great. And great. Okay, great. Thank you. So your name is? Jessica. And your name is... Let me get the mic over to you. Clara Elise and Jessica. All right, we'll start at the same positions. We'll use the same sponges. And I need to remind you what that position was. So just give me a thumbs up when I'm in the right position. All right, good. All right, same rules. Clara Elise and Jessica. We'll let Jessica be player 1. So Jessica, you can step or throw. What do you want to do? Gonna step, okay? You know what might be a good idea? Ali, why don't you put the mic on Clara Elise so you have the mic at either end and just run to and fro. That's good. All right, so Clara Elise, what are you going to do?
I'm going to step.
You're going to step? And Jessica, what are you going to do?
I'm going to step.
You're going to step? Ali and I are in danger here, but never mind.
I'm going to step.
Any votes now? Do people think that Jessica should throw? If you think she should throw, raise your hand. There's a large majority for step, so up to you. What are you going to do?
I'm going to step.
Going to step, okay. Clara Elise, any decisions?
I mean, this is pretty light. I don't think it's.
It's a pretty light sponge. It's pretty hard to throw this sponge. We've seen that. Okay. Stepping again.
There's some baby steps. I'm gonna throw.
You're gonna throw. Okay. Here we go. Okay, out the way. Oh, okay. Continue, please. Clara Elise's turn. Your step. Jessica has to step. Clara Elise has to step.
I'll throw.
All right, good. All right, so we've seen how the game works. Everyone understands how the game works. I want to spend the rest of today analyzing this game. All right, and before I do so, we should just talk about what this game is. Let me get some new boards down here. All right, so one quick announcement. I'm going to analyze this, and we're going to spend the rest of today analyzing this, but this is going to be quite hard, so I'm going to provide you a handout that I'll put on the web probably tomorrow that goes over this argument. So you don't have to take detailed notes now. You pay attention and see if we can follow the argument. Okay, so this game is called Duel. not surprisingly. And you may wonder, what are we doing? Some of my colleagues are here. What are we doing having a duel in class? And of course, one answer to that is it's kind of fun watching the future leaders of America throw wet sponges at each other. That's very reason in itself. But there are other reasons. Duels are real games. So those of you who are well-versed in Russian literature, will have seen duels before, right? Or at least read of duels. There are some famous duels in Russian literature. Anyone want to tell me some famous duels in Russian literature? Any Russian majors here? No? Nobody want to give me a shot at this? Really? Nobody? This is Yale. Come on. Well, how about in War and Peace? Okay, there's a duel like this in War and Peace. All right, and in War and Peace, I think and without giving away the ending, actually it's in the middle of the book and it's 800 pages long, so it isn't exactly the ending, right? But in War and Peace, I think we're led to believe that the hero, the protagonist, Pierre, shoots his gun. It's a gun. In War and Peace, it's a gun and not a sponge. That's a surprise. He shoots his gun too early, we're led to believe. All right? There's a famous one in Onegin, right? In Pushkin's Eugene Onegin. And there are lots of others, actually. So there's lots in literature. All right? There are also settings which aren't exactly out of literature. So one example would be in a bike race. How many of you ever watched the Tour de France? Anyone know what I mean by the Tour de France? Yeah, you don't watch it. So this is a bike race that goes around France. It takes stages. And in the Tour de France, there's a key decision. There's a game within the game. And the game within the game, I'm looking at Jake, who's a real cyclist here, but the game within the game is when do you try to break away from the pack, which is called the peloton. Right? And if you break away too early from the peloton, it turns out that you're going to get reeled in. It turns out that over the long haul, the peloton can go much faster than you. So if you break too early, they're going to catch you up. On the other hand, if you break too late, then you're going to lose because there are going to be some people in the peloton who are just excellent sprinters. So if you break too late, the sprinters are going to win the race. All right? So you have to decide when to break from the peloton. Right? This is the second most important game within a game in the Tour de France. The most important game within a game is where to hide your steroids. All right? All right. So let me give you one other example. So imagine, I'm going to give you a more economic example. It's meant to be an economics class. Imagine there's two firms, and these two firms are both engaged in R&D, research and development, and they're trying to develop a new product, and they're going to launch this new product onto the market. All right? But then the nature of this market is, maybe it's a network good, the nature of this market is there's only going to be one successful good out there. Right? Essentially, there's going to be one standard, let's say, of a software or a technological standard, and only one of them is going to survive. The problem is, you haven't perfected your product yet. If you launch your product too early, it may not work, and then consumers are never going to trust you again. But if you launch it too late, the other side will have launched already, they will have got a toehold in the market, and you're toast. All right? So that game about product launch is like Duel, except you're launching a product rather than launching a sponge. Is that right? All right? Now, all of these games have a common feature, and it's a new feature for us. It's about the nature of the strategic decision. In most of the games we've looked at in the course so far, the strategic decision has been of the form, where should I locate? How much should I do? What price should I set? Should I stand for election or not? Right? Here, the question of the strategic decision is not of the form, what should I do? It's of the form what? When? It's of the form, when am I going to launch the sponge? We know perfectly well what you're going to do. You're going to throw the sponge. The strategic issue in question is when. All right? So the issue here is when. All right. So to analyze this, I'm going to need a little bit of notation, and let me put that notation up now. All right? So in particular, I want to use the notation Pi of D to be what? Let Pi of D be player I's probability of hitting if I shoot at distance D. All right, so Pi of D is the probability that I will hit if he or she shoots at distance D. All right? Okay, right, everyone happy with that? This is the only notation I'm going to use today. All right? And I'm going to make some assumptions about the nature of this probability, but they're not, two of the assumptions are pretty innocent. So let's draw a picture. All right, so the picture's going to look like this. Here's a graph, and on the horizontal axis, I'm going to put D. This is the distance apart of the two players. And on the vertical axis, I'm going to put P, which is the probability, or PR, the probability. All right? So here they're at distance 0, and I'm going to make an assumption about what the probability of hitting is if you're at distance 0. What's the sensible assumption? What's the probability of hitting somebody with your sponge if you're 0 distance away? 1. Okay, I agree. So 1. All right, so the first assumption I'm going to make is if they're right on top of each other, they're going to hit with probability 1. And the second assumption I'm going to make is as you get further away, this probability decreases. Right? It doesn't have to look exactly like this, but something like that. All right? And that also, I think, is that an okay assumption? Right? As you're further away, there's a lower probability of hitting. Now, I'm not going to assume that these two players have equal abilities. For example, I don't know, I didn't ask them, but one of our two football players might be a quarterback and the other one might be a linebacker or a running back, and I'm assuming the quarterback is probably more accurate. Is that right? So I'm not going to assume that they're equally good. So it could be that their abilities look like this. This could be P1 of D, and this could be P2 of D. Everyone okay with that? All right. So shout this out. In this picture, who is the better shot and who is the less good shot? Who's the better shot? 1, right? 1 is the better shot because at every distance, if player 1 were to throw, player 1's probability of hitting is higher than player 2's probability of hitting, as drawn. All right? Now, I don't even need to assume this. It could well be that these probabilities cross. Right? It could be that these curves cross. It could be that player 1 is better at close distances, but player 2 is better at far distances. That's fine. We'll assume it's like this today, but I'm not going to use that. Okay? I could do away with that. All right? As drawn, player 1 is the better shot. Now, I'm going to make one assumption that matters, and it's really a critical assumption. All right? I'm going to make this assumption that keeps the math simple for today, but we have enough math to do anyway. I'm going to assume that these abilities are known. I'm going to assume that not only do you know your own ability of hitting your opponent at any distance, I'm going to assume you also know the ability of your opponent to hit you. All right? All right. Now let's look at this a second. We've got a bit of notation on the board. Let's discuss this a second. What do we think is going to happen here? In this particular example, we have a good shot and a less good shot. Who do we think is going to shoot first? Who do we think is going to shoot first? Let's try and cold call some people. All right. So, you sir, what's your name?
Frank.
Frank. So who do you think is going to shoot first? The better shot or the worse shot?
The better shot, but it also depends on who steps first as well, I think.
Well, let's assume player 1 is going to step first.
Then player 1.
So Frank thinks player 1 is going to shoot first because player 1 is the better shot. Who thinks? Let's see. So what's your name?
Nick.
Nick. Who do you think is going to shoot first?
I think player 2 will shoot first.
All right. So let's talk why. Why do you think player 1 is going to shoot first? Well, let's do a poll. How many people think the better shot's going to shoot first? How many people think the worse shot's going to shoot first? How many of you are being chickens and abstaining? Quite a few, right? Right? Okay. All right. So why do we think the better shot might shoot first?
Well, because at equal distance, he has a better shot of...
Because he has a better chance of hitting, all right? He has a better chance of hitting. But why do you think that the less good shot might shoot first?
He knows that if P1 gets too close, he's gonna win anyway. So he might as well take a shot with a lower chance, before P1 is guaranteed to hit him.
Okay. So we have two arguments here. The first argument is maybe the better shot will shoot first because after all he has a higher chance of hitting. And the other argument says maybe the worse shot will shoot first. To what? To preempt the better shot from shooting him. All right. But now we get more complicated. Because after all, if you're the better shot, and you know that the worst shot may be going to try and shoot first to try and preempt you from shooting him, you might be tempted to shoot before the worst shot shoots to preempt the worst shot from preempting you from shooting him. And if you're the worst shot, maybe you're going to try and shoot first even earlier to preempt the better shot from preempting the worse shot, from preempting the better shot from shooting the worse shot, and so on. All right? So it's clear, what's clear is that this game has a lot to do with preemption. Preemption's a big idea here. But I claim it's not at all obvious. It's not at all obvious who's going to shoot first, the better shot or the worse shot. Is that right? So those people who abstained, raise your hands again. Those people who abstained before. Seems like it's a pretty sensible time to abstain. It's not obvious at all to me who's going to shoot first here. All right? Are people convinced that at least it's a hard problem? Yeah? Yes or no? People convinced? Yeah, okay, good. It's a hard problem. Okay, good. So what I want to do is, as a class, as a group, what I want us to do is solve this game. And I want to solve not just who is going to shoot first, I want to figure out exactly when they're going to shoot. All right? So we're going to do this in the next half hour. And we're going to do it as a class. Right? So you're going to do it. So we're going to nail this problem, basically. All right? And we're going to do it using two kinds of arguments. One kind of argument is an argument we learned the very first day of the class. And that's a dominance argument. And the second kind of argument is an argument we've been using a little bit recently. And what kind of argument is that? What is it? Backward induction. So we're going to use dominance arguments and backward induction, and we're going to figure out not just whether the better shot or the worse shot's going to shoot, but exactly who's going to shoot when. All right. Let's keep our picture handy. Get rid of... Well, I can get this down, I guess. And we'll... Can we still see the picture? Yeah. All right, let's proceed with this argument. All right, so to do this argument, I first of all want to establish a couple of facts. All right, my page and my notes. I want to establish two facts. And we'll call the first fact, fact A. All right. Let's go back to our two players we had before. In fact, maybe it would be helpful to have our Can I use our first two players as props? Can I have you guys on stage? While they're coming up. All right. Sorry, guys. I'm exploiting you a bit today. All right. Hope you both signed your legal release forms. All right. All right. Why don't you guys sit here a second so I can use you as props. So imagine that these two guys still have their sponges. All right. Let's actually set this up. So suppose that Shebby has a sponge and Patrick still has his sponge. All right. And suppose it's Shebby's turn. All right. And suppose that Shebby is trying to decide whether he should throw his sponge or not. Whether he should throw his sponge or not. Can I have that other mic? Here we go. Let me give you a mic each so you have them for future reference. All right. So Shebby is trying to decide whether to throw his sponge or not. And suppose that Shebby knows that Patrick is not going to shoot next turn when it's his turn. So Shebby's trying to decide whether to shoot, and he knows that Patrick is not going to shoot next turn when it's his turn. What should Shebby do? Shebby, what should you do?
Take a step.
Take a step. So he says take a step. That's right. Why should he take a step? What's the argument why he should take a step? Well, let's find out. What's the argument?
Because I'll just be one step closer and I'll have another chance to decide.
Shout it out so you can be heard. Yes, that's right. That's right. Shout out so you can be heard.
I'll be one step closer and I'll be able to make the same choice next time anyway.
Good. Hold the mic up to you. You're a rock star now, okay? All right, good. All right? All right. He's correctly saying he should wait. Why should he wait? Because he's going to be closer next time. So the first fact is, assuming no one has thrown yet, if player I knows at, say, distance D, that J will not shoot, let me call it tomorrow, and tomorrow he'll be closer, he'll be at distance D minus 1, then Shebby correctly says, I should not shoot today. And again, recall the argument. The argument is you'll get a better shot, a closer shot, the day after tomorrow. All right? All right? Now let's turn things around. Suppose conversely, once again, we're picking on Shebby a second, so Shebby has his sponge, no one has thrown yet, and suppose Shebby knows that Patrick is going to throw tomorrow. Right? Suppose he knows that Patrick is going to throw tomorrow. Now what should Shebby do? Now that's a harder decision. What should Shebby do? All right, he knows Patrick's going to shoot tomorrow. What should he do? Should he shoot or what? What's the answer this time? What do you reckon?
It depends.
It depends. I think that's the right answer. Right? It depends. Good. So the question is, someone else. I don't want to pick entirely on these guys. So what does it depend on? Right? It's right that it depends. What does it depend on? Yeah.
If the other guy's chance is greater than or less than 50% of getting you.
All right. So it might depend on the other chances being greater than less than 50%. It certainly depends on the other guy's ability and on my ability. Everyone clear on that? But everyone agree that whether I should shoot now, if I know the other guy is going to shoot tomorrow, depends on our abilities. But how exactly does it depend on our abilities? Yeah, go ahead.
It depends on if...
Shout out.
It depends on if your probability to hit is greater than his probability to miss.
Good. Good. Your name is?
Osman.
Osman. So Osman is saying, let's be careful here, it depends on whether my probability of hitting, if I throw now, is bigger than his probability of missing tomorrow. Now, why is that the right comparison? That's the right comparison because if I throw now, my probability of winning the game is the probability that I hit my opponent. And if I wait and take a step, then my probability of winning the game is the probability that he misses me tomorrow. Right? So I have to compare winning probabilities with winning probabilities. I have to compare apples with apples, not apples with oranges. Everyone see that? Okay, so let's put that up. Right, so the same assumption, assuming no one has thrown, if I know at D that J will shoot tomorrow at D minus 1, then I should shoot if, need a gap here, if I's probability of hitting at D, and let me leave a gap here, is bigger than, let's make it bigger than or equal to, doesn't really matter about the equal case, is greater than or equal to J's probability of missing tomorrow. Right? Because this is the probability that you'll win if you throw, and this is the probability that you'll win if you wait. Okay? So let's put in what those things are. So the probability that I will hit at distance D, that's not that hard, that's PID. Everyone happy with that? What's the probability that J will miss tomorrow if J throws? What's the probability that J will miss? Somebody? Shout it out? Yep. Right, 1, let's be careful. So it's 1 minus PJ, but what distance will they be at? D minus 1. So it's 1 minus PJ, D minus 1. All right? All right, so this is the key rule. If Shebby knows that Patrick's going to shoot tomorrow, then Shebby should shoot if his probability of hitting, PID, is bigger than Patrick's probability of missing, 1 minus P Patrick, D minus 1. All right? Now I want to do one piece of math. This is the only math in this proof. All right? So everyone who's math phobic, which I know there's a lot of you, can you just hold on to your seats? Don't panic. There's a little bit of math coming, okay? This is the math. I want to add PJ D minus 1 to both sides of this inequality. All right, that's it, okay? All right, so what's that tell me? If I add PJ D minus 1 to this side, I get plus pj d minus 1. Everyone happy with that? And on the other side, if I add pj d minus 1, I get just 1. Everyone happy with that? All right. So here's our rule. Our rule is, let's flip it around. If Patrick hasn't thrown yet and thinks that Seb is going to shoot tomorrow, then Patrick should shoot now if his probability of hitting now plus Chevy's probability of hitting tomorrow is bigger than 1. Right, let's call this star. Let's call this star. And let's put this stuff up somewhere where we can use it for future reference. All right. Sorry, guys, I'll use it again in a minute. I know you're feeling self-conscious up there. Believe me, I'm self-conscious up here too. All right. Okay, so let's look at that star inequality up there. Now, way out here, is that star inequality met or not met? It's not met. It's not met, right? Because way out here, these two probabilities are small, so the sum is less than 1. And in here, is the star inequality met or not met? Let me pick on you guys. So Patrick, is it met or not met in here? Shout into your microphone.
It's met.
It's met. Thank you. Okay. All right. So in here, the inequality is met. The sum is bigger than 1, and out here it's less than 1. If we put in all the steps here they are getting closer and closer together. Here's the steps. They get closer and closer together. Right. We put these steps in. There's going to be some step where, for the first time, the star inequality is met. So notice that they start out here, they get closer and closer. It's not met, 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 and suddenly it's going to be met. Maybe around here. Let's just try and pick it out. Maybe it's here. Right, so this might be the first time that this star inequality is met. Let's call it d star. Right, everyone understand what d star is? At every one of these steps to the right of d star, when we take the sum of the probability id plus pj d minus 1, we get something less than 1. But to the left of d star, or closer in than d star, the game is proceeding this way, it's proceeding right to left here, they're getting closer and closer. To the left of d star, the sum of those probabilities is bigger than 1. Right, so again, d star is the first step at which the sum of those two probabilities exceeds 1. Right? Everyone okay about what d star is? Anyone want to ask me a question? Okay? People should feel free to ask questions on this. I want to make sure everyone's following. Is everyone following so far? Yeah? I need to see all your eyes so you don't look like you're stuck in the headlamps like you were on Monday. All right, we're better off than we were on Monday. Good, okay. Okay, so here's our picture. And I actually want a bit more space. I'm not going to have much more space. All right. All right, so now I'm going to tell you the solution. The solution to this game is this. I claim that the first shot should occur at d star. Right, so that's my claim. The first shot should occur at d star. No one should shoot until you get to d star, and whoever's turn it is, whether it's Chevy's turn or Patrick's turn at d star, that person should shoot. That's my claim, and that's what we're going to prove. Okay, everyone understand the claim? It says, nobody shoots, nobody shoots, nobody shoots, nobody shoots, nobody shoots, nobody shoots, shoot. Okay? Okay? All right, let's prove it. Everyone ready to prove it? Yeah? People to be awake. If your neighbor's not awake, nudge them hard. All right, good. All right, let's start this analysis way out here. Well, let's start way out here, miles apart. All right, these guys are miles apart. Now I want to use them as props. So I've got these guys. Let's put them, stay where you are, Patrick, but stand up, and stay over here somewhere, but just where that black line is. All right, so maybe they're even further than this. They're really far apart. All right, and here they are miles away, and let's say it's Chevy's turn. It's Chevy's turn. He's way out here. That's the first step of the game. Imagine it's even further, because it was even further. All right? And let's think through what should be going on in Chevy's head. Right? There are two possible things going on. He's going to think about what Patrick's going to do. So this is Chevy's turn. Here he is. Right? And he should think, tomorrow it's going to be Patrick's turn. All right? And there's two possibilities. One possibility is that Patrick is not going to shoot tomorrow. All right? And if we think that Patrick is not going to shoot tomorrow, which fact should Shebby use? Should he use fact A or fact B? So which fact should he use?
Fact A.
Fact A, okay, so using fact A, he should not shoot. All right? Alternatively, he could think that Patrick's going to shoot tomorrow. Is that right? He could think Patrick's going to shoot tomorrow. If he thinks Patrick's going to shoot tomorrow, which fact should he use?
B.
B. He should use fact B, in which case he has to look at this inequality up here. Look at this inequality and say, I'll shoot if my probability of hitting now plus his probability of hitting tomorrow is bigger than 1. Well, let's have a look. This is Patrick's probability of hitting today, and this is Shebby's probability of this is Shebby's probability of hitting today, and this is Patrick's probability of hitting tomorrow. And is the sum of them bigger than 1 or not? Is it bigger than 1 or not? It's not bigger than 1. So what should Shebby do? He should step, right? He should step. All right? So he'd step. All right? He'd step. All right? Now it's Patrick's turn. All right? And once again, imagine this distance is still pretty large, and there's two things Patrick could think. Patrick could think that Shebby's that Shebby's not going to shoot tomorrow. Right? So here's Patrick. He's looking forward to Shebby tomorrow, and he could think that Shebby's not going to shoot tomorrow. If he thinks Shebby's not going to shoot tomorrow, which fact should he use?
A.
Should use fact A, okay? And if he's using fact A, he should not shoot. Right? Alternatively, he could think that Shebby is going to shoot tomorrow, in which case he uses fact
B.
B. All right? And what does he do? He adds up his probability, Patrick's probability of hitting today, plus Shebby's probability of hitting tomorrow. He asks, is that sum bigger than 1? And he concludes no. So we have no shot here and no shot here. And notice that both of those arguments were dominance arguments. In each case, whether Shebby thought that Patrick was going to shoot tomorrow or not, in either case, he concluded he should not shoot today. Right? And when it was Patrick's turn, whether Patrick thought that Shebby was going to shoot tomorrow or not, in either case, he concluded he should not shoot today. So he takes a step forward. All right? And this argument continues. It'll be Shebby's turn next, and once again, he'll look at these two possibilities. If he thinks Patrick's not shooting tomorrow, he wants to step. If he thinks Patrick is going to shoot tomorrow, he's again going to want to step the way it's drawn. And once again, we'll conclude step. All right? And we'll go on doing this argument, and everyone sees that in each case, this dominance argument will apply. It won't matter whether I think you should shoot tomorrow or not. In either case, it'll turn out that I should step forward, whether fact A applies or whether fact B applies. All right? So we'll go on going forward, and we'll have no shot, no shot, no shot, no shot, no shot, and we'll arrive at D star. Okay, 2, 1, 2, 1, 2, 2, 1, 2, 1, 2, 1. All right, so it turns out that D star is going to be Shebby's turn again. All right, and at D star, we try exactly the same reasoning. At D star, he says, if I think Patrick is not going to shoot tomorrow, what should I do? What should I do if I think Patrick's not going to shoot tomorrow?
Not shoot.
Not shoot. But now something different occurs. Now he says, if I think Patrick is going to shoot tomorrow, then when I look at my inequality up there, my star inequality, and add up my probability of hitting today, which is this line here, plus Patrick's probability of hitting tomorrow, which is this line here, suddenly he finds it is bigger than 1. Right? He finds it is bigger than 1. So now, if Shebby thinks that Patrick is going to shoot tomorrow, what should Shebby do?
I should shoot.
He should shoot. All right? So up until this point, a dominance argument has told us no one should shoot. But suddenly, we have a dilemma. The dilemma is, if Shebby thinks Patrick's not shooting, he should step. And if Shebby thinks Patrick is shooting, he should shoot. Everyone with me so far? So what have we shown so far? We've shown that no one should shoot until D star, but we're stuck because we don't know what to do at D star, because we don't know what Shebby should believe at D star. We don't know whether Shebby should believe that Patrick's going to shoot, or whether Shebby should believe that Patrick's not going to shoot. So how do we figure out what Shebby should believe Patrick's going to do? What? Wait. Wake up the guy in orange there. Right? The guy with the ginger hair, that's right. What's the answer to that question? Good. The answer is backward induction, right? Good. Round of applause for remembering the answer. All right, good. Good. Backward induction is the answer to all questions, especially when you're asleep, right? Okay. So now we're going to use backward induction. But where does backward induction start here? Backward induction starts at the back of the game. And what's the back of the game here? The back of the game is where? It's when these two guys, neither of them have thrown their sponge, and they've reached here. All right, so come in a second. Step. All right, and let's assume it's Patrick's turn, and they're absurdly close. They're uncomfortably close. All right, if they had longer noses, they'd be touching, right? They're at distance 0. They're at distance 0. And at distance 0, at d equals 0, let's suppose it's Patrick's turn, right? At d equals 0, no one is shot, it's Patrick's turn, he's got the sponge. What should Patrick do? Shout it out, Patrick.
Shoot.
You should shoot. Patrick should shoot, right? At d equals 0, say it's 2's turn. And the answer is he should shoot because the probability of hitting at distance 0 is 1. Is 1. All right? Let's just move you to the side of it so people can see the board. So I know it's an awkward dance, but here you are, right? Stop there. That's good. Okay. So at distance 0, they should certainly shoot. All right? So now let's go back a step in the backward induction. So at distance 1, so let's take a step back. All right, so take a step back. It's Cheby's turn at distance 1. So it's Cheby's turn. And what does Cheby know? What does Cheby know at distance 1? Cheby, what do you know? Shout it out.
That Patrick will shoot next turn.
Right, so now Cheby knows that Patrick's going to shoot tomorrow. So which fact should Cheby use in deciding whether he should shoot today?
B.
You should use fact B, and that tells us, right, so 1 knows that 2 will shoot tomorrow, so by B, 1 should shoot if his probability of hitting at distance 1 plus Patrick's probability of hitting at distance 0, if that is bigger than 1. Well, is it bigger than 1? All right, let's have a look. We had a shot in here already. We put a shot in here, and we're looking at distance 1. All right, and so we're looking at this distance here plus this distance here. And is it bigger than 1? Yeah, it's bigger than 1. Here's a bit more math. I lied to you before. 1 plus something is bigger than 1, okay? All right, so this is bigger than 1, so shoot. Let's put it on our chart as shoot. All right, let's go back a step. Sorry, I'll have to have Cheby go, all going backwards. Right, now we're at distance what? We're at distance 2. We're at d equals 2. And it's Patrick's turn. 2's turn. And what does Patrick know? Shout it out, Patrick.
I know that Cheby's going to shoot next turn.
Right, Patrick knows that Cheby's going to shoot next turn, so Patrick therefore should use which fact?
Fact B.
Fact B. And fact B tells him that he should, let's put this in, so 2 knows that 1 will shoot tomorrow, so by B, it's all the same thing, we know that 2 should shoot if P2 of 2 plus P1 of 1 is bigger than 1. So if we look at it on the board, here we are, it's 2's turn. He's looking at this distance plus this distance. And is it bigger than 1? It is bigger than 1, so he should shoot. And we can go on doing this argument backwards. We'll find that Cheby should shoot here, because this plus this is bigger than 1. And we'll know that here, Patrick, once again, will know that Cheby's going to shoot tomorrow, so he should use fact B. So he should shoot, provided this plus this is bigger than 1, but it is. And now we're back at D star, and the question we had at D star, the question we'd left hanging at D star was what? At D star, we knew already that Cheby would not shoot if he thought Patrick was not going to shoot tomorrow, but he should shoot if he thinks Patrick is going to shoot tomorrow. But what does Cheby know at D star?
I know Patrick's going to shoot.
He knows Patrick's going to shoot, so he should shoot. Is that right? He knows Patrick's going to shoot by backward induction, so he should shoot. So we just solved it. What do we actually show?
we showed, have seats, gentlemen, sorry to keep you up here, right? We know that prior to D star, no one will shoot, not shoot. And we know that at D star, and in fact at any point further on, we should shoot. That's horrible writing, but it says shoot. All right? So we've shown more than we claimed. We claimed that the first shot should occur at D star, but we've actually shown more than that. We've shown that even if you went beyond D star, and if somebody had forgotten to shoot at D star, at least you should shoot now. And give me like 2 more minutes, or 3 more minutes to finish this up, because we're at a high point now, okay? All right, everyone okay to wait a couple of minutes? Okay. So what do we prove here? We proved that the first shot occurs at D star, whoever's turn it is at D star, whoever's turn it is at D star. It wasn't that the best guy, the better shot should shoot first, or the worst shot should shoot first. It turned out that given their abilities, there was a critical distance at which they should shoot. Right? If you go back to the 18th century military strategy, you should shoot when you see the whites of their eyes, which is at D star. All right? All right? But we learned something else on the way. I claim we learned that if you're patient and you go through things carefully, that the arguments we've learned in the course so far, dominance arguments and backward induction arguments, can solve out a really quite hard problem. This is hard. Right? It would have been useful for the guy in War and Peace or in Yegin or the guys cycling in the Tour de France or you guys who are sponges to know this, and we can solve this exactly using backward induction. And everyone in the room can do it. Let me just push the argument a tiny bit further. One thing we've always asked in this class is, okay, that's fine if everyone knows what's going on in the game. Here we have our smart Yale football players, and they know how to play this game, so they're going to shoot at the right time. But what happens if instead of playing another smart Yale football player, they're playing some uneducated, probably simple-minded football player from, say, Harvard? All right? Now that changes things a bit, doesn't it? Because we know that the Yale football player is sophisticated, has taken my class, and knows that he should shoot at D star. But the Harvard guy doesn't know anything anymore, right? So they're stuck. So if you're the Yale guy playing the Harvard guy, how does that change your decision? Should you shoot earlier than D star when you're playing against the Harvard guy, or later than D star when you're playing against the Harvard guy? Let's try our Yale guys and see what they think. What do you think, shall we? Microphone up?
Definitely not earlier.
Definitely not earlier. That's the key thing, right? Now, why? Why definitely not earlier?
Because if you miss, the other person has a probability of 1.
All right.
You have a higher chance of missing.
All right. So I claim it's definitely, Sheb is right. It's good because I'm just claiming the Yale football players are sophisticated. Sheb is right that even if you're playing against a Harvard guy, you shouldn't shoot before D star because it was a dominant strategy not to shoot before D star. Right? It doesn't matter whether you think the Harvard guy is going to be dumb enough to shoot early or not. If he is dumb enough to shoot early, so much the better. You should wait till D star. Notice, that argument doesn't depend on you playing against somebody who's sophisticated, or someone who's less sophisticated, like a Harvard football player, or somebody who's basically, a chair, like a Harvard football player. Right? 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 You shouldn't shoot before D star because it's a dominant strategy not to shoot before D star. Now you might want to wait a little to see if they're not going to shoot early, to see if they're not going to shoot, but you certainly shouldn't shoot early. And let me say this with one other thing. Every time when we play this game in class, whether it's here or up in SOM, people shoot too early. People shoot too early. They miss. Right? You can do kind of econometrics on this. You could figure out that on average abilities, I'm sometimes getting the better shots, sometimes getting the worse shots. On average, I should see people hitting about half of the time, all right, over a large sample. Right? But here I tend to see people miss, as we did today, almost all the time. Why do we see so many misses? Why do we see so many misses? So one problem may be that people are just overconfident. They're overconfident on their ability to throw. Right? And there's a large literature in economics about how people tend to be overconfident. But there's another possible explanation, and let me just push it past you as the last thing for today. I think Americans, I think this doesn't go for the Brits, Americans have what I call a proactive bias. You guys are brought up since you're in kindergarten, maybe before, and you're told you have to be proactive. You have to make the world come to you. Right? Right? And my evidence for this is based on sophisticated empirical work watching SportsCenter. So on SportsCenter, when they interview these sweaty athletes after the game, the sweaty athletes say, "It's great. I now control my own destiny." Right? Well, I'm a Brit. I think controlling my own destiny sounds kind of scary to me. Doesn't like a good thing at all. All right? In fact, if I wanted to control, hang on, we'll be finished in a minute. If I wanted to control my own destiny, I wouldn't have got married. Right? 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 But no, that's going to be edited off the film. But the point I want to make is this: every time I play this game and I ask people why they shoot early, I hear the same thing, and it's evidence of this proactive bias. People say, "Well, at least I went down swinging." And the problem is, in life, the aim in life is not to go down swinging, it's not to go down. All right? So one lesson to get from this lecture is, sometimes waiting is a good strategy. All right, well, we'll come back to it on Monday. So today I want to look at two kinds of games and then change topic a bit. And the games I want to look at are about ultimatums and bargaining. And we'll start with ultimatums and we'll move smoothly through, and we'll see why it's an easy transition in a while. All right, so the game we're going to play involves two players. There's two players. Whoops, 1 and 2. And the game is this. Player 1 is going to make a take it or leave it offer. Take it or leave it offer to player 2. And this offer is going to concern a pie. And let's make the pie worth $1 for now. All right, we'll probably play this for real in a bit, so we'll play it for $1. All right, so it's a split of a pie. We can think of the split as offering S to player 1 and 1 minus S to player 2. All right, S to player 1 and 1 minus S to player 2. And player 2 has two choices. 2 can accept this offer, and if 2 accepts the offer, then the shares are, then they get exactly the offer. Player 1 gets S, and player 2 gets 1 minus S. All right. Alternatively, player 2 can reject. And if player 2 rejects the offer, then both players get 0. Both players get nothing. All right, it's a very simple game. There's $1 on the table. I'll take it out in a minute. There's $1 on the table. All right, and our two players are going to bargain for this, but it isn't much of a bargain. Player 1's basically going to announce what the division is going to be. 2 can either accept that division, or no one gets anything. All right? Everyone understand the game? So I thought we'd start off by playing this game for real a couple of times. So why don't I come down and do that? All right. So why don't we play with some people in this row? I've been playing with that row all the time. So Ali's going to help me find somebody.
I found somebody.
You found somebody, okay. So the person behind you?
Yeah.
And your name is?
Equia. Equia.
You have to shout out to people, but this doesn't make a noise. Shout. Equia?
Equia.
Equia, thank you, Equia. And so you'll be player 1, and player 2 will be this gentleman here, whose name is, shout out?
Noah.
Noah, okay. So Equia, do you know each other? That's okay, okay. So Equia can make any offer she wants. We'll play this for real money, all right? So there's a real $1 at stake. You can make any offer you want. It can be in fractions of pennies, if you like, of the amount of $1 that you're going to offer to Noah, and the amount you're going to keep yourself. There you go.
A penny.
Shout it out so everyone can hear you. When you stand up, stand up. So this is your moment in the lights, all right? When you stand up as well. There we go.
I'm going to offer him a penny.
You're going to offer him a penny. And Noah, are you going to take a penny?
No.
Noah's not going to take a penny. So I didn't lose any money on that. So no one made any money. I didn't lose any money. That seems pretty good. Let's try a different couple. Let's move around the room a little bit. So why don't you, Ali, why don't you take the guy behind here, whose name is, shout out?
Gary.
Gary. All right, so Gary, why don't you stand up? And
we'll let Gary play with the gentleman in here. What's your name in here?
Anish.
Anish? Yeah. Right, stand up. And do you know each other? All right, so what do we let Anish be player 1 this time? You understand the rule of the game?
Yeah.
So make your offer.
30 cents.
Which is that?
I'll offer him 30 cents.
You're offering him 30 cents.
No, that's okay.
He's saying no as well. Okay. So we're not. All right. Let's raise the stakes a bit. Let's make it $10. All right. So we're not getting much acceptance here. Let me try a third couple. All right. Working my way back. So how about you? What's your name?
Courtney.
So when you stand up as well, we'll let Courtney be player 1. And actually, I want you to sit down so I can do it from here. And you are.
Danny.
Danny, all right, so Courtney's going to be player 1 and Danny's going to be player 2. These weren't our dating couple from earlier, right? We're safe from that. Okay, good. Right, so Courtney, what are you going to offer?
$5.
$5, which is half of the $10.
Accept.
All right, accept. All right. So it turned out in this game that a lot of people are rejecting offers. Let's have a look at it on the board a second. Let's think about it a second. And we'll come back. We're not done with this couple. We're not done with any of you couples. We're going to come back to you. All right. So in this game, it has it's pretty simple to analyze this game by backward induction. Right? By backward induction, we're going to start with the receiver of the offer, and the receiver of the offer is choosing between the offer made to them, which is in our notation is 1 minus s, and in our 3 examples, that was a penny, then it was 30 cents, and then it was half of it, so call it 50 cents just to be consistent. All right? And we actually saw 2 of those offers rejected, but according to backward induction, assuming that people are trying to maximize their dollar payoffs here, what should we see the receiver do? They should accept, right? They should accept even the somewhat insulting offer of a penny that was made. Even that somewhat insulting offer should be accepted by Noah, right? So Noah didn't accept the offer of a penny, and let's come back over there. So Noah didn't accept the offer of a penny, and I forget who it was, but our second player didn't accept an offer of 30 cents. But we've just argued they should have been accepted. They should have been accepted. In fact, when Aquia made the offer of 1 penny to Noah, I think she assumed that Noah would accept it. Is this right? Why do you think Noah was going to accept it? Shout out.
Because I felt he'd be better off with a penny than nothing.
You thought he'd be better off with a penny than nothing, all right? All right, and then when you saw an offer, the offer came up a bit. Who was my second offerer? Here was my second offerer. You offered a bit more. Why did you offer more?
I felt 30 was a pretty fair share. It's a lot better than nothing.
All right, 30 seems better than nothing, although not necessarily fair, but it's still better than nothing. All right, and where was my rejecter of the second offer? Who rejected the second offer? Why did you reject 30 cents?
It's just a pride thing.
It's a pride thing. It's a pride thing. All right, and pretty soon we converged onto 50 cents, which notice is nowhere near backward induction. It's nowhere near backward induction. So the third offer, which is Courtney, is that right? Why did you offer, what was it, half of it?
Because half is better for me than nothing.
Half is better than you for nothing, and you figured he's going to reject otherwise. And in fact, he didn't reject. Why didn't you reject?
Because 5 is better than nothing.
5 is better than nothing. But the 5 is better than nothing argument would have argued against making any rejection in this game. Is that right? That's right. So here's a game where backward induction is giving a very clear prediction. The clear prediction is, first of all, the second player will accept whatever's given to them, and second, given that, the first player should offer them essentially nothing, should offer them just a penny. Right? So backward induction predicts that the offer will be essentially, let's say, 99 cents and 1 cent, or even virtually $1 and nothing. All right? But in fact, we don't get that. We get a lot of rejection of these low offers, and often we get offers made much, much higher in the vicinity of half. All right? Now, why? Why are we seeing a failure of backward induction in this game? I think this is not just you guys. It's a very reliable result in experimental data. All right? So why do we see so many people in this ultimatum game both offer more and, more importantly, reject less than small amounts? Right, so let's talk about it. So one person said it's a pride thing. It's a pride thing. Let's try the other aisle while I'm here. So what's the smallest offer you would have accepted? What's your name, first of all?
Jeff. I don't know, a cent.
A cent, right? So there are some backward induction players in the room. All right, all right. Who would have rejected a cent?
Who would have rejected 10 cents? Should be going, we should be going down at least. Who would have rejected 30 cents? Few people rejected 30 cents, not many actually. All right? How many people would have rejected 50 cents? One person even would have rejected 50 cents, right? But essentially no one, okay. So what's happening here? Why do people think people are rejecting what is essentially money from my pocket, right? There's nothing going on here, I'm just giving you money. Why are they rejecting being given money?
Like overall the stakes are really low. So if you have any value on sort of like pride, what people said, you know, it's not worth a penny or 10 cents.
All right, so it may be pride going on here. So certainly one thing is about pride. It turns out that people do this even in quite high stakes games, but you're right, certainly that trade-off is going to start to bite. All right, what else is going on? So I agree, pride is part of what's going on. What else is going on here? Let's try and get some conversation going. There's somebody in here. I can get the mic in. Shout out your name and really shout.
Peter.
Yeah, go on.
Change is cumbersome.
Change is cumbersome. Okay, you didn't want the change. Okay, fair enough, fair enough. But if the stakes go up, that would get rid of that. Yeah.
Maybe people are tying their own outcomes to the other players' outcomes as well.
Right, so maybe people have different payoffs here. Maybe people are comparing their payoff to the other person's payoff. That certainly seems like a plausible thing to be going on here. You might feel less happy about getting 20 cents knowing the other person's getting 80 cents, for example.
You might be trying to teach them a lesson to get them to offer more.
Right, you might be trying to set a sort of moral standard here. All right, so there's some notions of indignation or even teaching people that they really should offer people more. All right, what else could be going on here? Yeah.
If people know I'm not going to accept less than 50 cents, then they should give me 50 cents by backward induction.
Right, so part of what's going on here, actually this game was a one-shot game, right? We just played it once, and we could have played it, in fact they often do play this way in the lab, you could have played it without anybody knowing who the other player was, all right? But particularly in this setting where everyone can see everyone else, and even in the lab where people actually can't see people, but they might imagine that the game is really repeated, you could imagine people trying to establish a reputation. Is that right? So there's lots of these reasons. There's sort of moral indignation reasons, or teaching a lesson reasons, pride reasons. There's also this basic reason that people might be thinking this game is, I should play this game as I would a similar situation in life where I might want to be establishing reputation. All right? So there's a certain amount of confusion going on in the game, but there's also a certain amount of a lot of things make sense. Now notice that once we've established that people are going to reject small offers in this game, once we've established people are going to reject small offers, it makes perfectly good sense to offer a lot more than nothing. All right? So it's not that surprising that once we've established the idea that people are going to reject small offers, you're going to see people making offers that are reasonably large, although not usually larger than 50 cents. Why is 50 cents so focal here? Why is 50 cents so focal? It's not a trick question, I'm just asking, why do people think 50 cents is so focal? I think it's typical that people end up offering around 50 cents. Why? It sounds fair, right? It seems fair. There's some notion of fairness. It's not clear, by the way, what ethical principle is involved here, right? It's not clear that if you're walking along the street and you happen to find $1 at your feet, that you should pick it up, and anyone else you happen to see at that moment, you should give 50 cents to. Right? That's essentially what the situation is, and you just chanced upon this $1 that I just gave you. It isn't clear that there's any particularly great moral claim to give it to someone else, but I think people read this as a situation about splitting a cake in an environment of distributional justice. They view it as a larger picture. Is that right? So it turns out there's a large literature on this. There's a large experimental literature on the ultimatum game, and there's an even larger literature on an even simpler game, in which I give people $1, I say you can give whatever share you want to the other person, and they don't even get a chance to accept or reject. Right? That's called the dictator game. Right? The dictator game, literally, you're just simply given $1 and you can give whatever share you want to the other person. Right? It turns out even in the dictator game, people give quite a lot of money. Right? That suggests that there really is some notion of fairness or some notion of distributional justice going on in people's heads here, rightly or wrongly. All right? So one thing this should tell us is even in extremely simple games, we should be a little bit careful about reading backward induction into what's going to happen in the real world. Part of this is because, as I mentioned the very first day of the class, people care about other things than just the obvious payoffs, and part of it is about more complicated things like reputation and so on.
All right, having said that, let's nevertheless, for the purpose of today, act as if we are going to do backward induction, and let's embed this into a slightly more complicated game. All right, so the more complicated game is as follows. All right, so we're going to have a two-period bargaining game. Two-period bargaining. In this two-period bargaining game, the beginning of the game is exactly the same. So there's $1 on the table, and player 1 makes an offer to 2, and once again we can call this offer S and 1 minus S. Just the same as before. And just as before, player 2 can accept the offer, and if they accept the offer, then this is indeed what they get. All right, but now, if 2 rejects, which is 2's other alternative, if player 2 rejects the offer, then we flip the roles. We play the game again, but we flip the roles. So we go to stage 2. All right, this is everything we say up here is stage 1. And down here we go to stage 2. And in stage 2, player 2 gets to make an offer to 1. Player 2 gets to make an offer to 1. And once again, we can call this, we better be careful. Let's put 1s here just to indicate we're in the first round, and 2s here to indicate we're in the second. All right, so we make offers S2 and 1 minus S2, where S2 is that goes to player 1, and 1 minus S2 is that goes to player 2. So 2 gets to make an offer to player 1, and now 1 can accept or reject. If she accepts, then she gets her share from here. The offer is accepted. And if she rejects, then we get nothing. All right, so this game is exactly the same as playing the previous game, except we flip roles. But we're going to add one catch. The catch is this. In the first round, the money on the table is $1. All right? But if we end up going into the second round, right, so the first offer is not accepted, and we go into the second round, then part of the money is lost. And in particular, we'll assume that the money on the table is delta. Right, where you can think of delta as being just some number less than 1. Right, so if you want a concrete example, think of this as being 90 cents. Right? So the idea here is, if you get into the second round, time has passed, it's costly, and so money in the second round I think of it as money in the second round as being worth less, or you can actually think of this cake being eaten up. Some of it's thrown away, some of it's wasted. All right, everyone understand the game? All right, so this is very similar to the previous game, but we've got this second stage coming in, and we've got discounting. So this is the idea of discounting. How many of you have heard the term discounting before? All right, so you probably saw it in a finance class or a macro class, where we think about there being a value of money, value of time. That money today is worth more than money tomorrow, partly because you could put the money today into the bank and it could earn interest, partly because you're simply impatient to get that money and go and have lunch, particularly on the day in which the clock's changed. All right? Okay, so let's try this game again, and let's just play it for real. So let's come down again. Everyone understand the game? Basically the same rules except with this flipping around and with the possibility that the cake may shrink. Let's see what people have learned. So who are our first pair? Our first pair were Aquia and... Who was Aquia's? And Noah, all right? So Aquia, what are you going to offer? You're player 1 here, all right? But if your offer is rejected, Noah's going to get to make an offer to you. All right, so what are you going to offer this time?
$45.99. So 45 cents. Yeah, 45 cents. 46.
46, okay, so he gets 46 if he accepts the offer, is that right? Yeah. 46 if he accepts the offer. All right.
I'll accept that.
He's accepted that. Okay, that was easy. That was easy. So Akua got 54 cents, and Noah got 46 cents. All right. Who was our second pair? Who was our second pair? So that was I forgot Anish, right? And Gary. All right. So Anish, what are you going to offer this time?
I'll offer 43.
43. You were going to push the envelope a little bit.
All right.
All right. That one got accepted as well. Okay. So people are converging here. All right, and what about our third offerer and receiver? It was Courtney and Danny. So Courtney?
30.
30, so it's 30 for him.
I'll accept.
Oh, 3 acceptances, all right. All right. Let's find out something here. So I was hoping to get into the second round. So supposing, okay, so you accepted, that's fine. That's fine. All right, no chicken sounds around the room. All right, so it's Danny, right?
Yeah.
So, Danny, had you rejected, or you accepted, but had you accepted, what would you have offered in the second round?
45.
45, all right, 45. And would you have accepted that in the second round if your 30 had been accepted?
Yes.
Yeah, so, okay, so you might have done better, it turns out, all right? Right. Let's go back through to the other rejections, so the other acceptances. So, my second couple, you offered 43, is that right? Right? And you said yes to 43, is that right? Had you rejected 43, what would you have offered back in return?
43.
43, the same thing back. Would you have accepted it?
He gets 47.
He'd have got 47 in that case?
Yeah, I'd take it.
You'd accepted that, okay. And Akua went first, and she offered 45 to Noah. And Noah, had in fact you rejected, what would you have offered back?
I would have also done 45.
Same thing back. And would you have accepted it?
Yeah.
Okay, so we can see here that the decision to accept or reject partly depends on what you think the other side is going to do in the second round. Is that right? So here you are, you're making, if you're in the middle of this game, if you're player 2, you've received an offer, right? None of these offers sounded crazy. I mean, 30 cents was the lowest one, but none of them sounded crazy. And you're trying to decide whether you should accept or reject this offer. And one thing you should have in mind is, what would I offer if I reject? And will that offer that I then offer in the next round be accepted or rejected? Is that right? All right? And so if we just work backwards, we can see what you should offer in the first round should be just enough to make sure it's accepted, knowing that the person who's receiving the offer in the first round is going to think about the offer they're going to make in the second round and going to think about whether you're going to accept or reject in the second round. Is that right? Right? So that sounds like a bit of a mouthful, but that mouthful of reasoning is exactly backward induction. Right? It's exactly backward induction. It's saying to figure out what I should do in the first round, I need to figure what I should offer in the first round. I need to figure out whether player 2 is going to accept or reject. And to figure out whether he or she is going to accept or reject, I have to put myself in his or her shoes and figure out what he or she would offer if she did reject and what he or she thinks I would do if I got that second round offer. Is that right? All right, so let's try and analyze this as if backward induction was going to work here, as if we didn't have to worry about things like pride here. All right, so this is the game we're actually playing, so let's keep that one. And actually analyze it on the board. I want to walk us from a relatively mundane game of take it or leave it offers to a more complicated game in which there can be several rounds of offers. But we're going to go slowly, so we'll start this with 2 rounds. All right? All right. So first of all, let's just look at the stage 1 game. The stage 1 game, and let's keep in track what the offer is and what the receiver is. This is the offerer, and this is the receiver. All right? And in the one-stage game, the game only has one stage, then we know from backward induction what the result should be. It isn't what we find in the lab, it isn't what we find in the classroom, but we know what we should get. The offerer should offer to keep everything, essentially, or maybe 99 cents, but let's call it 1, and the receiver gets nothing. All right, so again, I'm approximating a little bit because it could be 99 cents and a penny, but who cares? Let's just call it $1 and nothing, if it's a one-stage game. All right, so now let's consider a 2-stage game. All right, in the 2-stage game, the person who's making the offer in the first stage
needs to look forward, to anticipate what would happen if her offer was rejected by player 2 and player 2 went forward into the second stage. Is that right? So in the two-stage game, in the first stage of the two-stage game, the person making the offer wants to anticipate what the receiver would offer in the second round were the receiver to reject her offer. Okay. But we can do that by backward induction. We know that in the second round, if the receiver rejects the offer, then the second round of the two-stage game is what? It's a one-stage game. All right? And we've just argued, at least we believe in backward induction, in that case, player 2, who is then the offerer, will offer $1, and player 1, who is now the receiver, will accept it and get nothing. All right? So player 1 in the first round of the two-stage game wants to make an offer that's just enough to get player 2 to accept it now. All right? So let's think about this. So if player 1 offers 2 something more than what? Well, tomorrow player 2 can get $1, all right, but that's $1 tomorrow. All right, so $1 tomorrow is worth how much today if we're discounting? It's just worth delta, right? It's just worth delta. So if player 1 offers player 2 more than delta times 1, which is what player 2 can get tomorrow, then 2 will accept. And if player 1 offers 2 less than delta times $1, because you can get $1 tomorrow, but that's only worth delta, that $1 tomorrow is worth just delta today, then 2 will reject. All right? So the offer has to be exactly enough to get accepted, which is exactly delta dollars. All right, delta dollars. All right, so player 2 knows that she can get, let's put it in pink, player 2 knows she can get $1 tomorrow, so you need to offer her at least delta today to make it as good for her as getting $1 tomorrow. All right, we know the receiver must be offered at least delta tomorrow, which means the offerer is going to keep 1 minus delta. All right, so this, in the first round of the two-stage game, player 1 should offer 1 minus delta for herself and delta for player 2, and player 2 should accept that because delta dollars today is as good as $1 tomorrow. All right? Now another way to see that is in a picture, so let's just draw a picture. All right, let's put the payoff of player 1 here and the payoff of player 2 on this axis. All right, and these are, we're going to assume they're just going to maximize dollars, so there's no pride in here. And if we just look at the one-stage game, we're simply looking at this line. All right, the offers in the one-stage game, it could be that player 1 gets everything herself and gives nothing to player 2. It could be that player 2 keeps everything ends up getting everything and player 1 gets nothing, and it could be any combination in between. Right? And we argued by backward induction, although not in reality, in backward induction, in the one-stage game, player 1 makes an offer to player 2, which is kind of an insulting offer. Player 1 says, I get everything and you get a penny. All right, so this is the one-stage game. In the two-stage game, in the two-stage game, if things are settled in the first stage, this line represents the possible divisions between player 1 and player 2. Right? But if we end up going into the second stage, the pie is shrunk. The pie is shrunk, instead of going from 1 to 1, it goes from delta 1 to delta 1. Or if delta is 0.9, it goes from 0.9 to 0.9. So let's draw that line in. Right, so we get into the second stage, we'll end up being here. All right, and this goes from delta dollars here to delta dollars here, where these dollars are being evaluated at time 1. Right, so the pie is shrunk.
If we get into the second stage, then by backward induction, player 2 knows, player 2 isn't an ultimatum game, player 2 will be making the offer, and player 2 says, whatever cake is left, I'm going to take all of it, and you're just going to get a penny. So if we get into the second stage, then player 2 will make this offer to player 1. All right, player 2 will say, I'm going to keep all of the whole of the pie, which in in first period dollars is worth delta. So I'm going to end up with a payoff of delta, and you're going to end up with a payoff of essentially nothing. All right? Player 2 knows that they can therefore get at least delta dollars, or delta in current day dollars worth from rejecting your offer. Since they can get at least delta current day offers from rejecting your offer, the lowest offer you can make to them is an offer that gives them at least delta. So the offer you're going to make is this offer. This is the two-stage offer. It happens in the first stage. Player 1 makes an offer that gives player 2 what player 2 could get in the second round, and gives player 2 delta, and keeps 1 minus delta for herself. All right, everyone understand the picture? So this picture is just corresponding to this table. Right? The thing people tend to get confused about here, I think, is they get confused between current dollars and discounted dollars. So we're going to do all the analysis here in terms of the first period dollars. Dollars tomorrow are going to be worth delta. There's a hand up. Can I get a shouting out? Yeah. Yes, sorry. Let's put those labels bigger. Yes. So this is the outcome if it was a one-stage game, and this is the outcome if it was a two-stage game. Right? The offer's made and accepted. All right, let's roll it forward. Let's look at a three-stage game. Let's keep this picture handy and think about a three-stage game. So the beginning of the game is the same. All right, we're going to look at three-stage bargaining. And the rules in three-stage bargaining are pretty much the same as in two-stage bargaining, but now there's two possible flips. In three-stage bargaining, in the first period, in period 1 makes the offer, and if it's accepted, the game's over. All right? In period 2, so if reject, then we go to period 2, when 2 makes the offer, and if it's rejected now, this time by player 1, then we go to period 3, where once again 1 makes the offer. So you can see where we're heading. We're heading towards an alternate offer bargaining model. I'm going to make an offer, Jake's going to either accept or reject, then he'll make an offer, and we'll flip to and fro. There's a question. Let me try and get a mic out to the question. Here you go. Yeah.
Yeah, I have a question about the two-player game. If delta
shout out so people can hear.
If delta is the best that player 2 can get tomorrow, then why would one offer player 2 delta discounted by delta today?
Good. Okay, right. So good. So I think I was confusing about it. Something behind me clear. So tomorrow, player 2 can get everything that there is. All right. So whatever pie is left tomorrow, player 2 can get all of it. All right. So call that pie tomorrow 1, and evaluate it in period $1 as being worth delta. All right. All right. That makes sense. Okay, so I think I misspoke on that, so let me say it again. All right, so every period there's this pie. All right, in every period, if it was the last period of the game, the person making the offer is going to get the whole pie. All right, but if I view that pie tomorrow from today, right, a pie of $1 tomorrow is only worth delta dollars today. A pie of $1 the day after tomorrow is only worth delta dollars tomorrow and delta squared dollars today, and so on. All right, so that's the way in which we're going to do discounting here. Good. All right.
All right? So in this game, if one makes an offer, if it's accepted, it's over. If it's accepted, then we're done. And if this offer is accepted, then we're done. And if this offer is accepted, then we're done. And in the third round, if it's rejected, then both players get nothing. All right? And once again, we're going to assume that the players are discounting. So what does it mean? What does it mean to say they're discounting? It means that dollars in period 1 are worth dollars. Dollars in period 2 are discounted by delta. And dollars in period 3 are discounted by delta times delta, or if you like, by delta squared. All right, and just to put this into real notions of money, if you think of delta as being 90%, then $1 in period 1 is worth $1. $1 in period 2, viewed from period 1, is worth 90 cents, and $1 in period 3, viewed from period 1, is worth 81 cents. All right? Okay. So what do we think is going to happen here? Well, once again, we can do backward induction. Here we are in our picture. Let's look at the three-stage game. And once again, when we analyze, as always, when we analyze these games using backward induction, we want to start at the end. If we start at the end, we know that at the last stage, that's the third stage of the three-stage game, looks like what? It looks like the one-stage game. And in the one-stage game, we know the offerer will get everything. All right? So again, so the last stage of the three-stage game, we know the person who makes the offer, who this time will be player 1, will get everything. However, that everything is only worth delta in period $2, and it's only worth delta squared in period $1. All right? So in the first period of this game, we know that if the offer is rejected, we know what's going to happen. So again, in the first period of this three-stage game, if the offer is rejected, then we'll go into a two-stage game. Right? We'll go to a two-stage game, and we already know what happens in a two-stage game. In a two-stage game, the person who gets to make an offer gets 1 minus delta, and the person who receives the offer gets delta. All right? So we know in the first stage of the game that the person who receives the offer always has the outside option of saying, no, I reject, and we know that that person tomorrow will get 1 minus delta. But 1 minus delta tomorrow is worth how much today? It's worth delta 1 minus, tomorrow they're going to get 1 minus delta dollars, so today that's worth delta 1 minus delta dollars. All right? So the offer I have to make in the first round to make sure that the other person accepts it has to be just better in discounted dollars than what they're going to get tomorrow. They're going to get 1 minus delta tomorrow, so I have to give them delta 1 minus delta today. All right? Which means I keep for myself 1 minus delta 1 minus delta. And if you don't like the algebra, let's look at the picture. In the picture, in the one-stage game, this is the offer. In the two-stage game, we know if we get into the second round, player 2 gets everything. Right? So we have to give him that much today. And if we get into the third round, now we're looking at delta squared here, and delta squared here. Delta squared and delta squared. We know that if we get into the third round, the person who makes the offer in the third round will get to get everything. So we can actually work our way along. All right? So in the third round, the person who makes the third offer will get everything. So in the second round, you'd have to give them that much. So in the first round, you'd have to give player 2 that much. All right? Say it again. In period 3, the person making the offer can get everything. All right? So in period 2, they must be getting delta times that. So in period 1, you have to give them at least this much. All right? And this here is the offer you'd make in the three-stage game. All right?
So in the picture, we're just doing a little zigzag on the chart. We're also always working across the diagonal. All right. So we've done the one-stage game. The one-stage game, the person making the offer gets everything. In the two-stage game, the person making the offer offers just enough to get the offer accepted, which is delta, because that's what $1's worth tomorrow. In the three-stage game, the person making the offer makes just enough to get the offer accepted, which is delta times what the receiver would get tomorrow. What they get tomorrow is 1 minus delta, so they get delta 1 minus delta today. All right? How about the four-stage game? Let's see if we can do that. So if we go to the four-stage game now, in the four-stage game, if the person receiving the offer rejects the offer, then tomorrow they can get 1 minus delta, 1 minus delta. So I need to offer them enough now in current dollars so they will prefer that to getting 1 minus delta, 1 minus delta tomorrow. So how much must I offer them? I have to offer them at least delta times that much. So I have to offer them delta times 1 minus delta times 1 minus delta. Like this. Right? And again, I have to keep the rest, I'll keep the rest for myself, so I'll get 1 minus delta, 1 minus delta, 1 minus delta. All right? And so the principle is always give people just enough today so they'll accept the offer, and just enough today is whatever they'd get tomorrow discounted by delta. All right? So actually this backward induction isn't so bad. All right? What makes it a little bit easier is you don't actually, when you go through an extra stage of this, you don't actually have to go all the way to the beginning. You can actually start where you were last time and just discount once more by delta. All right? Now let's see if we can see any kind of pattern emerging in this algebra. All right? So let's just multiply out these brackets. In the four-stage game, this thing is actually equal to, just multiplying through, it's 1 minus delta plus delta squared minus delta cubed. Hope it is, anyway. That's what this is. And this thing is equal to delta minus delta squared plus delta cubed. All right, just multiplying out the brackets. All right? Does anyone see a pattern emerging here in these offers? We had offers of 1 and then 1 minus delta. We could also multiply out this one. It might be helpful to do so. This is actually 1 minus delta plus, this is 1 minus delta plus delta squared. All right? Anyone see a pattern? What these offers look like? They kind of alternate, right? So let's have a look what the... Rather than do every stage, should I do one more stage to see if we can see a pattern emerging, or should I jump straight to 10 stages and see what happens? Go straight to 10, you'll say? Let's do one, no, let's do one, okay, let's jump straight to 10. Okay, so imagine that this game actually had 10 rounds. All right, so this is the 10-stage game. And let's just continue our chart down here. So here's a bit more space here. All right, 10 stages. 10-stage game. I'm going to continue my chart, and my chart says in the 10-stage game, what am I going to get? So the offer is going to be the same pattern: 1 minus delta plus delta squared minus delta cubed dot 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 plus delta to the 8 minus delta to the 9. Everyone see that? So what I'm doing is I'm continuing the pattern from above.
Right, so if I had 10 stages, I always start with a 1. The positive and negative terms just alternate, and I have as many terms as 1 minus the stage I'm in. So in the 4-stage game, I ended up at delta cubed. So in the 10-stage game, I'll end up at delta to the 9. All right, everyone happy with that? All right, so the 4th stage offer is this slightly ugly thing, 1 minus delta plus delta squared minus delta cubed, dot, 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 dot. All right, so plus delta to the 4 minus delta to the 5, etc., plus delta 8 minus delta 9. Right, that's a pretty ugly thing, but fortunately, some point in high school, you learned how to sum that thing. Do you remember what this is? What do you call objects like this in high school? Anyone remember? Objects like 1, delta, delta squared, delta cubed, delta to the 4, what are they called? They're called geometric series, right? They're called geometric series. Anyone remember how to sum them? We know that S is equal to this. Right, this is what the offer is. If there's 10 rounds, we know the offer is accepted. All right, so the way to remember how to sum it is the trick for summing it is to multiply both sides of this equation by the common ratio. So multiply both sides by delta. So if I multiply this side by delta, I'm going to multiply the other side by delta, and this 1 will become a delta. This delta will become a delta squared. This delta squared will become a delta cubed. This delta cubed will become a delta to the 4th, dot, dot, dot. There'll be a minus delta to the 8 coming from the 7th term. There'll be a plus delta to the 9 coming from the delta 8th term. And there'll be a minus delta to the 10. Right, everyone okay with that? I just multiplied everything through by delta, and I just shifted it along one for convenience. What do I do now? Anyone remember? Add the two lines together. Let's add the two lines together. All right, so by summing, on this side, I get 1 plus delta S10. All right, on the other side, what's kind of convenient is everything cancels. The 1 comes through, I get a 1, but these two terms cancel, and these two terms cancel, and these two terms cancel, and so on, all the way up to the end, where I get minus delta to the 10. Everyone okay? All the other terms have cancelled out? All right, so now just sorting out my algebra bit, I'm going to take it on the other side. I'm going to have that the offer you make, this is what you're going to get to keep, so the amount I claim I should keep in the first round is 1 minus delta to the 10 over 1 plus delta. I have to be a little bit careful about the notation here, because it may be a little bit confusing. The 10 here doesn't mean to the 10th power, it's just the offer in the 10th round. Whereas the 10th here really does mean in the 10th power. Okay? All right, so if we play this game for 10 rounds, the offer you'd make would be 1 minus delta to the 10 over 1 plus delta, which means that the amount you're offering to the other side, which is 1 minus s, would be delta plus delta to the 10 over 1 plus delta. All right? So let's just summarize where we are. We started off by considering a very simple game, a one-stage take-it-or-leave-it offer. We know that in that take-it-or-leave-it offer, player 1 is going to claim everything for herself and offer nothing to player 2. Then we considered a two-stage game, which was the same as the one-stage game, except that if player 2 rejects the offer, let's call player 2 he gets to make an offer to player 1 in the second period. We know that in the second period of that two-stage game, player 2 can keep everything for himself. Everything for himself tomorrow is worth delta today. So you have to offer him at least delta today and keep 1 minus delta for yourself. Then we looked at a three-stage game. In this three-stage game, If player 2 rejects in the first round, player 2 can make you an offer in the second round, but now if you're player 1 and you reject in the second round, you get to make an offer to player 2 in the third round. We argued that in the second round of this game, the person, if player 2 rejects you in the first round and makes an offer in the second round, it'll be in a two-stage game, and they'll be able to keep 1 minus delta of the pi for themselves. So you have to offer them at least delta times 1 minus delta today for them to accept the offer, keeping the rest for yourself. Then we looked at a four-stage game. In the four-stage game, if player 2 rejects your offer, he can make you an offer, but if you can reject the offer, you can make him an offer, but if he rejects that offer, he can make you an offer. And once again, we asked, how much do I have to offer player 2 now for him to accept the offer now? He knows that if he rejects the offer, he can get this amount, 1 minus delta times 1 minus delta, tomorrow. So I have to offer him delta times that today, and once again I keep the same to myself. Right, that's just a summary of what we did, and then what we did was we cheated. We jumped to the 10th stage, just noticing that a pattern had emerged, and we found in the 10th stage, this is the offer you'd make, just according to the same pattern, and it was this horrible thing, and then we used a little bit of high school math to simplify this thing, and it turns out this is the amount you'll keep for yourself, and this is the offer you'll make to player 2. All right, in each case they'll be accepted. Did I make a math mistake? Thank you. Yes, let's put a superscript in here. Thank you. Good. All right. So what do we observe here? So the first thing to observe is in the one-stage game, if we believe backward induction, you certainly want to be the person making the offer. In the one-stage game, in the ultimatum game, there's a huge first-mover advantage. In the two-stage game, it's not clear if you want to make the offer. It depends on how large delta is. But if delta is a big number, like 0.9, you'd rather be the person receiving the offer. In the three-stage game, it looks like you'd probably rather make the offer, but it's not so clear. Right? So where does it go to as we go down the path here? As it goes down towards the 10-stage game. Looks like in the 10-stage game, you'd probably still prefer to make the offer than not, but they're certainly much closer together than they were before. Some of that initial bargaining power has been washed out by the fact there are 10 stages. All right? So let's try and push this just a little bit harder. Instead of looking at the 10th stage offer, what if we look at the infinite stage offer? So what if in principle, we look at the infinite stage of this game? All right? So I can make you an offer, you can say no and make me an offer, and then I can reject and make you an offer, and then you can reject and make me an offer, and so on and so forth. All right? So we look at this term, if in principle you can make an infinite number of offers. All right? So what's this term going to look like if I can make an infinite number of offers? So I claim it's going to look like this: 1 minus delta to the infinity over 1 plus delta. And over here, it's going to converge towards this, it would be a bit more formal. And over here, we'll have delta plus delta to the infinity over 1 plus delta. However, now I get a little bit simpler. What is delta to the infinity? It's 0, right? So 0.9 times 0.9 times 0.9 times 0.9 times 0.9 is 0. So this last term disappears, as does this one, and we just get 1 over 1 plus delta and delta over 1 plus delta. So if we make alternating offer bargaining, a bargaining game where in each round I make you an offer, you can accept it, or you can reject and make me an offer, and we imagine there's no bound to this game, it just goes on arbitrarily long, then our prediction is that player 1, the person who makes the first offer, will get 1 over 1 plus delta of the initial pi, and player 2 will get delta over 1 plus delta of the initial pi. Let's try and get a handle about what those numbers are. All right? So if you imagine these offers can be made fairly rapidly, Right? For example, I can make an offer today, you can make an offer back to me in half an hour's time, and then I can make an offer back to you in half an hour's time, then it's reasonable to assume that the pie is not shrinking very fast. Right? The discount factor is not a big deal here. All right? So if these offers can be made in rapid succession, then we might think that delta itself is approximately 1. The pie isn't shrinking very fast. If delta is approximately 1, right, if we take delta to 1 here, right, we think that time isn't that valuable, given how rapidly we can make offers to and fro, then what does this make this equal? In the case where delta is equal to 1, what do we get? We get a half, which means this will also be a half. So we learn something from this which is kind of surprising. If you do alternating offers, the sort of standard, very natural game of bargaining, sort of the kind of bargaining you might do in the bazaar in a market, or the kind of bargaining you might imagine going on in negotiations between baseball players or their agents and teams or general managers of teams, right, which offers just go to and fro, and they go to and fro fairly rapidly, and in principle they could make lots and lots of offers. In principle, what this model tells us is, in principle, we're going to end up with each side splitting whatever the pie was equally. Right? Very, very different from the ultimatum game, where all the bargaining power was on the person who made the first offer. All right? All right, so what are the lessons here? What can we conclude from this? We've looked at alternating offer bargaining, and we've concluded under special conditions, we've concluded that you get an even split. Right? So you get an even share, an even split, 50-50 split, if three things are true. The first thing is there's potentially infinite many offers, potentially can bargain forever. And if discounting is not a big deal, what does discounting really not being a big deal means? It means those offers can be made in rapid succession. All right, so no discounting. No discounting, or if you like, rapid offers. If you had to wait a year between every offer, then that discount factor would be a big deal. But I actually made a third assumption, and I made it without telling you. What was the third assumption I made? I snuck a third assumption past you without telling you. What was that third assumption? Let me get the mic again. So I claim I snuck a third assumption. There was somebody. Well, let me start over here. What was the third assumption?
I don't know if this is what you're looking for, but they know how big the pie is.
They know how big the pie is. That's true. That's a big deal, actually. It's true, but there's something else going on here. What else is going on here?
We assumed that both players were rational.
We assumed that. That's true, but we've kind of been assuming that throughout backward induction. You're right. None of this backward induction would apply so cleanly if we didn't assume that. What else did I assume here? It's hidden, actually. I snuck it in.
Discount factor is a constant?
We assume the discount factor is a constant. That's true, but not just constant, but something else. You're on the right lines. They're the same, right? I've assumed here, implicitly, I've assumed that both people are equally impatient. They have the same discount factor. The same discount factor, delta 1 equals delta 2. Right, why does that matter? Well, let's just think about it intuitively a second. Suppose that one of these players is very, very impatient. They need the money now. If it's cake, they need the cake now. They're very impatient. And the other person is very patient. Right? They can wait forever to get this bargain to come across. All right? Who do you think is going to do better, the patient player or the impatient player? The patient player is going to do better. Right? The patient player is going to do better. The way we ended up, the way we did all this analysis, is we assumed that those discount factors were the same. We assumed that each person was discounting time at the same rate, perhaps because they were facing the same bank with the same interest rate. But in practice, often one side is going to be in a hurry to get the dispute resolved, and the other side can sit around forever. Right? And in that world, the side who can sit around forever is going to do much better. All right? Now we're going to look at relaxing this assumption, and this assumption in particular, we're going to relax it on a homework exercise. All right, so in your homework exercise, you're going to try redoing part of this analysis, good practice anyway, but doing it in a setting where the discount factors are different. All right, so one thing we learned here was, yes, you get an even split, but it depends on these three assumptions. All right? And it's kind of important because when you think about bargaining, I think a lot of people simply assume intuitively that whatever the bargain is about, people will eventually split on the middle. When you're bargaining about a house and what price you're going to pay for a house, all these things, you kind of implicitly have this assumption that you're going to end up splitting the difference. What I'm arguing here is you will split the difference in this natural bargaining game, but only under very special assumptions. And in particular, the assumption of patience is critical. All right? There's another remarkable thing here, though. It's also hidden. So not only did we end up with an even split, but something else remarkable happened in this bargaining game. What was the other thing, somewhat amazingly, very unrealistic thing that occurred in this bargaining game? Let's see if we can spot it. So one thing was an assumption I made, and the other is actually a prediction. Yeah?
So the first offer will be the offer that's accepted?
Good. Good. Did everyone see that? So in this bargaining game, I set it up as alternating offer bargaining. So the image you had in your mind was of haggling. I made an offer. You guys thought about this offer. Shall I take this offer? Maybe I won't take this offer. You make me an offer back to me. And we kind of haggled to and fro. But actually, in the equilibrium of the game, none of that happened. That all happened in our minds. We thought about what offer we would make, and we thought about what offer you would make back to me if I made you this offer and you rejected it, and so on. We did this backward induction exercise, but it was all in our heads. Right? In this game, the actual prediction is the very first offer is accepted. The very first offer is accepted. There's no haggling. There's no bargaining. All right? Now that doesn't seem very realistic. Right? There's no haggling. Backward induction suggests that we should never see bargaining. Never see the actual process of bargaining. What we should see is an offer's made and it's accepted. Now, what is it about the real world that allows for haggling to take place? If this was a model of the real world and we believe in backward induction, then we're done. So why is it, in fact, in the real world, we see people make offers to and fro? What's different about the real world than this model? All right, let's talk about it a bit. How many of you must have all bargained for something in the real world. None of you probably bargained for a house yet, but you might have bargained for a car or something. All right? And in the real world, you make offers go to and fro, right? What's going on? Why are we getting offers in the real world, whereas we don't in this game? What are we missing? Yeah, let's try up here.
In the real world, you don't actually know what the other person's discount factor is, therefore you have uncertainty as to what your highest possible offer can be.
Good, good. So in the real world, unlike the model on the board, not only are those discount factors different, but you probably don't know how patient or impatient the other side is. You can get some ideas about how patient or impatient the other side is by looking at their characteristics, for example. For example, if you know that the person you're bargaining with over their car, you're trying to buy their car, and they're a graduate student who's just got a job in, I don't know, Uzbekistan or something, and they ain't going to be taking their car with them, and they're leaving next week, you know they're in a hurry. All right? So there's times when you're going to know something about what other people's discount factor is, how patient they are, but lots of times you're not going to know. All right? So one thing is, you just don't know what the discount factor is. By the way, what else might you not know about the other side? What else might you not know? Yeah?
How big the surplus is that you're splitting.
Good. You might not know this good that you're selling. You might not know. We've been talking about there being one pie which you're carving up, and everyone knows the size of the pie, right? But in the real world, I might not know this object that's being sold. I might not know how much this object is worth to the other side, and he or she may not know how much it's worth to me, right? So that lack of information is going to change the game considerably. In particular, I might want to turn down some offers in this game in order to appear like a patient person. Or I might want to turn down some offers in the game in order to appear like somebody who doesn't really value this all very much. All right? And in so doing, I'm going to try and get you to make me a better offer. All right? So what's going on in haggling and bargaining, according to this model, what's missing in this model, is the idea that you don't know who it is you're bargaining with. You don't know how much they value the objects in question. You don't know how impatient they are to get away with the cash. All right? So it's a big assumption here, very big assumption, is that everything is known. Right? So both patients, both the size of the pie, or let's call it the value of the pie, the value of the pie and the value of time is assumed to be known. But in the real world, you typically don't know the value of the pie to the other side, and you typically don't know how much they value time. All right, so that produces a whole literature on bargaining, none of which we really have time to do in this class. It's a pity, because bargaining is kind of important. So instead, I want to spend the last 5 minutes just introducing... well, is it really worth introducing a new topic in the last 5 minutes? No, I don't think it is. Let me talk a little bit more about bargaining rather than that. All right. So what does this suggest? Right? What does this suggest if we're going out in the real world? All right, actually taking this to reality. Right? So one thing it suggests is people for whom it's known that they're going to be impatient, people for whom it's known that they desperately need this deal to go through, are going to do less well in bargains. Right? We already know people may do less well in bargaining because they're less sophisticated players. But here, it isn't that they're less sophisticated. They can be as sophisticated as you like, but they're just going to be in a hurry. Right? We already talked about the graduate student who's leaving for Uzbekistan. Right? But who else, typically, in bargaining, is going to need cash now? Who else is going to be in a weaker position when they're bargaining, socially in our society? So, I'm trying to get questions out here, yeah?
And labor management disputes labor.
So that's a good question, right? It's a good question in labor management disputes. There's one going on right now in Hollywood. It's not clear there, right? It could be the management side who's in a hurry because they just need right now to get David Edelman's script written, right? That would tend to favor labor. But it could be the labor side. Why might it be the labor side? So did everyone know this? There's a writers' strike going on in Hollywood right now. All right, so the people on the management side who are in the weakest position are the people who are in the most hurry to get this resolved, and those are guys with the fewest scripts in the pipeline, and that tends to be late-night TV shows. So those guys really want this thing settled fast. They're in a weak bargaining position. On the other hand, there may be a reason why Labour's in a weak bargaining position. Why might Labour be in a weak bargaining position relative to management?
They have rents to pay.
Right, they have rents to pay. They have immediate demands on their cash. Right? The typical worker is typically poorer than your typical manager, not always, but typically. All right, and they just have to pay the rent. They have to feed their children. All right. So there's a more general idea there. More generally in bargaining, the people who are poorer typically this isn't just poor in terms of income; it's poorer in terms of wealth. Are going to be more impatient to get things resolved. And that's going to put them in a weaker bargaining position. So in bilateral bargaining, right, having low wealth and being known to have low wealth puts you in a weaker position. And that means that typically people who are poorer are going to do less well, although the late-night TV show may be an exception. All right? All right? Right, so you think a little bit about whether just setting up a bargaining position makes things equal for everybody. Right? Any other thoughts about who has strength and who has weakness in bargaining? What other kind of stunts do we see people do in bargaining? What else is kind of missing here that we need to think about? If we're, what we want to do in this class is develop these ideas and take them to the real world. So what other real world things here are kind of missing? Yeah.
Usually people will make their first offer a lot higher than what they're actually willing to accept.
Right, so typically you're right. Typically people come, typically bargaining isn't just a series of random numbers. Typically people start out high and then they concede towards the middle. Is that right? So if I'm the buyer, I start out with a low price and come up, and if you're the seller, you start off with a high price and come down. All right? So again, that seems to be about establishing reputation and trying to indicate how much I want this good. All right? There's something worth saying here, which we haven't got time to do in this class, and I hope you'll have time to take if you take the follow-up class 156. We can actually show formally that in a setting in which buyers and sellers are bargaining, and buyers and sellers do not know how much the good is worth to the buyer or how much it costs to the seller, typically you cannot expect to get efficiency. I'm going to say that again. Right? So it's kind of an important economic fact that's missing from 115 and unfortunately missing from this class. But if we go to a more real-world setting in which people's values are not known, not only are the offers not accepted immediately, and not only is there some inequity in that the poor tend to be more impatient and do less well, but also you get bad inefficiency. And the inefficiency occurs essentially because the sellers want to seem like they're hard, and the buyers want to seem like they're hard, and you get a failure for deals to be made. All right, so some deals are actually going to be lost or take a long time in coming. You're going to get some strikes before the deals occur, and that's all inefficient. All right, so bargaining, not in this model, but in the real world, tends to lead to inefficiency. All right, so I'll leave it there. We'll have an early-ish lunch since we're all starving. So today we have a lot of stuff to get through, but it's all going to be fairly formal. We're not going to have time to play a game today. Today's going to be a day when we have to learn some new ideas. So the reason we need to go through some new formal ideas today is we've kind of exhausted what we can do with the ideas we've gathered so far. So just to bring us up to date where we are, in the first half of the semester, so before the midterm, we looked at simultaneous move games. And one way to think about those simultaneous move games were games where when I make my choice, I don't know what you've done. And when you make your choice, you don't know what I've done. All right? And since the midterm, we've been looking at simple examples of sequential move games under perfect information, in which I typically do know what you did when I get to make my choice. All right? And you know I'm going to know what you did when I get to make my choice. And what I want to be able to do moving forward is I want to be able to look at strategic situations that combine those two settings. I want to be able to analyze games which involve both sequential moves and simultaneous move games. All right? And in particular, I want to see how we can extend the technique we've been focusing on for the last few weeks, which is backward induction. I want us to see how we can extend the notion of backward induction to cope with games where some parts are sequential and some parts are simultaneous. All right? So we're going to look at a lot of examples, and we're going to introduce some new ideas, and I'm going to try and walk you through that today. So that's our goal. Let's start with an example. So here's a very simple game in which player 1 moves first and has 3 choices. Let's call them up, middle, and down. And then player 2 moves, and player 2 has 2 choices from each of these nodes, and we'll call the choices suggestively up and down, and here we'll just call them left and right. All right, and the payoffs are as follows: 4, 0, 0, 4, 0, 4, 4, 0, 1, 2, 0, 0. So this is just a standard game of perfect information, much like all the games we've seen since the midterm. In fact, it's a relatively easy one. So we know how to solve this game. We solve this game using what? Using backward induction. And that isn't so hard here. We know that player 2, if player 2 finds herself up here, she will choose 4 rather than 0. If she finds herself here, she'll choose 4 rather than 0. And if she finds herself here, she'll choose 2 rather than 1. So player 1 won't want to go up here because he'll get 0. And he won't want to go into the middle because he'll get 0. And he won't want to go, but if he goes down, player 1 will choose left, and player 1 will get 1. So player 1 will choose down. So backward induction predicts that player 1 chooses down, and player 2 responds by choosing left. And just staring at this a second, notice that the reason in this game, taking a step back from backward induction a second, the reason player 1 did not want to choose either up or middle was because that move was going to be observed by player 2, and in either case, player 2 was going to crush player 1. Right? So if player 1 went up, player 2 was playing this sort of strictly competitive game with player 1, and player 2 could make a choice that gave 2 4 and 1 0. And conversely, if player 1 chose middle, player 2 could crush player 1 by choosing up, which gave, once again, player 2 4 and player 1 0. So there was a good reason here to avoid going into the part of the game following up or middle, and the reason was 2 has a huge second mover advantage in those parts of the game. That clear to everybody? So I now want to consider a similar but importantly different game. So I'm going to draw the game again. Well, before I draw it, let me say what I'm going to do. So I want to introduce a new idea, and the new idea is going to be that player 2 will not be able to distinguish between up or middle. So let's say it again. So if player 1 chooses down, player 2 will observe that, just as we've done before in our standard perfect information games. But if player 1 chooses either up or middle, I want to capture the idea that player 2 doesn't know which of those 2 choices was made. Right? That's clearly going to change the game a lot, and the first question is, how do we represent that idea in a tree? So let me try and show a good way to represent that in a tree. So the game has the same structure to it. Player 1 is, again, choosing between up, middle, or down, and player 2, once again, is choosing here up or down, and here left or right. And the payoffs haven't changed. They're still 4 0 0 4 4 0 0 4 1 2 and 0 0. So that's exactly the same as you have in your notes already. But now I want to adapt this tree to show how we indicate that player 2 cannot distinguish, cannot observe whether 1 chose up or middle, but can observe if player 1 has chosen down. And the way we do that, very simply, we draw a dotted line between the 2 nodes of player 2, between which 2 cannot distinguish. So this idea here, what this dotted line indicates, is that these 2 nodes are set in the same information set. So our new idea here is the idea of an information set. I did. Thank you. 0 4 4 0. Thank you, Dave. All right, payoffs are meant to be the same on the left as on the right. All right, so the idea here is that player 2 cannot distinguish these 2 nodes. Player 2 knows that she's in this information set. She knows that player 1 must have chosen either up or middle. She knows that player 1 did not choose down, but she doesn't know whether she's really here or here. Okay? Now, what happens in this game? This game is a very different game. Why is it a different game? Well, let's try and apply that loose intuition we talked about before. We said previously in the old game that if player 1 chose up, 2 knew that player 1 had chosen up and observed that by choosing down, player 2 could crush 1. And if player 1 chose middle, player 2 could observe that player 1 had chosen middle, and this time by choosing up, could crush 1. The problem is that now in this new game, player 2 doesn't know whether she's here, in which case she would want to choose down, or here, in which case she'd want to choose up. Right? So player 2's choice is not so obvious anymore. That simple backward induction argument has disappeared. Moreover, player 1 knows that player 2 will not be able to reserve between up or middle, so it isn't necessarily the case that player 1 will want to choose down anymore. It's still true that if player 1 did choose down, that player 2 would be able to observe that and will choose left. So that part of the argument's the same. What do we think is going to happen here? Well, we don't know, but let me give a suggestion what might happen here. Player 1 might say, hey, I could randomize between up and middle. I could choose half the time up and half the time middle. If I choose half the time up and half the time middle, player 2 isn't going to know, in general, isn't going to know what I've done. It isn't quite clear what player 2 is going to do. And since I'm randomizing between up or middle, whatever player 2 is going to do, I'm going to get half the time 4 and half the time 0 for an expected value of 2. Right, so said again, so player 1 might decide in this game to randomize 50-50 between up and middle, knowing that half the time, therefore, he will get 4, and half the time he'll get 0, for an expected value of 2, which notice is better than he got by choosing down. All right? So this change in this game, changing the information in this game, not only led to a different game, it led to a very different outcome. All right? So here, one might, for example, they might randomize between up and middle. And over here we know exactly what one does. One chooses down. One chooses down. So we get very different outcomes because of this change in information in the game. And the theme of today is that information is going to matter. The way we're going to model information is by thinking about these information sets, and as we go through today, I want to start giving you some formal definitions. So this is the idea. Now let's look at the formal definition. There's going to be a lot of writing today, so I hope you brought a notepad with some room on it. All right, so the first formal definition of the day comes off that last example. The formal definition is the idea that I want to capture the idea that players down the tree may not know exactly what was done up the tree. And the formal definition is going to go through the idea of an information set. So an information set of player I, in this case above player 2, but more generally of player I, is a collection, or a set if you like, it's a collection of player I's nodes between which, or I guess it could be more than 2, so let's say among which I cannot distinguish. All right. It's going to turn out that by clever use of information sets, we're going to be able to use our technology of drawing trees, to capture all sorts of interesting and increasingly complicated information settings. All right? In this particular game, it's the case that player 1 knew that player 2 was not going to be able to distinguish between up or middle in this tree, and player 1 knew that player 2 would be able to distinguish in the left-hand tree. We can even use information sets in a more elaborate tree to capture the idea that player 1 may not know what player 2 is going to know. But I won't do that now, I'll leave that later, and you'll see some examples of that on the homework. All right, so we have our formal definition. This is going to be the first of our big tools of the day, but let me just put down a few things that we have to be careful about, a couple of rules. So these information sets have to obey certain rules. And certain things are not allowed. Certain things are not allowed. So in particular, the following is not allowed. Here's a tree in which player 1 moves first, and player 2 does not observe player 1's move, so these two nodes are player 2's nodes, they're in the same information set, which means player 2 is not meant to be able to distinguish between these two nodes. And suppose, however, the tree looked like this. Okay, so I claim that this is crazy. We couldn't allow this. It wouldn't make any sense to allow this. Can anyone see why? Why is this not really a sensible tree? Anyone see that? Why is that not a sensible tree? Do you want to grab somebody? Yeah, Ali, there's just the guy behind you. Yeah, that's good. That's great. Shout out.
If player 2 knows that he has 3 choices, then he'll know he's at the top node.
Exactly, exactly. In this tree, you haven't put the payoffs in, but if player 2 observes that she has 3 choices, she knows she must be at the top node. If she observes she has 2 choices, she must be at the bottom node. Right? So in this tree, it was supposed to be the case that 2 didn't know whether she was here or here, but merely by observing how many choices she has, she could infer whether she was at the top node or the bottom node. So that can't make any sense. So this is not allowed. So we'll put a great cross through that one. Now the second thing that's not allowed is a little bit more subtle, and actually is an interesting thing. And this is just kind of bookkeeping, but the second thing's more interesting. So let's have a look at it. Here's a more interesting tree. Player 1 moves first. Player 2 observes that move. All right, and player 2 moves second. And then at the bottom of this, player 1 may have another chance to move again. So again, I haven't put payoffs in here. Player 1 moves first, player 2 moves second, and if player 2 chooses down here or up there, then player 1 gets to move again. Now I claim again that this is not a sensible tree. It's not a sensible arrangement of information sets. Can anyone see why this isn't sensible? Why is this not sensible? Yeah, Stephen, yeah. Shout it out.
Player 1 knows what node he's at based on the first choice that he made.
Exactly, exactly. So to get to the upper node here for player 1 must have chosen up before. And to get to the lower node here, player 1 must have played down before. So provided that player 1 remembers his or her own move, she knows where she is. Is that right? Right, so provided player 1 can recall what she herself did earlier on the tree, she should be able to distinguish these things. So we're going to rule this out, but I just want to make a remark here. There's an assumption in ruling it out, and the assumption is we're assuming perfect recall, or perfect memory. We're assuming perfect recall. And people don't always, in the real world, players don't always have perfect recall. There are 2 reasons, and we're always going to assume this, but let me just make a remark. There are 2 reasons why people might not have perfect recall. One reason is, like me, they're getting old. Right? They simply can't remember what they did yesterday. All right, so when I'm driving home, I know roughly how many traffic lights I have to go through before I turn right, but I sometimes forget which traffic light I'm at, and I turn right too early, or too late. All right? That doesn't happen to you guys, but it happens to me as I'm getting a bit senile. All right? So old age would rule out perfect recall. A more important example, perhaps, is if players of games are themselves institutions. It's sometimes useful, and we've often talked about it in this class, to imagine a player of a game being a firm or a country or some kind of institution in which the actual decisions may be being taken by different actual people within the firm, institution or country. Right? And this assumption of perfect recall is saying that the players within the institution knew what the other players within that same institution were doing. Right? So if we're modeling General Motors as one player, this assumption is assuming that the chief financial officer and the chief executive officer of GM are observing each other's actions, are on the same page. The left hand knows what the right hand's doing. All right? We are typically going to assume that, but just to make the point, it is an assumption. All right? And it's quite interesting to see what happens if you relax it. All right, so with that in mind, we can move to our next definition. And this is something I've referred to early on in the class, but I want to be formal now. Now we can be formal. We've talked earlier on in this class about the idea of perfect information. So, for example, when we talked about Zermelo's theorem, we talked about games of perfect information. And we said informally what this was. A game of perfect information is a game where each player in the game can observe all previous moves. Right, that was our informal definition, but we can now give a formal definition very simply. Perfect information is a setting where all information sets in the tree Games of perfect information are games where all information sets in the tree contain just one node. All right, I want to be clear here. So what we're saying here is if we have a tree in which every information set is a singleton, we basically never bother with any dotted lines, that's a game of perfect information, and that shouldn't be a surprise to anybody here, because that's exactly how we drew trees since the midterm. Is that right? Of course, the novelty is we're now going to be allowed to look at games of imperfect information. Right, the reason we're doing this is because it will be interesting, as in the example we just seen, to think about games where information is not perfect. So what is the definition of imperfect information? Imperfect information, formal definition, is not perfect information. All right, we've defined what perfect information is. Imperfect information is the rest. All right, in the real world, there's a lot of games that turn out to have imperfect information. There's lots of strategic situations where I'm going to be able to observe some things that you've done, but other things I won't know quite what you've done. All right. Okay, let's go straight to an example. All right, so I don't think we really need to keep that definition very focal, so let's get rid of that board. All right, let's do an example. There are many examples today. All right, so this example is going to be a tree in which player 1 moves first. Player 2 cannot observe this move, and sometimes, rather than labeling both of these nodes with a 2, I'll just put a 2 on the information set, right, so just to indicate that both of these nodes belong to player 2. So player 2 moves second, and we'll call player 1's move up or down, and we'll call player 2's move left or right. Kind of suggestively, left or right. Okay. So what's the information set here? The information set is indicating the fact that player 2 cannot observe whether player 1 moved up or down. Player 2 cannot observe whether player 1 chose up or down. All right, now why does that matter? I haven't put the payoffs in yet, but I will in a second. It matters because had this game been a game of perfect information, had this information set, had there been two information sets here, this dotted line not been there, then player 2 could have chosen separately whether to choose left or right at this node, or left or right, and left or right at this node. But since player 2 doesn't know whether she's at the upper node or the lower node, she doesn't know whether player 1 chooses up or down, she really only has one choice to make here. She's either choosing left at both nodes, or she's choosing right at both nodes. And just to pull it back to our first example in the class, we saw the same feature there. When we moved from a game of perfect information to a game of imperfect information, we reduced the choices available for player 2. Here, player 2 could choose separately up or down at these two different nodes, but here, player 2 only makes one choice that has to apply to both nodes, because player 2 cannot distinguish those two nodes. All right? So let's have a look and see, once we put some payoffs on, what it does in this particular game. All right, so here's some payoffs. 2, 2, minus 1, 3, 3, minus 1, and 0, 0. All right, so once again, player 2 cannot separately choose at the upper node or the lower node. She's either choosing left or she's choosing right. But it turns out that this game is a little easier than the game we started with. Why is it easier than the game we started with? It's easier than the game that we started with because, from player 2's point of view, whether she thinks she's up here or whether she thinks she's down here, she has the same best choice in either case. If she thinks she's at the upper node, then by choosing left she'll get 2 and right she'll get 3, so right seems better. If she thinks she's at the lower node, then choosing left gets minus 1 and right gets 0, so once again right is better. So in fact in this particular game, regardless of whether player 2 thinks that player 1 chose up
and hence she's at the upper node, or whether player 2 thinks that player 1 chose down, and hence she's at the lower node, player 2 is going to make the same choice in this game, namely right. So notice that this particular game actually solves out rather like backward induction. Rather like backward induction. We actually know, even though player 2's choice is a little bit more complicated because she doesn't know where she is, it's actually clear what player 2 will do at this information set. Now if we push this forward a little bit harder, we can see why. Player 1 in this game has 2 strategies, up or down, and player 2 has 2 strategies. She either chooses left or right. Notice she only has 2 strategies because she has to choose the same thing at these 2 nodes. She doesn't know where she is. All right? Okay, so let's draw up the matrix for this game and see if it looks familiar. All right, so player 1 is choosing between up or down, and player 2 is choosing between left or right, and the payoffs are as follows. Up left is 2, 2. Up right is -1, 3. Down left is 3, -1. And down right is 0, 0. All right? Down right is 0, 0. So what game is this? It wasn't meant to be a trick question, so somebody wave their arm in the air. What game is this? Shout it out if you like. This is Prisoner's Dilemma, right? This is an old friend of ours. This is Prisoner's Dilemma. A game we saw the very first day. But notice, what have we seen here? This is Prisoner's Dilemma that we have seen many, many times. That's almost unbearably familiar to most of you. Right? And here's Prisoner's Dilemma as represented the way in which we talked about games before the midterm. But here is the same game. This is also Prisoner's Dilemma, but now I've drawn in a tree. Here I drew it in a matrix, and here I drew it in a tree. Now that we have information sets, we can represent all the games that we studied before the midterm, all the games that were simultaneous move games, we can study using trees by building information sets. And what's the key observation here? It doesn't really matter whether player 1 moves first or player 2 moves first. It doesn't really matter what's happening temporally in this game. What matters is information. When player 1 makes her move, she doesn't know what player 2 is going to do. All right? Or she doesn't know what 2 is doing. And when player 2 makes her move, she doesn't know what 1 is doing. Right? And that's a simultaneous move game, even if time is passing. The key is information, not time. All right? Now, on the way here, I snuck something in. And I should just tell you what I snuck in. I snuck in what a strategy is. I went from a tree, or an extensive form game, to a normal form game. And we've already done that a couple of times before in the class. We did it with the entry game, for example, about a week ago. All right? But there, all we did was we defined what a strategy was in a game of perfect information. And just to remind you, a strategy in a game of perfect information is a complete plan of action. It tells the player in question what they should do at each of their nodes. All right? But now, we have to be a bit more careful. We can't have a strategy, once we move to imperfect information, we can't have a strategy tell you what to do at each of your nodes, because you yourself can't distinguish between those nodes. All right? So we need to adapt our notion, our definition of a strategy to make it appropriate for these more complicated games. So let's just adapt it in the obvious way. Definition. I'll just define pure strategies for now. A pure strategy of player I is a complete plan of action. So this is the same as before. It's a complete plan of action. It's a complete plan of action. But what does it mean to be a complete plan of action? It can't tell me what to do at every single node. That can't be the right definition because I can't distinguish nodes. So all it can be doing is telling me what to do at each information set. All right, so it specifies what player I should do. Should perhaps is the wrong word. Let's just say will do.
will do at each of I's information sets. All right? So you go back about a week, you'll see almost exactly the same definition of a strategy, but the previous definition told I what to do at each node, and this one just tells I what to do at each information set. What I'm doing is tidying up the previous definition so we can apply it to the more interesting games we're going to look at from now on. All right, so now we have the definition of a strategy. We can carry on the idea we've just seen here. So what's the idea here? Any game you give me in the form of a tree, I can rewrite the game in the form of a matrix. All right, so let's see some other examples of that idea. A lot of new ideas today, but some of them are just tidying up and kind of bookkeeping, and some of them are more interesting. All right, so let's start with a tree. Let's make it a slightly more interesting tree than the one we've seen before. Actually, that's too interesting. Let's go a little bit slower. So let's have player 1 have 2 choices, and player 2 have 3 choices. All right, so here's a simple tree, and let's put some payoffs in, but let me just put some letters in for payoffs rather than put in numbers. All right, so we'll call these actions up and down, and we'll call this action left, middle, and right, and left, middle, and right, and we'll call the payoffs A1, A2, B1, B2, C1, C2, D1, D2, E1, E2, and F1, F2. All right, so just to keep track of it. And I want to show you how we take this tree and turn it into a matrix. All right? So how do we turn it into a matrix? Well, we look and say, how many strategies has player 1 got, and how many strategies has player 2 got? So player 1 here just has 2 strategies, up or down, and player 2 has 3 strategies, either left, middle, or right. Again, they can't choose separately at these 2 nodes, so they really just have 3 choices, left, middle, or right. So leave a space here in your notebook, leave a space to the right here, and let's draw the matrix for this tree down here. All right, so here's my matrix. Player 2 is choosing left, middle, or right, and player 1 is choosing up or down. All right, and the payoffs go in the obvious way. So A1, A2, B1, B2, C1, C2, D1, D2, E1, E2, and F1, F2. All right, so everyone understand that was just a simple exercise to show we can go from an extensive form, a tree, to the normal form, the matrix. All right. However, okay, so that was easy, right? However, there's an interesting thing here. It isn't obvious that this is, if I just gave you the matrix, it isn't obvious that this is the tree from which it came. Let me draw another tree that I claim corresponds to that same matrix. Right? Here's another tree. So this other tree, instead of having player 1 move first, it's going to have player 2 move first. Player 2 better have 3 choices, and we better call them left, middle, and right. And it better be the case that player 1 is in one big information set, and player 1 only has 2 choices, which we'll call up and down. All right, that's what this matrix is telling us. It's telling us player 2 had 3 choices, and player 2 had 3 choices, and player 1 had 2 choices. So that's true in the matrix I've drawn. And let's be a little bit careful where the payoffs are. So left up, that's easy. That's going to be A1, A2. Left down is going to be D1, D2. middle up is going to be B1, B2. Middle down is going to be E1, E2. Right up is going to be C1, C2, and right down is going to be F1, F2. All right, so I have to be a little bit careful where I put the payoffs, but I think that's right, what I just did. And notice that what I did here, I started from this tree. It was an easy operation to construct the matrix, so easy that it was kind of boring. And it's not that hard to see that I can go the other way and construct this other tree from the matrix. This is also a tree in which player 2 has 3 strategies, and player 1, this is all player 1, has 2 strategies. All right, so what? Well, what do we learn from this? All right, well, let's look at this more carefully. This tree is a tree in which player 1 moved first, and player 2 didn't observe player 1's choice. Is that right? This is a tree in which player 2 moved first, and player 1 didn't observe 2's choice. Right? What are we noticing here? They're really the same game. There's no difference between these two games. All right? They're really the same game. It doesn't matter whether it's player 1 moving first and player 2 who's unable to observe 1's choice, or whether it's player 2's moving first and player 1 who is unable to observe 2's choice. Right? All that matters is that neither player could observe the other person's choice before they got to move. They both correspond to exactly the same game. All right? So what's the message here? The message is something we've talked about before in the class, but I'm trying to make it a bit more formal about it. The message is that what matters is information. What matters is information, not time. Not time. Clearly, time isn't an irrelevant thing. I couldn't know something that hasn't happened yet. All right, so time is going to have effects on information, but ultimately what matters is information. What do I know, and when did I know it? All right? So the key idea that we're trying to capture with these information sets, just to repeat, is what did the player know, and when did they know it? Right, that famous expression from the Watergate trials. All right. Okay, let's look at a more interesting example and see if we can actually talk about what's going to happen in these games. So by the end of today, I want to have enough machinery so we can actually start analyzing these games and predicting what's going to happen. All right, so as we go on, we'll get more complicated, so let's get a little bit more complicated now. Once again, here's a game in which player 1 is going to have 2 choices, and we'll call those choices up or down. It's getting a familiar theme. And once again, player 2 is going to move next, and now this time, just to keep things simple, we'll have player 2 just have 2 choices, left or right, or left or right. But now to make things more interesting, let's have player 1 move again. So if up right happens, then player 1 gets to move again, in which case player 1 is going to choose up or down. And I'll use a little u and a little d to distinguish it from the ones further to the left of the tree. All right, so this is a very simple tree. Player 1 moves first, player 2 moves second. I forgot to put a 2 in here. And then if up right has occurred, then player 1 gets to move again. Let's put some payoffs in. So let's have this be 4, 2, 0, 0, 1, 4, 0, 0 again, and 2, 4. All right, let's just carry on analyzing this game using exactly the methods we've been talking about in the class today so far. So the first thing I'm going to do is I want to turn this into a matrix. I want to turn this into a matrix. And the first thing to do on that route is to try and figure out how many strategies does player 1 have and how many strategies does player 2 have. All right? And before we even do that, let's try and figure out how many information sets they have. All right? So I claim that player 2 just has the one information set. Is that right? Player 2 just has the one information set. but player 1 has 2 information sets. This information set at the beginning of the game, and then potentially the second information set further down the tree. All right? A strategy must tell the player what to do at each of their information sets. So the strategies for player 1 are what? Well, one strategy is up and then up again. Another strategy is up and then right. Another strategy is down and then up. And a fourth strategy is down and then right. And notice something which we've seen already in this class before. There's a little bit of a redundancy here. These two down strategies force the game into a part of the tree where this node will not arise. But put less grandly, if player 1 chooses down, she knows that she won't have to make a choice of up or down later on. Jake. Thank you. Sorry, thank you. Thanks, Jake. All right, let me start again since I did the wrong notation. All right, so player 1's choices are up and then up, up and then down, down and then up, and down and then down. Thanks, Jake. Sorry. All right. Now, why are there 4 strategies? It's a bit of a surprise, perhaps, because if player 1 chooses down, then she knows she will never have to make a choice at her second information set. Nevertheless, we write down when we write down a strategy, we have to write down an instruction for every single information set, so we include both of those strategies. Strategies for player 2 here are a little bit easier. Strategies for player 2 are just left or right. All right. With that in mind, let's draw up the matrix. So player 1 here has 4 strategies, and they are up, 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 down, down, up, and down, down. And player 2 has 2 strategies, and they are left or right. All right, everyone okay so far? We're just basically transferring things across. And now we have to transfer the payoffs across. So up, up, followed by left is going to be 4, 2. Up, up, followed by right is going to be 0. So up, up, right. It's very easy to think of as up, right, up. So up, right, up is 0, 0. Up, left, up, down, left is the same as up, left, down. So it's again 4, 2. Up, down, right is going to be up, right, down. So it's going to be 1, 4. Down, up, left is the same as saying down, left. So it's going to be 0, 0. All right. Down, up, right is going to be 2, 4. Down, down, left is once again going to be 0, 0. And down, down, right is once again going to be 2, 4. All right, does everyone see how I got the payoffs? I just used those strategies to tell me which way I'm going through the tree. If I combine them, it gives me an entire path and gets me to an end node. All right, and you can see this redundancy we talked about. We pointed out that these things are kind of the same thing, and you can see in the matrix that the bottom 4 squares of the matrix have repetition. Right? This row is the same as that row. All right, everyone happy with that? Okay, we have a matrix. Let's analyze it by finding the Nash equilibria in this game. All right? So to find the Nash equilibria in this game, we're going to find best responses. All right, so let's start by asking, what is the best response to left? So if player 2 chooses left, player 1's best response is either up, up, or up, down. If player 2 chooses right, then player 1's best response is either down, up, or down, down. All right, everyone okay so far? All right. If player 1 chooses up, up, then player 2 is going to choose left. If player 1 chooses up, down, then player 2's best response is to choose right. If player 1 chooses down, up, then player 2's best response is to choose right. And if player 1 chooses down, down, then player 2's best response is to choose right. All right, so this is kind of slow, and I just want to be careful. I'm going slow for a reason. We're going to gradually get harder. I want to be a little bit careful. I can see people looking a little sleepy around the room. I know it's kind of lunchtime. If you see your neighbour getting sleepy, give them a good sharp elbow, because I think this isn't a good time to fall asleep. In some sense, I'm worried you're going to miss something, and it's then going to get harder and you're going to miss things. All right, so what are the Nash equilibria in this game? We know how to do that. The Nash equilibria must be up, up, followed by left. Should I get them all? Down, up, followed by right. And down, down, followed by right. I want these 3 Nash equilibria. Okay, so that wasn't such a big deal. I got 3 equilibria in this game, and if I'd simply given you this game in the first half of the semester, I hadn't shown you the tree, you've never seen this tree, I just gave you this game, and said find the Nash equilibria in this game, and that'd have been a question on the midterm, we'd have stopped here. Right, we'd have said, okay, I found these Nash equilibria, maybe you'd have gone on and found mixed ones, I don't know, but essentially we'd be done at this point. Right? Let's say again, if we'd started, as we would have done before the midterm, with me giving you a payoff matrix and asking you to find the Nash equilibria, then at this point we'd be done. We'd have found the 3 Nash equilibria, it's the 3 pure strategy Nash equilibria. The problem is, if we go back to the tree, to the dynamic game, the game that has some action going on in it, and actually look at this game, it's not clear that all of these Nash equilibria are really equally plausible. All right? Can anyone see what might be a bit implausible about some of these Nash equilibria? What's implausible about them? Any takers on this? Well, let's look at this game again. Right, this game is a little bit complicated. It's not clear what one should do here, perhaps. And perhaps it's not clear what player 2 should do here, because after all, player 2 doesn't know where he is, and he doesn't know whether player 1, if player 1 gets to move again, is going to choose up or down. But, what's the but? Yeah, can we get a mic on Patrick?
Yeah, so if you look at it backwards, you can cross out player 1's second choice. He's always going to choose down, so
Good.
that's 1-4 at that node.
Good.
So then you know player 2 is always going to choose right because his payoff is always 4.
Good.
So then player 1's not going to have, player 1 knows which to choose then. He's going to choose down.
Good, good. So let's just walk through what Patrick just said. That's very good. So if we just analyze this game the way we've been taught to analyze trees, essentially using backward induction, we first of all observe that if player 1 gets to move again here, she'll know where she is, and she'll know she's choosing between 1 and 0. She's going to choose down. Is that right? She's going to choose down. But knowing this, player 2, even though player 2 doesn't know where he is, player 2 actually has a pretty easy choice to make. He knows that if he chooses left, he either gets 2 or 0, but if he chooses right, he gets 4. Right? 4 is bigger than 2, 4 is bigger than 0, so player 2 is actually going to choose right. And given that player 2 is going to choose right, player 1 is essentially choosing between 1, if she chooses up, which would be followed by right and down, and 2, which would what happens if she chooses down, followed by right. So this game we can essentially analyze through backward induction. It's not quite backward induction because we had to add in this little piece about 2 not knowing where she was, but it turned out no matter where she was, she had a dominant strategy, she had a better strategy once she figures out that player 1 is going to choose down. Is that right? If we go back and look at these Nash equilibria, the prediction that we just got, which is what? Down for player 1, right for player 2, and then down again for player 1, all right? That strategy is this one. Right? So one of these Nash equilibria corresponds to our sensible analysis of this tree. But the other 2 do not. These 2 Nash equilibria are inconsistent with backward induction. Right? They're inconsistent with backward induction. Right? They're perfectly good Nash equilibria. If we'd given you this matrix at the midterm, you'd have thought they're just fine. But it turns out both of these Nash equilibria involve player 1 choosing a strategy up that we know that player 1 is not going to do if reached. And one of these Nash equilibria involves player 2 choosing a strategy left that in fact she's only choosing because she thinks player 1 is going to choose up, which in fact we've just argued player 1 is not going to do. All right? The people at the back, there's a little bit too much volume bouncing off the wall there, so just keep it down on the balcony. Thank you. All right? All right? So these two Nash equilibria, they're perfectly good Nash equilibria of the game, but they don't make any sense. Right? They're completely inconsistent with the way we've learnt to talk about games. All right? Now, we've seen this before. We saw it on the entry game. This is a much more complicated, much more interesting example, but we saw in the entry game, when there was one entrant entering into a market, that in that game there were actually two Nash equilibria, and one of them, we argued, was incredible. Here it's a bit more complicated, but nevertheless, these two equilibria seem like bogus equilibria, or phony equilibria, or equilibria we wouldn't really believe in. And the reason we don't believe in them is that they don't correspond to backward induction and our common sense intuitions about backward induction. All right? So we need some new notion. The aim of the class has been what? We want to be able to model games that have both sequential moves and simultaneous moves, and we want to be able to look at the games and use our techniques from both halves of the class. We want to be able to use the idea of Nash equilibrium from the first half of the class, and we want to be able to use the idea of backward induction from the second half of the class. But what we're learning here is that Nash equilibrium, if we just take the notion of Nash equilibrium and plonk it down on these sequential move games, it will produce equilibria that don't make any sense. So we need a more refined notion of equilibrium, a better notion of equilibrium than just Nash equilibrium to deal with these settings where we have both simultaneity and sequential moves. We have both some perfect information and some imperfect information. All right, that was one example. Let me give you a second example if that example wasn't yet convincing. All right, let me leave that example up. So far, we've seen that Nash equilibrium gets us into trouble in these games, and we've seen it got us into trouble because it basically conflicted with our backward induction intuitions. Now I'm going to show you a different game, and we're going to see it again. Nash equilibrium is going to get us into trouble. All right? This is going to be a three-player game. We'll get more complicated as we go along. So another example, this time with 3 players. So as the examples get harder, I need you to be more alert to see if you can follow them. All right, so this a more complicated tree. Here's a tree in which player 1 moves first and chooses between A or B. And if player 1 chooses A, the game is over. She gets 1, and the other 2 players get nothing. If she chooses B, then players 2 and 3 get to play a little game down here, in which 2 moves first in this little sub-game, and 3 moves second. And the payoffs in this sub-game are as follows. Again, using player 1's payoff first. So there's 0, 1, 1, 0, 0, 2, 0, 0, minus 1, and 2, 1, 0. All right? So this is quite a complicated game. It's got 3 players for a start, so it's going to be a little bit hard to draw it up in a matrix. But nevertheless, let me try and do that. So I claim that we can model this game as follows. It's a game in which player 1 is choosing which matrix. Let's call this matrix A and matrix B. Player 1 is choosing the matrix. Player 2 is choosing, let's call them up and down. Player 2 is choosing up or down, and player 3 is choosing left or right. All right, and notice in this game, players 2 and 3 actually can observe the choice of A or B to start with. All right, so let's try and put in the payoffs in the correct places. It's not always easy to do, but let's try. So A is easy. If player 1 chooses A, then the payoffs in this matrix are somewhat trivial. Because if player 1 chooses A, whatever anyone else does, the payoff is 1, 0, 0. All right? So somewhat uninteresting matrix over there. But if player 1 chooses B, then life gets more interesting. Then if player 2 chooses up and player 3 chooses left, we end up here. So that's 0, 1, 1. If player 2 chooses, this is 2 and this is 3. This is 2 and this is 3. If player 2 chooses up and player 3 chooses right, then we're at 0, 0, 2. All right, so this is 0, 0, 2 going in here. If player 2 chooses down and player 3 chooses left, then we're at 0, 0, minus 1. Everyone okay with that? And if player 2 chooses down and player 3 chooses down, then we're down here, which is 2, 1, 0. All right? Okay, so here's a little game. Player 1 is choosing the matrix. Player 2 is choosing the row in the matrix, albeit trivially on the left-hand side. And player 3 is choosing the column in the matrix, again, albeit trivially on the left-hand side. We don't really care about this picture very much. All right? Okay, so now what? Now what? Well, once again, we could look for Nash equilibria in this game. It turns out there are lots of Nash equilibria in this game. Let me just show you one Nash equilibrium, and then we'll talk about it. All right, so I claim that there are lots of Nash equilibria, and one of them is the Nash equilibrium A up, left. A up, left. So let's just see what that is in the tree, first of all. So player 1 chose A. Player 2 chose up and left, but it followed A, so we end up here. We end up at 1, 0, 0. All right? All right, so A up left is this box in the tree. All right? Now let's just check that that actually is a Nash equilibrium. All right, so we all know how to do this from the first half of the class. To check that that's a Nash equilibrium, we better check that no individual player can do better by deviating. So let's start with player 1. If player 1 deviates, holding player 2 and 3 fixed, then player 1 will be switching the matrix from matrix A to matrix B. Is that correct? All right, so we'll move from this box in the left-hand matrix to the equivalent box in the right-hand matrix. All right? And player 1's payoff will go from 1 to 0. From 1 to 0. So player 1 doesn't want to deviate. Everyone happy with that? Player 1 doesn't want to deviate here. How about player 2? If player 2 deviates, holding players 1 and 3 fixed, then player 1 is going to switch rows in this matrix. So we'll move from this box to, from this box to this box. Player 2 was making 0 before. She's still making 0, so she has no incentive to deviate. And the same argument applies for player 3, because she will be choosing the column, holding the row and the matrix fixed, so once again, she gets 0 in either case. All right, so everyone happy with that? So that actually is a Nash equilibrium. And again, if this had been the midterm, I could have set this up, I could have given you these matrices, or the story behind them, and you'd have found this, I could have asked you whether this was a Nash equilibrium, and the answer would have been yes. But I claim that, once again, this is just not a believable Nash equilibrium. It is a Nash equilibrium. Formally, it's a Nash equilibrium. But it's not a plausible prediction for how this game's going to be played. Why is it not a plausible prediction for how this game's going to be played? Anyone see? Stare at the tree a bit. Right? So in the information here, in the pre-midterm information, it's fine. But knowing about the actual structure of this game, I claim this makes no sense at all. Why does it make no sense? Well, notice that if player 1 were to switch her action from the prescribed action A to action B, then we'd be here. All right? And notice that the tree from here on in looks like a little game. Is that right? The tree from here on looks like a little game. All right? So this thing here, let's put it in green, this thing here is a little game within the game. It's a sub-game. All right? And this sub-game really only involves 2 players. The 2 players that it involves are players 2 and player 3. Player 1's done. Player 1's put us into this game. But now in this little sub-game, it's a little sub-game involving just player 2 and player 3. So we can analyze this little sub-game. If we analyze this little sub-game, what will it give us? What will we find? All right? So let's look at this sub-game. So look at the green sub-game. The game that would have happened had player 1 chosen B. This is a sub-game involving just players 2 and 3, so why don't I just forget player 1? All right, we know what, player 1 is part of the game, he's getting payoffs, but player 1 has made their move, they're not really involved anymore. So let's just look at this game as a game involving players 2 and 3, and let's look at the matrix for players 2 and 3. So this is actually it corresponds to the matrix above. It's a matrix in which player 2 is choosing up and down. Here it is, up and down. And simultaneously, player 3 is choosing left or right. Here it is, left or right, at this information set. And the payoffs are 1, 1, 0, 2, 0 minus 1, and 1, 0. All right. All right. So this is, I claim, a representation of this little green game. Perhaps we should put this in green as well. All right, this thing corresponds to that thing. All right, everyone okay with that? All right. So if player 1 had chosen B rather than A, then we'd be involved in a little game, a game within a game, or a sub-game involving just players 2 or 3, and we can analyze that game. That's a straightforward game. Here it is. And what would we do with that game? We'd look for the Nash equilibrium in that game. So let's look for the Nash equilibrium in this game. So what do we notice about this game? So if player 3 chooses left, then player 2 would rather choose up. If player 3 chooses right, then player 2 should choose down. If player 2 chooses up, then player 3 would rather choose right, because 2 is bigger than 1. And if player 2 were to choose down, then player 3 would choose right again, because 0 is bigger than minus 1. All right? So in fact, in this little sub-game, actually, player 3 has a dominant strategy. Right? If it turned out that we got involved in this little sub-game, player 3 has a dominant strategy, which is to play right. And moreover, this sub-game has just one Nash equilibrium. If I'd given you this sub-game on its own, it's clear that the Nash equilibrium of this sub-game, or this game within a game, is down right. It's down right. So what's that telling us? It's telling us if player 2 and 3 ever get called upon to play in this game, and that only happens when player 1 chooses B, if player 2 and 3 ever get called upon to play in this game, we know from when we were young, or at least from before the midterm, we know that they're going to play Nash equilibrium in that sub-game, and the Nash equilibrium in the sub-game is going to have player 3 choosing right, and player 2 choosing down. right? But the equilibrium we talked about, this equilibrium we argued before about, AUL, the equilibrium we talked about before, AUL, doesn't involve player 2 choosing down. In fact, she chose up. And it doesn't involve player 3 choosing right. In fact, she chose left. All right? So let's sum up. We found an equilibrium of this game. This equilibrium of this game was AUL. But I claim this is not a plausible equilibrium. It's not a plausible equilibrium because it predicts that if we actually were to play the game within the game, we wouldn't play equilibrium. Let me say it again. In the whole game, A up left is an equilibrium. But I claim it's a silly equilibrium because it involves the prediction that if in fact we ever got into the game within the game, we would no longer play equilibrium. And that doesn't seem right. If we're going to believe in equilibrium, we should be consistent and believe in equilibrium throughout. All right? So this brings us to a new idea. Right? And the new idea is going to have two parts to it. The first part is kind of on the board already. It's something we talked about informally. It's the notion of a subgame. It's the notion of a subgame. Right? What's a subgame? It's a game within a game. All right? I've been using that informally, but we need to start thinking about more formally what it means. All right, so I talked about it informally. I said that green object is the game that would be played were player 1 to choose B. And we talked about other subgames in this class. We talked about the subgame that would happen in the entry game if one of those rival pizza companies moved in the Miami market or something. There was a game within a game. When we talked about the Tour de France, we talked about there being a game within a game that is about when you break away. But now I want to be formal about this notion of a game within a game and introduce some nomenclature. So the formal definition is this. Definition: a subgame is a part of a game informally that looks like a game within the tree. And it has three properties. It satisfies the following three properties. So one, since it looks like a game itself, the subgame must start from a particular point. Right? So it starts, the subgame must start, it starts from a single node. And let's just look at the example. In the example we just looked at, the subgame started from this node here. Second, it comprises all successors to that node. So in our example, here's our subgame, here's our green subgame. Here's the node it starts from. Here are all the nodes that are successors of that node. These are the children, and these are the grandchildren. Right? If you have this grandparent node, you have to have all of his children and all of his grandchildren. All right? So it comprises all the successors of that node. And finally, and this is important, it does not break up any information sets. It does not break up any information sets. So a subgame, Informally, it's just a little game within the game. But slightly more formally, I can't put one node that's part of an information set into this subgame unless I'm going to put all the nodes that are part of that information set into the subgame. All right, let's have a look at some examples. We've got one example up there. The entry game looked something like this. Right, the entry game looks something like this. So what are the subgames here? So no secrets here. This is a subgame. Right? There's actually another subgame. You want to see what the other subgame is? The whole game is a subgame. All right? The whole game is itself a subgame. Somewhat trivially. All right? So this particular game, which is the schematic of the entry game, it has actually two subgames, but only one proper subgame. Here's a more complicated example. All right, this is actually going to be quite a complicated example, just to make life interesting. So 1 is going to move, then 2 is going to move, and then 1 is going to move again. This is all one big information set for player 1. And 1 is going to move like this. So again, without payoffs, this is a little tree, and the key point here is this is an information set. All right, let's stare at this tree a second and figure out what are and are not subgames. So first of all, this was a subgame and this was a subgame. What about this thing here? Is that a subgame? It's not a subgame. What rule does it break? It's breaking up an information set, right? It's breaking up an information set. So that's no good because of rule 3. What about this thing? That doesn't break up an information set. I've got the whole information set in there. Is that any good? No, that's no good because it doesn't start from a singleton node. That's no good. It violates 1. And if we do this, if we look at this piece, that piece there, that's also no good. Why is that no good? Again, it breaks up an information set. All right, so this is no good again because of rule 3. All right, so you can practice at home drawing trees and trying to identify what are and what are not subgames. All right, so with the definition of a subgame now formal, right, it's basically just formalizing something we've talked about before, which is the idea of a game within the game. I want to introduce what's going to be our new solution concepts. And this is going to be the solution concept we're going to use, essentially, almost until the final. Definition. So just remember what our task is. Our task is to come up with a solution concept that picks up the idea from the first half of the semester, namely Nash equilibrium, but does so in a way that respects what we've learned in the second half of the semester, namely that games have sequential elements and people move by backward induction. So in particular, what we want to rule out are those Nash equilibria that instruct players down the tree to play in subgames according to strategies that are not Nash equilibria. Say it again. We want to rule out those Nash equilibria that instruct people way down the tree to play according to something which is not a Nash equilibrium. We want our new notion to say, wherever you find yourself in a tree, play Nash equilibrium. And that's exactly what the definition is going to say. So a Nash equilibrium, NE, S1 star, S2 star, all the way up to Sn star, is a subgame perfect equilibrium. It's a subgame perfect equilibrium, so that's an SPE. It's a subgame perfect equilibrium if it induces a Nash equilibrium in every subgame of the game. All right, so a subgame perfect equilibrium, it has to itself be a Nash equilibrium, of course, but it also has to instruct players to play a Nash equilibrium in every subgame. Let's take that immediately back to our examples. In this example, we know, let's bring it down, in this example, we know that this is a subgame. We know that in this subgame there is only one Nash equilibrium, and that Nash equilibrium involves player 2 choosing down and player 3 choosing right. All right, so we know that player 2 is going to choose down according to that equilibrium, and player 3 is going to choose right according to that equilibrium. So if we now have to look for an equilibrium of the whole game, let's go back to player 1's choice. Player 1, if they choose A, will get 1. If they chose B, then they know that this Nash equilibrium will be played, so they'll get 2. They prefer 2 to 1, so the subgame perfect equilibrium here is player 1 chooses B, player 2 chooses down, and player 3 chooses right. This is an equilibrium of the game, and it induces, here it is, it induces an equilibrium in the subgame. All right, so in that example, the subgame perfect equilibrium is found by first of all looking in the subgame, find the equilibrium in the subgame, and then go back and look at the equilibrium in the whole game. The equilibrium we end up with, it is a Nash equilibrium in the whole game, but more importantly, it induces a Nash equilibrium in the subgame. Let's just go back to our other example, then I'll stop. So our other example was here. Here was our other example. And we claimed, hang on everybody, we claimed that the good equilibrium here, the one we believed in, was down, down, right. All right? Where are the subgames in this game? Where are the subgames in this tree? Anybody? So I claim there's only one real subgame here, and that's this piece. All right? This is a subgame. All right? What's the Nash equilibrium of this somewhat trivial subgame? The Nash equilibrium of this somewhat trivial subgame is that player 1 must choose down. So for a Nash equilibrium to be a subgame perfect equilibrium, here are our 3 Nash equilibria, 1, 2, 3. For this Nash equilibrium to be a subgame perfect equilibrium, it's got to instruct player 1 to choose down in the trivial subgame. And here it is. This is our subgame perfect equilibrium in this game. Now I know today was a lot of formal stuff, a lot of new ideas. When we come back on Monday, we'll first of all give you a game that refreshes these ideas, and then we'll go straight to applications. So trust me, there will be applications. It will be useful. See you on Monday. There's a homework to come in, and there's another one on. So last time we covered a whole bunch of new ideas, and it was really quite a lot of ideas for one class. Here's some of the ideas we covered. We talked about information sets, and these were ways to allow us to model imperfect information. So what's imperfect information? It's a way of being able to capture both simultaneity in moves and sequential moves in the same game. So it's a way that's going to allow us to meld the lessons from before the midterm and after the midterm. Then we talked about what strategies meant in this context, and the basic idea is strategies are instruction. A strategy for each player gives them an instruction at each of their information sets. Then we talked about what subgames were, and leaving aside the technicalities, subgames were just games within games. And finally, we introduced the idea of subgame perfection, which is our new solution concept that refines the idea of Nash equilibrium. And what subgame perfection is going to do is it's going to instruct the players to play a Nash equilibrium in every subgame. Another way of saying it is, a subgame equilibrium is a Nash equilibrium in the whole game, but in each subgame, it induces Nash play as well. All right? Now we're going to see today examples. If we have time, I'll go through 3 different examples, and I'll tell you at the end of each example what it is I'm hoping to be the takeaway from that example. All right, so last time was a lot of formal stuff. Today's going to be a lot of examples. Okay. That's our agenda. Here's a game. Here's our first example. And I call this game Don't Screw Up, for reasons we'll see in a minute. All right, so this is a game in which player 1 has to choose between up and down. If player 1 chooses up, then player 2 gets to move and chooses between left and right. And if player 2 chooses left, then player 1 gets to move again, and player 1 chooses between up or down. All right, everyone looking at that game? So why don't we play this game? Since we haven't played a game for a while, we'll play a couple of games today. So what I'm going to do is, let's divide the class in two. So if I just draw a line down the middle of the class, okay? Everybody to my left, to your right, everybody over this side of the class is a player 1. Okay, you're all player 1s. All right? And everyone on this side of the class, you're player 2, including you guys hiding from the camera. All right, you're player 2s. All right? Okay, so let's figure out what we're going to do. Right, everyone had time to look at the game? All right, so player 1s, you get to move first. Those of you who are going to choose down, raise your hand now. Raise your hand, wave in the air. Keep it up so the camera can see you, okay? And those of you who are going to choose up, raise your hands. All right, lots more ups. Those of you who chose up, why don't you all stand up? Why should I don't do all the exercise here. So all those who chose up, stand up. All right, so you can see that choosing down ends the game. So this many people are still playing the game. All right, everyone who's still sitting down, everyone who's sat down here has exited. All right, player 2s, you get to move now. All right, so player 2s, those of you who choose right, including the people on this aisle, those people who choose right, raise your hand now. One right over there. Those of you who choose left, raise your hands. All right, why don't you guys all stand up? Just to get you awake on Monday morning, right? Everyone's sleepy otherwise. All right, let's go back to player 2s. Let's go back to player 2. All right, so those of you who are still alive, sorry, player 1, those of you who are still in the game, so those of you who chose up the first time, how many of you now choose down? Raise your hand if you choose down, and raise your hand if you choose up. All right, just to get a sample of this, let's get the 2s to sit down again so people can see them. So 2s sit down. All right, those of you player 1s who are still in the game, who are choosing up, raise your hand now. All right, I think it's everybody. It's everybody. Is that correct? Okay, you can all sit down, okay? Okay, so let's just talk about this game for a while, and then we'll analyze it. Now, this is not a difficult game from the point of view of stuff we've done since the midterm. It's pretty clear what we should do in this game by backward induction. So why don't we start there? Okay, so by backward induction, we find that if player 1 gets to move a second time, then they're choosing between 4 and 3, and they're going to choose 4. All right? And player 2, if they get to move, knowing that player 1 is going to choose up tomorrow, they're going to be choosing between 3 if they choose left, or 2 if they choose right. So they're going to stay in the game and choose left, which is what most of you did. All right? And finally, player 1, at the beginning of the game, knows that player 2 is going to choose left, whereupon she's going to choose up. So if she chooses up, she's going to end up getting 4, and if she chooses down, she's going to get 2, so she's going to choose up. So it's clear what backward induction does in this game, and that's what most people did in the game. Is that right? Is that right? However, not everybody did it. Some of the player 1s actually, when you raise your hand, those are people who chose down. The ones who chose down. There were more than that, because you didn't all stand up. Those who didn't stand up just now, raise your hand. People are hiding now, but it's okay. Those people who chose down, they may have had a reason for choosing down, and their reason for choosing down might have been that they thought that even though they can do backward induction, so even though they know that by backward induction up gets them the better answer, they might be worried that if they choose up, player 2 will screw up and choose right. And notice that if player 2 chooses right, then player 1 only gets 1, whereas down yielded 2. So in some sense, down was the, quote, safe thing to do for player 1, given that they might be worried that player 2 might screw up.
Right? Does that roughly just nod if this is the case? For those people who chose down, is that kind of what you were thinking? Some people are shaking their heads, but some people are nodding. That's a good sign. All right? All right? Now, why might player 2, in fact, screw up and choose right? Because player 2 might themselves think that player 1 might screw up at this stage. If player 1 were to screw up at the last stage and choose down, then player 2, by choosing left, would only get 1, and for him, the safe option, therefore, is right, which yields 2. All right? So to get the backward induction answer here, which most of us did, to get the backward induction answer here relies on player 1 trusting player 2 to play backward induction, and that requires player 1 to have trust in player 2 trusting player 1 not to screw up on the last stage. So say it again, player 1 needs player 2 not to screw up, and that means player 1 needs to trust that player 2 will trust her not to screw up. All right, everyone see the game? Okay. So let's try and analyze this game using what we learnt last time and see what we find. So the first thing to do is let's look at strategies in this game. So player 2 just has 2 strategies, left and right, because player 2 only has 1 information set. And notice this game is actually a game of perfect information. Right? This game is a game of perfect information, so it's going to be very easy. Player 1 has 2 information sets, this information set and that information set. At each of them, player 1 has 2 choices, so she must have 4 strategies in all. All right? So this game, when we put it in its matrix form, is going to be a 4x2 game. Here it is. And the strategies for player 1 are up, 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 down, down, up, and down, down. And the strategies for player 2 are just left and right. And now we can put the payoffs in. So up, up, left gets us 4, 3. Up, up, right gets us up, up, right gets us 1, 2. Up, down, left gets us 3, 1. Up, up, right gets us 1, 2 again. We end up exiting the game here. Down, up is easy because it's just exiting the game at the first stage. So all of these are going to be just 2, 1. Okay, we're happy with that? Right, so all I've done is translate the game into its matrix form. And let's look for Nash equilibria in this game. All right, just look for Nash equilibria. Let me do it at the board since it's quite easy at this stage. So to look for Nash equilibria, let's just worry about pure strategy equilibria for now. All right, so if player 2 was choosing left, then player 1's best response is the up-up strategy. And if player 2 is choosing right, then player 1's best response is either down-up or down-down. That's exactly the conversation we just had. If player 2 was going to, quote, screw up and choose right, then player 1 wants to get out of the game immediately. All right? Conversely, if player 1 is choosing up-up, then player 2 is happy and is going to choose left. It's trusting player 1. If player 1 was going to choose up-down, however, then player 2, that's player 1 screwing up at the second stage, so in that case player 2 wants to get out of the game and choose right. If player 1 is choosing down-up, then player 2 is actually, that doesn't matter, they're indifferent, and if player 2 is choosing down-down, then once again player 2 is indifferent, since they don't get to move at all. All right? So from this we see that there are 3 Nash equilibria. Let me call them 1, 2, and 3. All right, so one Nash equilibrium is up, up, left. Another Nash equilibrium is down, up, right. That's here. And a third equilibrium is down, down, right. Down, down, right. All right, so there are 3 pure strategy Nash equilibria in this game. And let's just see what they do. So the first one, up, up, left, is up, left, up. So it gets us to here. All right? So this one is the same equilibrium as corresponds to backward induction. Is that right? This one's the backward induction equilibrium. And the other 2 are different. Down, up, right, and down, down, right both end up down here, exiting the game immediately.
Right? So both of these other equilibria fail backward induction. So let's put backward induction with a line through it. Right? They're failing backward induction. All right? And so you may ask, why are they equilibria? We've seen examples like this before, for example, in the entry game. We also saw examples last time. So in this game, the reason these are equilibria, even though they fail backward induction, is exactly coincides with that conversation we just had about worrying about the other person screwing up. All right, so in particular, if player 1 thinks that player 2 is choosing right, that is to say, thinks that player 2 is going to screw up, then player 1 doesn't want to travel up the tree because she knows she'll be carried down here, and instead she just chooses the safe option and gets 2. Right, so from player 1's point of view, if player 2 was going to choose right, then getting out of the game, doing the safe thing, is the best response for player 1. And from player 2's point of view, if player 1's exiting the game, it really doesn't matter what player 2 says she's going to do, right, because she doesn't get to move anyway. All right, so that's why these are both equilibria. Okay, so what we want to do next, we've translated this into a tree, we've written down the strategies. We want to actually see which of these Nash equilibria are subgame perfect. Which of these Nash equilibria are subgame perfect? All right, let me give myself a bit more room here because I want to keep this in sight, so let's get rid of this. And raise this one. All right. So the next question is, which of these 3 Nash equilibria are subgame perfect? All right, to do that, we need to start by identifying the subgames. And of course, having just hoisted that board up there, I have to hoist it down again. Okay, so what are the subgames here? Well, the simplest subgame is this simple subgame at the end in which player 1 moves. All right, that's a very obvious subgame, is that right? That's a little game with a game. It's a rather trivial game because it's a one-player game, but it is a game. So let's examine that one first. That's the last subgame. All right, so the last subgame here is a somewhat trivial subgame. It looks like this. Player 1 is the only mover, and they're choosing either up or down, and the payoffs are 4-3 and 3-1, and frankly, we don't really care at this point what player 2's payoffs are, because player 1 is the only person who's playing in this subgame. All right, but nevertheless, let's put them there. And if we write this up as a matrix, here it is as a matrix. It's player 1 is the only mover. They're choosing between up and down, and the payoffs are 4-3 and 3-1. And of course, player 2 doesn't get to move, so player 2 is irrelevant here. And clearly, the only Nash equilibrium in this game, is for player 1 to choose up. Right? Player 2, it doesn't really matter what they choose. There's nothing they can do about it anyway. But for player 1 to choose up is the Nash equilibrium. So the Nash equilibrium in this trivial subgame is 1 just chooses up. Is that right? So let's look at the play induced by our 3 candidate Nash equilibria in this subgame. All right? So each of our candidate Nash equilibria, here they are, this one, and this one, have an instruction of how player 1 should play in this subgame. And let me just pause a second. The reason that these 3 equilibria have an instruction for how player 1 should play in the subgame is because of our definition of a strategy. Each strategy tells the player how they should move at every information set of that player. So even if the strategy is such that that information set won't be reached, the strategy still has to tell you what you would do when you got there. And now, for the first time perhaps, we're going to see why that redundancy helps us. All right? So let's look at the instructions. Each of them gives an instruction. The first one tells us to play up in the subgame. First one says up. The second one says up again. And notice this was redundant, right? Once you've chosen down, you know you're not going to get to make a choice at the third node, or your second node. But nevertheless, There's the instruction, and it says up. Right, and the third one says down. All right, it says down. So this is the instructions of these three equilibria in this little subgame. Right, this is the play prescribed by these three equilibria in this subgame. All right, two of them say up, and those ones are going to induce the Nash equilibrium in the subgame. But the third one does not. The third one says down, and that's not allowed. That's not allowed in a subgame perfect equilibrium, because in a subgame equilibrium, a subgame perfect equilibrium has to prescribe play in every subgame that's Nash. And here, the third equilibrium is telling player 1 to choose down, which is not a Nash equilibrium in the subgame. All right? So 3. So what are we doing here? Let's make it clear. We're finding the subgame perfect equilibria, and what we've done is, number 3 is eliminated because it induces play in this subgame that is not Nash equilibrium. Not a Nash equilibrium in the subgame. All right, we're already putting stuff together now. This really to be able to draw this conclusion, we really used the fact that strategy 3 contained a redundant instruction, an instruction down at this node that was never reached. But that helped us get rid of it. All right, so that one's gone. That one's gone. 3 is gone. All right, let's proceed. I'm going to run out of board space here. Have people got this one down? People got this down? All right, I'll bring it back in a second. Almost. Let me give it a second. All right. What I want to do now is look at the next subgame. All right. Maybe what I can do, if I just remove this comment, I can work on the right-hand board. That'll allow you just to look at it. So all that comment said was 3 is eliminated. And let me work now on the right-hand half of this board. That'll allow it to be up there a bit longer. Okay. So let's now look at the next subgame. And again, we're going to work from the back. So the next subgame back is the subgame that starts from this node. All right, the subgame that starts from that node. All right, so let's identify that in a different color. I use blue, so let me use pink. So now we're going to look at this subgame, this big pink subgame. All right, and again, in this pink subgame, this game looks like this. It starts with player 2 choosing between left and right, and then player 1 has to choose up or down, and the payoffs are 1, 2, 4, 3, and 3, 1. All right, once again, let's look at the matrix form of this subgame. And this is a little bit less trivial than the last one, because now there are really 2 players playing. So here's the matrix that goes along with this. Player 1 is choosing between up or down, and player 2 is choosing between left or right. And this is slightly cheating, because in fact player 1 player 1 of course knows what player 2 is going to have done by the time she moves, but never mind, it'll do for now. All right, and let's put the payoffs in. So up left is 4, 3, and down left is 3, 1, and up right is 1, 2, and this must also be 1, 2. All right, everyone happy with that? Just putting the payoffs in. And let's just look again just at pure strategy Nash equilibria here. Okay, there are actually mixed ones, but let's just worry about pure ones for now. All right, so the pure Nash equilibria here in this little subgame are what? Well, let's just see. If 2 chose left, then 1 wants to choose up. If 2 chooses left, then 1 wants to choose up. If 2 chooses right, it doesn't really matter what 1 chooses, because she isn't going to get to move anyway. All right. Conversely, if 1 chooses up,
then 2 wants to choose left. That's the example of 1 not screwing up, so 2 wants to stay in the game. But if 1 was to choose down, then player 2 would like to get out of the game. So if player 2 thinks 1 is going to screw up, she wants to exit the game. All right, and very quickly we can see there are 2 equilibria here. One of them is up left, and the other one is down right. All right, they correspond to playing down this way, that's down right, and up left, playing up this way. All right, and once again, let's look at our 3 equilibria in the parent game. Here's our 3 equilibria in the parent game. 3, and let's see what play they induce in this little subgame. So we'll do exactly what we did before. So 1, 2, and 3. These are our 3 equilibria from above. And equilibrium number 1, up left, in this game prescribes up left. Is that right? And equilibrium number 2, down up right, here prescribes up right. And equilibrium number 3, down right, here prescribes down right. So which of these are prescribing Nash equilibria in the subgame? Well, up left is an equilibrium, it's that one. Up left is an equilibrium, so this is okay. And down right was an equilibrium, so 3 is okay in this subgame. All right? But upright is not. Upright is not a Nash equilibrium. All right? So in this subgame, Nash equilibrium number 2, the down-up-right equilibrium, is prescribing play that is not a Nash equilibrium in the subgame, so it's eliminated. It can't be a subgame perfect equilibrium. So here, 2 is eliminated since it induces non-Nash equilibrium play in this subgame. All right? And now we're done. We know about the whole game. So what we did here, we started with the whole game. We found there were 3 Nash equilibria. We found that only one of them agreed with backward induction. We then looked at the subgames. We first of all looked at that blue subgame, and we found that one of the equilibria, equilibrium number 3, was eliminated. Equilibrium number 3 is not prescribing Nash behavior in this subgame. Right? Then we looked at the slightly more complicated subgame, the pink subgame, and we found that equilibrium number 2 prescribes the behavior upright, which is not Nash in this subgame. Right? At this stage, we've eliminated 2 of the 3 equilibria, and we're just left with 1. And the one we're left with, the only subgame perfect equilibrium, the only equilibrium that wasn't eliminated by the fact it would prescribe bad behavior in subgames, the only SPE is number 1, which is up, and left. And what do we notice? We notice that that's the equilibrium, that's the play that backward induction would have selected. All right, so notice this is the backward induction prediction. All right, so what are the lessons here? The lessons here are that our new idea, our idea of subgame perfect equilibrium, is pretty easy to go about finding. You just look at subgames and check that the play in each subgame has to be Nash play. All right, in fact, if you start at the back, you'll construct it by rolling backwards, much like we did backward induction. Right? Start at the last subgame and work backwards. And the second thing is, not surprisingly given that remark, not surprisingly, where backward induction applies, for example, in this game, the subgame perfect equilibrium will find the equilibrium that is consistent with backward induction.
And remember, that was our aim last week. We wanted a way of refining Nash equilibrium to throw away those Nash equilibria that were inconsistent with backward induction. So subgame perfect equilibrium has done that. It tells us now, if backward induction applies, the Nash equilibria you should focus on are the subgame perfect equilibria. And indeed, most people in the class played that equilibrium just now. All right? Okay. So that's really all I want to say about this example. But let me just make a remark in passing. I made this mark in the middle, so let me just make it again. When we write down strategies, those strategies tell us what seem to be redundant moves. But being forced to write down those redundant moves is useful, because it allows us to model what other people think you would have done at those later nodes. And sometimes I have to think what you think I would have done at this later node before I decide not to go down that branch of the tree. So being able to write down everything in a strategy allows us to have everything in front of us and makes that analysis simple, and that's exactly what we did here. All right, so this was a fairly mundane example because in particular we didn't use any kind of information set. So next, let's look at an example that does use some information sets. All right, so new example. Let me clean this off. And once again, I want to play this example, but what I'd really like to do, we're going to call this game the matchmaker game. The matchmaker game. And what I'd actually like to find out is, do we still have our couple we tried to send on a date, our hapless couple we tried to send on a date in about week 3? Are you guys still here? Ah, there's the guy. What's your name again? David. And what was the... Is she hiding? Oh, there she is. Thank you, thank you. And your name was? Nina. Nina and David. Good, good. Can we get some mics to Nina and David, actually? Let me do it. And I'll go on talking while I'm doing this, so that's okay. Where's David? Thank you. And let me grab him. Ali, can you get mic to Nina? That would be great. Thank you. All right. So for weeks, we've been trying to get this couple to go on a date. It's our attempt to get economics majors to become real people. It's a hard thing to do. And they're kind of the hapless couple because first of all we send them to the movies and they end up going to different movies. And then we sent them off for a romantic weekend in New England and they end up doing different things. And one went to the theatre, another went apple picking. I forget which way around it was. And at this point, I figure I'm a pretty bad matchmaker. So what I'm going to do is I'm going to introduce a third player into the game as the matchmaker. So first of all, I'll write down what the game is. All right? So the game at this point, the game's going to look like this. Player 1 is the matchmaker. We can call him player M if you like. And he has a choice. He or she has a choice. She could not send the couple out on the date, or she could send the couple out on the date. Right? But being a better matchmaker than me, if she sends them out on the date, she's going to stake some money. She'll pay for the date. She'll pay for the date. All right? And in the date, once again, they're trying to meet. And once again, unfortunately, they haven't figured out where to meet. All right? We'll put the payoffs in a second. We'll tell you what the strategies are. All right, so what I'm going to assume here is I'm going to let Jake, our TA, be our matchmaker. And the reason I'm choosing Jake is I think he's the nearest thing I have in mind in this class to being a Jewish mother. I mean, he's neither Jewish. I think he's not Jewish and he's not my mother, but he is the TA who's responsible for bringing me some drink every day in case I pass out in the lecture. So that's the nearest thing I can think of. So Jake's going to be our Jewish mother, and Jake's going to either send these guys on a date or not. And Jake's smarter than me at this. He's actually good at matchmaking. And what he's going to do is he's going to send them somewhere where they really, well, he knows Yale students better than I do, and he's going to send them really somewhere where they're going to meet. So he's going to send them to go to the same lecture class next year, and then they'll be sitting in the aisles in this huge lecture class, and they're bound to meet. All of you have sat next to other people at some point. So that seems like a good idea. So the classes he thinks of sending them to, he says, go to a large lecture class. So they're either going to go to the Gaddis class, which is called Cold War, or to the Spence class, which is called China. Everyone know about these classes, right? Right? And these seem like reasonable classes to go to meet your, to have a date, to meet somebody. I mean, the Cold War, kind of fun class. I mean, you hope it isn't a prediction of the future relationship, but Cold War seems all right. And China's, by all accounts, is a fantastic class. It involves, something involving 20 million people, most of whom are in the class, I gather. So it's a pretty big class. So let's do that. So we'll call this Unfortunately, Jake makes the same mistake I do. He's not going to tell them which class to go to. So they have to decide whether to take Gaddis or Spence. And once again, they're coordinating. We'll call them players 2 and 3. So here they are trying to coordinate, and the payoffs are as follows. So let's put in Jake's payoffs first of all. So if they manage to coordinate, first of all, if Jake doesn't send them, everybody gets nothing. All right? And if Jake does send them and they coordinate, Jake makes 1 because he feels really happy about this. After all, I mean, there must be some motivation for people matchmaking. If they coordinate down here, Jake gets 1 as well. But if they fail to coordinate, Jake feels rotten about it, particularly because he paid for them to go to this class, whatever the cost of a class at Yale is, which is probably quite a lot, actually. I don't know. All right. So, okay, we'll call it 1, though. All right? And otherwise, the payoffs are exactly the same as the payoffs we used when we looked at this game earlier on in the course. So the payoffs are going to be 2-1 here, and 0-0 if they fail to coordinate, and 0-0 here if they fail to coordinate, and 1-2 here. All right, so the implication of this is that player 2, who we'll assume is David, is that right? So David would like to meet Nina, but all other things being equal, he'd like to meet her at the Cold War. And Nina would like to meet David, but all other things being equal, she would like to meet in China. I mean, not literally in China, but in the class China. All right? All right, so this is our game. All right, and we're going to analyze this game. But before we analyze it, let's try and play it. So what we need to do is, first of all, let's make sure things work smoothly. Let's have David write down which class he's going to choose, and Nina write down which class she's going to choose. I've lost sight of Nina. Somebody needs to point out. There she is. Right, write down what class you're going to choose. Okay. Something been written down? Okay. And Jake, you got your mic there. Sorry, Jake. Are you gonna send this hapless couple or not?
So I have Dave in my section actually, and I hear how much he's been talking about Nina. So I'm going to roll the dice and send him.
All right, going to send them. Okay, good. All right, so we have them going off to this class. All right, and now let's see what they wrote down. So Dave, what did you write down?
I'm going to give it and go to China.
You're going to go to China, and Nina?
I chose S.
You do? Great, so they managed to meet. So that was a successful date. So let's give them a round of applause, all right? I hear it's a great class, too, and in fact, I don't think it's going to happen forever, because I think he must be approaching retirement, so that seems a pretty good choice. So good, okay, that worked very well. Let's have a look now at this. Let's analyze this game and see what we can do with this game, all right? So how are we going to analyze this game? So no surprise, we're going to use the idea of a subgame perfect equilibrium. All right, I'll collect the mics later, don't worry. All right, so we're going to use the idea of a subgame perfect equilibrium. So how do we figure out how to work out what a subgame perfect equilibrium is? We're going to use the same basic idea that we used when we've been using all along in backward induction. And it's the same idea in the game we just looked at just now. What we're going to do is, rather than start from the last decision node, we can't do that anymore, and work backwards. Instead of doing that, we're going to start from the last subgame and work backwards. And in this example, it's pretty obvious what the last subgame is, right? The last subgame, the game within a game, there is only really one, the game within the game is this object here. Is that right? This is the game within the game. Now, I could, at this stage, I could do something else. I could write down the whole matrix for the whole game and have Jake choose the matrix and Dave and Nina choose the row and the column, but that's going to take, that's going to get us astray. So we could do that, but let's not worry about that. Let's just start doing things backwards. So when we do things backwards, we'll start at the last subgame, and that last subgame is an old friend of ours. It looks exactly like this. Let's just write it in. All right. So it involves players 2 and 3. All right. And 2 was choosing between Gaddis and Spence, and 3 was choosing between Gaddis and Spence, and their payoffs were let me leave a space here, so it's 2, 1, 1, 2, 0, 0, 0, 0. So here are the payoffs of the relevant players in the game. But while we're here, why don't we put in Jake's payoffs as well? So Jake's payoffs were 1 here, -1 here, -1 here, and -1 there. All right, so the only relevant players here are players 2 and 3, but I've put player 1's payoffs in as well, because why not? Why not just keep track of them? Okay, everyone happy that that's exactly describes this little game? All right, for all intents and purposes, we can forget the first payoff, but there it is. All right, and this is a game we've seen many times so far. It's the battle of the sexes, or the battle of Dave and Nina, and in this game, we already know what the equilibria are. So the equilibria here, let me just underline best responses. So if Nina is choosing Gaddis, then Dave chooses Gaddis. If Nina is choosing Spence, then Dave would like to choose Spence, and conversely. All right, so I just underlined the best responses for the players who are actually involved in the game. I haven't bothered underlining anything for Jake because he isn't a player in this game. That make sense? All right, so the pure Nash equilibria in this game, are essentially Gaddis, or Spence. All right? All right, that's pretty easy. All right, and from Jake's point of view, each of these pure strategy Nash equilibria yield a payoff for him of what? What does he get? If they go to Gaddis, he's happy that they met and he gets 1. And if they choose Spence, he's happy that they met and he gets 1. Jake doesn't really matter. Jake himself doesn't really mind whether Dave and Nina learn about China or learn about the Cold War. He just wants them to meet. All right, so both of these yield 1 for Jake. Both yield a value, let's call it, a value of 1 for player 1, who's Jake. All right? So from Jake's point of view, going back a stage, and what we're going to do now, just a bit with backward induction, we're going to roll the game back. So we started by analyzing this subgame, and now we're going to roll back a stage, just as we did with backward induction. So when we roll back, Jake is moving here. If Jake chooses not to send them, then we get 0, 0, 0, but the key part of this is the first 0, that's Jake's payoff. And if Jake sends them, then what Jake gets is the value to Jake, oh, well, okay, I'll put it Jake, but value to player 1, okay, value to Jake of the Nash equilibria in this subgame. All right, rather a big thing to write, but that's what Jake gets. And the others do too, the others get that as well. And in this case, rather than writing that long piece, this is just equal to 1. Is that right? Right? So if Jake sends them, he knows that they're going to play a Nash equilibrium in this subgame, or he believes they're going to play a Nash equilibrium in this subgame, and either of those two Nash equilibria in the subgame, hang on a second, either of the two Nash equilibria in the subgame yield a payoff to Jake of 1. All right? So actually, one of them is 1. One of them yields payoffs of 1, 1, 2, and the other yields payoffs of 1, 2, 1. But since Jake is the only mover here, let's just focus on Jake. All right? So from Jake's point of view, he's really choosing between 0 and 1, so he's going to choose send. All right? So the subgame perfect equilibrium, therefore, there are actually 2 of them here. One is send Spence, that's what actually happened. But there's another one, which is send Gaddis. Right, that would also have been a pure strategy subgame perfect equilibrium. Right, so in either case, what we did is, just to remind ourselves, we first of all solved the equilibrium down the subgame, the equilibrium in this blue subgame. We figured out how much that equilibrium was worth for everybody, but in particular for Jake, but for everybody. And then we rolled that payoff back and looked at Jake's choice. Right, in this particular case, that gave us 2 equilibria, send Spence, and send Gaddis. However, some of you must be suspecting at this point that there's actually another subgame perfect equilibrium here. How do we know that? Well, just think about this game. I mean, we've been trying to send this couple on a date all semester. They haven't gone on a date all semester. I'm embarrassing them now, but they haven't gone on a date all semester. So there must be some possibility that they would fail to coordinate. And it would be a pretty weird notion of equilibrium that concluded that they always manage to coordinate, and hence Jake always wants to send them. Is that right? So let's also look at the other equilibria here. Now, the reason there's another equilibrium in this subgame, the reason there's another equilibrium in the whole game, the reason there's another subgame perfect equilibrium in the whole game, is that there's another Nash equilibrium in the subgame. What's the other Nash equilibrium in the subgame? They could mix, right? They could mix, right? Right? So it turns out that in the subgame, here it is, there's also a third mixed equilibrium. There is a mixed Nash equilibrium. All right? Now we know how to work that out. We could write down a P and a Q, and we could look for those indifference conditions and solve it out. But this is a subgame. Sorry, this is a game. This subgame corresponds to a game we've seen many times in this class so far, and I think we probably remember what that equilibrium is. Is that right? I do anyway. So let's see if you remember it as well. I'll write it down, and we'll see if you all look alarmed. So I claim the other equilibrium has Dave playing with probability 2/3, 1/3. And has Nina playing with probability 1/3, 2/3. Right, so this is another equilibrium in the subgame. People remember that this was an equilibrium in Battle of the Sexes, yeah? Yeah, people are nodding at me, yeah, okay. So it isn't too unintuitive. We all know how we'd work it out. We could go back and put in the P and the Q, but it isn't too unintuitive. It has Dave going more often to the lecture course that he would prefer, all other things being equal, and it has Nina going more often to the lecture course that she would prefer, all other things being equal, and they do so in just such a way as to make each of them indifferent. All right, now this subgame induces a different value for Jake. Right, so suppose Jake thinks, I trust Dave and Nina to play a Nash equilibrium in their subgame, but I don't know which one it is, and I think maybe they're going to play this one. All right, so suppose Jake thinks that this is the equilibrium that Dave and Nina are going to play. So now, should Jake send them or not? Well, let's work it out. Let's work it out. So now, if he sends them, if Jake sends Dave and Nina, or more anonymously, if player 1 sends players 2 and 3, all right, then with what probability will they meet? In what probability will they meet? Well, this is just a little math exercise. Let's have a look at the game again. So, Dave is playing 2/3, 1/3, is that right? And Nina is playing 2/3, 1/3. All right, is that right? So the probability of their meeting is the probability of this box, they could meet at Gaddis, plus the probability of this box, they could meet at Spence. Is that right? So the probability of this box is 1/3 times 2/3. So this box has probability 2/9. And the probability of this box is 2/3 times 1/3. So this box has probability 2/9. So the probability of their meeting is 2/9 plus 2/9, that makes 4/9. Right, everyone okay with that? All right, so if Jake sends Dave and Nina and they play this mixed strategy equilibrium, then they meet with probability 2/9 plus 2/9, 2/9 at Gaddis, 2/9 at Spence, for a total of 4/9. All right, which means they fail to meet, and hence fail to meet with probability, well, if they're meeting with probability 4/9, what must be the probability that they're failing to meet? 5/9, thank you. So they fail to meet with probability 5/9. All right? So Jake's expected payoff, if he sends them, the value for Jake of this equilibrium is what? So the value to Jake of this Nash equilibrium, if he sends them, is 4/9 times 1 plus 5/9 times minus 1 for a total of minus 1/9. Everyone okay with that? Right, so if Jake sends them, they fail to meet 5/9 of the time, and he gets minus 1 each of those times. They succeed in meeting 4/9 of the time, he gets plus 1 each of those times. So his expected payoff, his expected value from sending Dave and Nina on the date is minus 1/9. All right? So from Jake's point of view, what this game looks like, if he thinks that this is the Nash equilibrium being played, if he doesn't send, he gets 0, and if he does, he gets the value of this Nash equilibrium, which in this case is minus 1/9. So he's not going to send. All right, and the SPE here is not send, mix. All right, where this is the mix. All right? So there's a third equilibrium here in which our matchmaker says this hapless couple is just too hapless, they're going to play the mixed strategy equilibrium, in which case it isn't worth my while sending them on the date. You guys were lucky because Jake chose the other equilibrium. Figured you were playing the other equilibrium, which it turned out that you were. All right? So in this game, there were 3 subgame perfect equilibria. 1 for each of the Nash equilibria in the subgame, as it turned out. There was one in which Jake sent them, and they coordinated on the pure strategy equilibrium in the game SS. There was one in which Jake sent them, and they coordinated on the pure strategy equilibrium in the subgame GG. And there's one in which Jake didn't send them, but had he in fact sent them, they would have both mixed, and hence, for a lot of the time, failed to coordinate. All right? And what's the big lesson here? Right, the big lesson of the first game we saw this morning was that subgame perfect equilibrium implies backward induction. Right? The big lesson of this game, other than the fact that we're getting closer to getting Dave and Nina on their date, the big lesson of this game is to show that to find subgame perfect equilibria, all you have to do is keep your head and solve out the Nash equilibria in each of the subgames, roll the payoffs back up, and then look for behavior up the tree. Right, once again, you look for the Nash equilibria in each of these subgames, roll the payoffs back up, and then see how behavior, see what the optimal moves are higher up the tree. All right? So we have time to do one more example. All right? And the third example I want to do is more of an application. All right? So far we've seen some fairly simple examples. Now I want to do an application. And the application I want to do is kind of a classic business school case, if you like, or mini case, involving strategic investment. All right? And the game is this, or the setting is this. There are 2 firms. We'll call them A and B. And these 2 firms, initially, before we start considering considering what we're actually going to talk about, initially, they are playing Corno competition. So 2 firms, and they're playing Corno competition. And we can imagine that they're producing fertilizer. Right? Imagine that they're producing fertilizer. All right? And let's be specific here. Let's assume that the prices in this market are given by the following demand curve: 2 minus 1/3 times QA plus QB. Right, so this is the demand curve that they face. All right, and we'll assume that costs, marginal costs, C is equal to $1 a ton. All right, so this is the price in dollars per ton, price per ton in dollars, and the costs are $1 per ton. Right? And in a minute, what we're going to do is we're going to consider a change in this game. But before we do that, let's just remind ourselves what the Cournot equilibrium of this game would look like. All right, let's do a bit of a review. All right, so it's a while since we've seen Cournot, so let's remind ourselves. So I claim that the Cournot quantity chosen, Q star, has the formula A minus C over 3B. Is that right? Right? If you go back in your notes, you'll find it. So I'm not going to re-solve it here. We've done it many times. So A minus C minus 3B, trust me, is what came out of our calculation before the midterm. And what I want to do is, I just want to make sure we can translate that into numbers here. It's all we're having in letters, but let's translate it into numbers. So in particular, this A is this 2. Is that right? This C is this 1. And this B is this 3rd. Is that right? So let's just put that down. So what in this case, this is 2 minus 1 over 3 times a third. Right? 2 minus 1 times 3 minus a third. So this says that the quantity is 1, and this is in million tons. So the quantity here, the Cournot quantity, is 1,000,000 tons each. Right, so 1 each. So in this equilibrium, each of these two firms is producing 1,000,000 tons of fertilizer. All right? And what else do we know? We know, therefore, what prices must be. Let's just do that before we even get started. So prices must be 2 minus a third times the quantity that the first firm produces plus the quantity that the second firm produces. So that's 2 minus 2/3. So that should be 4/3, if I've got that right, or 1 1/3. So prices here are $1.33 per ton. All right? And finally, profits. So profit for each firm here in this equilibrium, before we even start the game, before we start the more interesting part of the game, profit is what? So they're going to get $1.01 for every ton they produce. It's going to cost them $1 to produce each ton, and they're producing 1 million of these things. All right? So their profits are, should be a dollar sign here as well, their profits are 1/3, if these are millions, they're producing 1/3, their profits are 1/3 of $1 million. All right? All right? So this is their per period profit. Right? In each period they're doing this. Each year they're doing this, and this is their profits in each period. All right? So this is a simple model we've done many times before. This is Cournot, and now we're going to make it more interesting. Everything, if the algebra here was a bit quick, don't worry about it. Check it at home. It's just basic algebra. All right? So now suppose that you are the manager of firm A. All right? This is classic business school case. I'm looking up at my business school students in the balcony. All right? You're the manager of firm A, and you have to choose whether to accept an offer to rent a new machine. All right, so this new machine has two features. All right, three features. The first feature is it only works for A. All right, so this machine is being offered to you. It wouldn't fit in to firm B's technology. So this is only being offered for A. The second feature of this machine is it costs $0.7 million in rental. So each year you rent this machine, you'd have to pay $0.7 million. All right? But that's the bad news. The good news is it will lower A's costs to 50 cents a ton. All right, so classic business school situation. You're the manager of a firm, you're involved in competition with another firm, B, and suddenly an opportunity comes along to rent some new technology. It's going to cost you 0.7 a year to rent this machine, but it will lower your costs by 50 cents a ton. All right, so this is a classic thing that you might be asked in your interview for Morgan Stanley next week. How many of you are interviewing with investment banks? No one's going to admit it. In a couple of years when you're interviewing with these guys. All right? So what's the obvious question? The obvious question is, should you go ahead and rent this new technology or not? Should you rent it or not? To rent or not to rent? To rent or not to rent? All right, less dramatic than its equivalent question in the English class, but important nevertheless. All right. This board is stuck, unfortunately, so I'll have to raise that a bit more. There we go. All right. So what I want to do is I want to analyze this 3 times. And each time I analyze it, I want us to see what I'm doing, what mistakes I'm making, because I want you guys, when you interview with Morgan Stanley about this kind of thing, to impress them so that they tell lots of people to come to Yale and preferably give lots of money to Yale. All right, so we're going to look at this way 3 different times. And the first thing we're going to do, the first way we're going to look at this, is look at it as if we were accountants. We're going to look at the accountant's answer to this question. And some of you may decide you don't want to interview with Morgan Stanley or McKinsey. You might want to interview for some accounting firm when you leave Yale. God forbid, but you might. All right, so let's have a look at how the accountants would answer this question. All right, so I think the accountants would do this. They would say, oh, before we do this, let's have a poll. How many people think you should rent, you've got time to think about it now, so how many people think you should rent the new machine? And how many people think you should not rent the new machine? Oh, I'm not going to allow abstentions here. Let's try it again. All right, without no abstentions, right? You can't abstain in an interview. All right. So you're on the spot. You're in the boardroom. All right. How many think you should rent the new machine? Raise your hands. Wave them in the air. How many people think you should not rent the new machine? All right. So we're split kind of down the middle. I'm looking at my MBA students, see which they voted. Which did you guys vote? Rent or not vote? Rent. Okay, the MBA students think rent. We'll see if that's right. All right, so let's move forward. All right, so accountant's answer. So I think what the accountant's going to say is this. They're going to say, right now you're producing 1 million tons a year. All right, the new machine saves you a year. Let's put per annum. Let's try and be fancy here. So 1 million tons per annum. The new machine saves you 50 cents per ton. So if you rent this new machine, you're producing 1 million tons a year. It's going to save you 50 cents a ton. So it's going to save you 1 million a year in variable cost. Right? Those people who own 115 or 150 know what I mean by variable cost. Is the cost you're going to save in actual production of your fertilizer. So it saves you 500,000 a year. Right? Unfortunately, it costs you cost of machine, which is a fixed cost, has a fixed cost of 0.7 million a year. All right, and 0.7 is bigger than 0.5, so you should not rent. All right, so 0.5 is less than 0.7, so don't rent the machine. Right? How many of you said no? Was this kind of the back of the envelope calculation you were doing? Is that right? Right? It's kind of back of the envelope calculation that accountants do. Right? So what's going on here? Now, our business school student up in the balcony says you should rent. He took accounting. I know he did that because you have to take accounting at business school. So what's wrong? Did he fail accounting, or is this answer wrong? The answer is wrong. Right, there's 2 things you need to know about accountants. One is that they're usually boring, and the other is that they're often wrong. Right? They're more often boring than wrong, but they're almost always boring. But all right. So this answer is kind of boring, right? And it happens also to be wrong. Why is it wrong? It's wrong because we made an assumption here that's not a good assumption. We made the assumption that you're going to go on producing the same amount per year after you've invested in the new machine that lowers marginal costs as you are producing beforehand. All right? All right? We made the assumption that it would lower we know it lowers your costs, and we assumed implicitly you'd go on producing 1 million tons a year. But that's not right. So let's try and have a more sophisticated answer. And if you want to be more sophisticated and less boring than accounting, what class would you want to take? Economics, probably, right? All right, so let's have a look at an economics answer. Let's look at an economics 115 answer. How many of you have taken economics 115? How many of you are in 115 at the moment? Quite a few, okay. So let's have a look at the economics answer. Let's see why that previous answer was wrong. So here is QA, and here is cost of $1. Your new cost will be 50 cents. All right, I'm putting prices and costs on this axis. All right, and here is your residual demand curve. This is the demand curve you face after the other guy has finished producing. So this is your residual demand curve. It's the demand curve on that part of the market you're supplying, or not being supplied by the other side of the market. And to figure out your optimal quantity on your residual demand curve, what you should do, it's like you're a monopolist on this residual demand curve, so you should set what? Yeah, say it again, shout out. Yeah, if the answer isn't backward induction, it's probably marginal revenue equals marginal cost, right? So let's try that. So here's the marginal revenue curve. Right, roughly speaking, it should be twice as steep. This is residual marginal revenue. All right, and here's what you used to produce. Right, so we know what this is. This was 1 million tons. Right, this was marginal revenue hitting marginal cost. Now your costs have gone down. So notice that your quantity, your new quantity, has gone up. Your new quantity has gone up because you've slid down the marginal revenue curve as the marginal cost curve dropped. Is that clear to everybody? All right. So this is the kind of picture that you probably saw a lot of in 115. Is that right? Or in 150 for that matter. Is that correct? So notice in this picture, we can actually see the accountant's answer, the boring answer. The boring answer is this rectangle. Right? This rectangle, this is the accounting answer. This rectangle is 0.5 times 1. So it comes out as a half. And that was the accountant's answer. And what did they miss? What did the accountants miss? They missed the triangle, right? They missed the triangle. They missed this triangle. So I told you they were boring. They're a little bit square, so they tend to miss triangles. All right? So here's the triangle that they missed. All right, so we missed this triangle. All right, and how big is this triangle? Well, we could do it at home. It's half base times height. All right, so we could figure this out. We know the slope of this line. We know the slope of this line is 1/3. We know the slope of this line is 2/3. We know that the height of this triangle is 1/2. We know we could figure out what the width is as well. Therefore, we could do half base times height. Turns out that this has area. I did this at home, so let me just write it down. It has area 3/16. All right. So again, everyone could figure out the area of a triangle at home. Is that right? You all know that from your probably junior high school geometry. So assuming I did it correctly at home, this is 3/16, which is approximately 0.19. Right, so we missed this 0.19. We missed this 0.19. All right, so how are we doing now? So we know from the accounting answer, we had 1/2 in savings. We know from the economics answer that we should add another 0.19 to this, that's the triangle, for a total of 0.69. But unfortunately, this is still less than 0.7, which is the cost of the machine, the per annum cost of the machine. So it looks like we should still not rent. So even after taking Economics 115, which is a good thing to do and is much less boring than accounting, and will get you the accounting answer anyway if you do things carefully, we still end up concluding you shouldn't rent. But our guy from the business school said you should rent, right? So did he fail economics as well as accounting? Or is this answer wrong? This answer is still wrong. This answer is still wrong. Oh, where's a ton? Okay. All right. There we go. I think that board is broken. All right, this answer is still wrong. Didn't really want to delete that. That's a shame. Well, I've done it now. All right. You've all got those numbers somewhere. I hope they're in my notes. This answer is still wrong. We need to get the right answer. All right, so what we need is a third answer, which is the game theory answer, which is also known as the right answer. All right, what are we missing? What's wrong with the economics answer? Somebody. What's wrong? Everyone knew it was wrong. Why is it wrong? It looked pretty good. What's wrong with it? What's wrong with it? Let's bounce down here. I've got somebody in the front row will help me. Why is this? What did I do wrong?
Firm B also changes its quantity.
Right. We assumed, not only in the accounting answer, we assumed that firm A kept its quantity fixed, that we kept our quantity fixed, and that was wrong. But in addition, firm B is going to change its quantity, isn't it? Firm B is going to change its quantity. Let's remind ourselves why. We're still playing Cournot competition. Here's our Cournot diagram with QA and QB. So prior to making this investment, the model is symmetric. Here it is. And this is the old best response of firm A, and this is the best response of firm B. All right? And what we learned just now in the economics answer is what? We learned that firm A, as its costs go down, will produce more for each possible quantity that firm B produces. So regardless of what generated this residual demand curve, as the costs go down for firm A, it increases its quantity. Right? So we know that. We know that. So what's that telling us? It's telling us that the new best response of firm A is shifted to the right. This is the new best response of firm A. It shifts to the right. It now produces more for any given quantity that firm B produces. All right? So QA has gone up. That was our economics answer. All right? But that leads firm B to do what? To produce less. That leads to QB producing less. Notice we slid down firm B's best response line from the old equilibrium to the new equilibrium, and at the new equilibrium, firm B's production has gone down. By the way, what kind of game is it where as firm A increases its strategy, firm B decreases its strategy in response? Strategic substitutes, right? So because this is a game of strategic substitutes, good interview word, right? Good word to mention in an interview. Because this is a game of strategic substitutes, we know that firm B reduces its quantity. As firm B reduces its quantity, is that good for A or bad for A? It's good for A, right? This is good for A. This is good for firm It softens competition, right? It softens competition, right? And as a consequence, it leads to an increase in profit. Again, we don't have time today, but what we could do is we could go back and we could recalculate the new Cournot equilibrium, right? We could calculate this. We could, as a homework exercise, try it, calculate the new Nash equilibrium, and notice this is a Nash equilibrium in a subgame. All right? Why is this a subgame? Because firm A made its decision whether to buy this new machine or not, and then they played Cournot. So the Cournot game, the game up here, what is this? This is the subgame. Right? This is the diagram of the subgame, if you like. Right? It's the best response. It's the best responses in the subgame. So what subgame perfection tells us to do here is, first of all, work out the new equilibrium in the subgame, work out how much that new equilibrium is worth for firm A, and then roll it back to the investment decision. Right? It turns out when we do that, we get an extra $0.31 million. All right, so we do it at home, we get an extra $0.31 million. So it turns out that our MBA student was right, good. All right? It turns out that if you add this 0.31 to the 0.69 we had already, we get 1, which of course is much bigger than 0.7, and indeed you should rent the machine. All right? Now I want you to have two takeaway lessons from this game. The first takeaway lesson is this. When you're analyzing a game like this, be it in the real world or in a job interview, the first thing you want to do is what? You want to look at the subgame. You want to look what would happen if you did invest and solve out the new Nash equilibrium in that subgame. Then you want to roll back the value of that subgame back into the initial decision, which is the strategic investment decision, whether to buy this, whether to rent this machine or not. All right, so schematically, the game looks like this: rent or not rent, and in either case, you play Cournot. Right, there's a subgame in each case. In this case, you play symmetric Cournot when you both have the same costs, and here you play asymmetric Cournot where you have different costs. And the way we analyze this game is we solve out the symmetric Cournot. We actually did that up front. We now solve out the new equilibrium in this asymmetric Cournot game, this one here. Right, this is the old one, and this is the new one. Solve it out, work out how much profit you're going to get, and roll that back, remembering that it costs you 0.7 million to make this step. So that's the first takeaway lesson. But the second takeaway lesson is more general. So let me just pause and get everyone to wake up again so I make it. The second takeaway lesson is this. What tipped the balance here from the economics answer and the accounting answer were the strategic effects. It was the strategic effect. This was a strategic effect. It was the effect of the other firm or other players changing their behavior. And the most common mistake to make when you're thinking about strategic decisions is what? It's to forget that they're strategic. It's to forget that the other players are going to change their behavior. In this example, the other firm cuts back its production so much as to make that investment profitable. But let me give you two other examples. Example number one, you're designing a tax policy for the US. The dumb way to analyze this is to say, look at what people are doing now, push through the new tax numbers, and act like an accountant and crunch out how much money the government's going to make. Right? Why is that wrong? Because you're forgetting that as you change the tax code, people's behavior changes. Incentives change and people's behavior change. It leads to a mistake in designing the tax code. You need to take into account strategic effects, how behavior changes. Example number 2, closer to home. You're designing a new curriculum for Yale. So you change the rules of the curriculum. And when analysing it, you say, I wouldn't say this, but some people on a committee might say this, under these new rules, if we look at what people used to do, they will now do more of this and less of that, and they'll learn this and learn that. What are you missing? You're missing that students are players, and students change their behaviour as you change the curriculum rules. All right? So the biggest lesson of today's class is, don't be like an accountant, partly because it's boring and you won't go on your dates, and partly because you'll miss out on these important strategic effects. We'll come back and look at